What if the history we know is incomplete? What if, buried deep within Earth's geological record, lie the ghosts of a civilization that rose and fell millions of years before our own? Our journey begins there, searching for a lost chapter of our planet's story. But the mysteries aren't confined to our world. They extend to the darkest objects in the cosmos, where what we call black holes might be something else entirely. Hollow stars powered by dark energy, challenging the very laws of physics. And what if the grand structure of our galaxy has a hidden dimension, an unseen architecture of cosmic rivers and magnetic fields, stretching high above and deep below the familiar plane of stars? Join us as we explore the hidden realities of our universe, from a lost world on Earth to the secret nature of gravity's monsters, and the invisible framework that holds our cosmos together. As we prepare to journey millions of light years away to witness this cosmic marvel, let's ground ourselves for a moment. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. Imagine something so huge, so powerful, and so intense that it makes our sun look like a tiny spark. Now picture this monstrous star burning with such fury that it could blast entire solar systems apart. This isn't science fiction, it's real. Somewhere far out in the universe, astronomers have found the biggest and most terrifying star ever discovered. Its size, heat, and energy are beyond anything we can truly imagine. When we look up at the night sky, we see little twinkling dots. They seem so small, just tiny pinpricks of light scattered across the darkness. But those little lights are actually gigantic, blazing balls of fire, cosmic furnaces filled with violent energy. Inside them, powerful nuclear reactions are constantly taking place. These reactions create the energy that lights up galaxies, allows planets like Earth to exist, and even bends space and time itself with their gravity. But not all stars are the same. Some are calm and steady, like our own sun, which has been shining peacefully for about 10 billion years. Others, however, are unimaginably massive, true giants of the universe. These enormous stars shine so brightly that they could easily swallow entire planets and still hunger for more. They're not just bright, they're terrifyingly powerful. So what exactly is a giant star? In astronomy, the word giant isn't just a way to describe something big, it's actually a specific stage in a star's life. After a star has used up all the hydrogen fuel in its core, the fuel it has been burning for millions or billions of years, it begins to change. It starts fusing heavier elements in a shell surrounding its core. This new kind of fusion creates a powerful outward pressure that pushes the star's outer layers far into space. The star begins to swell, growing hundreds of times larger than it used to be. This stage is called a red giant, and it looks like a bloated version of the star's former self. For stars that are much bigger than the Sun to begin with, this process becomes even more extreme. These grow into red supergiants, and in rare cases into hypergiants, enormous celestial beasts so massive they could cover entire solar systems. But how do scientists measure something so unbelievably huge? Astronomers use special units that are hard for most people to imagine. For example, our Sun has a radius of about 696,000 kilometers. That's already enormous. But take Betelgeuse, a famous red supergiant. Its radius can be up to 900 times larger than the Sun's. If you placed Betelgeuse where our Sun is now, its surface would stretch far beyond the orbit of Mars, yet even Betelgeuse is not the biggest. There is another star called WHG 64 that dwarfs it. This colossal star, a true cosmic leviathan, may have a radius up to 1,540 times that of the Sun. That would make it large enough to stretch beyond the orbit of Jupiter if it sat in the centre of our solar system. Imagine a single star swallowing half the solar system. That's how huge we're talking. But a star's terrifying size isn't its only frightening trait. There's also its brightness, or luminosity, which is the total amount of energy it gives off every second. Our Sun produces just the right amount of energy to warm Earth and support life. It's a steady, reliable star. But the largest stars? They produce hundreds of thousands of times more light and heat than the Sun. They burn through their fuel at incredible speed, shining furiously bright, but only for a short time, and when they die, they go out with a spectacular explosion. Many of these monster stars are found in strange places, faraway galaxies like the Large Magellanic Cloud, a small irregular galaxy near our own. These galaxies have lower amounts of heavy elements like carbon, oxygen and iron, what astronomers call low metallicity. This makes it easier for stars to grow bigger before they begin to lose their mass. These galaxies are like cosmic nurseries where extreme stars are born, stars that challenge the laws of physics with their enormous power. But in space, being big comes with a price. The bigger a star is, the faster it lives. Its heart burns so hot and so fast that it quickly uses up all its fuel. While a smaller star like our Sun can live for around 10 billion years, the bigger stars only survive for a few million years. These aren't gentle old gods watching over the universe. They are fierce, blazing giants, beautiful and terrifying, living fast and dying young in the darkness of space. In the far corners of space, beyond the familiar swirl of our Milky Way, lie galaxies so strange and wild that they seem to break the rules of how stars are supposed to form. These aren't quiet, peaceful places. They're chaotic, raw, and bursting with energy. Perfect homes for monsters of the cosmos. Some of the brightest and biggest stars ever discovered, like the enormous Stephenson 218 and UY Scuti, come from these bizarre galactic neighbourhoods, far from the calm lanes of our own galaxy. These massive stars don't just pop into existence out of nowhere. They are born in extreme environments, harsh, rare places that act like cosmic pressure cookers. Many of these stars come from satellite galaxies or galactic groups with strange chemical makeups, where furious waves of starbirth, called starbursts, are constantly shaking up the clouds of gas and dust. To truly grasp how terrifyingly powerful these gigantic stars can be, we need to first understand where they come from and how they grow. One key factor in the birth of these giants is something called metallicity, which in astronomy refers to how much of the gas contains elements heavier than hydrogen and helium. These heavier elements, which astronomers call metals, include things like carbon, oxygen and iron, materials created inside older stars and then scattered into space when those stars died. Here's the surprising part. The less of these metals a gas cloud has, the easier it is for it to collapse and form a massive star. That's because metals help gas clouds cool down by releasing heat, which makes them break up into many smaller stars. But in places with fewer metals, like certain regions in a nearby galaxy called the Large Magellanic Cloud, the gas clouds stay warmer and more intact. Instead of breaking into tiny pieces, the whole cloud can collapse into one or just a few very large stars. These metal-poor galaxies become star factories, not for tiny flickers of light, but for huge, blazing titans. In such places, star clusters are born in great numbers, sometimes hundreds or even thousands of stars forming all at once. In the middle of this cosmic chaos, some lucky stars begin to suck up more gas than their neighbours. They grow fast, devouring their surroundings in a kind of cosmic cannibalism, where only the strongest survive and thrive. The first stars to form, especially those in the densest parts of a gas cloud, get the biggest helping of material. They hoard the cosmic fuel and become supergiants, hypergiants, and what astronomers sometimes call monster stars. But it's not just where a star forms, it's also how the gas cloud moves. If there's turbulence, wild, chaotic motion, or if the cloud spins just right, it can push material toward the centre with stunning speed. And when gravity wins over pressure, a single star can grow to be dozens or even hundreds of times more massive than our Sun before it even fully ignites. There's a strange cosmic irony in all this. While it's harder to form these enormous stars once they exist, they dominate everything around them. Their powerful light and radiation can change the shape of nearby gas clouds. Sometimes they trigger the birth of new stars. Other times their energy is so intense that they stop star formation entirely, like a cosmic queen demanding all the attention and refusing to let anyone else shine. Here's one of the most fascinating things scientists have discovered. It may have been much easier for these colossal stars to form in the early days of the universe. Back then, the first galaxies were filled mostly with pure hydrogen and helium, no metals at all. This was the perfect setup for what astronomers call population 3 stars, the first generation of stars ever. These ancient giants might have been hundreds or even thousands of times heavier than the Sun. We've never seen them directly, but their descendants, like the modern behemoth stars, might still be shining, far away, as echoes of that long-ago chaos. One of the best places to study this kind of extreme starbirth is a nearby dwarf galaxy, called the Large Magellanic Cloud, or LMC for short. If the Milky Way is like the capital city of our cosmic neighbourhood, the LMC is the wild frontier, a rough, energetic place full of surprises. Even though it's small, just about 1/10 the mass of the Milky Way, the LMC packs a powerful punch. Located around 163,000 light-years from Earth, it orbits our galaxy like a close companion, and despite its size, it's incredibly good at producing massive stars. In fact, it creates more high-mass stars per unit of gas than the Milky Way does. The LMC is like a galactic forge, glowing with fiery star nurseries and bright clouds of gas called nebulae. One of the most famous of these is 30 Doradus, better known as the Tarantula Nebula. It's one of the most active star-forming regions anywhere in our local galactic group. So what makes the LMC so special? It all comes down to chemistry and chaos. Its gas has a lower metallicity than the Milky Way, meaning it has fewer heavy elements. This keeps the gas warmer and less likely to break into small pieces, leading to fewer but much larger stars. The LMC doesn't go for balance, it goes for extremes. This makes it the perfect birthplace for giants like the behemoth star. Hidden deep within the LMC and wrapped in a thick cloud of dust, this star is almost impossible to see, even with powerful infrared telescopes. But what we do know is jaw-dropping. It is over 1,500 times wider than our Sun and shines with a light 280,000 times brighter. And it's not just big, it's also slowly falling apart. The behemoth star is losing its outer layers in a steady glowing breath, like a tired giant exhaling its life into space. Because it's so close, with less dust blocking the view, the LMC has become a cosmic laboratory where scientists study how stars live and die, especially the massive ones. Telescopes like the Hubble Space Telescope and the Very Large Telescope can look straight into its star clusters and nebulae, watching giants being born, living out their fiery lives, and collapsing into silence. Even more fascinating is the idea that the Milky Way's gravitational pull might be stirring up the gas in the LMC, sparking even more waves of star formation. Some scientists believe that billions of years from now, our two galaxies will collide in a spectacular cosmic dance. It would be like fireworks on a galactic scale, with stars flying out like glowing sparks. The LMC offers us a glimpse into what the universe was like in its younger, wilder days. Its strange structure, its metal-poor gas, and its furious star nurseries all reflect what early galaxies may have looked like. So when we study stars like the behemoth star, we're not just learning about one giant, we're peeking into the ancient drama that shaped the cosmos itself. The Large Magellanic Cloud isn't just a small galaxy next door, it's a primordial furnace, a wild, beautiful reminder that in the universe, size isn't everything, but extremes make all the difference. A hypergiant star is one of the rarest and most extreme kinds of stars in the entire universe. These giants shine with incredible brightness, have massive sizes, and lose material from their outer layers at astonishing rates due to their powerful stellar winds, streams of gas blown away by their own intense radiation. In the language that astronomers use to classify stars, called the MKK system, a hypergiant falls into luminosity class 0. But you don't often see this class 0 label written down in scientific papers. It's mostly used for very special types of stars, like yellow hypergiants, red supergiants, and blue supergiants that show strong glowing lines in their spectra, what scientists call emission spectra. More commonly, hypergiants are described with labels like Ia 0 or Ia+, while red supergiants don't usually get those special classifications, even when they're massive. Why are astronomers so fascinated by hypergiants? Because these stars hold important clues to how stars are born, how they change over time, and how they eventually die, often in huge explosions called supernovae. Famous examples of hypergiants include the Pistol Star, a blue hypergiant that lies close to the centre of our galaxy. It's one of the brightest stars ever discovered. Rho Cassiopeiae, a yellow hypergiant that is so bright you can see it with your own eyes from Earth, and Mu Cephei, also known as Herschel's Garnet Star, which is one of the biggest and brightest stars ever observed. Back in the year 1956, two astronomers named Feast and Thackeray used the term supergiant, which was later changed to hypergiant, to describe stars that were brighter than an absolute magnitude of -7. That's extremely bright. Later, in the year 1971, another astronomer named Keenan suggested using the term hypergiant only for those supergiants that show a very wide, bright emission line in a part of their light spectrum called H-alpha. This feature hints at a very extended atmosphere and strong mass loss. Today, Keenan's rule is still the one most scientists use, which means that in some cases, a regular supergiant might actually shine brighter than a hypergiant of the same type. One way scientists can tell a star is a hypergiant is by looking at its spectral lines, the fingerprints of light that tell us what the star is made of. In hypergiants, these lines are usually stretched and shifted toward the red end of the spectrum, a feature called the P Cygni profile. But when it comes to the coolest hypergiants, those with lower surface temperatures, this method isn't very useful, so astronomers mostly rely on how bright the star is and how much material it is losing. Stars that start their lives with more than 25 times the mass of our Sun don't stay in the stable main sequence phase for very long. Instead, they quickly become blue supergiants, shining brightly while still quite hot. Then, without changing brightness much, they expand and cool into red supergiants. Later they shrink again, heat up, and might go back and forth between hot and cool phases in what scientists call blue loops. In the end, they usually explode as a supernova, or lose their outer layers and turn into a special kind of hot star called a Wolf-Rayet star. But if a star is born with more than 40 times the mass of the Sun, it's too powerful to ever settle into a red supergiant phase. These stars are so luminous that their outer layers can't stay stable and are blown away before the star gets a chance to cool down. The most massive stars of all, especially those that spin quickly and have more internal mixing, may skip all intermediate stages and become Wolf-Rayet stars directly. Hypergiants live at the very top of the Hertzsprung-Russell diagram, which is a chart astronomers use to compare stars by brightness and temperature. These hypergiants might be either freshly evolved massive stars that have just left the main sequence, or they might be older stars that have already gone through the red supergiant phase and lost much of their mass. Just looking at their brightness and temperature isn't enough to tell the difference. Young massive stars with lots of hydrogen left are usually more stable, while older stars that have burned most of their hydrogen and are filled with heavier elements become unstable. Their atmospheres become puffed up and harder to hold together due to high radiation pressure and weaker gravity. These unstable, massive stars near the Eddington limit, the point where radiation pressure nearly blows the star apart, are the ones we call hypergiants. Yellow hypergiants, in particular, are thought to be stars that have already passed through the red supergiant phase and have lost most of their hydrogen-rich outer layers. Some yellow supergiants are still on their way to becoming red supergiants, but that stage is short and rare. Because yellow hypergiants are in the post-red supergiant stage, they have an upper brightness limit of about 500,000 to 750,000 times the brightness of the Sun. Blue hypergiants, on the other hand, can be several million times brighter than the Sun. Most hypergiants don't shine with a steady light. Their brightness changes slightly because of chaotic processes happening deep inside them. However, in some zones of instability, especially where luminous blue variables, LBVs, and yellow hypergiants exist, these changes can be more dramatic. Hypergiants don't live very long. While stars like the Sun can survive for around 10 billion years, hypergiants last only a few million years. They are born in the largest, most crowded star-forming regions in space. Because they burn through their fuel so fast and die young, we haven't found very many of them, despite the fact that they are incredibly bright and can even be seen in nearby galaxies. Some stages in their lives, such as the LBV phase, might only last a few thousand years, which is like a blink of an eye in the vast history of the universe. Hypergiants are not just huge, they shine with an almost unbelievable brightness. As a star's mass grows larger, its brightness increases dramatically. In fact, hypergiants are often so luminous that they reach a point known as the Eddington limit. This is the critical balance point where the outward push of light and radiation from inside the star becomes strong enough to nearly equal the inward pull of gravity. If the radiation becomes just a little stronger than gravity, it could actually start to blow the outer layers of the star away. In simpler terms, imagine the star is trying to hold itself together with gravity, but the light it's producing is pushing outward with such force that it could start tearing the star apart. If the light pressure goes beyond this Eddington limit, the star would begin to lose mass in violent bursts, shedding huge amounts of material. These powerful outbursts stop the star from becoming even more luminous, acting like a kind of safety valve to prevent it from burning too brightly for too long. One of the best-known examples of this is Eta Carinae, a truly monstrous star that might be around 130 times more massive than our Sun. Its light shines with a power estimated to be 4 million times brighter than the Sun. Astronomers believe Eta Carinae has already gone beyond the Eddington limit at least once. This might have happened between the years 1840 and 1860, during a series of gigantic outbursts, where the star lost mass much faster than current science says should be possible through ordinary stellar winds. Usually stars lose material through winds powered by what's called line-driven radiation. That means atoms in the star's outer layers absorb light at specific wavelengths, helping to push material away. But hypergiants like Eta Carinae are so intense that they may also have continuum-driven winds, a more extreme kind of radiation pressure that doesn't need the presence of metal atoms like carbon or iron. This is important because many massive stars, especially very old ones or those born in the early universe, are metal poor, meaning they don't have many elements heavier than helium. This continuum radiation might explain how the very first stars in the universe, born right after the Big Bang, were able to lose mass and stay below a certain size, even though they had no metals at all. It could even be the reason why stars can only grow so massive before something stops them. Another idea scientists are exploring is that hypergiants might sometimes experience deep internal explosions. These would happen far below the surface, in the star's inner layers, where heat convection, the process of moving heat around, is not working properly. If the heat can't escape the way it's supposed to, the density of the material might flip, creating instability and possibly leading to a huge blast that throws parts of the star's outer layers into space. But this is still a theory, and hasn't been studied deeply yet. There's also a curious concept called a pseudo-photosphere. Normally, the photosphere is the visible surface of a star, the layer where its light escapes. But in some hypergiants, especially when powerful stellar winds are present, this visible surface might not be the real outer layer of the star. Instead, it could be a thick cloudy shell of wind that forms a fake surface. This wind-made surface would be much cooler than the hotter star underneath. Scientists think this might explain why some bright stars, like yellow hypergiants, appear cooler than expected. These stars might actually be luminous blue variables, LBVs, that have formed a pseudo-photosphere and just look cooler than they really are. Hypergiants are massive, evolved stars that shine with incredible brightness. On a diagram called the Hertzsprung-Russell diagram, which maps out different types of stars by their temperature and luminosity, hypergiants often overlap with other kinds of stars. It's sometimes hard to tell if these differences in classification mean the stars started out differently, are at different stages of life, or if we're just seeing them in different ways. While many theories agree on how these stars behave, the exact categories can get blurry. Most supergiants, which are already enormous stars, aren't as bright as hypergiants, though a few come close. What sets hypergiants apart is how wild and stormy they are. Their outer layers are often shedding mass, and they show strong hydrogen emissions in their light spectrum. Supergiants that started with less mass usually don't go back to a cooler red supergiant stage. Instead, they explode as supernovae or end up as white dwarfs, small, dense remnants. Luminous blue variables, LBVs, are a special class of very hot and bright stars that show sudden changes in their light spectrum. Most of the time, they exist in a quiet state, in a region where brighter stars are usually hotter. but sometimes they have huge eruptions and shift to a strange zone on the diagram where stars of all brightness levels settle at about 8,000 degrees Kelvin, or roughly 13,940 degrees Fahrenheit. This area is near the unstable territory where yellow hypergiants are found. Scientists still aren't sure if yellow hypergiants ever manage to evolve into LBVs or go straight into exploding. Blue hypergiants live in the same area of the diagram as LBVs but don't always show the same behaviour. Some LBVs have hypergiant-like features some of the time, but not all astronomers agree on whether they should be considered true hypergiants. Some experts believe blue hypergiants might later turn into LBVs, or that LBVs could become blue hypergiants again. Others think some lower mass LBVs may be transitioning into or from cool hypergiants, or maybe they're something entirely different. Then there are the mysterious Wolf-Rayet stars. These are some of the hottest stars we know of, and they've already lost most of their outer layers. One specific group called WNL stars, which stands for late-type Wolf-Rayet stars, are a bit cooler and show nitrogen in their light. Some of these stars might be the stage hypergiants reach after losing enough mass. But there's a twist. Some hydrogen-rich WNL stars might actually be the ancestors of blue hypergiants or LBVs. A few related types, like OFT stars and WN9 stars, may be short-lived phases between massive main sequence stars and hypergiants. Even more fascinating is that some LBVs in their quiet phase have been seen showing WNL-like spectra, and some stars thought to be off-WNL types have suddenly changed, looking more like blue hypergiants. It turns out that rapid spinning in massive stars causes them to fling away their outer layers quickly, skipping the supergiant stage altogether and going straight into the Wolf-Rayet phase. Despite their strong light and heavy emissions, stars like Wolf-Rayet stars/stars, cool/stars, off plus and off types are not officially considered hypergiants. They belong to their own special families, with unique spectral features that set them apart. Hypergiant stars are some of the rarest and most mysterious giants in the universe, and that makes them incredibly difficult to study. These stars are not just rare, they are unpredictable too. Many of them have constantly changing light signatures, known as spectra, which can make it hard for astronomers to understand exactly what's going on inside them. Because of this, scientists often place hypergiants into broad groups based on the general patterns they see in their light, rather than specific details. Some of the most fascinating hypergiants are part of a special group called luminous blue variables, or LBVs. These are unstable, massive stars that go through wild changes in brightness and behaviour over time. In fact, some of them are only considered hypergiants during certain parts of their life cycles. Here are a few extraordinary examples. AG Carinae is a truly massive star located in the Carina constellation, far in the southern sky. It belongs to the LBV class and is in the middle of a dramatic transformation, from an O-type star, a very hot and bright star, into a Wolf-Rayet star, which is a stripped-down, burning core nearing the end of its life. Eta Carinae, perhaps one of the most famous stars in our galaxy, also lives in the Carina constellation, specifically inside the breathtaking Carina Nebula, officially called NGC 3372. Eta Carinae is a true monster of a star. Its mass could be anywhere from 120 to 150 times greater than the Sun's, and it shines with a light that is about 4 to 5 million times brighter than our Sun. Because of its strange and extreme behaviour, some scientists think it may be something even more exotic than a typical LBV. P Cygni, found in the northern constellation of Cygnus, is another key member of this group. It is so important that it serves as the prototype, or the textbook example, of what an LBV's light spectrum usually looks like. S Doradus, located in the Large Magellanic Cloud, a nearby galaxy, in the southern constellation of Dorado, is another famous LBV. In fact, for a long time these stars were actually called as Doradus variables because of how well this star represents the group. The Pistol star, officially known as V4647 Sagittarii, lies close to the very centre of our Milky Way galaxy, in the constellation of Sagittarius. It is over 25 times more massive than our Sun, and blazes with the power of about 1.7 million suns. Scientists think it might be an LBV, but they haven't yet confirmed whether it changes brightness over time. Not all hypergiants are blue. Some come in other colours too. Yellow hypergiants usually have what's called a late A-type to early K-type spectrum, which means their surface temperatures are lower than blue stars but still very hot. When A-type hypergiants are especially bright, they're sometimes referred to as white hypergiants instead. There are also some cooler hypergiants, which show up as red or orange stars. Two of these likely exist in a set of newly discovered star groups called the scutum red supergiant clusters. One of these stars is named F15 and might be joined by F13 in a cluster called RSGC1. Another one, known as star 49, is part of RSGC2. Some of these red or cool hypergiants belong to the K to M spectral types, which include the largest stars ever seen when measured by their radius. These stars can be truly gigantic. Some of them have radii between 1,000 and 2,000 times that of the Sun. That means if they replace the Sun in our solar system, they could stretch far beyond the orbit of Jupiter. Even though astronomers don't often label red supergiants with the special hypergiant class, the term red hypergiant is sometimes used to describe the most bloated and unstable among them. Red supergiants are some of the most gigantic stars we know, truly titans of the cosmos. These stellar giants belong to what astronomers call the supergiant class, officially known as luminosity class 1 in the Yerkes or Morgan-Keenan system. In terms of volume, red supergiants are the largest stars in the entire universe, even though they are not the most massive or the most brilliant in terms of energy output. Two of the most famous and brightest red supergiants are Betelgeuse, which sparkles in the constellation Orion, and Antares A, the glowing heart of the Scorpius constellation. These two are the only red supergiants visible with first magnitude brightness, meaning they shine as some of the brightest stars in our night sky. Stars are grouped into different categories based on how bright they are and how strong gravity is at their surface. Scientists use the patterns in a star's light, known as its spectrum, to figure this out. Certain lines in the spectrum tell us how tightly packed the star's material is. If the surface gravity is low, that means the star is big and puffy, and that usually means it's extremely luminous or bright. Using this method, stars are sorted into groups or luminosity classes: supergiants, bright giants, giants, subgiants, and dwarfs, like our Sun, which is a main sequence star. Even within the first class, there are further divisions. A star can be a regular supergiant, a very bright one, or fall in between. In some rare cases, especially for the most extreme stars with very weak gravity and intense mass loss, astronomers might call them Class 0 or Ia+, marking them as hypergiants, the wildest of all stars. However, the term hypergiant is almost never used for red supergiants, except for a few very unstable examples like VY Canis Majoris and NML Cygni, sometimes called red hypergiants. The word red in red supergiant tells us that these stars are cool, at least compared to other stars. Most red supergiants belong to the M-type class, which includes the coolest stars, and a few are K-type, which are slightly warmer. But K-type supergiants are quite rare, as they don't stay in that stage for very long. Some of these K-type stars are even referred to as orange supergiants, for example Zeta Cephei, or yellow hypergiants, like the star HR 5171AA. Red supergiants have surface temperatures below 4,100 degrees Kelvin, which is cooler than the Sun, but they are so large that they still shine with incredible brightness. These stars can be several hundred times to even more than 1,000 times the size of our Sun in radius. However, a star doesn't have to be huge to be called a supergiant. What really matters is how bright it is compared to its temperature. For example, Alpha Herculis is a cool giant star with a radius between 264 and 303 times that of the Sun, yet it is not classified as a supergiant. Meanwhile, Epsilon Pegasi, a K2 supergiant, has a radius of only 185 times that of the Sun, yet it qualifies because of its brightness and other features. Despite being cooler than our Sun, red supergiants are tens of thousands or even hundreds of thousands of times more luminous, simply because of their enormous size. The biggest red supergiants are believed to reach a maximum size of about 1,500 times the Sun's radius. Beyond that point, a star would become so unstable that it simply couldn't hold itself together. This theoretical limit is known as the Hayashi limit. These stars are not born this big. They start out as massive hot stars with about 10 to 40 times the mass of our Sun. Over time, they swell into red supergiants as they burn through their fuel. But stars with more than about 40 solar masses do not become red supergiants. Instead, they go through different evolutionary paths, often staying hot and compact until the end. At the upper range of red supergiant size and brightness, these stars lose mass at astonishing rates, far faster than our Sun. In fact, they can blow off millions of times more material than the Sun every year. This fierce shedding of outer layers creates glowing clouds of gas and dust, nebulae, surrounding the star. By the time a red supergiant reaches the end of its life, it might have lost a huge fraction of its original mass, usually ending up with about 10 times the Sun's mass when its core finally collapses. Exactly how much mass remains depends on how fast the star spins and what elements it started with. Red supergiants are also variable stars, meaning their brightness changes over time. Most of them flicker and fade slightly, although not always in a regular pattern. Because of this, they are called irregular or semi-regular variables, and they even have their own subclasses: slow semi-regular variables and slow irregular variables. Sometimes these stars vary only a little, but a few can change brightness by as much as 4 magnitudes, which is a huge shift in visible light. Studies have shown that these brightness changes happen for a few reasons. Some red supergiants show many overlapping rhythms, caused by things like pulsations, massive stellar winds and surface disturbances. Others show changes due to large convection cells, giant bubbles of hot gas rising and falling on the star's surface. These are much fewer in number, but far larger than those found on the Sun, and can lead to brightness variations as the star spins. When scientists look at red supergiants through powerful instruments called spectroscopes, they see a complex pattern of absorption lines, dark fingerprints of different elements and molecules in the star's outer layers. These spectral features, especially metal lines and molecular bands like those from cyanogen, Cn, or calcium, Ca2, help astronomers figure out a star's size and brightness class. Red supergiants are wonders of the universe, the slow-burning titans near the end of their lives. Though they're not the hottest or the heaviest, they are among the largest and most luminous objects in the cosmos, and one day, these giants will end their lives in spectacular supernova explosions, enriching space with the heavy elements needed to form new stars, planets, and maybe even life itself. Around red supergiant stars there is a cloud of gas and dust called circumstellar material, and this region often glows in a special way known as maser emission. Think of a maser like a cosmic laser, but instead of light, it emits intense microwaves. These emissions usually come from water vapor and silicon monoxide, but sometimes they also come from hydroxyl molecules, although this happens only in thin specific layers around the star. Astronomers can use incredibly precise radio telescopes, like the Very Long Baseline Interferometry or the Very Long Baseline Array, to map these masers. This helps scientists study the shape and behavior of the material around red supergiants in amazing detail. It also allows them to measure exactly how far away these stars are by using a method called parallax. So far, this technique has mostly been used on individual stars, but in the future, it could help us better understand the layout of our entire galaxy and find red supergiants that are hidden behind thick clouds of dust. Even though red supergiants have burned through all their hydrogen fuel deep in their cores, the outer layers of these stars still contain mostly hydrogen. However, just before they explode, they lose so much of their outer material that helium can become as common as hydrogen on the surface. In some extreme cases, theoretical models suggest that they could lose nearly all of their hydrogen, leaving helium as the most abundant surface element. When stars first evolve into red supergiants and leave the main part of their life, called the main sequence, they usually have more oxygen than carbon at their surface, and nitrogen is the least abundant of the three. This reflects the chemical mix they were born with. But as the star ages, deep layers of nuclear fusion products are stirred up to the surface. This process, known as dredge-up, depletes carbon and oxygen while increasing nitrogen, because the star has been fusing hydrogen into helium using a process called the CNO cycle. Red supergiants are slow spinners. They rotate very slowly, or sometimes barely at all. Even if a star spun quickly earlier in its life, the strong winds and mass loss slow it down drastically by the time it becomes a red supergiant. Some red supergiants, like Betelgeuse, do show a bit of rotation, and scientists think this might be due to interactions with a companion star in a binary system. Interestingly, even though the outer layers rotate slowly, the cores of these stars can still be spinning rapidly, creating a large difference between core and surface rotation speeds. Stars are often grouped by a classification called luminosity class, and red supergiants fall into one of these. But this system can mix very different types of stars into one group. Scientists prefer a more precise definition. A true red supergiant is a massive star that begins fusing helium in its core without forming a degenerate, extremely dense helium core, or undergoing a helium flash. These stars will always go on to fuse even heavier elements and eventually collapse in a spectacular explosion known as a supernova. Some less massive stars, those with lower mass than typical red supergiants, can still appear like supergiants based on their brightness. They might reach a luminosity of about 1,000 times that of our Sun while on a phase called the asymptotic giant branch, AGB. But these stars are quite different. They have different chemical compositions, they pulsate in different ways, and they end their lives not with supernovae, but by shedding their outer layers and becoming white dwarfs surrounded by glowing shells called planetary nebulae. There is a special class of these AGB stars called super AGB stars. These stars have masses of about 7 to 9 times that of our Sun. They're right on the edge, massive enough to begin fusing carbon in their cores, but not quite able to reach the conditions that form an iron core. Some of them might still explode, producing a rare kind of supernova caused by a process known as electron capture. A rare group of bright, low-mass stars called RV Tauri variables, which lie on an unstable region of the star chart, also belong to the AGB or post-AGB category. They pulse in brightness in a distinctive semi-regular way. Red supergiants develop from main sequence stars that began life with a mass of between about 8 and 30 to 40 times that of the Sun. Stars more massive than this don't cool down enough to become red supergiants. Less massive stars go through a different path. They form dense helium cores, experience a helium flash, burn helium around a core of carbon and oxygen, then shed their outer layers and end up as white dwarfs. Interestingly, some AGB stars may temporarily shine as brightly as real red supergiants, reaching tens of thousands of times the Sun's brightness. And some super AGB stars, those in the 7 to 9 solar mass range, can even begin to fuse carbon and may end in unusual supernovae caused by the collapse of an oxygen neon core without ever building up iron. Main sequence stars with between 10 and 30 or 40 times the Sun's mass start out extremely hot. Their surface temperatures are between about 25,000 and 32,000 degrees Kelvin. These stars are classified as early B-type or very late O-type stars. They are already very bright, glowing with a power of between 10,000 and 100,000 times that of the Sun, thanks to a fast type of fusion called the CNO cycle. Inside, they are fully mixed by convection. But unlike the Sun, their outer layers are not convective. After spending about 5 to 20 million years burning hydrogen in their cores, these massive stars run out of fuel. They then begin to burn a shell of hydrogen around a helium core. This change causes them to expand and cool, turning into supergiants. Their brightness increases to about 3 times what it was, and helium becomes more abundant at the surface, up to about 40%, but heavier elements are still mostly unchanged. As they cool further, these stars often cross an unstable region known as the Cepheid instability strip. Some of the most massive may temporarily become yellow hypergiants. Eventually they cool into the red supergiant phase, reaching late K or M spectral types. During this time, helium fusion begins deep in the core, but it doesn't immediately affect the surface appearance. The star develops a huge convective zone reaching from the surface deep into the interior, which brings nitrogen and some heavier elements to the surface. Some red supergiants go through blue loops, temporary periods when they get hotter before cooling back into the red phase. These loops are caused by a mix of factors: mass, rotation, and the star's chemical composition. During a blue loop, the star's temperature can rise to around 10,000 degrees Kelvin. Blue loops are more likely when the helium core grows large compared to the rest of the star and leads to rapid mass loss. Within just 1 or 2 million years of becoming red supergiants, these stars run out of helium in their cores. They then begin to burn carbon and eventually fuse even heavier elements layer by layer. This continues until the core is made of iron, which cannot be fused to produce energy. At this point, the core collapses in a matter of seconds, triggering a supernova explosion. From the moment carbon fusion begins, the star has only a few thousand years left. In most cases, the collapse happens while the star is still a red supergiant. Its hydrogen-rich outer layers are blown off, producing a Type II supernova. The ejected hydrogen cools slowly, so the brightness of the explosion stays high for a long time before finally fading, a signature of Type IIp supernovae. The most luminous red supergiants, those with lots of heavy elements like the Sun, can lose most of their outer layers before the final explosion. These evolve into yellow hypergiants or luminous blue variables and explode as Type IIL supernovae. These still have hydrogen, but not enough to create the long-lasting brightness plateau. If the star has lost nearly all of its hydrogen, it may produce a rare Type IIb supernova. These start with a normal hydrogen spectrum, but the hydrogen lines fade quickly, making them look more like a Type Ib supernova. Astronomers have identified the stars that exploded in Type IIp supernova. They had surface temperatures between 3,500 and 4,400 degrees Kelvin, and luminosities between 10,000 and 300,000 times that of the Sun. These match predictions for lower mass red supergiants. A few stars have been seen just before Type IIL and Type IIb explosions. These stars had temperatures up to about 6,000 degrees Kelvin and luminosities around 100,000 times that of the Sun. They seem to be slightly more massive red supergiants that were losing mass quickly. Interestingly, no one has yet observed the explosion of the most luminous red supergiants. Scientists believe these stars shed all their outer layers and become Wolf-Rayet stars, hot, stripped-down stars, before they finally explode. Red supergiants are giant stars that have reached an advanced stage in their life, but they don't stay in that phase for long. In fact, these stars are always quite young, no older than about 25 million years. That might sound like a long time to us, but in the life of a star, it's actually very short. Red supergiants are born from very massive stars, and those massive stars usually only form in big groups of stars called clusters. So we usually expect to find red supergiants hanging around places where lots of stars were born together. However, there's a twist, because only the rare, really massive stars can become red supergiants, and because these giants burn through their fuel so fast, there are never many of them in one place at the same time. Even in a big cluster, you might only find a handful of red supergiants. For example, the massive star cluster known as Hodge 301, located in the famous Tarantula Nebula, has only 3 red supergiants. Before the 21st century, the largest number of red supergiants ever found in a single cluster was 5. That was in a cluster called NGC 7419. More often than not, these stars are found alone rather than in groups. For instance, the bright and famous red supergiant Betelgeuse shines alone in the Orion OB1 association, and Antares stands out in the Scorpius-Centaurus group. But things started to get more exciting in the year 2006. That's when astronomers discovered several huge star clusters near the base of one of our galaxy's spiral arms, called the Crux Scutum Arm. Each of these clusters held multiple red supergiants. One of them, called RSGC-1, has at least 12 red supergiants. Another, RSGC-2, also known as Stephenson-2, has at least 26. Then there's RSGC-3 and RSGC-4, also called Alicante-8, each with at least 8 red supergiants. Altogether, astronomers have confirmed the existence of 80 red supergiants in just a small patch of sky in the direction of these clusters. This remarkable collection of stars appears to be the result of a giant wave of star formation that happened about 10 to 20 million years ago near the centre of our galaxy, where the central bar of the Milky Way begins. Astronomers have also found more big star clusters on the opposite side of this galactic bar. However, none of them contain quite as many red supergiants as the clusters near the Crux Scutum Arm. Even though red supergiants are rare in the universe, They shine so brightly and can be so large that we can spot them from far away, even with just the naked eye. Some of these stars even change brightness over time, which makes them even more interesting to astronomers. A star named Mira was once believed to be a red supergiant, but scientists now know that it belongs to a different type of giant star known as an asymptotic giant branch star. Some red supergiants are even more extreme. They're so huge and so bright that they're called red hypergiants. These monsters of the cosmos can have radii that are more than 1,000 times larger than our Sun. In a major survey of the nearby Magellanic Clouds, 2 small galaxies that orbit our Milky Way, astronomers found about a dozen very bright M-class stars that were each more than 250,000 times as luminous as the Sun. These enormous stars had sizes starting from about 1,000 times the radius of our Sun and going even higher. A subgiant is a special kind of star that sits in between 2 more familiar types of stars. It shines more brightly than a typical main sequence star like our Sun, but it is not as bright or as large as a giant star. The word subgiant can mean 2 things. It refers to a specific group in the system used to classify stars by their brightness, and it also describes a particular stage in a star's life as it ages and changes. The name subgiant was first introduced back in the year 1930. It was used to describe stars in the G and early K spectral classes, with absolute magnitudes between +2.5 and +4. These stars seem to fill a gap between the clear-cut examples of main sequence stars like the Sun and giant stars such as Aldebaran. Even though subgiants were not as common as the stars in the main sequence or the giant category, astronomers realized they were an important part of the bigger picture. Stars are sorted using a system called the Yerkes spectral classification, which uses letters and numbers to show how hot a star is, like a 5 or M1, and Roman numerals to show how bright a star is compared to others of the same temperature. In this system, luminosity class 4, the Roman numeral 4, is used for subgiants. These stars are positioned between class 5, main sequence stars, and class 3, giant stars. To figure out what class a star belongs to, astronomers don't just measure its brightness directly. Instead, they compare its light spectrum with those of other stars that are already well understood. Certain patterns in the spectrum, such as how deep or wide particular absorption lines are, can reveal how strong the gravity is at the star's surface, which helps determine whether it's a dwarf, subgiant or giant. Later studies showed that some stars originally labelled as subgiants were actually made up of 2 stars whose light blended together, or they were stars that varied in brightness over time. Even so, many of those early stars are still used today as the standard examples of subgiants. Interestingly, subgiant classifications are rare for the very hottest stars, O-type, and for stars cooler than spectral type K1. The subgiant branch is also the name of a phase in the lives of stars with low to medium mass, like the Sun. But not every star that looks like a subgiant is actually going through the subgiant phase, and vice versa. For example, stars like FK Comae Berenices and 31 Comae Berenices are probably in the subgiant evolutionary phase, even though they are sometimes labelled as giants. This can happen because a star's classification is influenced by more than just its brightness. It can also be affected by things like how fast the star spins, how much metal it contains, and even unusual chemical patterns. When a star like the Sun gets older, the amount of hydrogen in its core starts to run out. As this happens, the core contracts and heats up, making the hydrogen fusion around it go faster. This increases the star's brightness, and causes it to gradually move off the main sequence and begin the transformation into a subgiant. This shift shows up in a star chart called the Hertzsprung-Russell diagram as a widening of the main sequence band, because stars brighten as they age. Once the hydrogen in the core is completely used up, the core collapses and gets even hotter. Hydrogen then begins to fuse in a shell surrounding the core. This shell burning produces even more energy than the previous core burning phase. The outer layers of the star begin to swell and cool, and when the surface temperature drops to around 5,000 kelvins, the star becomes brighter again. This is when the star begins its journey up the red giant branch. The brief period of change between the main sequence and red giant stages is known as the subgiant phase. How this subgiant phase unfolds depends on the mass of the star. For example, stars with less than 40% the mass of the Sun, or 0.4 solar masses, are mostly made of convective material, meaning heat and particles flow through the star like boiling water. These stars keep fusing hydrogen throughout their entire volume and don't go through a subgiant stage at all. In fact, their life on the main sequence is so long, many times longer than the current age of the universe, that we have never seen one evolve beyond it. On the other hand, stars that are at least 40% as massive as the Sun develop a more complicated structure with a central core that doesn't convect. As soon as they run out of hydrogen in the core, the surrounding shell begins to fuse hydrogen instead. At this point, even though the star is now technically a subgiant, there's not much visible change on the surface. As this hydrogen shell keeps fusing, it produces helium, which slowly accumulates in the core. The energy from the shell fusion pushes outward, causing the outer layers of the star to expand. Depending on the star's mass, it can grow to between 2 and 10 times its original size. Despite this growth, the surface temperature doesn't change very much, so the star's spectral class stays nearly the same, especially for less massive stars in this range. However, because the surface area of the star becomes much larger, it radiates much more energy. For example, a star with a radius twice that of the Sun would give off 4 times as much energy, while a star with 10 times the Sun's radius would release 100 times more. This dramatic increase pushes the habitable zone, the region where liquid water could exist on a planet's surface, much farther out. During this time, the helium core is still not hot or heavy enough to start fusing helium. It stays in balance with the hydrogen-burning shell around it. As the hydrogen shell slowly burns outward and adds more helium to the core, the outer layers of the star continue to expand. The brightness of the star remains roughly steady during this stage, so in star clusters the subgiant branch appears as a short horizontal line filled with stars. Eventually, after somewhere between 1 and 8 billion years, the helium core becomes so massive that it can no longer support its own weight. The core becomes what scientists call degenerate, meaning it is supported by quantum forces rather than normal gas pressure. This triggers another round of changes. The temperature rises, the fusion shell burns even faster, the outer layers become unstable and convective, and the star grows brighter, without changing much in surface temperature. At this point, the star officially enters the red giant stage. Stars that are as massive as our Sun, or even larger, behave quite differently from smaller stars during their long life on the main sequence. While they are still fusing hydrogen in their cores, these stars have a central region that is churning and mixing due to convection. Over time, this central region builds up a large core of helium. Before they even run out of hydrogen in the entire convective zone, the helium core has already grown to take up a big part of the star's interior. Eventually, hydrogen fusion comes to a stop in the center of the star. With no more nuclear energy to hold it up, the core begins to shrink and heat up. This also causes the whole star to shrink and its temperature to rise. Strangely enough, even though fusion has stopped, the star actually shines more brightly during this phase. This process of heating and contraction can last for several million years. At some point, the temperature around the core becomes high enough to restart hydrogen fusion, not in the core itself, but in a shell that surrounds it. This reignited fusion in the shell causes the star's temperature and brightness to stop increasing. Instead, the outer layers of the star begin to swell, and the star cools down. This moment, when the star shifts from heating up to expanding and cooling, creates a noticeable kink in its path on the Hertzsprung-Russell diagram. Astronomers call this kink the end of the main sequence and the beginning of the subgiant phase. For stars with a mass less than about 2 times the mass of the Sun, their helium cores are still below a certain limit called the Schoenberg-Chandrasekhar limit. But once hydrogen shell fusion kicks in, the core quickly grows heavier and crosses that limit. More massive stars, on the other hand, already have cores that exceed this limit even before they leave the main sequence. The exact mass at which this change happens depends on 2 things: how many heavy elements, known as metals in astronomy, the star contains, this is called metallicity, and how far mixing from the convective core reaches out, which is known as overshooting. Stars with low metallicity can have cores that are unstable to convection, even if they aren't very massive. Overshooting can also cause the core to grow larger before hydrogen is completely used up. Once the helium core grows beyond the Schoenberg-Chandrasekhar limit, it cannot stay balanced with the hydrogen-burning shell anymore. The core contracts again, and the star's outer layers expand and cool. This expansion pulls energy from the center, causing the star's brightness to drop. When the outer parts of the star cool enough, they become opaque, and a new round of convection begins just above the fusion shell. The expansion then stops, and the star's brightness begins to rise once more. This moment is known as the beginning of the red giant phase. In stars with an original mass of around 1 to 2 times the mass of the Sun, the core may become a compact, degenerate ball of helium before this phase starts, just like in lower mass stars. This stage, where the core collapses and the outer layers expand, happens very quickly in cosmic terms, usually within just a few million years. During this time, the star cools dramatically, dropping from its main sequence temperature of around 6,000 to 30,000 degrees Kelvin to a cooler 5,000 degrees. Because this transition happens so fast, astronomers don't see many stars in this phase. This creates a noticeable gap in star charts known as the Hertzsprung gap, especially visible in star clusters that are between a few hundred million and a few billion years old. For stars with more than about 8 to 12 times the mass of the Sun, again depending on metallicity, things move even faster. These massive stars have large, hot, convective cores powered by a process called the CNO cycle. For them, hydrogen shell fusion and even helium core fusion begin almost immediately after the hydrogen in the core runs out, leaving no time for a red giant phase. These stars, such as the early B-type main sequence stars, quickly pass through a short subgiant stage and become supergiants. Sometimes during this brief transition, they are classified as giant stars based on their spectra. In the case of extremely massive stars, like O-class main sequence stars, the whole transformation from main sequence to giant and then to supergiant happens across a very narrow range of temperature and brightness. In fact, some of these stars may become giants, or supergiants even before they have finished burning all their hydrogen. Because of how short and confusing this phase is, astronomers rarely label such stars as subgiants. For example, a measure of surface gravity, called log-G, is used to help classify these stars. O-type giants typically have a log-G value of around 3.6, while O-type dwarfs are closer to 3.9. In comparison, K-type stars like Aldebaran have much lower surface gravity, around 1.59, and smaller stars like Alpha Centauri b have much higher values, near 4.37. This wide range allows room for stars like Eta Cephei, a subgiant, to fall neatly in between with a log-G of about 3.47. Some of the most famous massive subgiants include Theta 2 Orionis A and the primary star of the Delta Cassini system, both of which are O-class stars with masses exceeding 20 times that of the Sun. In general, stars with fewer heavy elements, low metallicity, tend to be hotter and smaller than stars with more heavy elements, high metallicity. For subgiants, this makes things a bit more complex because age and the size of the helium core at the moment a star leaves the main sequence can vary. Stars with low metallicity tend to develop bigger helium cores before leaving the main sequence, so even stars with relatively low mass can show the distinctive hook at the start of the subgiant phase. For instance, a star with just one solar mass but very low metallicity, 0.001, which astronomers classify as an extreme population 2 star, can end its main sequence life with a helium core nearly twice as massive as that of a higher metallicity, 0.02, population 1 star. That low metallicity star will also be more than 1,000 degrees hotter and over twice as luminous at the start of its subgiant life. As it continues evolving, the temperature gap between the two types becomes smaller, but the low metallicity star remains larger and nearly 4 times brighter by the end of the subgiant phase. These trends hold for stars of many different masses. For example, the minimum mass a star needs to become a supergiant rather than a red giant is noticeably lower in environments with low metallicity. The Hertzsprung-Russell diagram, often called the HR diagram, is one of the most important tools that astronomers use to understand how stars live and evolve. It is a kind of graph, or scatterplot, that helps us see the life stages of stars based on 2 main features: their temperature, or spectral type, and their brightness, which can be shown as absolute magnitude or luminosity. On the horizontal axis, the x-axis, you'll find either the temperature of the stars or their spectral class, which tells us what kind of light they give off. On the vertical axis, the y-axis, you'll see how bright or luminous the stars are. When we plot lots of stars on this graph, a clear pattern appears. Most stars fall along a wide diagonal band called the main sequence. This is where stars spend most of their lifetimes, steadily burning hydrogen in their cores. But that's not all the diagram shows. You can also spot a good number of red giants, which are stars in a later stage of life, and white dwarfs, which are the final remains of stars like our Sun, although white dwarfs are only seen if we observe very faint stars. Other areas of the diagram have far fewer stars since not all stars go through every possible stage. Subgiants are stars that have just started to leave the main sequence. They appear in a region above the main sequence, meaning they are brighter, but still below the red giants. On most HR diagrams there aren't many subgiants, and that's because a star only remains in this phase for a relatively short time, much shorter than the long main sequence phase or the giant phase. So we don't catch many of them in this brief in-between stage. Among these subgiants, the hot ones, especially those belonging to spectral class B, look very similar to main sequence stars and are hard to tell apart. But the cooler subgiants are easier to spot, as they fill the wide space between the cooler end of the main sequence and the red giants. Interestingly, below about spectral type K3, this space is completely empty. No subgiants are found there at all. Astronomers can also plot the life paths of stars on the HR diagram. These paths, called evolutionary tracks, show how a star changes over time. For a star of a certain mass, you can trace its journey from the main sequence to the subgiant phase, and then up to the red giant branch. If you look at a group of stars that all formed at the same time, such as a star cluster, you can often see this subgiant path clearly. It appears as a band of stars between the point where the main sequence ends, called the turn-off point, and the beginning of the red giant branch. However, this subgiant branch only becomes visible in star clusters that are several billion years old, because only then have stars between 1 and 8 times the mass of the Sun had enough time to evolve off the main sequence. For example, globular clusters like Omega Centauri and older open clusters like Messier 67 are old enough to show a well-defined subgiant branch in their colour magnitude diagrams, which are similar to HR diagrams but based on colour and brightness. Omega Centauri is especially fascinating because it doesn't just show one subgiant branch, it shows several, and astronomers are still trying to figure out why. The best explanation so far is that Omega Centauri might contain multiple generations of stars, meaning stars of different ages all grouped together in the same cluster. Some subgiant stars that are more massive than the Sun go through an area of the HR diagram known as the Cepheid instability strip. This happens during their first crossing of the strip, although some stars may pass through this strip more than once during a later phase known as a blue loop. Stars with masses between about 2 and 3 times the mass of the Sun may become delta Scuti variables, which are stars that pulsate in brightness. One example of this kind of star is Beta Cassiopeiae. If the stars are even more massive, they may become classical Cepheid variables during their crossing of the instability strip. However, because these massive subgiant stars evolve very quickly, it is quite rare and difficult to catch them in this short phase. One star, S. Vulpeculae, was once thought to be a subgiant on its first crossing of the strip, but later studies showed it was actually on its second crossing. Astronomers have also found planets orbiting subgiant stars. Some examples of these planetary systems include Kappa Andromedae b, Kepler 36b and c, TOI 4603b, and HD 2246993b. Betelgeuse is a massive red supergiant star located in the famous constellation of Orion, which appears in the night sky as a mighty hunter. It is usually the 10th brightest star that we can see with our eyes from Earth, and within its own constellation, it comes second only to the brilliant blue-white star Rigel. One of Betelgeuse's most striking features is its deep reddish colour, making it stand out clearly in the sky. This huge star is what astronomers call a semi-regular variable star, which means its brightness doesn't stay constant. Instead, it changes over time in a somewhat predictable pattern. Betelgeuse's brightness, or apparent magnitude, swings between 0.0 and 1.6, with a main cycle that lasts around 400 days. This makes it the star with the widest brightness range among all the brightest stars in the sky. In fact, if you were observing in near-infrared light, Betelgeuse would appear as the very brightest star in the sky. The star's official scientific name is Alpha Orionis, which is based on the naming system introduced by the astronomer Johann Bayer in the early 17th century. It's often shortened to Alpha Ori. Now let's talk about size. Betelgeuse is an absolute giant. Its radius is somewhere between 640 and 764 times that of our Sun. To put that into perspective, if Betelgeuse were magically placed at the centre of our solar system, its outer surface would stretch far beyond the orbit of Mars. It would swallow up Mercury, Venus, Earth, and Mars entirely, and even reach past the asteroid belt. Estimates of Betelgeuse's mass vary, but most calculations suggest it is between just under 10 and a little over 20 times heavier than the Sun. Despite being relatively close in cosmic terms, its exact distance from Earth is surprisingly hard to pin down. Current best guesses place it somewhere between 400 and 600 light-years away, which is quite a wide margin for a star that's considered nearby. In terms of intrinsic brightness, or absolute magnitude, Betelgeuse scores around -6, a number that marks it as exceptionally bright. But it hasn't been shining for long. Betelgeuse is a young star, less than 10 million years old, but it has evolved very quickly because of its large mass. Stars like Betelgeuse burn through their fuel quickly and don't live long. Astronomers expect that Betelgeuse will end its life in a powerful explosion known as a supernova within the next 100,000 years. When this happens, it will light up the night sky as brightly as the half moon and remain that bright for more than 3 months. But don't worry, this cosmic event, though spectacular, won't pose any danger to life on Earth. Betelgeuse wasn't always where it is now. It was once part of the Orion OB1 stellar association, a group of young, hot stars that includes those in Orion's belt. At some point, Betelgeuse was flung out of its birthplace and became what astronomers call a runaway star. It's now racing through space at a speed of around 30 kilometers per second, fast enough to produce a bow shock, like the waves in front of a boat that stretches over 4 light-years wide. Back in the year 1920, Betelgeuse made history as the first star outside our solar system to have its photosphere, the visible surface, measured directly. Scientists have since found that Betelgeuse doesn't have a perfectly round shape. Its angular diameter, or apparent size in the sky, varies between 0.042 and 0.056 arcseconds. These variations are due to several reasons, including its irregular shape, surface darkening near the edges, pulsations and differences in how it looks in various wavelengths of light. Surrounding Betelgeuse is a huge and lopsided cloud of gas and dust, about 250 times larger than the star itself. This cloud was created as the star began shedding its outer layers into space. Among all the stars visible from Earth, only the Sun and another red giant called R Doradus appear larger in the sky than Betelgeuse when measured by angular size. Something fascinating happened starting in October of the year 2019. Betelgeuse began to dim noticeably. By the middle of February in the year 2020, its brightness had dropped dramatically, becoming about 3 times dimmer than normal. From magnitude 0.5, it fell to around 1.7. Then, as mysteriously as it dimmed, Betelgeuse began to brighten again. By April of the year 2023, it had returned to a more typical brightness, reaching a peak of 0.0 in visible light. Infrared observations taken over the past 50 years showed no big change in the star's overall energy output. This led astronomers to believe that the dimming wasn't caused by the star getting weaker, but rather by something blocking its light. A study using the Hubble Space Telescope revealed that the star had likely ejected a large amount of material from its surface. This material travelled millions of miles into space, cooled down, and turned into a dust cloud that temporarily dimmed the star's light. Betelgeuse's striking red colour has fascinated people for thousands of years. The ancient Greek astronomer Ptolemy described its hue as hyperkeiros, meaning something like orangey red. Later translations rendered this description into Latin as rubedo, meaning ruddiness. Interestingly, Chinese astronomers observing 3 centuries before Ptolemy recorded Betelgeuse as yellow instead of red. If that report was accurate, it might suggest that Betelgeuse passed through a yellow supergiant stage during that time, something modern scientists now consider possible. In southern Australia, Aboriginal communities have passed down stories for generations that describe Betelgeuse's changing brightness, showing that even ancient observers noticed its variable nature. The star's brightness changes were also recorded in the modern era. In the year 1836, the English astronomer Sir John Herschel began documenting Betelgeuse's brightness in his book Outlines of Astronomy. Between the years 1836 and 1840, he noticed dramatic changes in how bright the star looked. In October of 1837, and again in November of 1839, Betelgeuse even outshone Rigel. After a quiet spell of about 10 years, Herschel observed another brightening cycle that peaked in the year 1852. Later observations continued to note these fluctuations. For instance, the American Association of Variable Star Observers reported that Betelgeuse reached a maximum brightness of 0.2 in the years 1933 and 1942, while dropping to a minimum of 1.2 in 1927 and 1941. This variability may be the reason Johann Bayer labelled Betelgeuse with the alpha designation in his Uranometria star atlas of the year 1603, suggesting it rivaled or even outshone Rigel, which normally bears the beta label. In the Arctic, the Inuit people also considered Betelgeuse brighter than Rigel, partly because it sits higher in their sky and appears redder. They called it a Lurajuak, meaning large star. The first actual measurement of Betelgeuse's size came in the year 1920, when Albert Michelson and Francis Pease, with help from John Anderson, used a 6-metre interferometer attached to a 2.5-metre telescope at Mount Wilson Observatory. They found an angular diameter of 0.047 arcseconds, which, using a parallax value of 0.018 arcseconds, suggested a diameter of around 384 million kilometres, about 2.5 times the distance from the Earth to the Sun. However, because of effects like limb darkening and observational challenges, the accuracy of this measurement had some uncertainty. In the years that followed, particularly during the 1950s and 1960s, 2 important breakthroughs transformed how astronomers understood stars like Betelgeuse. First were the stratoscope balloon projects, which lifted telescopes high into Earth's atmosphere and captured incredibly detailed images of the Sun's surface. Second was the groundbreaking book Structure and Evolution of the Stars, published in the year 1958. Written by Princeton astronomers Martin Schwarzschild and Richard Herm, this book helped introduce the use of computers to build models of how stars evolve. These efforts confirmed the presence of convective activity, similar to bubbling water, in the outer layers of stars like Betelgeuse. During the 1970s, astronomers witnessed some amazing breakthroughs in the way they observed stars. A major leap forward came with the work of French astronomer Antoine Laberry, who invented a technique called speckle interferometry. This clever method helped to reduce the blurriness caused by Earth's turbulent atmosphere, which had always made it difficult to get clear views of distant stars. Thanks to this innovation, ground-based telescopes could suddenly see with much sharper vision. It became possible to study the surface of stars like Betelgeuse, specifically its outer layer, known as the photosphere, in greater detail than ever before. Around the same time, astronomers also improved infrared telescopes placed on top of tall mountains like Mount Wilson in California, Mount Locke in Texas, and Mauna Kea in Hawaii. With these powerful tools, scientists started exploring the vast misty clouds of gas and dust that surround Betelgeuse. These clouds, known as circumstellar shells, appeared to contain enormous bubbles of gas. Astronomers believed these might have been formed by intense convection or boiling-like movements within the star, where hot gas rises and cooler gas sinks. But it wasn't until the late 1980s and early 1990s that researchers made even more dramatic discoveries. They began using a new technique called aperture masking interferometry. This involved placing a special mask with tiny holes over a telescope's opening, transforming it into a kind of makeshift interferometer, a tool that combines light from different points to create incredibly detailed images. Led by J.E. Baldwin and his team at the Cavendish Astrophysics Group, this method led to some of the most accurate measurements ever made of Betelgeuse's surface. It even revealed bright spots, hot areas on the star's surface that stood out against the cooler background. These were the first ever optical and infrared images of a star's surface other than our Sun, and they were first captured using ground-based telescopes like the COAST interferometer. These bright patches or hot spots were exactly what the famous astronomer Martin Schwarzschild had predicted decades earlier. Huge convection cells dominating the surface of giant stars like Betelgeuse. Then, in the year 1995, the Hubble Space Telescope took things even further. Using its faint object camera, it captured an ultraviolet image of Betelgeuse that was sharper than anything seen from Earth. Since Earth's atmosphere blocks most ultraviolet light, this type of image can only be taken from space. In that Hubble image, scientists noticed a bright region in the southwest part of the star that was about 2,000 degrees Kelvin hotter than the rest of the surface. Later, Hubble's Goddard high-resolution spectrograph showed that this hotspot might actually be one of the star's rotational poles. Based on this, scientists concluded that Betelgeuse's axis is tilted about 20 degrees from Earth's viewpoint, and its position angle is around 55 degrees from celestial north. By December of the year 2000, a new study measured Betelgeuse's diameter using the Infrared Spatial Interferometer, ISI. They found it to be about 55.2 milliseconds, which matched measurements taken by Albert Michelson almost 80 years earlier. Around that time, the Hipparcos mission estimated Betelgeuse's parallax at around 7.63 milliseconds, leading to an estimated radius of about 3.6 astronomical units, more than 3 times the distance between Earth and the Sun. But there was a surprise. In 2009, another study revealed that Betelgeuse had shrunk by about 15% since 1993, and it seemed to be shrinking even faster. Yet strangely, its brightness didn't change much. This made astronomers suspect that the shrinking might not be real. It could be due to shifting layers of gas in the star's extended outer atmosphere. Scientists also became deeply interested in the complex outer layers of Betelgeuse. Red supergiant stars like it play a crucial role in the galaxy by shedding matter that eventually helps form new stars and planets. But how they lose mass has remained a puzzle. Thanks to improved imaging techniques, astronomers began to close in on an answer. In July of 2009, the European Southern Observatory released spectacular images taken by the Very Large Telescope Interferometer. These images showed a huge plume of gas stretching 30 astronomical units, as far as the distance between the Sun and Neptune, away from Betelgeuse. This was just one of several such eruptions. In fact, astronomers have now found at least 6 layers of material around the star. Understanding how and why Betelgeuse is shedding so much gas may help explain how massive stars eventually explode as supernovae. Betelgeuse is also known as a pulsating semi-regular variable star. Its brightness goes up and down in cycles because its size and temperature are constantly changing. In one study, astronomers Richard Wassertonic, Edward Guinan, and Thomas Calderwood observed an unusually deep dimming and believed it was caused by a rare overlap of 2 cycles, a 5.9-year cycle and a 425-day cycle. By late 2019, other scientists began to wonder if this fading could be caused by something else, such as an eruption of gas or a thick dust cloud. Then, in early 2020, using the Hubble Space Telescope, astronomers found evidence that Betelgeuse had indeed blasted out a huge amount of superheated material. This material cooled and turned into a cloud of dust that blocked part of the star's light, about a quarter of its surface. Hubble had captured signs of this material moving through the star's outer layers during September, October, and November of 2019. By December, and into the first few months of 2020, many telescopes confirmed that Betelgeuse was much dimmer than usual. By January of 2020, Betelgeuse's brightness had dropped by a factor of about 2.5, going from magnitude 0.5 to 1.5. In February, it reached its faintest point in 25 years at magnitude plus 1.614, making it dimmer than Aldebaran and knocking it out of the list of the 10 brightest stars in the sky. This sparked widespread rumours that Betelgeuse might explode soon as a supernova. But astronomers reminded the public that this dramatic event probably won't happen for another 100,000 years. By mid-February of 2020, Betelgeuse had stopped fading and was even starting to brighten again. On February 22nd, the dimming seemed to end altogether. 2 days later, scientists found no major changes in the star's infrared emissions over the past 50 years, which suggested that the fading had nothing to do with the dying core. Instead, astronomers proposed that the dimming was likely caused by large dust grains forming close to the star, possibly from gas ejected in a prior outburst. Some also suspected giant star spots, cooler, darker patches on the surface, might be behind the dimming. Then, on March 31st, a rapid brightening was reported by several astronomers. Betelgeuse is usually hard to see from Earth between May and August, since it appears too close to the Sun in the sky. Just before its 2020 conjunction with the Sun, Betelgeuse had brightened to magnitude plus 0.4. But by June and July, the Stereo A spacecraft detected a new dimming of about 0.5 magnitudes, which was unexpected. A new brightness peak was expected around August or September, but the fading hinted that another dip might arrive sooner than predicted. On August 30th of 2020, astronomers spotted a second dust cloud coming from Betelgeuse, linked to a smaller dimming that had occurred on August 3rd. By June of 2021, scientists thought the dust might have formed when a cool patch developed on Betelgeuse's surface. This idea was confirmed again by another research group in August. Then, in August of 2022, another study using Hubble confirmed that the dust likely came from a surface mass ejection, similar to explosions on the Sun, but far more powerful. This dimming may have been caused by the overlap of a 416-day cycle with a 2010-day cycle, creating what astronomers call a grand minimum, a very deep low point in brightness. This idea was first suggested decades ago by astronomer L. Goldberg. In April of 2023, astronomers reported that Betelgeuse had returned to peak brightness, reaching magnitude 0.0 visually and 0.1 in the V-band, shining once again as one of the most dazzling stars in our night sky. Thanks to its deep orange-red glow and its prominent position in the constellation Orion, Betelgeuse is one of the easiest stars to spot with the naked eye. It stands out so clearly in the night sky that even casual stargazers can find it without the help of a telescope. Betelgeuse is one of the 3 bright stars that form the famous winter triangle, an imaginary triangle that helps people navigate the winter night sky. It also lies at the heart of another large star pattern called the winter hexagon, which connects several of the brightest stars visible during the colder months. Every year, in early January, Betelgeuse rises in the eastern sky just after sunset, marking the start of its most visible season. From about mid-September to mid-March, with the best viewing in mid-December, the star shines brightly in the night sky and can be seen from almost anywhere on Earth where people live, except for the most southern parts of Antarctica, south of 82 degrees latitude. By May in the northern hemisphere and June in the southern hemisphere, the red supergiant dips low in the western sky and can only be seen for a brief moment after sunset. A few months later, it reappears on the eastern horizon shortly before sunrise. However, during the in-between period, roughly June to July, especially around mid-June, Betelgeuse becomes invisible to the naked eye. It can only be seen using telescopes in daylight. An exception is in Antarctica, between 70 and 80 degrees south latitude, where it might still appear faintly in the north around midday twilight during the long polar night, when the sun never rises above the horizon. Betelgeuse is a variable star, meaning its brightness is not always the same. Its visual magnitude changes over time, ranging from 0.0 to about plus 1.6. At times, it can shine more brightly than the nearby star Rigel, making it the 6th brightest star in the night sky. On rare occasions, it even outshines Capella. But at its dimmest, Betelgeuse drops below stars like Deneb and Beta Crucis, and can become only the 20th brightest star in the sky. Astronomers have also discovered that Betelgeuse has up to 9 faint companions, stars that appear close to it in the sky. These companion stars lie at distances of about 1 to 4 arc-minutes away from Betelgeuse, and each one is dimmer than 10th magnitude, making them very hard to see without powerful telescopes. To measure how far stars are from Earth, astronomers use a technique called parallax. This is the apparent shift in a star's position in the sky when viewed from 2 different locations, in this case from opposite sides of Earth's orbit around the Sun. Even though the shift is tiny, often just a fraction of an arc-second, it can be used to calculate a star's distance. The first successful parallax measurement was done by Friedrich Bessel in the year 1838. Since then, scientists have tried to accurately measure the distance to Betelgeuse, but this has been surprisingly difficult. Knowing how far Betelgeuse is helps astronomers calculate many other important facts about it, such as how bright it really is, its luminosity, how big it is, its radius, how hot it is, its temperature, how old it might be, and how much mass it contains. Back in the year 1920, when astronomers first used interferometry, a technique to measure very small angles, to study the size of Betelgeuse, they assumed its parallax was 0.018 arcseconds. That gave a distance of about 56 parsecs, which equals around 180 light-years. But this estimate turned out to be too small, making all the other calculations, like its radius and brightness, completely inaccurate. Over the following decades, scientists proposed a wide range of possible distances for Betelgeuse, with some estimates as high as 400 parsecs, or about 1,300 light-years. Before the Hipparcos catalogue was published in the year 1997, there were already 2 somewhat conflicting measurements. One, made in 1991, suggested a parallax of 9.8 milliseconds, which placed the star at about 102 parsecs, or roughly 330 light-years away. Another estimate, published in 1993 from the Hipparcos Input Catalogue, gave a parallax of 5 milliseconds, translating to a distance of around 200 parsecs, or 650 light-years. Because these measurements were so different, astronomers ended up using a wide range of distances, which led to big variations in estimates of Betelgeuse's size, temperature, and brightness. When the full Hipparcos data was released in 1997, the measurement for Betelgeuse was 7.63 milliseconds, which suggested a distance of about 131 parsecs, or 427 light-years. This result had a smaller reported error than previous ones. However, later studies found that the uncertainties for variable stars like Betelgeuse had been underestimated. In the year 2007, a new and more accurate measurement was made, 6.55 milliseconds, with a smaller margin of error. This meant Betelgeuse was likely about 152 parsecs away, roughly 500 light-years, with an error of plus or minus 65 light-years. Then, in 2008, radio observations using the Very Large Array gave another result, a parallax of 5.07 milliseconds, suggesting a distance of about 197 parsecs, or 643 light-years, again with some uncertainty. The lead researcher, Edward Harper, explained that although the Hipparcos data was helpful, it still included unknown errors. So, they tried combining both sets of data, radio and optical, to balance out the mistakes and get a better estimate. Later observations using telescopes like ALMA and E. Merlin refined the parallax even more, giving a measurement of 4.51 milliseconds. This implied a distance of around 222 parsecs, which equals about 724 light-years, with some room for error on either side. In the year 2020, a new set of data came from the Solar Mass Ejection Imager, which is part of the Coriolis satellite. Along with 3 different modelling techniques, this produced a refined parallax of 5.95 milliseconds. This meant Betelgeuse was located at a distance of about 168 parsecs, or roughly 548 light-years. Based on this new measurement, astronomers concluded that Betelgeuse is likely 25% smaller and 25% closer to Earth than they had thought before. In the year 2022, a new study revealed something surprising about Betelgeuse. This massive star might actually be smaller and closer to Earth than scientists had thought before. The study was based on ancient records that showed Betelgeuse used to shine with a yellow colour about 1,000 years ago, but today it looks red. That colour change tells astronomers a lot. It suggests that Betelgeuse is not as massive as earlier estimates claimed, likely weighing around 14 times the mass of our Sun. This is significantly less than what was once believed. The study also pointed to a closer distance, about 125 parsecs, which is around 410 light-years away. That estimate fits well with earlier data collected by the Hipparcos satellite. However, the European Space Agency's current Gaia mission, designed to measure stellar distances with great precision, has trouble with stars that are too bright, such as Betelgeuse. The instruments on Gaia cannot handle stars brighter than about 6th magnitude. Because of this limitation, Betelgeuse did not appear in the mission's second data release from the year 2018, nor in the third release from the year 2022. Betelgeuse is classified as a semi-regular variable star. This means its brightness changes in a somewhat predictable pattern, but with many irregularities. Sometimes it follows cycles, but the brightness can vary a lot. The cycles can be different lengths, and there can even be times when no clear pattern is seen. It belongs to a special group called SRC stars. These are giant red stars that pulsate, with brightness changes of about 1 magnitude and cycles that last anywhere from a few dozen to several hundred days. Most of the time, Betelgeuse stays around magnitude plus 0.5 in brightness, but it can become as bright as magnitude 0.0 or fade as much as plus 1.6. It is listed in the General Catalogue of Variable Stars with a possible long-term cycle of about 2,335 days. Other, more detailed studies have found that Betelgeuse shows a main cycle of around 400 days, a shorter one of about 185 days, and a much longer secondary cycle of about 2,100 days. In February of the year 2020, astronomers recorded its faintest brightness in the V-band, plus 1.614. The changes in brightness are tied to the way Betelgeuse expands and contracts. These motions, called radial pulsations, are well understood. The periods lasting a few hundred days match the natural rhythm of the star's layers as they pulse in and out, either in the fundamental mode or in what's called the first overtone. Astronomers can detect these motions by observing the Doppler shift in the star's light, which tells them how fast parts of the star are moving toward or away from Earth. These shifts show that Betelgeuse is indeed expanding and shrinking, although changes in its temperature or light spectrum are not as clearly seen. Scientists have directly measured changes in Betelgeuse's diameter over time. They found that the 185-day pulses match the first overtone mode of pulsation. The ratio between this overtone and the longer period helps astronomers learn about what's going on inside the star and how old it might be. However, the long secondary cycle cannot be explained by simple radial pulsations. When astronomers use powerful instruments to examine Betelgeuse more closely, they sometimes see bright spots on its surface. These are likely massive convection cells, huge regions where hot gases rise and cool gases sink. Each of these cells might be nearly as wide as half the star and can emit 5 to 10% of Betelgeuse's total light. One idea is that the long secondary periods come from the motion of these cells combined with the slow rotation of the star. Other possible explanations include gravitational effects from a nearby companion star, magnetic activity in Betelgeuse's outer layers, or more complex non-radial pulsations such as gravity waves known as G-modes. Besides these regular pulsations, Betelgeuse also shows small, random variations in brightness. These are thought to be caused by granulation, small-scale turbulence on the star's surface, similar to what we see on the Sun, but much larger. On the 13th of December in the year 1920, Betelgeuse became the very first star beyond our solar system to have its size measured directly. Even though the technology of interferometry was very new at the time, the attempt worked. Using a technique that treated the star as a simple uniform disk, scientists estimated Betelgeuse's diameter at about 0.047 arcseconds. Taking into account limb darkening, the effect where the edges of the star look dimmer than the centre, they adjusted the measurement to around 0.055 arcseconds. Since then, other observations have measured Betelgeuse's angular diameter between about 0.042 and 0.069 arcseconds. When these angular sizes are combined with distance estimates ranging from 180 to 815 light-years, astronomers have calculated that Betelgeuse's radius might lie anywhere between 1.2 and 8.9 astronomical units, AU. To compare, Mars orbits the Sun at around 1.5 AU, the dwarf planet Ceres lies at about 2.7 AU, and Jupiter orbits at 5.5 AU. So if Betelgeuse replaced our Sun, its outer layer might extend beyond Jupiter's orbit, but would still fall short of Saturn's, which lies at about 9.5 AU. The size of a cool giant star like Betelgeuse is often reported using something called the Rossland radius. This is the distance from the star's centre to the point where the photosphere, the visible surface, becomes transparent enough that most of the star's light escapes. This value is based on the star's temperature and how much total energy it gives off. However, this differs from direct measurements, which must also account for limb darkening and the wavelength of light used for the observation. For example, a direct angular diameter of 55.6 milliseconds, MAS, could correspond to a Rossland diameter of 56.2 MA. If there are clouds of dust or gas around the star, this might reduce the measured diameter to as low as 41.9 MA. To solve these measurement challenges, astronomers have developed powerful tools. The original idea for astronomical interferometry was proposed by Hippolyte Fizeau in the year 1868. He suggested that looking at stars through two openings instead of one, similar to how human eyes create depth perception, could help measure the shape and brightness of stars. This idea led to the creation of the Michelson interferometer in the 1880s, and eventually to the successful measurement of Betelgeuse. Over the years, the technology improved rapidly. By using multiple openings, apertures, and combining the light through a mathematical method called Fourier analysis, astronomers could form highly detailed images. In the 1990s, this helped reveal the bright spots on Betelgeuse's surface. Other advances included adaptive optics, which correct for the blurring caused by Earth's atmosphere, space telescopes like Hipparcos, Hubble and Spitzer, and sophisticated instruments like AMBER, the Astronomical Multibeam Recombiner, which merges light from 3 telescopes to produce incredibly sharp images with millisecond resolution. Different wavelengths of light can give different sizes for Betelgeuse. In the visible range, the atmosphere scatters light more, making the star look slightly larger. In near-infrared, this effect is minimal, and astronomers can see the true edge of the photosphere. In the mid-infrared, the glow from the warm outer layers makes the star look bigger again. In the year 1996, Betelgeuse was measured as having a uniform disk size of 56.6 mass. In the year 2000, another team measured it as 54.7 mass. A slight adjustment for limb darkening gave a final value of about 55.2 mass. These values suggest a radius of around 5.6 AU, or 1,200 times the Sun's radius, assuming a distance of 197 parsecs. In 2004, near-infrared measurements found a smaller size of 43.33 ms. This helped explain why different wavelengths give different results. By 2009, measurements using the IOTA and VLTI interferometers strongly supported the idea that Betelgeuse is surrounded by dusty shells and a layer of molecules. These studies found diameters between 42.57 and 44.28 ms. A 2011 study confirmed these numbers, measuring a diameter of about 42.49 ms. That same year, the near-infrared diameter of 43.33 ms, paired with a distance of 152 parsecs, gave a physical size of about 3.4 AU, or roughly 730 times the radius of the Sun. In the year 2009, astronomers reported that Betelgeuse had shrunk in apparent size by 15% between the years 1993 and 2009. The 2008 measurement showed an angular size of 47 mas. The earlier measurement from 1993 was 56 mas. That meant a decrease in size of about 0.9 AU over 15 years. But this likely reflects changes only in the star's outer atmosphere, not the true photosphere, as measurements in other wavelengths showed an increase in size during that same period. Today, models usually place Betelgeuse's photospheric diameter at around 43 mad, with outer gas shells extending out to 50 or 60 mas. Assuming a distance of 197 parsecs, this translates to a diameter of about 887 times the radius of the Sun, with a margin of error of plus or minus 203 solar radii. Betelgeuse was once thought to be the star with the largest apparent size in the sky after the Sun. However, in the year 1997, astronomers measured another red giant, R Doradus, and found it had a diameter of 57 mass. Even though R Doradus is much closer to Earth, only about 200 light-years away, it appears larger in the sky. But because of its proximity, its actual size is only about 1/3 the size of Betelgeuse. Betelgeuse, one of the most famous stars in the night sky, is located far away from the path of the planets, the line known as the ecliptic. Because of this, the large planets like Jupiter or Saturn never pass directly in front of it, a rare event called an occultation. However, smaller objects like asteroids, which are more numerous and move in a wider variety of paths, can sometimes briefly pass in front of Betelgeuse from our point of view here on Earth. One such rare and fascinating event happened on the 2nd day of January in the year 2012. A faint asteroid called 2005 UW381, which shines at 19th magnitude, meaning it's incredibly dim and requires a telescope to see, partially blocked Betelgeuse's light. This event was only a partial occultation because the star's apparent size in the sky was actually larger than that of the asteroid. As a result, the brightness of Betelgeuse dipped just a tiny bit, by only about 0.01 magnitudes, barely noticeable even with precise instruments. Another intriguing event was predicted for the 12th day of December in the year 2023. This time, it was the 14th magnitude asteroid 319 Leona that was expected to pass in front of Betelgeuse at about 1:12 Universal Coordinated Time. Initially, scientists weren't sure if the asteroid would fully cover the star. The full occultation, if it happened, was expected to last only around 12 seconds and would be visible only along a very narrow path on Earth's surface. Because astronomers didn't yet have exact measurements of the asteroid's size and trajectory, the exact location of the viewing path was unknown at first. As scientists studied the data more closely, they refined their calculations. It turned out that the occultation, described as a dazzling ring of fire, would likely last around 5 seconds. The path of visibility, about 60 kilometers wide, would stretch across a long arc of the Earth, starting from Tajikistan, sweeping through Armenia, Turkey, Greece, Italy, Spain, across the Atlantic Ocean, then over Miami and the Florida Keys in the United States, and finally reaching parts of Mexico. This rare and accidental alignment offered astronomers a golden opportunity, not only to observe Betelgeuse dim momentarily, but also to gather valuable data about the asteroid Leona itself. Across Europe alone, about 80 amateur astronomers were coordinated by astrophysicist Miguel Montages and his team at the Paris Observatory to witness and study the event. Now let's turn to Betelgeuse itself, this massive glowing red supergiant in the constellation of Orion. It belongs to a class of stars known as M-type supergiants, with a designation of M1 to M2 Ab. The M means that the star is relatively cool and red in colour, while IA Ab indicates that it's a luminous supergiant, not the brightest possible, but close. Its spectrum has been so reliable that since the year 1943, it has served as a reference point for classifying other stars. Measuring Betelgeuse's brightness, its luminosity, is tricky. That's because we still don't know its exact temperature, size, or distance. But back in the year 2012, astronomers estimated its luminosity to be about 126,000 times that of our Sun, assuming it lies about 200 parsecs away, which is around 650 light-years. Since the year 2001, measurements of Betelgeuse's surface temperature have ranged from 3,250 to 3,690 Kelvin. These values change due to natural pulsations in the star's atmosphere, almost like it's slowly breathing in and out. Betelgeuse is a very slow spinner. Its latest measured rotational speed was just 5.45 kilometers per second, which is much slower than that of Antares, another red supergiant, which spins at about 20 kilometers per second. How long does it take Betelgeuse to complete a full spin? Scientists estimate around 36 Earth years, but because the star is tilted at about 60 degrees to our line of sight, this spin is not directly visible. Even though Betelgeuse spins slowly, it may still have some magnetic activity in its huge outer layers. In the year 2004, astronomers using computer models suggested that large magnetic fields might form in the star's atmosphere and influence how it loses mass and blows off dust. Then, in the year 2010, a group of scientists used a special instrument called a spectropolarimeter at the Bernard-Liot telescope in France. They discovered a weak magnetic field on the star's surface. This suggested that the powerful convection currents within Betelgeuse, similar to boiling water on a stove, could generate a small-scale magnetic dynamo, even without fast rotation. Unlike some stars, Betelgeuse doesn't have a visible companion orbiting it, so scientists cannot use gravitational measurements to figure out its mass. Instead, they use computer models. Modern estimates suggest that the star's mass lies somewhere between 9.5 and 21 times the mass of the Sun. Older estimates ranged even wider, from 5 to 30 solar masses. Based on how bright Betelgeuse is, and assuming it started with a luminosity between 90,000 and 150,000 times that of the Sun, it likely began its life with a mass between 15 and 20 solar masses. In the year 2011, astronomers introduced a new method for estimating Betelgeuse's mass. By analysing a detailed intensity profile using infrared interferometry, they came up with a current mass of about 11.6 solar masses, with possible values as low as 7.7 or as high as 16.6. Another analysis, using a statistical approach, suggested the current mass is probably between 16.5 and 19 solar masses, with an original mass between 18 and 21 solar masses. Another way to estimate the star's mass is by looking at where it sits on the colour magnitude diagram, which compares a star's colour and brightness. A study from the year 2022 looked at ancient records suggesting that Betelgeuse may have changed colour over the past few thousand years, from yellow or orange to deep red. This colour change implies a mass of around 14 solar masses, an age of about 14 million years, and a distance between 125 and 150 parsecs, or about 400 to 500 light years. Betelgeuse's movement through space, its kinematics, is also complex and somewhat mysterious. Massive red stars like Betelgeuse, which began life with about 20 solar masses, typically only live for about 10 million years. If we trace its motion backward, Betelgeuse would have come from a location about 290 parsecs away from the galactic plane, a spot where stars usually don't form. Also, its current path does not appear to cross the known star-forming regions of Orion, like the 25 Orionis group or the much younger Orion Nebula cluster, also called Orion OB1d. Modern measurements using the Very Long Baseline Array show that Betelgeuse is between 389 and 414 parsecs from the Orion Nebula cluster. So, scientists now think Betelgeuse may have changed direction in the past, possibly due to a powerful nearby event like a supernova explosion. In January of the year 2013, the Herschel Space Observatory observed that the winds blowing off Betelgeuse were crashing into the gas and dust of the surrounding interstellar space. This shows just how powerful and far-reaching the star's influence is. Most astronomers now believe that Betelgeuse is a runaway star, one that was ejected from its original home. It likely formed about 10 to 12 million years ago as part of a high-mass multiple star system in a group known as Orion OB1a. Because it is so massive, it has aged quickly, growing into the red supergiant we see today. But not all scientists agree on its origins. In the year 2015, researchers H. Bowie and J. Alves suggested Betelgeuse might actually belong to a newly discovered group of stars called the Taurean OB Association. In the final stages of a massive star's life, especially stars like Betelgeuse, something fascinating happens. They begin to lose huge amounts of their mass. In fact, it's possible for a star like Betelgeuse to shed as much as one solar mass, which is the mass of our Sun, every 10,000 years. This steady outpouring of material creates a thick and ever-changing cloud of gas and dust around the star called the circumstellar environment. In the year 2009, scientists published a study emphasizing just how important this mass loss is. They called it the key. to understanding not just how stars evolve, but also how the universe itself has changed since its earliest days. They even suggested that this process is deeply tied to the formation of planets and eventually the origin of life. Despite how crucial this is, scientists still do not fully understand how or why it happens. Back in the mid-20th century, a scientist named Martin Schwarzschild came up with a bold idea. He proposed that gigantic bubbles of hot gas called convection cells rise and fall within stars like Betelgeuse. He believed these turbulent motions could be behind the star's mass loss. More recent research has backed up this idea, but there's still a lot we don't know. Questions remain about how these convection cells are shaped, how dust forms in the outer layers, and what exactly triggers these stars to explode in spectacular Type II supernovae. In the year 2001, another scientist, Graham Harper, estimated that Betelgeuse was blowing out material through stellar winds at a rate of about 0.03 solar masses every 10,000 years. But more recent observations, especially those made since the year 2009, show that the star might not lose mass steadily. Instead, it might eject material in bursts or episodes, which makes it harder to know exactly how much mass has been lost overall. Interestingly, astronomers now think Betelgeuse doesn't just stay a red supergiant for the rest of its life. It might change phases again. At some point it may briefly become a yellow supergiant and then end its life either as a hot blue supergiant or as a Wolf-Rayet star, known for being very hot and stripped of its outer layers. Astronomers may be on the verge of understanding why this strange mass loss happens. They recently discovered a massive plume of gas stretching out from Betelgeuse, more than 6 times wider than the star itself. This plume suggests that the star isn't releasing gas evenly in all directions. Instead, it seems to be pouring out matter more in some directions than others. Normally, the surface of a star, called the photosphere, looks mostly round and symmetrical in infrared light. But Betelgeuse's outer layers don't match that shape. Using adaptive optics with a powerful telescope known as the Very Large Telescope, scientists saw lopsided patterns in the gas surrounding the star. 2 possible causes have been proposed, either giant convection cells bubbling beneath the surface or polar mass loss driven by the star's rotation. Digging deeper into the star's atmosphere using the AMBER instrument at the European Southern Observatory, scientists observed gas churning violently, with enormous bubbles rising and falling, some as large as the entire star. This violent movement is thought to be what created the huge gas plume observed by astronomer Pierre Cavella and his team. Betelgeuse's outer layers are much more complex than just a single photosphere. Scientists have now identified 6 additional parts of its atmosphere. Some of these regions are uneven, while others overlap each other in complex ways. Just above the surface, about 0.45 times the star's radius, or about 2 to 3 astronomical units, AU, lies the Emol sphere. This region contains molecules like water vapour and carbon monoxide, and has a temperature of around 1,500 kelvins, give or take 500. Water vapour was first detected in the star's light back in the 1960s during the stratoscope missions, but this discovery was mostly ignored for decades. Newer studies suggest the Emolsphere may also contain silicon monoxide and aluminum oxide, both of which help form dust grains. Farther out is a cooler, uneven gas envelope, stretching 10 to 40 astronomical units from the surface. This envelope contains more oxygen and nitrogen than carbon, likely because material from deep inside Betelgeuse, processed by nuclear fusion reactions, has been brought to the surface and mixed into the atmosphere. In the year 1998, radio telescopes produced detailed images of Betelgeuse's atmosphere. These revealed that the gas temperature was about 3,450 kelvins, give or take 850, similar to the star's surface temperature but cooler than expected for gas in that region. The Very Large Array images also showed that this gas cools further as it moves away from the star. Surprisingly, this cooler gas turns out to be the most abundant part of Betelgeuse's atmosphere. As scientist Jeremy Lim explained, this discovery changed how astronomers think about red supergiant stars. Instead of the atmosphere expanding smoothly from hot gas near the surface, it now seems that giant convection cells launch gas upward, adding chaos to the star's surroundings. This is also the region where Cavella spotted a giant plume of material, rich in carbon and nitrogen, extending in the southwest direction as far as 6 times the star's radius. The chromosphere, a hotter outer layer, was directly imaged by the Hubble Space Telescope using ultraviolet light. It showed a bright area on the southwestern side of the star's disk. Back in 1996, scientists found that the chromosphere extended about 2.2 times the size of the visible star, or about 10 astronomical units, and had a temperature of up to 5,500 kelvins. Later, in 2004, a more advanced spectrometer on Hubble, called ESTIS, discovered warm plasma, hot ionized gas, stretching out to 1 arcsecond from the star. Since Betelgeuse is about 197 parsecs away, this means the chromosphere could extend as far as 200 astronomical units. This hot plasma overlaps with both the cooler gas envelope and the dusty outer layers, all swirling around the dying star. The first idea that Betelgeuse might have a surrounding dust shell came in 1977, when astronomers noticed that older stars often emit extra radiation from such dusty layers. Using a technique called heterodyne interferometry, they concluded that most of this radiation came from beyond 12 times the star's radius, or about 50 to 60 astronomical units, roughly the distance of the Kuiper belt in our solar system. In the 1990s, astronomers took more measurements at different wavelengths, but the results didn't always agree. Some studies placed the inner edge of the dust shell between 100 and 200 astronomical units, depending on assumptions about the star's size. These studies made it clear that the dusty surroundings are not stable. In 1994, it was reported that Betelgeuse produces dust in bursts lasting decades, followed by periods of calm. By 1997, scientists noticed the dust shell's shape had changed drastically in just 1 year. This suggested that bright spots on the star's surface were unevenly heating the surrounding dust. In 1984, a study claimed that an enormous asymmetric dust shell existed 1 parsec, or over 200,000 astronomical units, from the star, but this has not been confirmed. Another study from the same year proposed that 3 dust shells stretched as far as 4 light-years in one direction. If true, it would mean Betelgeuse has been shedding its outer layers as it moves through space. As for the 2 outer carbon monoxide shells, their exact sizes remain uncertain, but rough estimates suggest one extends between 1.5 and 4 arcseconds, and the other reaches up to 7 arcseconds. If we assume the radius of Betelgeuse is about 5.5 astronomical units, similar to Jupiter's orbit, then the inner shell would stretch from about 300 to 800 astronomical units, and the outer one could go as far as 1,400 astronomical units. To put that in perspective, our Sun's heliopause, the outer boundary of the solar wind, is around 100 astronomical units, so this outer shell would be nearly 14 times the size of our entire solar system. Betelgeuse, one of the most famous stars in the night sky, is a red supergiant nearing the end of its life. But it didn't always look like this. Long ago, Betelgeuse began its journey as a blazing hot blue-white star known as an O-type main sequence star. After it ran out of hydrogen fuel in its core, the power source that kept it shining for millions of years, it transformed into a blue supergiant. Eventually it cooled and expanded into its current form, a huge reddish-orange-red supergiant. What comes next for Betelgeuse is even more dramatic. One day its core will collapse under its own weight, setting off a massive explosion known as a supernova. What remains afterward will be a dense, compact object, possibly a neutron star or even a black hole. However, how exactly this process unfolds depends on the original features of the star, especially how massive it was when it was born, how fast it was spinning, and what elements it was made of. Since we didn't witness Betelgeuse's birth, scientists rely on computer models of stellar evolution to estimate what it was like in its early days. These models are based on its current size, brightness, chemical composition, and behaviour. Although there's still quite a bit of uncertainty, researchers believe Betelgeuse was originally between 10 and 25 times more massive than our Sun. More modern models narrow this range to somewhere between 15 and 20 solar masses. As for its composition, scientists estimate that Betelgeuse was made up of roughly 70% hydrogen, 28% helium, and about 2.4% heavier elements, a mix not too different from our Sun, but with slightly more metals. Its original rate of rotation is harder to pin down, but models that assume a slow to moderate spin match Betelgeuse's current characteristics best. In its early years as an O-type main sequence star, possibly something like a hot bright 09V type, Betelgeuse would have been a dazzling presence in its region of space. Now, how long would it have taken Betelgeuse to reach its current red supergiant phase? That depends on its mass and how fast it was spinning. A star with 15 times the mass of the Sun might take between 11.5 million and 15 million years to become a red supergiant. Heavier stars evolve faster. A 20 solar mass star that spins slowly might take only 8.1 million years, while one that spins rapidly could take about 9.3 million years. Based on this, astronomers estimate that Betelgeuse is now somewhere between 8 million and 8.5 million years old. But how long has it already been a red supergiant? That's harder to tell. Scientists try to estimate this by looking at the material Betelgeuse has ejected into space, and by measuring the abundance of heavier elements on its surface. Some models suggest Betelgeuse may have been in this phase for as little as 10,000 years, while others stretch this to as much as 140,000 years. The star seems to go through bursts of heavy mass loss, and is moving quickly through space, which makes exact estimates tricky. However, the most widely accepted figure is that Betelgeuse has been a red supergiant for around 40,000 years, and that it likely left the main sequence about 1 million years ago. During this red supergiant phase, Betelgeuse has already lost a significant amount of mass, but not too much. Models suggest that it has shed less than 1 solar mass, giving it a current estimated mass of about 19.4 to 19.7 solar masses. This is more than what some other measurements suggest, such as those based on how it pulsates, or how its brightness fades toward the edge of its disk, known as limb darkening. Any star with more than about 10 times the mass of the Sun is expected to end its life in a violent collapse. For stars with up to 15 solar masses, this usually means a Type 2p supernova, the kind that explodes after the star becomes a red supergiant. More massive stars, however, can lose their outer layers more quickly and may evolve into hotter stars, becoming yellow or blue supergiants, or even stripped down Wolf-Rayet stars before exploding. These different paths can lead to different types of supernova, such as Type 2L, Type 2b, or Type IBC. For example, models of rotating stars with 20 solar masses predict a strange type of supernova, like the famous SN 1987A from a blue supergiant. On the other hand, a similar non-rotating star would likely still explode as a Type 2p supernova from the red supergiant phase, just like Betelgeuse is expected to do. How much longer do we have before Betelgeuse explodes? That depends on how much time it's already spent as a red supergiant and how massive it truly is. A rotating 25 solar mass star might stay in this phase for around 300,000 years, while a non-rotating 15 solar mass star might last up to 1 million years. Based on the best models, Betelgeuse might only have less than 100,000 years left before it goes supernova, if it's a non-rotating 20 solar mass star. However, if it's rotating, or if it's less massive than that, it could stick around much longer. Astronomers believe that Betelgeuse was born in the Orion OB1 Association, a stellar nursery where several other massive stars have already exploded. In fact, 3 runaway stars, Mu Columbae, AE Aurigae, and 53 Arietis, were likely launched from this region by supernova explosions that occurred 2.2, 2.7, and 4.9 million years ago, respectively. When Betelgeuse does eventually explode, it will likely go out as a Type 2p supernova. This kind of explosion is incredibly powerful. It would release about 2 times 10 to the power of 46 joules in neutrinos, tiny ghost-like particles, and another 2 times 10 to the power of 44 joules as the kinetic energy of the blast. From Earth, this event would be dazzling. At its brightest, Betelgeuse could shine with a magnitude between -8 and -12, bright enough to be seen in broad daylight and possibly rivaling the full moon, although probably not outshining it. After the explosion, its light would stay nearly constant for 2 to 3 months, thanks to the radioactive decay of cobalt formed during the blast. As the supernova's hydrogen shell cools and becomes more transparent, the light will fade, but it will remain a stunning celestial event unlike anything seen in recorded human history. In the year 1944, a German-American astronomer named Walter Baade came up with a way to group the different kinds of stars we see in our Milky Way galaxy. But Baade wasn't the very first to think about this. In fact, he mentioned in his paper that the idea had originally come from a Dutch astronomer named Jan Oort, all the way back in the year 1926. Baade noticed something very interesting. Stars that looked blue were usually found along the Milky Way's spiral arms, those curved arms that twist out from the centre of the galaxy like a giant pinwheel. On the other hand, yellowish stars were more commonly found near the thick central bulge of the galaxy and inside ancient clusters of stars called globular clusters. He divided the stars into two major groups, Population 1 and Population 2. Later, in the year 1978, scientists added a third group, Population 3, which is thought to be made of the very first stars that ever existed, although we've never seen one directly. What made these groups different was more than just their colour or where they were located. Scientists later found that these types of stars had very different light patterns, known as stellar spectra, basically fingerprints of what elements the stars are made of. These differences helped astronomers understand how stars form, how old they are, how they move, and even how galaxies like our own have changed over time. One of the biggest differences between these groups is their metal content. In astronomy, the word metal is used in a special way. It includes any element heavier than helium, such as oxygen, carbon, and iron, even though these aren't metals in everyday life. Here's the rule: the fewer metals a star has, the older it likely is. Population 3 stars were the very first stars to form in the universe, and they had almost no metals at all. Population 2 stars are also very old, with only small amounts of metals. Population 1 stars, like our Sun, are much younger and have the highest metal content. The Sun, for example, is a Population 1 star with about 1.4% of its mass made up of metals. By studying the light from stars, scientists found that older stars always have fewer heavy elements than younger stars. This tells us something big. Metals built up in the universe over time as generations of stars were born, lived, and died. This process is called stellar nucleosynthesis, which means stars create new elements inside them through nuclear reactions. According to our current models of how the universe began, almost all the matter created in the Big Bang was made of hydrogen, about 75%, and helium, about 25%, with just tiny traces of other light elements like lithium and beryllium. After the universe cooled down, the very first stars, Population 3 stars, were born. These stars had no heavy elements at all, which may have made them behave very differently from modern stars. Scientists believe these first stars were huge, possibly hundreds of times more massive than the Sun. Because of their size, they lived very fast and died young. When they died, many of these massive stars exploded in extremely powerful pair instability supernovae, a rare and energetic kind of explosion. These explosions scattered the first heavy elements, like carbon, oxygen, and iron, into space. These metals then became part of the gas clouds that would later form new generations of stars. Because Population 3 stars were so massive and burned out so quickly, scientists believe we can no longer see them in our galaxy today. However, we might catch glimpses of their light in very faraway galaxies from the early days of the universe. Interestingly, astronomers have discovered an extremely metal-poor star, slightly smaller than the Sun, that orbits in a binary system in the spiral arms of the Milky Way. This discovery gives hope that stars from the very early universe might still exist and be found. Some of the largest early stars didn't explode. Instead, they may have collapsed directly into black holes through a process called photodisintegration, where the star breaks apart from within. Some of the matter might have escaped during this process as powerful, high-speed jets of gas and radiation, helping to spread metals even farther into the universe. The oldest stars we've actually seen, Population 2 stars, have very low metal levels but not zero. These stars formed from gas that had already been enriched by Population 3 stars. As these Population 2 stars aged and died, they released even more metals into the surrounding space through supernova explosions and glowing clouds called planetary nebulae. The next generation of stars, Population 1, formed from this metal-rich gas, and thus have the highest metal content. These include stars like our Sun, These younger stars are usually found in the spiral arms of galaxies and tend to orbit the centre of the galaxy in smooth, nearly circular paths. Population 1 stars were once thought to be more likely to form planets because of their higher metal content. Metals are the building blocks of rocky planets. But recent observations from the Kepler Space Telescope have shown that small planets can form around stars with both high and low metal content. However, giant planets, like Jupiter, still seem more common around stars with lots of metals. Between population 1 and population 2, stars lies another group called the intermediate disk population, which shares characteristics of both groups. Population 2 stars, which have low metal content, are found mostly in the galactic halo and the central bulge of the Milky Way. These stars are especially common in globular clusters, which are tight balls of very old stars. Even though population 2 stars don't have many metals, they often have more of certain lighter elements called alpha elements, like oxygen and neon, when compared to iron. Scientists believe this is because type 2 supernova, which make alpha elements, were more common in those early times, while type Ia supernova, which make more iron, became common later. Now, population 3 stars are still just a theory. No one has seen one directly. The idea was first suggested by astronomer Neville J. Wolfe in the year 1965. These stars were probably incredibly massive, hot, and bright, made entirely of hydrogen and helium with little or no metals, except maybe if they picked up some material from nearby supernovae. They may have started the process of creating the elements needed to build planets, and even life itself. Although we haven't seen them directly, scientists believe they once existed because they explain how the universe became filled with heavy elements. Some clues come from the light of distant galaxies and quasars. For example, one very distant galaxy observed by the European Southern Observatory, called Cosmos Redshift 7, may have contained a pocket of population 3 stars around 800 million years after the Big Bang. It also had some redder, older population 2 stars. Some scientists even think there might have been 2 generations of population 3 stars, one group of massive stars that lived very briefly, and a second group that formed slightly later. There's still debate about whether the first stars were all supermassive or if smaller ones also existed. Some early theories suggested these stars could have been as big as 1,000 times the mass of the Sun and might have lived only 2 to 5 million years. Other theories suggest that the first stars may have formed in groups, with one big star surrounded by several smaller ones. If any of the smaller ones were ejected early, they might still survive today, perhaps even in our own galaxy. Some stars, like the very metal-poor He0 107 to 5240, may have been formed from the material left behind by population 3 stars. Based on the data, those early stars might have had masses between 20 and 130 times the mass of the Sun. Interestingly, studies of globular clusters in elliptical galaxies suggest that pair instability supernovae played a major role in their chemical makeup. That might be why we haven't seen any stars with 0 metal content. None of the small population 3 stars seem to have survived. Some theories even suggested that low-mass zero-metal stars like red dwarfs or brown dwarfs could be hiding in the universe and might be part of dark matter. But despite searches using gravitational lensing techniques, none have been found. Population 3 stars may also have formed the first black holes in the universe. These weren't the massive black holes we sometimes hear about, but smaller ones. If they managed to grow large enough, they could have become quasi-stars, another type of mysterious object that may have existed before heavier elements filled the universe. One of the major goals of NASA's James Webb Space Telescope is to try to find these elusive population 3 stars. On December 8, 2022, astronomers announced that they might have finally caught a glimpse of population 3 stars in a distant galaxy called RxJ 2129 to Z8HE2. If confirmed, it would be one of the biggest discoveries in modern astronomy, allowing us to look back in time and see the very first lights that ever shone in the universe. The life of a star is an incredible and dramatic journey that unfolds slowly across the vast ocean of time. This process, known as stellar evolution, describes how a star forms, changes, and eventually dies. A star's path through life depends almost entirely on how massive it is. The largest and heaviest stars burn brightly but live fast, often lasting only a few million years. In contrast, the smallest and lightest stars may shine steadily for trillions of years, outliving the universe itself, which, according to current estimates, is only about 14 billion years old. All stars begin their lives inside enormous dark clouds of gas and dust called nebulae, also known as giant molecular clouds. These clouds can stretch across 100 light-years and hold up to 6 million times the mass of our Sun. Over time, gravity pulls parts of these clouds inward. As the gas collapses, it breaks into smaller fragments. Inside each of these fragments, the gas gets squeezed tighter and heats up, turning into a glowing ball called a protostar. These protostars are the seeds of future stars. They are surrounded by dust and gas and are best observed using infrared telescopes, like NASA's Wide Field Infrared Survey Explorer, often called WISE. As a protostar grows by pulling in more gas and dust, it eventually reaches a balance and becomes a main sequence star, a stable, long-lasting phase where it shines by fusing hydrogen atoms into helium in its core. This nuclear fusion produces enormous amounts of energy, which is what makes stars shine. The type of fusion and how long it continues depends on the star's mass. For instance, if a star is about the same size as the Sun, what astronomers call one solar mass, it will burn hydrogen at its core for around 10 billion years. But much smaller stars like red dwarfs burn hydrogen so slowly that they could live for hundreds of billions or even trillions of years. On the other hand, giant stars that are many times heavier than the Sun can burn through their fuel in just a few million years. Once the hydrogen in the core is mostly used up, a star's life enters a new phase. In stars like the Sun, hydrogen fusion continues in a shell around the now helium-rich core. This causes the outer layers of the star to expand, and the star becomes a red giant. Eventually, these stars start fusing helium in their cores, and heavier stars can even go on to fuse elements like carbon, oxygen, and beyond in a series of onion-like shells. The end of a star's life depends again on its mass. A star like the Sun, when it runs out of fuel, sheds its outer layers, creating a glowing shell of gas called a planetary nebula, while its core shrinks into a small, incredibly dense object known as a white dwarf. These white dwarfs no longer produce energy, but they remain hot and slowly cool down over billions of years. Heavier stars, those with around 10 times the mass of the Sun or more, face a more violent ending. When they run out of fuel, their iron-filled cores collapse in an instant, triggering a colossal explosion called a supernova. What's left behind after this cataclysm is either a neutron star, which is incredibly dense and compact, or, if the original star was massive enough, a black hole, a region of space so dense that not even light can escape it. Very small protostars, those with less than about 8% of the Sun's mass, never become true stars. They do not get hot enough to ignite hydrogen fusion in their cores. These are known as brown dwarfs. Some of them are large enough to briefly fuse deuterium, a heavier form of hydrogen, but they never shine as brightly as full-fledged stars. Instead, they glow faintly and slowly cool off over hundreds of millions of years. Even smaller objects, those less massive than about 13 times the mass of Jupiter, are called sub-brown dwarfs, unless they orbit a star, in which case they are considered planets. Inside molecular clouds, long strands of dense gas known as filaments often appear. These filaments break up into smaller, tightly packed clumps of matter called gravitational cores, which are the direct ancestors of new stars. Sometimes, within a single filament, astronomers have found regular chains of dense cores, evenly spaced and occasionally containing pairs of protostars that shoot out jets of gas as they grow. As a protostar continues to grow and heat up, its central temperature eventually reaches about 10 million degrees Kelvin. At this point, hydrogen fusion begins through a series of reactions. For small to mid-sized stars, this is usually the proton-proton chain reaction. In slightly larger stars, those just a bit more massive than the Sun, another fusion method known as the carbon-nitrogen-oxygen cycle starts to play a bigger role. Fusion creates a powerful outward pressure that balances the pull of gravity, allowing the star to stay stable. This moment marks the beginning of the main sequence phase, which is the longest and most steady part of a star's life. Every star on the Hertzsprung-Russell diagram, a special chart used by astronomers, occupies a unique spot on the main sequence depending on how massive and hot it is. Tiny, cool red dwarfs live the longest. Massive hot blue stars, known as O-type stars, live fast and die young, sometimes after only a few million years. Stars like our Sun, called yellow dwarfs, spend about 10 billion years in this phase, and scientists believe the Sun is currently halfway through its main sequence life. As stars form, they can also develop disks of gas and dust spinning around them. These protoplanetary disks are where planets may eventually form, giving rise to complete planetary systems like our own solar system. As time passes, a star eventually uses up all the hydrogen fuel in its core, the very material that powers it through nuclear fusion. When this happens, the star can no longer stay stable as it once did on the main sequence of its life. During the main sequence stage, hydrogen atoms fuse into helium, producing energy that pushes outward and balances the inward pull of gravity. But once the hydrogen in the core runs out, that balance is lost. Without that outward pressure from fusion, gravity takes over. The core begins to shrink and grow hotter. One of two things can happen next, depending on how massive the star is. If it's not very massive, the core might stop collapsing when it gets so tightly packed that a strange quantum force called electron degeneracy pressure pushes back against gravity. If the star is more massive, then the core may become hot enough, about 100 million Kelvin, to start fusing helium instead. Whether electron degeneracy or helium fusion kicks in first depends entirely on the star's original mass. Now, here's the tricky part. For the smallest stars, we've never actually seen what happens when they stop making energy through fusion. That's because the universe itself is only about 13.8 billion years old, and these tiny stars live far, far longer than that, sometimes by many orders of magnitude. So their full life stories haven't had time to play out yet. According to current models, a red dwarf star with a mass of about 1/10, the mass of the Sun, could shine steadily for anywhere between 6 and 12 trillion years. That's 6,000 to 12,000 billion years. During this time, the star will slowly grow brighter and hotter. After that, it could take hundreds of billions of years more to finally shrink into a white dwarf. These tiny stars are unique. They won't puff up into red giants like larger stars. Instead, because they are completely stirred up by convection, they will keep burning hydrogen evenly until almost the entire star turns into helium. Stars that are a little heavier do become red giants. However, some of them aren't heavy enough to fuse helium in their cores, so after they expand and shine as red giants for a while, they don't climb to the brightest point of the red giant stage. Instead, they quietly fade and shrink down to become white dwarfs without going through the dramatic helium fusion phase. This slow exit is similar to stars on the post-asymptotic giant branch, just not as bright. But there's a turning point. Stars that start out with about 6/10 the mass of the Sun or more, what we might call mid-sized stars, can get hot enough to start fusing helium in their cores. These stars go through more complex stages of life after leaving the red giant phase. Stars with masses between about 6/10 and 10 times the Sun's mass become red giants. Enormous stars that no longer belong to the main sequence. These glowing giants usually fall into the K or M spectral classes, meaning they shine with a reddish or orange hue. On the Hertzsprung-Russell diagram, which maps out stars by their brightness and temperature, red giants sit along the right edge. Famous examples include Aldebaran in the constellation Taurus and Arcturus in Bootes. These mid-sized stars pass through two red giant phases. In the first, called the red giant branch, they have helium cores that don't yet fuse, and hydrogen burns in a shell around the core. Later, in the asymptotic giant branch, their cores are made of carbon and fusion happens in two shells, one burning helium and the other hydrogen. In between these phases, stars spend some time on the horizontal branch where they burn helium in the core. Many stars here cluster into what's called the red clump. They shine steadily as cool K-type giants. When a star leaves the main sequence and its core runs out of hydrogen, fusion continues in a shell around the core. The shell keeps adding helium to the core, making it grow in mass. This stage can last anywhere from a few million to 1 or 2 billion years, depending on the mass of the helium core. During this time, the star grows in size and cools down a bit. but its brightness stays similar or just a bit lower than it was before. Eventually something changes. In stars about the size of the Sun, the core becomes degenerate. It stops behaving like normal gas and is held up by quantum forces. In more massive stars, the outer layers grow cooler and thicker, making it harder for heat to escape. Both of these changes cause the hydrogen-burning shell to heat up and brighten, making the whole star swell up and rise onto the red giant branch. As the outer layers expand, they become full of convection, hot gas bubbling up and mixing with cooler gas. This mixing pulls fusion products from deep inside the star all the way to the surface. For most stars, this is the first time the materials created by fusion show up on the outside. Though the changes are subtle, scientists can detect them by studying the light from these stars. For example, they can see altered ratios of carbon and nitrogen, and differences in the isotopes of hydrogen and helium, especially from the CNO cycle. On the red giant branch, the helium core keeps growing. Since it's not in balance with the rest of the star, it heats up even more. That makes the hydrogen shell burn faster, increasing the star's brightness as it climbs to the tip of the red giant branch. Stars with degenerate helium cores all reach this tip with about the same mass and brightness. In more massive stars, the core might get hot enough to ignite helium fusion even before reaching the tip. For stars with helium cores between about 6/10 and 2 times the mass of the Sun, which are mostly supported by electron degeneracy pressure, something explosive happens, a helium flash. This ignition happens in just a few days. In heavier stars, the core isn't degenerate, so helium fusion begins smoothly over time without any flash. During a helium flash, the power released is incredible, around 100 million times the Sun's brightness for a few days, and for a brief moment it may spike up to 100 billion times the Sun's brightness, equal to the entire Milky Way galaxy. But this burst of energy doesn't reach the surface of the star. It's used up to expand the tightly packed core, so we can't actually see it from the outside. As the core expands, it cools, and hydrogen fusion slows down. The whole star contracts, though not all the way back to its original size. It settles into a new stable phase and moves to the horizontal branch on the Hertzsprung-Russell diagram. Its radius shrinks, but its surface temperature rises. Stars that go through a helium flash move to the cooler end of the horizontal branch and shine as red clump stars, hotter and dimmer than red giants. More massive stars with larger helium cores slide toward hotter parts of the branch. Some of them become unstable and start to pulse rhythmically, forming RR Lyrae variables. Others grow even hotter and may appear as part of the blue tail or blue hook. The exact appearance and structure of the horizontal branch in a star cluster depend on things like the star's chemical makeup, its age, and how much helium it has. Scientists are still working out the fine details through theoretical models. Once a star has used up all the helium in its core, it doesn't stop shining right away. Instead, it keeps burning both hydrogen and helium in layers or shells that surround a hot and dense center made mostly of carbon and oxygen. This next stage of the star's life follows a path on the Hertzsprung-Russell diagram called the asymptotic giant branch, which is like a second, more dramatic version of the earlier red giant phase. But this time, the energy is produced even faster, so the stage doesn't last as long. Even though there's a shell burning helium, most of the star's energy now comes from hydrogen burning in an outer shell. The helium that forms from this process slowly sinks toward the center of the star. Every once in a while, the helium-burning shell flares up with a sudden burst of energy. These powerful flashes are called thermal pulses, and they happen during the later stages of the asymptotic giant branch. Sometimes, thermal pulses can even continue after the star has left the asymptotic giant branch entirely. Depending on how massive and rich in elements the star is, there might be just a few of these pulses, or there could be hundreds. As the star continues to grow and change during this phase, something interesting happens. Deep inside the star, a large zone of hot, churning gas forms. This turbulent area acts like a conveyor belt, bringing material from deep in the star up to the surface. This event is called the second dredge-up, and in some stars it is followed by a third dredge-up. These dredge-ups can carry carbon from the core to the outer layers of the star, turning it into what's known as a carbon star. A cool, reddish star with strong carbon signatures in its light. But in some cases, a process called hot bottom burning converts that carbon into oxygen and nitrogen before it can reach the surface. The battle between these processes, bringing carbon up and burning it away, determines how bright and colourful these stars appear, especially in star clusters. One well-known type of star on the asymptotic giant branch is the Mira variable. These stars regularly expand and shrink, pulsing with a rhythm that lasts from several tens to several hundreds of days. Their brightness in visible light can change dramatically, by as much as 10 magnitudes, but their actual total energy output doesn't change as wildly. The more massive these stars are, the brighter they become, and the longer their pulsation periods. As a result, they lose mass very quickly, releasing large amounts of gas and dust into space. This makes them hard to see in visible light because they get wrapped in thick clouds, but they shine brightly in the infrared and often show signs of OH-Maser activity, which is a special kind of radio emission from molecules in their outer shells. These stars are rich in oxygen, unlike carbon stars, but both types form through the same dredging up process. Eventually, stars of medium mass reach the very top of the asymptotic giant branch. At this point, they've used up the fuel needed to keep burning their outer shells. Because they aren't heavy enough to start fusing carbon in the core, they begin to shrink and go through a phase known as the post-asymptotic giant branch superwind. During this time, they blow off their outer layers in a massive wind, creating a glowing cloud of gas and dust called a planetary nebula. In the centre of this nebula is an extremely hot core, the leftover heart of the star, which eventually cools down to become a white dwarf. The material that the star sheds into space is rich in heavy elements that were created inside the star. Depending on the type of star, the ejected gas might be full of oxygen or carbon. This gas forms an expanding shell called a circumstellar envelope that gets cooler as it moves farther away from the star. In these cooler regions, dust and complex molecules begin to form. Because of the intense infrared light from the central star, the conditions in the envelope become perfect for master emission, producing bright, focused radio signals from certain molecules. Interestingly, even after a star has entered the post-asymptotic giant branch stage, it can sometimes experience new thermal pulses. These create rare and mysterious stars called born-again asymptotic giant branch stars. These strange stars can take many forms. Now let's turn to more massive stars. In these stars, the core is already so large when the hydrogen shell begins burning that helium fusion starts before the core can become supported by electron degeneracy pressure. So when they expand and cool, they don't brighten as much as smaller stars, but they were already very bright while still on the main sequence. These stars grow into enormous and incredibly luminous supergiants. Eventually, their cores become so massive that even electron degeneracy can't stop them from collapsing. When this happens, they end their lives either as a neutron star or a black hole. Some extremely massive stars, those with more than about 40 times the mass of the Sun, burn so brightly that their intense light blows away their outer layers in powerful stellar winds. Because they lose their envelopes this way, they never become red supergiants. Instead, they stay very hot with a bluish-white colour throughout their lives. The most massive stars we see today have between 100 and 150 times the Sun's mass. If they were any larger, their outer layers would be blown away completely by their own radiation. However, some smaller stars can also avoid becoming red giants if they are part of a close binary system, where a nearby companion star pulls away their outer layers, or if they spin very fast. Fast spinning causes strong mixing, so the star doesn't develop a separate core and outer layer. As a massive star grows older, the core, no longer full of hydrogen, gets hotter and denser as it is fed by the surrounding hydrogen fusing layers. In the most massive stars, the core becomes hot enough to fuse carbon into even heavier elements like neon, sodium and magnesium through something called the alpha process. At the end of helium fusion, the core is mostly made up of carbon and oxygen. In stars heavier than about 8 times the mass of the Sun, this carbon ignites and fuses further, but stars just under this mass may only partly fuse carbon before becoming supported by electron degeneracy pressure. These stars eventually become white dwarfs made of oxygen, neon and magnesium. The exact mass limit for full carbon fusion depends on things like how many heavy elements the star started with, its metallicity, and how much mass it lost during its asymptotic giant branch phase. But in general, Full carbon burning begins in stars with around 8 to 9 times the Sun's mass. After the carbon is used up, the core reaches around 2.5 times the Sun's mass and gets hot enough to begin fusing even heavier elements. But before oxygen starts fusing, the neon starts capturing electrons, triggering a process called neon burning. In stars between about 8 and 12 solar masses, this can lead to a runaway reaction and end in a powerful explosion called an electron capture supernova. In even heavier stars, neon fusion happens more calmly. This is followed by the burning of oxygen and then silicon, until the core becomes filled with iron-like elements, which are the end products of fusion. Around this iron core, shells of lighter elements continue fusing. But the final stage happens fast. Once the core has finished turning carbon into iron, it only takes a few hundred years for everything to collapse. During this time, the outer parts of the star barely have time to respond, so the star still looks normal on the outside. Eventually, the iron core reaches what's called the effective Chandrasekhar limit, the maximum mass it can handle before collapsing. This limit is a bit higher than the original Chandrasekhar limit due to various effects like relativity, heat, and pressure from the outer layers. For red supergiants, the effective limit is around 1.34 times the Sun's mass, but in more massive stars it can be over 1.8 times the Sun's mass. Once the iron core hits this limit, it begins collapsing rapidly. Electrons are absorbed by iron nuclei, and the star's core can no longer hold itself up. What follows is a spectacular end, a supernova explosion, or in the case of even more massive stars, a direct collapse into a black hole. When a very massive star reaches the end of its life, something dramatic happens at its core. After using up all its nuclear fuel, the core can no longer support the immense weight of the star pressing down on it, so the core collapses under gravity's pull. This collapse leads to one of two outcomes. If the collapsing core is not too massive, it becomes an incredibly dense object called a neutron star. But if the core's mass is greater than a certain limit, known as the Tolman-Oppenheimer-Volkoff limit, then even neutron pressure cannot stop the collapse, and a black hole forms instead. During this sudden collapse, a huge amount of energy is released. Scientists still do not fully understand how this energy behaves, but we do know that part of it creates an enormous explosion known as a supernova. Depending on the structure of the star and what elements are present in its outer layers, this explosion might be a Type 1b, Type 1c, or Type 2 supernova. One of the most mysterious and powerful events in this process is the release of neutrinos, tiny, nearly massless particles that barely interact with anything. When the core collapses, a colossal flood of neutrinos rushes outward. This was directly observed in the famous supernova called SN 1987A, which exploded in the year 1987. These neutrinos don't just fly away. Some of them interact with the star's material. They can split atoms apart, knock loose neutrons and protons, and transfer heat and motion into the surrounding layers of the star. All of this contributes to the supernova's enormous shockwave, the wave that blasts the outer parts of the star into space. In the densest parts of the collapsing matter, electrons are sometimes forced to merge with protons, creating even more neutrons. As the shockwave rebounds, it slams into surrounding material, bombarding it with these loose neutrons. Some of the atomic nuclei catch these neutrons, leading to the creation of heavy elements even heavier than iron, and including radioactive ones, possibly all the way up to and beyond uranium. Now, it is true that older, non-exploding stars, especially red giants, can also create some heavy elements using neutrons released in slower side reactions. But the kinds and amounts of heavy elements made in red giants are quite different from those made during a supernova explosion. And interestingly, neither type of process alone can explain all the heavy elements we find in our solar system today. That's why scientists believe that supernovae, collisions of neutron stars, and mass ejections from red giants all play a role in creating and spreading these heavier elements across the universe. The energy released during the core's collapse not only makes heavy elements, but also hurls them outward at tremendous speeds, much faster than the escape velocity of the star. This is what powers the incredible brightness and force of a Type 1b, Type 1c, or Type 2 supernova. However, even today, scientists are not entirely sure how enough energy is transferred from the collapsing core to the rest of the star to cause such a powerful explosion. Computer models can explain part of it, but not all. One promising idea involves neutrino oscillations, the way neutrinos change types as they move through space. These oscillations may help transfer more energy, both by changing the total energy in each kind of neutrino, and through strange effects predicted by Einstein's theory of general relativity. Some fascinating clues come from binary neutron stars, systems where two neutron stars orbit each other. These systems must have come from two separate supernovae, and their behaviour gives us insight into the differences between various types of supernova explosions. In particular, if a star's core is mostly made of oxygen, neon and magnesium, the supernova it produces may be observably different from one coming from a core made mostly of iron, even if they explode with similar energies. Among the most extreme cases are the largest stars in the universe. The most massive stars known today can sometimes be completely destroyed in an especially powerful kind of supernova caused by something called pair instability. In this rare type of explosion, the energy released is greater than the gravitational energy holding the star together, so the entire star is blown apart, leaving behind no black hole at all. Even more massive stars that existed billions of years ago were so large that, instead of exploding, they collapsed instantly into black holes due to a process called photodisintegration, where their intense heat broke apart atomic nuclei and triggered total collapse. After a star dies and burns up its fuel, what's left depends on how massive it was during its life. A star with a mass similar to our Sun, about 1 solar mass, will shrink into a white dwarf, a very dense object with a mass of about 0.6 solar masses packed into a space no bigger than the Earth. White dwarfs stay stable because the gravity pulling inward is balanced by a special kind of pressure that comes from electrons being squeezed together. This is called electron degeneracy pressure, which is a result of the Pauli exclusion principle, a rule in quantum physics that says two electrons cannot occupy the same state at the same time. Interestingly, white dwarfs behave in a counterintuitive way. The more massive they are, the smaller they get. Once they form, white dwarfs don't burn any more fuel. They simply shine by releasing leftover heat into space. This cooling process takes billions of years. When a white dwarf is newly formed, it is extremely hot. Its surface can be hotter than 100,000 Kelvin, and its core is even hotter. In its first 10 million years, a lot of its energy is lost through the emission of neutrinos. After about 1 billion years, most of its heat has been radiated away, and it continues to cool. The makeup of a white dwarf depends on how massive the original star was. A star with a mass between about 8 and 12 times the mass of the Sun will go through a phase where it fuses carbon into elements like magnesium, neon, and small amounts of others. If such a star loses enough of its mass before collapsing, it can leave behind a white dwarf made mostly of oxygen, neon, and magnesium, as long as the carbon burning is not too violent to cause a supernova. Stars with masses around that of the Sun don't get hot enough to burn carbon, so they form white dwarfs made mostly of carbon and oxygen. These white dwarfs are not heavy enough to collapse on their own, unless extra matter is added to them later. On the other hand, very small stars, those with less than half the Sun's mass, can't even ignite helium fusion, and will eventually leave behind white dwarfs made mostly of helium. Over a very, very long time, a white dwarf cools so much that it becomes a cold, dark object known as a black dwarf. However, the universe is still too young, less than 14 billion years old, for any black dwarfs to have formed yet. But if a white dwarf gains more mass, either by merging with another star or by pulling in material from a nearby companion, it can become too heavy. If it grows past a certain point, called the Chandrasekhar limit, which is about 1.4 solar masses, electron pressure can no longer support it. What happens next depends on its composition and core temperature. The star may collapse into a neutron star, or the heat may trigger runaway fusion of carbon and oxygen, causing a bright Type 1a supernova. Type 1a supernova can shine many times brighter than the Type 2 supernova caused by massive star death, even though they release less total energy. No white dwarf can exist beyond the Chandrasekhar limit unless it's spinning extremely fast. Then centrifugal force might help support the extra weight. Sometimes, in a close binary system, a white dwarf can slowly pull hydrogen from its larger companion star. This gas builds up around it, and once it gets hot enough, the hydrogen suddenly fuses in a violent burst. This event is called a nova. Unlike a supernova, the white dwarf survives a nova and can go through the cycle again. Normally, when we look at atoms, the tiny building blocks of everything around us, they are made up mostly of empty space. Most of their volume comes from the cloud of fast-moving electrons that surround a tiny dense centre called the nucleus. To understand how small the nucleus is compared to the whole atom, imagine this. If an atom were as big as a football stadium, its nucleus would only be about the size of a speck of dust floating in the air. But something extraordinary happens when a massive star reaches the end of its life, and its core collapses under its own immense gravity. The pressure becomes so incredibly high that it forces the electrons and protons inside atoms to combine through a process called electron capture. This process creates neutrons. Once the electrons are gone, electrons that normally help keep atomic nuclei apart, there is nothing left to stop the neutrons from being crushed tightly together. What results is an object made almost entirely of neutrons, packed together in a super dense ball, like one gigantic atomic nucleus. Around this dense core there may be a thin shell made of super compressed matter, usually made mostly of iron, unless other types of matter fall onto it later. These remarkable objects are called neutron stars. They are incredibly small compared to normal stars. Each one is only about 10 kilometers across, which is roughly the size of a large city. But they are unimaginably dense. A single teaspoon of neutron star matter would weigh more than a mountain on Earth. The neutrons inside resist being crushed any further because of a quantum rule called the Pauli exclusion principle, which says that no two neutrons can occupy the same quantum state. This force is similar to the one that keeps white dwarfs from collapsing, but the neutron version is much stronger. When the core of a dying star becomes a neutron star, something else amazing happens. As the star shrinks, it starts to spin faster and faster, just like a figure skater spinning more quickly when pulling in their arms. This happens because of a law in physics known as the conservation of angular momentum. Some neutron stars spin incredibly fast, making hundreds of complete rotations every single second. The fastest ones spin in about 1.5 thousandths of a second, which means more than 600 spins in just 1 second, while others may take a few seconds to spin once. Now, some of these spinning neutron stars have magnetic poles that sweep past Earth like the beam of a lighthouse. Every time the beam points toward us, we detect a pulse of energy, often in the form of radio waves. These pulsing neutron stars are called pulsars, and they were the first type of neutron star ever discovered. While they usually emit radio waves, some pulsars also give off visible light, X-rays, or even gamma rays. However, not all collapsing stellar cores stop at the neutron star stage. If the remaining mass of the core is too high, greater than about 2 to 3 times the mass of our Sun, although the exact number is still uncertain, even the pressure from neutron degeneracy is not enough to stop the collapse. In that case, the core keeps shrinking until it becomes a black hole, an object so dense and with gravity so powerful that not even light can escape from it. Black holes are predicted by Einstein's theory of general relativity. According to this theory, once something crosses the boundary around a black hole, called the event horizon, it can never escape. No matter, no light, and no information can come back out. However, some new theories in quantum physics suggest that this rule might not be absolute, and there could be tiny effects that allow some information to leak out. Today, the existence of black holes is strongly supported, not only by theoretical predictions, but also by many kinds of astronomical observations. Scientists have detected black holes by watching how stars orbit around them, by measuring gravitational waves, and by observing the bright X-rays emitted by hot matter falling into them. Even now, scientists do not completely understand what happens during a core collapse supernova, the powerful explosion that often happens when a massive star dies. It is still a mystery whether some stars can collapse directly into black holes without producing a visible supernova, or whether they first form unstable neutron stars that later collapse into black holes. Also, it is not fully known how a star's starting mass and chemical makeup determine whether it becomes a white dwarf, a neutron star, or a black hole. To solve these puzzles, astronomers must study many more supernovae and the remains they leave behind. To better understand how stars live and die, scientists use something called a stellar evolutionary model. This is a set of complex computer programs that simulate how a star changes from the moment it is born until the moment it becomes a remnant like a white dwarf, neutron star, or black hole. These models begin with basic information about a star, like how massive it is and what elements it contains. The models also use well-understood physics rules, such as the idea that the forces inside the star must balance to keep it from collapsing. The models then calculate how the star's brightness and surface temperature change over time. Using this information, the models show how the star moves across the Hertzsprung-Russell diagram, a special chart that astronomers use to track the life stages of stars. These models are extremely useful. They allow scientists to estimate how old a star is, just by comparing its current properties to the results of the models. In this way, astronomers can piece together the life story of a star and better understand the fate that awaits it. Imagine the universe had its own Hall of Fame for the biggest, brightest, and most mind-blowing stars ever discovered. Without a doubt, standing tall and proud in that imaginary gallery would be a truly enormous and mysterious star known as the Behemoth. This is not just any star. It's a bloated, burning monster that doesn't even live in our Milky Way galaxy. Instead, it hides far away in a neighbouring galaxy called the Large Magellanic Cloud, which is like a companion galaxy orbiting ours. The Behemoth is so huge, so bright, and so puzzling that it's forcing scientists to rethink what stars can actually do. It was first discovered back in the 1970s by 3 astronomers named Westerlund, Olander, and Hayden. The star's name, WH-G64, comes from the first letters of their names. Even in the early days after its discovery, the Behemoth grabbed attention because of its jaw-dropping size. Astronomers believe its radius, the distance from the centre to the outer edge, is around 1,500 times larger than the Sun's. To help you picture that, if this star replaced our Sun in the centre of the solar system, its fiery surface would swallow up Mercury, Venus, Earth, and Mars, and it would reach almost all the way to Jupiter's orbit. That's truly enormous. To make it easier to imagine, think of the Sun as the size of a tennis ball. Now imagine the Behemoth as a sphere the size of an entire football stadium. That's how much bigger it is. But size isn't its only superpower. The Behemoth also shines with incredible brightness. It gives off nearly 280,000 times more light than our Sun. Yet strangely enough, we don't see all that light directly. That's because this titanic star is wrapped in a thick, dusty cloud shaped like a donut. This dusty shell, made of gas and ash thrown off by the star itself, blocks a lot of its light and makes it hard for astronomers to observe. But this dusty veil is more than just a cosmic cloak. It's a warning sign. It shows that the Behemoth is probably in the late stages of its life. The material the star is throwing off is not just a small puff. It stretches almost an entire light year across, which is nearly 6 trillion miles. This cloud is slowly drifting outward, pushed by fierce stellar winds and the star's unstable outer layers. It's like the star is shedding its skin as it prepares for a dramatic end, maybe a massive explosion known as a supernova. That kind of mass loss is common in stars that are burning through their fuel faster than they can keep up. The Behemoth is burning bright and fast, and it won't be able to keep it up forever. And here's another twist. For a star that burns so brightly, it's surprisingly cool on the surface. Its temperature is only about 3,000 to 3,400 Kelvin, cooler than most stars, and low enough to place it in the category of red supergiants. These are giant stars that have swelled up near the end of their lives, glowing red due to their lower temperatures. But even among red supergiants, the Behemoth is strange. It may be sitting at, or even beyond, a physical boundary known as the Hayashi limit. This limit tells us that a star of a certain size and mass shouldn't be able to stay stable if it gets too cool. And yet, the Behemoth seems to be breaking that rule, which has left astronomers scratching their heads in confusion. Is it really one single star? Or could it be 2 stars orbiting each other so closely that they look like one? Because of the thick dust and its great distance, we're not sure. Some scientists think there might be a second star hiding. maybe a hot, bright blue O-type or B-type star just out of sight. If that's true, the behemoth could actually be a binary system, two stars in a close relationship possibly interacting and influencing each other. That could help explain why it's losing so much material. Perhaps the companion star is pulling it away or stirring things up through gravity. But for now, no second star has been confirmed. It remains a mystery. Another fascinating part of this story is where the behemoth lives, in the Large Magellanic Cloud. This galaxy is famous for housing unusual and massive stars. One possible reason is that its chemical makeup is different from that of the Milky Way. It has fewer heavy elements, what astronomers call metals, and that could allow stars there to behave in strange ways, growing bigger, evolving faster, and dying more dramatically than stars in our own galaxy. The behemoth might be the perfect example of this. It's a cosmic giant born in an environment that allowed it to become far larger and more extreme than we would normally expect. In many ways, it's a star that challenges the rules, and one that continues to fascinate and puzzle astronomers today. The behemoth star isn't just bigger than our Sun, it's much bigger. And when it comes to brightness, it doesn't just outshine the Sun a little, it outshines it in every possible way scientists can measure. This enormous star is estimated to shine about 280,000 times brighter than our Sun. That makes it one of the brightest stars ever discovered in the entire universe. But what does that actually mean in everyday terms? Let's break it down. The amount of energy a star releases every single second is called its luminosity. Our Sun has a luminosity of about 3.8 times 10 to the power of 26 watts, which is enough to warm our planet, drive the weather, and keep life going from a distance of about 150 million kilometers away. Now imagine taking that same amount of energy and multiplying it by 280,000. That gives us a staggering number, around 1.064 times 10 to the power of 32 watts. That's such a massive amount of energy it becomes nearly impossible to imagine. It's not just the difference between a candle and a campfire, it's more like comparing a tiny matchstick to the detonation of an entire planet. The behemoth star is a roaring furnace in space, so intense and so powerful that its light alone reshapes the environment around it. This blinding brightness isn't just an impressive statistic, it has real effects on the star's surroundings. The radiation it gives off is so powerful that it pushes away the star's own outer layers. This creates violent stellar winds, streams of particles flying outward, and forms giant shells of dust and gas that expand into space like ripples from a cosmic explosion. Most of the light coming from this gigantic star isn't even visible to the human eye. It shines mostly in infrared and visible wavelengths, but the light is so intense that it could be spotted across millions of light years, even from other galaxies, if there wasn't a thick, murky cloud of dust blocking our direct view. That's where infrared telescopes come in. Since regular optical telescopes can't see through the dust, astronomers use powerful instruments like those at the Very Large Telescope in Chile to peer through the veil. These telescopes pick up the star's infrared light and study its spectral fingerprints, unique clues that tell us how much energy the star gives off, what elements are swirling in its atmosphere, and how fast it's losing its outer layers to space. But all this dazzling brightness comes at a price. The behemoth star is not young. In fact, it's near the end of its life. Stars that burn this bright are also burning through their fuel at an unsustainable pace. They live fast and die young. While our Sun still has around 5 billion years left before it reaches the end of its life, the behemoth star will likely survive only for a few million years, a mere blink when compared to the age of the universe. The extreme energy it pours out is a sign that it's living on borrowed time. It's like a runaway nuclear reactor operating at full blast, knowing the end is coming soon. And that brightness? It's not just something to admire, it's dangerous. The intense radiation it gives off can split apart molecules, destroy DNA, and evaporate entire atmospheres. If there were a planet unlucky enough to orbit too close to this monster, life wouldn't stand a chance. The radiation would fry everything in moments. In truth, the behemoth star is not the kind of star you'd want as a neighbour. It's not cozy, it's not gentle, it's a brutal force of nature, flooding space with heat, light, and destruction. Even stranger, this star doesn't shine at a constant rate. It goes through waves of brightening and dimming, which scientists believe are caused by instabilities inside its core. Each flicker and change in brightness could be a signal. Maybe it's collapsing, maybe it's preparing to explode, or maybe something even more mysterious is happening deep inside. So why do scientists spend time studying something so extreme, so unpredictable and so terrifying? Because studying the behemoth star helps us understand the lives and deaths of the largest stars in the universe. This kind of star is incredibly rare, and its intense light gives us a rare window into a process that only happens in the most powerful corners of the cosmos. It's like watching a slow-motion replay of a cosmic disaster, one that reveals how galaxies grow, how heavy elements are created, and how the universe transforms over time. In its final, furious blaze, the behemoth star tells a story billions of years in the making, and helps us uncover the secrets of the stars themselves. Usually when we look at the universe, we imagine planets tracing perfect circles around the sun, comets streaking across the darkness, and countless stars scattered like sparks across the night sky. But what if the real secrets of our cosmic neighbourhood aren't just spread out around us, but also towering above and plunging far below? High above, titanic bursts of gamma rays blaze toward the galactic north. Deep below, unseen rivers of gravity twist and pull, shaping our path through the stars. Together they reveal that our solar system isn't a flat stage, it's a vast, layered theatre with heights and depths still waiting to be uncovered. When most people imagine looking up at the universe, they picture the sweeping arc of the Milky Way, its bright stars scattered like glowing grains of sand across the night sky. Astronomers often speak of the galactic North Pole, a direction that points outward from the plane of our galaxy and offers a clear view of distant space. The North Pole has historically attracted a great deal of attention because of its clarity and the wealth of ancient galaxies that can be seen in that direction. But the universe is never one-sided. For every north, there is a south, and just as the galactic North Pole gives us a window into the cosmos, its counterpart, the galactic South Pole, reveals a view no less valuable, no less extraordinary, and no less profound. To look toward the galactic South Pole is to open another cosmic window, one that helps us balance our picture of the universe and understand the Milky Way from both above and below. The galactic South Pole is not an abstract concept but a precise point in the sky. It lies in a constellation known as Sculptor, a faint grouping of stars first catalogued by the French astronomer Nicolas Louis de Lacaille in the 18th century. This constellation is not especially bright or obvious, but hidden within its borders is a doorway to the farthest reaches of the universe. To understand its position, imagine the Milky Way as a great spinning disk, something like an enormous celestial pinwheel. The disk is flat with spiral arms winding outward, filled with billions of stars, clouds of gas and streams of dust. From this disk rise two poles, the north and the south. The galactic South Pole is located exactly 90 degrees beneath the plane of this disk, standing as the precise opposite of the galactic North Pole in the system astronomers use to map our galaxy. Although the North Pole often takes the spotlight in research papers, conferences and headlines, the South Pole is equally crucial. Without it, astronomers would see only one side of the galaxy's symmetry. By comparing the North and the South, they can test whether the Milky Way is balanced, whether its halo of stars and dark matter is truly spherical, or whether one side has been shaped differently by history and time. From Earth, the galactic South Pole is most clearly visible in the skies of the Southern Hemisphere. People in places such as South America, Africa and Australia have the best vantage point to study it. For those living in the Northern Hemisphere, this pole never rises above the horizon, making it a treasure hidden from half of humanity's eyes. Like its northern twin, this southern region of the sky is unusually quiet. In astronomy, quiet means that it is not crowded with nearby stars, glowing gas, or the dark streaks of interstellar dust that so often block our view. Instead, the centre of this polar region is remarkably empty. And in astronomy, emptiness is a blessing. A quiet field gives us a wide-open window into the deep universe, allowing us to see beyond the Milky Way and into the greater structures that make up the cosmos. Clusters of galaxies, vast filaments of matter, and the immense dark voids in between. The galactic South Pole has long been a favoured hunting ground for astronomers who want to map the universe in 3 dimensions. One of the most famous of these projects was the 2-degree field galaxy redshift survey, often abbreviated as 2D-DFGRS. This ambitious effort, carried out in the late 20th and early 21st centuries, measured the distances to more than 200,000 galaxies. Why was the galactic South Pole chosen for such a monumental project? The answer is simple: clarity. Because this region of the sky has very little dust or gas in the way, it suffers from extremely low extinction. In other words, its view is not blurred or dimmed by material within our galaxy. This clarity makes it one of the best cross-sections of the universe available to astronomers. By studying the galaxies beyond the South Pole, scientists were able to create some of the first large-scale maps of the universe's cosmic web. These maps reveal that galaxies are not scattered randomly through space. Instead, they are strung together in vast chains and sheets, with enormous voids in between, an arrangement often called the cosmic web. The galactic South Pole was one of the first windows through which humanity saw this grand architecture. Although looking outward through the South Pole shows us the universe beyond, it also reveals secrets about our own galaxy. By tracing how stars and gas thin out as we move away from the Milky Way's central disk, astronomers can measure the shape of the galaxy's halo, the vast, faint sphere of stars and invisible dark matter that surrounds the disk. When data from the North and South Poles are compared, astronomers gain an especially powerful tool. If the Milky Way were perfectly symmetrical, the 2 poles would look identical, but research suggests that this is not the case. The southern view, in particular, shows hints of asymmetry. These irregularities may be the lingering scars of ancient galactic collisions. Over billions of years, the Milky Way has not grown in isolation. Instead, it has pulled in and absorbed smaller galaxies, a process sometimes called cosmic cannibalism. The stars and dark matter from these captured systems leave behind faint streams, ripples and clumps that are easier to detect when viewed from the clear vantage of the South Pole. In this way, the galactic South Pole becomes a kind of historical record, preserving evidence of the Milky Way's violent growth. The galactic South Pole is not only a window into history, it is also a practical tool for modern astronomy. Many space observatories use it as a calibration field. Calibration means checking and fine-tuning the instruments to make sure their measurements are accurate. Telescopes such as Galex, which observed ultraviolet light, Spitzer, which studied the infrared universe, Chandra, which focused on X-rays, and Planck, which mapped the cosmic microwave background, all relied on the polar regions of the galaxy for this purpose. Because these areas are relatively free of foreground clutter, they are perfect places to test instruments against faint and distant signals. For example, the Planck spacecraft used the galactic poles to refine its measurements of the cosmic microwave background, the faint afterglow left over from the Big Bang nearly 14 billion years ago. Without the clear skies of the galactic South Pole, such delicate observations would have been nearly impossible. The galactic South Pole is also home to 2 of the Milky Way's closest companions, the Sculptor Dwarf Galaxy and the Fornax Dwarf Galaxy. These small, faint galaxies orbit our own much larger system, and though they contain far fewer stars than the Milky Way, they are scientifically priceless. Because these dwarf galaxies are dominated by dark matter, studying them helps astronomers refine their models of how galaxies form and grow. By tracking the motion of stars within Sculptor and Fornax, researchers can measure how invisible dark matter shapes their gravity. These measurements, in turn, reveal clues about how the Milky Way itself has been building its mass over billions of years. In a sense, Sculptor and Fornax are like living fossils, small ancient systems that preserve the conditions of the early universe. Their presence near the galactic South Pole makes this region even more important. The South Pole also overlaps with an area known as the South Galactic Cap, a high-latitude region that has become a favourite target for deep sky surveys. Just as the North Galactic Cap has revealed immense filaments of galaxies and the vast emptiness of cosmic voids, the Southern Cap offers a complementary view. Only by combining surveys from both the North and the South can astronomers build a complete 3-dimensional map of the universe. If one half were missing, the picture would be unbalanced, like trying to understand Earth's geography while ignoring an entire hemisphere. The galactic South Pole ensures that our cosmic cartography is full and accurate. In recent years, a new field of astronomy has emerged, the study of gravitational waves. These are ripples in space-time itself, produced by cataclysmic events such as the collision of black holes or the merger of neutron stars. Projects such as LIGO in the United States and Virgo in Europe have already detected dozens of such waves, confirming predictions first made by Albert Einstein more than 100 years ago. In the coming decades, new observatories, including a space-based mission called LISA, will expand this work. For gravitational wave astronomy, the polar regions of the galaxy are invaluable. Because they are visible for long stretches of time, they allow continuous monitoring of potential events. The galactic South Pole, therefore, is not just a window to light, it is also a listening post for the deep rumble of the universe. Another mystery that the South Pole helps to unravel is the Milky Way's magnetic field. Like invisible lines of force, these magnetic fields thread through the galaxy, shaping the motion of charged particles, guiding cosmic rays, and influencing the flow of interstellar plasma. While most of these fields follow the spiral arms of the galaxy, some curve upward and downward into the halo. By observing them from the vantage of the South Pole, astronomers gain a vertical perspective, as though stepping back to see the entire structure in 3 dimensions. Mapping these magnetic lines is essential for another reason. They create foreground noise that can interfere with the search for faint cosmic signals. By carefully studying the magnetic fields at the galactic South Pole, scientists can build cleaner models that help separate the whisper of the early universe from the hum of our galaxy. In the language of science, the galactic South Pole is also known as a control field. When researchers study the universe, they need reference regions, patches of sky that are relatively empty and quiet, against which they can compare their more crowded observations. The South Pole provides exactly such a region. By using it as a baseline, astronomers can test their models of dark matter density, refine measurements of baryon acoustic oscillations, the faint ripples in the distribution of galaxies left over from the early universe, and confirm the reality of faint distant galaxy clusters. Without such a control field, many cosmological results would remain uncertain. It is true that the galactic North Pole often receives more attention in news headlines, especially when deep field images or cosmic microwave background studies are released. But the South Pole is no less important. Together, the 2 poles offer balance, symmetry, and perspective. The South Pole is a mirror to the North. It shows us whether our galaxy is truly even or slightly skewed. It provides a second calibration point for our instruments, ensuring that our cosmic measurements are accurate. It gives us access to quiet regions of space, where the universe can be studied in its purest form. Perhaps most importantly, it reminds us that no single viewpoint is enough. To truly understand the Milky Way, the cosmic web, and the grand structure of the universe, we must look in both directions, north and south, above and below, outward and inward. Try to picture yourself rising high above the solar system, far beyond the Earth, the Sun, and the planets. From this impossible height, you look down, not from any mountain or spacecraft, but from a place that floats outside the familiar bonds of home. You're no longer tied to the spinning Earth or to its curved horizon. You're out in the silence of space, where directions such as up and down lose their usual meaning. Here in space, there is no floor, no ceiling, no walls, only endless blackness scattered with stars. Yet astronomers, the people who devote their lives to understanding the universe, cannot afford to wander without guidance. They need a fixed direction, a stable marker, something that never wavers no matter where they look or how far they travel. On Earth, we have the North Pole, the South Pole, and the lines of latitude and longitude that help sailors and pilots find their way. But what about in space? That is where the idea of the galactic North Pole comes in. The galactic North Pole is not a glowing star, nor is it a bright beacon shining above the Milky Way. It is instead a point, an invisible, purely geometric direction in the sky that scientists use as a kind of cosmic compass. Though it cannot be seen with the naked eye, its importance is extraordinary. By pointing toward it, astronomers decide which way is above the flat disk of our galaxy. To imagine this more clearly, think of the Milky Way as an enormous disk, something like a record or a DVD, only millions of times larger than our entire solar system. It is wide but very thin, with billions of stars, clouds of gas and streaks of dark dust spread across its surface. Now, if you were to stick a pin straight through the middle of that disk at a perfect right angle, the pin would poke out on both sides. One end would point upward. That is the galactic North Pole. The other end would point downward. That is the galactic South Pole. The galactic North Pole lies in the sky in the direction of a faint constellation known as Coma Berenices, the Hare of Berenice. It is not a famous constellation like Orion or Leo, though Leo, the Great Lion, rests nearby. Coma Berenices is made of soft, dim stars that look almost like a cloudy patch. Yet in that quiet patch of sky, astronomers have anchored one of the most important reference points in all of space. Unlike Earth's North Pole, which shifts over time because of the planet's wobble, the galactic North Pole is fixed in a way that feels eternal. The Earth may tilt and lean, but the galaxy's frame remains steady. It is, in short, the ultimate up of the Milky Way. One might ask, why is this so important? Why does anyone care which way is up when there is no gravity in space to define it? The answer is that the universe is not a random sprinkle of stars. It is highly structured. Galaxies spin, stars form in vast clusters, black holes pull on their surroundings, and invisible rivers of gravity shape the paths of galaxies themselves. To measure any of this, astronomers need a fixed frame of reference. When scientists study the tilt of galaxies, the movement of our own solar system, or mysterious phenomena such as the Great Attractor, an enormous gravitational anomaly pulling entire galaxies toward it, they need to say, we are moving this way, tilted at this angle, pointing in this direction. Without a standard point like the galactic North Pole, every measurement would be uncertain. Just as a pilot uses pitch, roll, and yaw to describe the orientation of an airplane, astronomers use three-dimensional directions to describe the orientation of the solar system. The galactic North Pole is the anchor of that system. To find this special point, astronomers invented what is called the galactic coordinate system. It works much like Earth's latitude and longitude. On Earth, the equator divides the globe into north and south, and from there we measure degrees of latitude. Longitude lines, running from pole to pole, let us measure east and west. In the galaxy, the disk of the Milky Way plays the role of the equator. The galactic North Pole is defined as the point lying at 0 degrees longitude and plus 90 degrees latitude in this system. Its mirror opposite, the galactic South Pole, lies at minus 90 degrees. When astronomers point their telescopes at this direction, something remarkable happens. Their view clears. The dense clutter of stars, gas and dust that fills the main disk of the Milky Way falls away. Instead of peering through a fog of galactic material, the telescopes gaze through a much cleaner window of space. This window makes the galactic North Pole one of the best places in the entire sky for deep observations. Through it, astronomers have spotted some of the most distant galaxies ever known. Light that has travelled for billions of years streams through this opening, reaching our instruments without being swallowed by the dust of our own galaxy. By observing through this direction, scientists have also mapped the halo of the Milky Way, a vast, ghostly bubble of dark matter, thin gas, and scattered ancient stars that stretches far beyond the glowing spiral arms. The halo is invisible to ordinary sight, yet it contains much of the galaxy's hidden mass. Without the clear path offered by the galactic North Pole, charting this faint structure would have been nearly impossible. But the usefulness of this cosmic compass does not end there. The galactic North Pole also provides one of the best vantage points for studying the cosmic microwave background radiation, the faint glow left over from the birth of the universe itself. This radiation, which fills every corner of space, is the cooling afterglow of the Big Bang, the event that began the universe nearly 14 billion years ago. To study this delicate signal, scientists need quiet regions of sky, places not filled with the noisy radiation of stars, dust and gas. The Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck Observatory both turned their eyes toward the galactic North Pole for exactly this reason. Looking there is like peering back across nearly the entire history of the cosmos, to a time when the first atoms were forming and light itself was just beginning to travel freely. Even newer branches of science, such as the study of gravitational waves, rely on knowing the orientation of the galaxy. Gravitational waves are ripples in space-time created when enormous objects, like black holes or neutron stars, crash into one another. Detectors on Earth, such as LIGO and Virgo, record the faint tremors from these cataclysmic events. But to make sense of the signals, astronomers must know exactly where they are within the galactic frame. These violent events are not scattered randomly. They cluster around regions of great mass, following the invisible skeleton of cosmic structure. By mapping their positions relative to the galactic north and south poles, patterns emerge that would otherwise remain hidden. Meanwhile, our solar system itself is far from fixed. The Sun, along with its planets and comets, drifts in a slow, stately orbit around the centre of the Milky Way. This journey takes roughly 230 million years to complete. In other words, since the time of the dinosaurs, the Sun has circled the galaxy less than 3 times. As the solar system moves, its angle to the galactic North Pole changes. The journey is part of a graceful, endless dance, a slow circling in the sea of stars. Knowing where the galactic North Pole is today helps scientists trace where we were long ago and predict where we will be millions of years from now. It is almost poetic that something so invisible, something that no eye can see without mathematics and careful definition, can serve as such a powerful anchor. The galactic North Pole does not shine, does not glow, and yet without it we would be lost. It is the silent compass needle of the galaxy, guiding our measurements, our observations, and even our imagination. This naturally leads to a deeper question. What truly lies above the North Pole of the Sun? If we were to rise straight upward, past the fiery crown of the Sun, past the circling orbits of the planets, and past the far-off cloud of comets that marks the edge of our solar system, what would we find? The answer is not a wall, nor an edge, nor a ceiling. We would pass into the immense open dark. We would pass distant galaxies, glowing quasars, and webs of matter stretching across billions of light years. Each layer would carry us farther back in time, farther into the unfolding story of the universe. And through it all, the galactic North Pole would remain our arrow, pointing the way into the greatest mysteries of all. Far above the blazing surface of our Sun, past the boiling storms that churn across its face, there lies a region that is both mysterious and powerful, the solar polar region. This is not an empty, quiet stretch of space. It is a place alive with invisible forces, where the Sun's magnetic fields bend, twist and stretch like giant ropes under tension. It is also where rivers of blazing hot plasma, streams of charged gas so hot that atoms themselves have been torn apart, are constantly shifting and flowing outward. If you look toward the equator of the Sun, the story looks different. There, dark patches known as sunspots appear and fade like bruises on the solar surface, and violent explosions called solar flares burst outward with tremendous force. But the poles of the Sun are quieter in comparison. Quieter, yes, but not silent, and certainly not lifeless. The poles are not a place of inactivity. They are like hidden engines, quietly but powerfully shaping the environment of the entire solar system. What happens above the poles does not stay there. It stretches outward and influences the space that every planet, every comet, and even our Earth must live within. The Sun is not steady or unchanging. It has a natural rhythm, a heartbeat of sorts, called the solar cycle. This cycle repeats roughly every 11 years. During this time, the Sun's magnetic field becomes tangled and chaotic, then slowly reorganizes itself, flipping its north and south poles in the process. One of the calmest moments in this cycle is known as the solar minimum. This is the quiet phase, when sunspots nearly vanish and the Sun's magnetic field smooths itself out. At the poles, during solar minimum, the field lines straighten and stretch outward into space like tightly drawn arrows. From these poles, powerful but invisible rivers of solar wind, streams of high-speed particles shoot outward across the solar system. These particles are not drifting aimlessly. They are busy workers in the construction of something enormous, the heliospheric current sheet. This is an unimaginably large and warped spiral of magnetic influence that spreads out from the Sun like a giant rotating skirt, wrapping around every planet and every piece of space within the solar system. It is one of the greatest invisible structures in existence, and it begins, in large part, with the winds flowing outward from the solar poles. In the year 1990, humanity took its first bold step toward exploring this unseen world. That year, the Ulysses spacecraft was launched. Ulysses was unique because it was designed not to circle around the Sun's equator, like most spacecraft naturally would, but to soar high over its poles. It was the first mission to view the Sun from this extraordinary angle. Throughout the 1990s and into the early 2000s, Ulysses completed several journeys above both the north and south poles of the Sun. What it discovered was groundbreaking. The winds above the poles, it revealed, were not the same as those near the equator. At the poles, the solar wind blew faster, was thinner, and far more steady. In contrast, the winds near the Sun's equator were thicker, denser, and more chaotic, changing speed and direction in unpredictable ways. This fast polar wind is not just an interesting curiosity. It is one of the key forces that sculpts the heliosphere, the gigantic bubble that surrounds our entire solar system. The heliosphere is not just empty space, it is a shield. It acts like a protective barrier that pushes back the most dangerous cosmic rays coming from deep in the galaxy. Without it, Earth and the other planets would be exposed to far higher doses of deadly radiation. The heliosphere is, in a very real sense, a life-preserving cocoon. And the steady winds of the poles are part of what gives it its shape. You can think of the space above the Sun's north pole as a kind of cosmic gateway. It is the starting line from which streams of energy, particles, and magnetic waves launch outward into the galaxy. If you followed those streams outward, far past the orbit of Neptune and Pluto, you would eventually reach the edge of the heliosphere, the place where the Sun's influence finally fades and the galaxy takes over. At this outer edge, the solar wind particles are fewer and weaker. The Sun's magnetic field stretches into long, thin strands that eventually begin to tangle with the great magnetic fields drifting between the stars. This is where the Sun's power surrenders to the greater forces of the Milky Way galaxy. In the year 2012, a spacecraft named Voyager 1 reached this frontier. Launched back in the late 1970s, Voyager 1 had travelled for decades before finally crossing the invisible boundary of the heliosphere. It did so near the Sun's northern edge, which means that, in a galactic sense, it passed above the Sun's north pole. What lies beyond this border? The local interstellar medium, a thin sea of gas, dust, and high-energy cosmic rays flowing between the stars. Right now, our Sun is drifting through a patchy part of this medium known as the local interstellar cloud. This cloud is slightly warmer and denser than the surrounding space, and it presses against the heliosphere, squeezing it on one side and stretching it on another, like the wind pressing against a balloon. Because the Sun is not standing still but racing through the galaxy at thousands of miles per hour, the heliosphere is not a perfect round bubble. Instead, it forms something more like a teardrop, with a blunt nose facing forward in the direction of the Sun's travel. Interestingly, this nose is not perfectly centered. It tilts slightly upward, toward the region above the solar system's midplane and close to the Sun's north pole. This tilt means that many of the strange effects, particles and waves that deep space probes encounter, come from above, not from the flat plane of the planet's orbits. In a sense, the north pole of the Sun is not just pointing upward, it is pointing forward, toward the future, into the direction the Sun itself is travelling through the galaxy. If you could rise even higher, leaving the heliosphere altogether, the view above the Sun's north pole would open into the wider galaxy. This direction offers one of the clearest windows into deep space. Unlike other directions where interstellar dust blocks and scatters light, the path above the North Pole is relatively clean and clear. This gives astronomers a nearly unobstructed view into the depths of the cosmos. Powerful instruments such as the Chandra X-ray Observatory and the Planck spacecraft have taken advantage of this direction. By peering along this window, they have studied distant galaxies, measured faint radiation left over from the birth of the universe, and tracked mysterious high-energy X-ray sources. The North Pole of the Sun, in other words, points directly into some of the clearest lines of sight we have into the grand history of the cosmos. Even cosmic rays, the ghostly particles that zip across the universe and constantly rain down on Earth, show unusual behaviour in this direction. Studies have revealed that slightly more of them seem to arrive from the galactic north than from other directions. This suggests that the region above the Sun is not just empty sky, but may be shaped by hidden structures and energetic events we do not yet fully understand. In many ways, the space above the Sun's North Pole is not fully the Sun's domain, but it is not fully the galaxies either. It is a borderland, a transition zone where the two powers overlap. On one side, the Sun's influence still flows outward. On the other, the vast forces of the Milky Way press inward. Together they create a frontier, a cosmic meeting ground where two great realms, the solar and the galactic, touch and intermingle. It is in this frontier that some of humanity's most daring spacecraft have already travelled. The twin Voyager probes went this way, and more may follow. NASA is currently studying the idea of an interstellar probe, a spacecraft designed specifically to leave the heliosphere and explore the interstellar medium directly. If built, it too would most likely travel northward, upward, and outward, just as Voyager 1 did. This path above the Sun's North Pole, then, is not just an abstract idea for scientists. It is a direction that humanity itself has already begun to follow. From the first discoveries of Ulysses to the long journey of Voyager 1, and perhaps soon to the future interstellar probe, we have been reaching outward through this northern corridor. Every step takes us farther from the cradle of the Sun and closer to the ocean of stars beyond. To travel northward above the Sun is to leave behind the familiar rhythms of our solar system and enter a realm shaped by the galaxy itself. It is a journey from the known into the unknown, from the warm glow of our star into the deep, cold mysteries of interstellar space. High above us, hidden within the hazy glow of the Milky Way, lies a structure so mysterious that most people on Earth have never even heard its name. Yet astronomers have been carefully studying it for many decades, searching for answers to questions that remain unsolved to this very day. This strange formation is called the North Galactic Spur, and to the naked eye it appears like a faint ghost stretching across the northern heavens, almost as if an enormous dusty bridge had been hung across the stars. At first glance, the spur is easy to overlook. Unlike the bright, dazzling band of the Milky Way that shines with the light of billions of stars, this feature is tricky to spot. In visible light, it is hidden and obscured by thick clouds of gas and dust, which block much of its natural glow. But when astronomers turn their special instruments toward it, radio telescopes that can detect invisible radio waves, detectors that sense microwaves, and even X-ray instruments that capture the most energetic forms of light, the North Galactic Spur suddenly reveals itself. Through these cosmic new eyes, it becomes one of the most striking and powerful features in the entire sky. The spur is not a small or local cloud of dust. It is enormous. In maps made with radio waves, it appears as a long, curving filament shaped almost like a giant arc. This arc rises high above the flat plane of the Milky Way galaxy and then curves back downward again, forming a sweeping loop. The structure seems to begin close to the very heart of the galaxy, not far from the galactic center itself, and then it extends outward across a vast portion of the northern sky. To the imagination, it looks almost like the mark of a cosmic paintbrush. Picture a giant hand sweeping across the heavens with a single brushstroke, leaving behind a glowing trail. That trail in many ways resembles the shape of the North Galactic Spur. Its sheer size is difficult to grasp. On the sky, it stretches across dozens of degrees, covering a region far larger than the Moon, the Sun, or even many familiar constellations. Despite decades of study, astronomers are still debating what exactly the spur is. Several competing theories exist, each one fascinating in its own right. One popular idea suggests that the spur is part of something called a superbubble. A superbubble is a gigantic shell of gas and dust, pushed outward by the combined explosions of many massive stars. When giant stars reach the end of their lives, they do not fade quietly. Instead, they explode as supernovae with unimaginable power, releasing more energy in a single moment than our Sun will produce over its entire lifetime. If several of these colossal stars exploded in the same general region of the galaxy, their shock waves could combine, sweeping gas and dust outward into a gigantic arc. Over time, this would leave behind a loop-like scar across the heavens, the very scar that we now see as the North Galactic Spur. If this explanation is correct, then the spur is more than just a faint arc of dust. It is a cosmic memory, a visible reminder of the titanic violence of ancient stars that perished millions of years ago. Other scientists argue for a very different explanation, one that places the spur much closer to home. According to this view, the spur may not be part of a massive galactic shell at all. Instead, it could be a wall belonging to something called the local bubble. The local bubble is the region of space that our solar system is currently drifting through. It is filled with very hot, very thin gas, which is electrically charged and spread out over hundreds of light years. This bubble too was likely carved out by a chain of nearby supernova explosions. But these explosions happened relatively recently, perhaps only a few million years ago, and not far from our Sun. If this theory is true, then the North Galactic Spur is not a vast galactic structure spanning thousands of light years. Instead, it is more like a nearby scar, a local wall of gas and dust left behind by violent events that took place in our cosmic neighbourhood not too long ago. There is also a third possibility, which combines the first two. Some astronomers believe that the spur might actually be both a local structure and a galactic-scale feature layered on top of one another. If that is the case, then when astronomers point their telescopes at the spur, they are looking through several overlapping layers of gas and dust. Each layer could be located at a different distance, moving at a different speed, and shaped by different events. This overlap makes the problem extremely complicated. It is a bit like standing on the ground and trying to sketch the shape of a mountain range while thick clouds drift across the view. The clouds might hide some peaks, exaggerate others, and even create illusions. Untangling the spur's true shape and origin is just as tricky. The North Galactic Spur is not simply a curiosity for astronomers to puzzle over. It also plays a very important role in some of the most sensitive scientific experiments ever conducted. One of the greatest achievements of modern science was the discovery and study of the cosmic microwave background, or CMB. This faint glow is the afterlight of the Big Bang itself, the leftover radiation from the birth of the universe nearly 14 billion years ago. In order to study this faint signal, scientists launched satellites like WMAP, Wilkinson Microwave Anisotropy Probe, and later the Planck mission. These instruments measured the CMB with incredible precision. But there was one major challenge. Our own galaxy produces microwave radiation as well, which can contaminate the signal. The North Galactic Spur was one of the biggest sources of this contamination. Because it shines strongly in polarized radiation, it created a kind of foreground noise that scientists had to carefully subtract from their data. Without accounting for the spur, the delicate patterns of the CMB, which reveal information about the early universe, could have been completely misinterpreted. At one time, some researchers even thought that signals from the spur might be hints of something much stranger: dark matter annihilation near the galactic center. Dark matter is one of the biggest mysteries in science. It does not emit or absorb light, yet its gravity shapes galaxies and clusters of galaxies. When astronomers detected unusual radiation near the center of the Milky Way, some believed it might be the result of dark matter particles colliding and destroying each other. But later studies revealed that much of this strange radiation was not exotic at all. It was caused by ordinary structures like the spur. This was an important lesson. It showed just how critical it is to understand our own galactic environment. Misinterpreting something nearby can lead to false conclusions about the universe itself. The spur also provides scientists with a rare opportunity: the chance to study magnetic fields on the scale of the galaxy. Normally, magnetic fields are invisible, but inside the spur, tiny dust grains align themselves with the Milky Way's magnetic field lines. This alignment causes the dust to emit polarized light waves that are oriented in specific directions. By mapping this polarized light, astronomers can trace the otherwise invisible structure of the magnetic fields that weave through the galaxy. This is an extraordinarily difficult thing to study, and the spur serves as a natural laboratory for it. In this sense, the spur is not just a cosmic curiosity, but a crucial scientific tool. And yet, even with all this knowledge, the North Galactic Spur remains a mystery. It does not behave like a simple arc. It does not fit neatly into any current model of the Milky Way structure. At times, it seems like a trick of perspective, a strangely shaped cloud of dust that just happens to look like a sweeping arc when viewed from Earth. At other times, it seems like something vast and powerful, a structure whose true shape we're only beginning to glimpse. The truth may be stranger than any of the current theories. The universe, after all, often surprises us. The future holds hope for solving this riddle. New missions with advanced technology will soon provide astronomers with three-dimensional maps of the sky at an unprecedented level of detail. One such mission is Sphere X, the spectrophotometer for the history of the universe, epoch of Ryanization, and ICES Explorer. With instruments like these, scientists may finally be able to measure the true distance of the spur, trace its actual shape, and uncover its origins. Perhaps they will find that it is a nearby wall of the local bubble, or perhaps they will discover that it is indeed the scar of ancient supernova from the heart of the galaxy. Or maybe, as often happens in science, they will find something entirely unexpected, something no one has yet imagined. Until that day arrives, the North Galactic Spur remains what it has always been, a dusty bridge suspended above our heads, stretching across the northern sky. It carries with it mystery, history, and the echoes of events that shook our galaxy long before humans ever looked upward to wonder about the stars. When you look up into the night sky and see the glowing band of the Milky Way, imagine that faint ghostly arc running across it. Think of the massive stars that may have exploded to create it, or the cosmic bubbles of gas that may surround us. Think of the magnetic fields, the radiation, and the secrets hidden in its light. High above our heads, far beyond the reach of the mountains, airplanes, and even satellites, there is a hidden but immensely powerful point in the northern sky. It is called the North Celestial Pole. You cannot touch it, and you cannot see it directly, for it is not a star or a planet. It is simply a point, a direction in space. Yet its importance is so great that for thousands of years it has guided sailors across dangerous seas, led explorers across deserts and forests, and helped astronomers unlock the secrets of the heavens. It is one of those quiet mysteries of the universe, invisible, untouchable, but shaping the way humans have travelled, built, and dreamed for countless generations. To understand the North Celestial Pole, imagine the Earth spinning like a great top. Our planet rotates around an invisible line called its axis of rotation. This axis runs through the Earth from the geographical North Pole to the geographical South Pole. If you extended that axis far, far out into space, the point where it touched the northern sky would be the North Celestial Pole. From our point of view on Earth, this pole looks like the exact centre of the heavens, the very spot around which every star of the northern sky appears to turn each night. When we watch the stars rising and setting, what we are really seeing is the effect of our planet's constant spin. The stars seem to move in great circles, but the North Celestial Pole stays fixed, holding everything together like the central nail in a spinning wheel. This makes it far more than a curious astronomical detail. The North Celestial Pole is the foundation stone of celestial navigation, the reference point for astronomy, and the pivot on which our understanding of the heavens rests. Marking this special spot for us is a star of great renown, Polaris, also known as the North Star. Polaris is not the brightest star in the night sky. That honour belongs to Sirius, but its position makes it one of the most important. Polaris sits almost exactly above the Earth's geographical North Pole. If you were standing at that icy tip of the planet, Polaris would shine directly overhead, right at the zenith of the sky. To travellers, this meant something extraordinary. Polaris always pointed north. No matter where you stood in the northern hemisphere, if you could find Polaris, you could find your direction. For countless sailors who crossed dangerous oceans before the invention of the compass, Polaris was a lifeline. They would keep their eyes on this steady star, steering their ships across the vast Atlantic or Pacific with the confidence that Polaris never lied. On land, explorers moving through deserts or uncharted forests looked for it too, knowing it was a natural compass set high in the heavens. Polaris earned its reputation as the anchor of the night sky because it barely shifts its position, while other stars wheel around it in circles. In long exposure photographs of the night sky, stars appear as glowing arcs or complete rings, but Polaris stands still, marking the north with calm certainty. Yet this perfect alignment is not eternal. Our planet is not a perfectly steady spinning top. It wobbles. This wobble is known as axial precession. Just like a child's top begins to trace a circle as it slows down, the Earth's axis also traces a huge, slow circle in the sky. One complete wobble takes about 26,000 years. That is longer than the entire span of recorded human history. This immense cycle slowly shifts the North Celestial Pole across the sky, changing which star serves as the North Star. About 5,000 years ago, the star Thuban in the constellation Draco was the North Star. Ancient Egyptian builders who raised the Great Pyramids of Giza may have aligned them with Thuban rather than with Polaris. Today, in our time, Polaris holds the title. About 12,000 years from now, the bright star Vega in the constellation Lyra will take Polaris's place as the guiding star of the North. This means that the honour of being the North Star is temporary. Polaris may seem unchanging to us, but in the grand rhythm of the cosmos, it is only passing through this role. This slow shift is not just of interest to astronomers. The position of the North Celestial Pole affects many areas of human activity. Astronomers align their telescopes with the pole to track stars and galaxies across the night sky. Without this reference point, it would be far harder to observe distant objects with precision. Engineers use the celestial pole as a reference to orient satellites and to calibrate the instruments of spacecraft travelling beyond Earth. Even communication antennas on the ground are often aligned using Polaris. Tiny shifts in the pole's position reveal the effects of the Sun and the Moon tugging on our planet. These measurements are used in precise timekeeping, in planning space missions, and even in long-term studies of climate. Many ancient structures, from stone circles to pyramids, were aligned to the North Star of their time. As the pole shifted, these monuments became silent witnesses to the changing sky. The pole, then, is more than an abstract idea. It is a tool of navigation, a guide for science, and a thread that ties human history to the heavens. From Earth, the North Celestial Pole acts like a great hinge on which the heavens swing. Every night, as our planet rotates, the stars appear to wheel around this fixed point. To the naked eye, this motion is subtle, but with patience, you can see it. Over the course of hours, constellations rise in the east, arc across the sky, and set in the west. The pole stays steady, unmoved, while the rest of the sky dances around it. Long exposure photographs show this beautifully. In such pictures, stars do not appear as single points of light but as long trails, curved like arcs of a circle. All of these circles share the same centre, Polaris, and the North Celestial Pole. It is the photographic proof that our world spins, night after night, always turning around that invisible pivot. The story of North is larger than just Earth. Our solar system has its own north, defined by the tilt of the Sun's equator. This does not line up perfectly with the Earth's north, because our planet's orbit is tilted compared to the Sun. On an even greater scale, our Milky Way galaxy has a north pole as well. It is located in the constellation Coma Berenices, far from Polaris. This means that up for Earth is not up for the solar system, and neither is up for the galaxy. Astronomers must juggle all these different definitions of north when mapping the stars or studying the faint afterglow of the Big Bang, the cosmic microwave background radiation. Because of these different poles, astronomers use three main coordinate systems to describe positions in the sky: equatorial coordinates, tied to the Earth's rotation and the North Celestial Pole; ecliptic coordinates, tied to the Sun's yearly path across the sky; galactic coordinates, tied to the structure of the Milky Way galaxy. The North Celestial Pole is the starting point of this great framework, anchoring one of the most important coordinate systems in astronomy. The North Celestial Pole is also a delicate measuring stick. Astronomers track its tiny movements against the background of distant stars. These measurements reveal the gravitational pull of the Moon and the Sun on our planet, the redistribution of mass within the Earth's oceans and atmosphere, and even the slow melting of ice caps. By studying the pole's position with precision, scientists can refine our calendars, improve climate models, and prepare for space missions that demand pinpoint accuracy. Because the Earth's axis slowly sweeps a circle in the heavens, the view of the universe changes across the ages. New stars rise into prominence, constellations shift, and the seasonal skies transform. What we see today is not what our ancestors saw thousands of years ago, and it will not be what our descendants see thousands of years from now. The North Celestial Pole, therefore, is not just a static marker. It is the silent hand that turns the great wheel of the heavens, reshaping human skies over millennia. When you look up at Polaris on a clear night, you are gazing directly down the Earth's axis of spin, at the pivot point of the sky. To generations of people, it has symbolized constancy, guidance, and direction. Yet its very constancy is an illusion, for the pole itself is always on the move. It is a paradox, a point that seems permanent, but is in truth part of a vast, slow, and graceful motion that spans tens of thousands of years. The North Celestial Pole reminds us that even the steadiest things in the heavens are not fixed forever. They too are part of the great dance of the cosmos. When most people imagine the universe, the first picture that comes to mind is often a vast black emptiness sprinkled with countless shining stars. It looks still, silent, and lifeless, like a frozen ocean that never moves. But this picture is far from the truth. Space is not empty at all. It is alive with invisible forces, rivers of particles, and great unseen structures that shape everything around us. Among these hidden powers, one of the most mysterious and most important is the magnetic field. Magnetic fields are not something we can see with our eyes, yet they are everywhere. They guide the paths of tiny particles, influence the birth of stars, and even shield planets from dangerous cosmic radiation. Here on Earth, we live inside a magnetic cocoon created by our own planet's molten core, and without it, life as we know it would probably not exist. But Earth's magnetic shield is only one small layer of protection. Far above us, surrounding our entire solar system, there is an even greater shield, the heliosphere. The heliosphere is like a giant bubble blown into space by our sun. It is created by the solar wind, a steady, invisible stream of charged particles that the sun sends out in every direction. This wind never stops. It constantly flows outward, filling the solar system and pushing against the thin material that exists in the space between stars. Inside this protective bubble, the sun is in charge. Its winds and its magnetic fields control the environment, shaping the space through which Earth and the other planets travel. But beyond the bubble, the power of the sun fades, and something else begins to take over: the forces of the wider galaxy. At this boundary, the interstellar magnetic field makes its presence known. This magnetic field does not belong to our sun at all. Instead, it belongs to the galaxy itself, the great sea of stars, gas, dust, and energy that stretches far beyond anything our eyes can see. The edge of the heliosphere is not a sharp, solid wall like the sides of a glass jar. Instead, it is more like the blurry, shifting boundary where two oceans meet. On one side is the solar wind, pushing outward with all its strength. On the other side is the interstellar medium, the extremely thin mixture of gas, dust, and magnetic fields that fills the spaces between the stars of the Milky Way. When these two forces collide, neither side wins outright. Instead, they wrestle in a constant tug of war. The solar wind slows down, becomes disturbed, and finally halts at a border known as the heliopause. This is the true edge of the sun's influence, the place where the solar wind can no longer push back against the greater powers of the galaxy. Just beyond this invisible line, especially above the northern pole of the sun, the magnetic field of the galaxy itself begins to bend, twist, and flow through the region. It is here, in this strange frontier zone, that two invisible powers, the sun and the galaxy, weave themselves together. In the year 2012, humanity received a glimpse of this frontier unlike any before. A small spacecraft launched all the way back in the late 1970s finally reached the edge of the solar system. This spacecraft was Voyager 1, a probe built to study the outer planets, but destined to go much farther. Voyager 1 became the first human-made object to leave the heliosphere and enter interstellar space. For decades, scientists had wondered what this crossing would look like. They expected that when the spacecraft passed the heliopause, the direction of the magnetic field would change suddenly, flipping like a compass needle in reverse. But that was not what happened. Instead of an abrupt change, Voyager recorded something stranger and more beautiful. The solar magnetic field did not end at all. It bent gently, twisted, and slowly merged with the galactic magnetic field beyond. It was as though two invisible rivers had met, their currents weaving together into a tangled net of lines that folded, joined, and spiraled into one another. This discovery shocked scientists. It meant that the edge of the solar system was not a clean break, but rather a zone of blending, a kind of cosmic handshake between our sun and the galaxy. These magnetic fields above the heliosphere are not just background scenery. They play an active role in the life of our solar system. In fact, they are like both gatekeepers and highways. From the farthest reaches of the universe, powerful particles race through space. These particles, called cosmic rays, are born in violent places, exploding stars, jets of energy from black holes, and massive supernova remnants. They travel at nearly the speed of light, carrying immense energy. The magnetic fields at the edge of the heliosphere decide how many of these particles can enter our solar system. Sometimes the interstellar field blocks them, sometimes it bends them aside, and sometimes it channels them straight toward Earth and the other planets. During times when the sun is active and stormy, its magnetic shield grows stronger, making it harder for cosmic rays to get inside. But when the sun becomes quiet and calm, its shield weakens, and the galactic magnetic field pushes harder, allowing more cosmic rays to stream in. Scientists have even found that many of these particles come more easily from the direction of the galactic north, above the plane of the Milky Way. This is not just theory or guesswork. Instruments have actually seen signs of these magnetic battles. The spacecraft IBEX, which stands for Interstellar Boundary Explorer, along with the Cassini spacecraft that once orbited Saturn, have detected a strange glowing feature in the sky. They found a faint ribbon of energetic particles stretching across the heavens, like a scar etched in light. This ribbon appears to be aligned with the direction of the local interstellar magnetic field. In other words, it is a visible mark left by the invisible forces pressing against our solar bubble. This discovery was powerful evidence that the Sun and its heliosphere are not free-floating or untouched. Instead, they are being squeezed, shaped, and even wrapped by the galactic magnetic fields that surround us. Yet, despite these discoveries, the true shape of these magnetic lines remains a riddle. Scientists are still asking, are the lines neat and smooth, curving gently like the field around a simple bar magnet? Or are they tangled and twisted, knotted by ancient explosions, stirred by the spinning of the Milky Way, and churned by winds from countless stars? The answer is more than just a matter of curiosity. The way these lines are arranged has a direct impact on the future of space exploration. Magnetic fields can accelerate particles to nearly the speed of light, or they can trap them in deadly belts of radiation. They can disrupt spacecraft signals, expose astronauts to dangerous cosmic rays, and even confuse navigation systems that rely on charged particle flows. So how strong are these mysterious fields? Measurements suggest that the magnetic field just outside the heliosphere has a strength of about 36 microgauss. That is far weaker than the magnetic field on Earth, but it is still strong enough to shape the flows of particles and even influence the structure of the heliosphere itself. Some scientists believe that our solar system is currently drifting into a new part of the local interstellar cloud, a different patch of galactic material with slightly different magnetic conditions. If that is true, then in thousands of years the shape of the heliosphere could change. It might shrink or grow, offering more or less protection from deadly cosmic radiation. Over such timescales, the very environment of our planets could be reshaped by the invisible magnetic powers of the galaxy. There may even be a link between our local magnetic field and one of the Milky Way's largest and strangest features, the North Galactic Spur. This is a gigantic arc of gas, dust, and magnetic activity that rises above the disk of the galaxy like a great arching wave. Some researchers think that the interstellar magnetic field surrounding our solar system may align with this colossal structure. If so, then our solar system could be sitting inside a kind of wide magnetic corridor, a channel through which particles, dust, and radiation flow across the galaxy. If this connection is real, then our solar system's place in the galaxy is not random, but part of a much larger cosmic design. To uncover the truth, scientists are already preparing new missions. One of the most promising is the Interstellar Mapping and Acceleration Probe, or IMAP. This mission is scheduled for launch in the late 2020s. IMAP's mission will be to map out how particles gain speed at the edge of the heliosphere and how the galactic magnetic field shapes that process. Its instruments will be far more advanced than those of IBEX or Voyager. With sharper eyes and more sensitive detectors, IMAP may finally reveal the true shape and direction of the invisible lines above the Sun. For the first time, we may be able to see not just where our solar system ends, but how it fits into the grand magnetic framework of the galaxy. The more we learn, the clearer it becomes that the edge of our solar system is not a quiet boundary. It is a living, shifting frontier, a battlefield, a shield, and a gateway all at once. The heliosphere protects us, yet it is also vulnerable to the greater forces of the galaxy. The magnetic fields that twist above the sun are not static. They bend, weave, and ripple, shaped by the life and death of stars, by the spinning of the Milky Way, and by the restless winds of space. They decide how cosmic rays reach us, how spacecraft travel, and how humanity may one day journey to the stars. Space, it turns out, is not an empty void. It is alive with power. And at the edge of the sun's great bubble, where our star meets the galaxy, the invisible web of magnetism reminds us that we are part of a much larger cosmic story. When people look up into the night sky, most of the attention is usually drawn to the wide, bright band of the Milky Way. From Earth, it looks like a misty river of light stretched across the heavens, its countless stars merging into a shining path. Astronomers have long known that this glowing streak is actually the flat disk of our galaxy, made up of stars, clouds of gas, and drifting dust. But what very few people realize is that this glittering disk is not the whole story. Far above and far below this shining spiral lies something much bigger, stranger, and harder to see. Surrounding the Milky Way on every side is a vast, ghostly sphere of matter. It is so faint and so spread out that it almost seems invisible, like a giant transparent bubble encasing the galaxy. Astronomers call this hidden structure the galactic halo. Even though our eyes cannot see it, its invisible gravity has a powerful grip on everything inside the Milky Way, binding stars, gas, and even our own solar system into a single cosmic family. As the sun and its planets continue their endless journey around the center of the galaxy, they do not travel through empty blackness. Instead, they drift inside the lower edge of this immense and mysterious halo, brushing against a structure whose true nature still puzzles even the brightest minds in astronomy. The galactic halo is not one single thing. It is made up of two very different parts. The first is called the stellar halo. This portion is filled with some of the most ancient stars in existence, along with great swarms of globular clusters. A globular cluster is a tight ball of hundreds of thousands, or even millions, of stars all bound together by gravity. These clusters are not new arrivals. They have been orbiting the Milky Way for billions of years. Unlike the stars in the galactic disk, which move in neat, ordered circles around the center, the stars of the stellar halo wander like drifters. Their paths are not smooth or level, but stretched and tilted, sometimes carrying them high above the galactic plane. They seem almost restless, traveling in directions that reveal they are not native to the Milky Way. In fact, these stars and clusters act like fossils in the sky. They preserve a record of events from the galaxy's ancient past. They whisper stories of cosmic violence, telling astronomers that the Milky Way was not built all at once, but grew over time by swallowing smaller galaxies. When these tiny galaxies crashed into ours, their remains were scattered and smeared across the halo. Each lonely star wandering on a tilted path is a survivor from those long ago collisions. The second and much larger part of the halo is even more mysterious. It is made of something called dark matter. Dark matter is one of the strangest concepts in all of science. It does not shine like stars, does not glow like hot gas, and does not reflect a light in any way. To telescopes, it is completely invisible, and yet dark matter outweighs every star, planet, and gas cloud in the entire galaxy. Astronomers believe that most of the Milky Way's mass, perhaps more than 80% of it, is locked away in this invisible material. The dark matter halo stretches outward for hundreds of thousands of light years, forming a gigantic, unseen web around the galaxy. The proof of its existence lies in how it pulls on the stars. If we only counted the visible matter, the stars, gas, and dust, the Milky Way's spiral arm should spin much slower than they do. But they do not. They spin far faster, as though an enormous hidden weight is keeping them bound together. That hidden weight is the dark matter halo, quietly holding the galaxy in place. Our own solar system lies within the lower portion of this halo. Above us is not empty silence, but a strange region filled with rarefied gas, ancient wandering stars, and the invisible grip of dark matter. The airless emptiness here is so thin that its density is far lower than even the best vacuum chambers scientists can create in laboratories on Earth. Yet, despite being so ghostly and empty, the halo is vital to the galaxy's stability. It acts almost like a cosmic cushion, pressing gently on the Milky Way and helping it keep its shape. Without the halo's influence, small companion galaxies might slowly drift away into the endless wilderness of intergalactic space. The halo keeps them bound to us, circling like distant moths around a central flame. In recent decades, astronomers discovered that the halo has another hidden layer, one they call the circumgalactic medium. This is a vast ocean of scorching hot gas that surrounds the Milky Way like a hazy veil. It is almost invisible to ordinary eyes, but it glows faintly in X-ray light. Scientists have detected it not by direct pictures, but by the way it interferes with light from even more distant objects such as quasars. The temperatures of this gas are astonishing. They range from about 1 million to 10 million degrees on the Kelvin scale, so hot that no solid object could survive inside it. In fact, astronomers believe that this cloud may contain more matter than all the stars in the Milky Way combined. The gas is not spread evenly. It tends to cluster above and below the galactic disk, almost as if the Milky Way were breathing fire out of its poles. Studying this circumgalactic medium is incredibly difficult. Unlike a star or a planet, it cannot be photographed clearly. Instead, scientists must assemble a picture of it from faint clues, the way it bends radio waves, the way it scatters light, and the delicate absorption lines it leaves on beams of light travelling from even farther galaxies. To investigate this fiery halo, astronomers have launched special space observatories. Satellites such as ROSAT, Chandra and XMM Newton have been essential in collecting data about the hot gas, and the future holds even more promise. Planned missions such as EXORISM and Athena are designed to provide sharper, more detailed observations of this mysterious region, hopefully unlocking secrets that are still hidden from us. It would be easy to think of the halo as a quiet container, passively surrounding the Milky Way. But the truth is far more dramatic. The halo is alive with energy and violence. Rising high above and below the galactic centre are two colossal structures called the Fermi bubbles. These bubbles are not small, they stretch for tens of thousands of light years, dwarfing our entire solar system many times over. They are made of searing gamma-ray radiation, the most energetic form of light in the universe. Their discovery shocked astronomers who realised that such enormous features must have been created by incredibly powerful events. The leading idea is that these bubbles were blown into existence by the central black hole of the Milky Way. This black hole, a monster with a mass of millions of suns, occasionally erupts in violent outbursts. Long ago, it may have swallowed a massive cloud of gas or even a small galaxy, releasing titanic blasts of energy that carve these two glowing lobes into the halo. The Fermi bubbles prove that the halo is not static. It can be disturbed, reshaped, and stirred up by forces that lie deep within the galaxy's heart. And we, on our small planet Earth, are not separate from this story. Our solar system floats within the galactic halo. The Sun and its planets orbit the Milky Way's centre at a distance of about 26,000 light-years. But this orbit is not a flat path. Instead, the solar system bobs gently up and down through the galactic plane, like a ship riding the swells of a cosmic ocean. One complete up and down cycle takes between 30 and 35 million years. Over such long spans of time, our solar system passes through different layers of the halo, sometimes through denser regions, sometimes through thinner ones. Some scientists have wondered if these passages might influence events on Earth. Could the solar system's journey through the halo affect the flow of comets, sending more of them toward the inner solar system? Could it even play a role in long-term climate shifts or mass extinctions? These ideas remain uncertain, but they remind us that the halo is not just a distant abstraction. It may be quietly influencing the story of life on Earth itself. The galactic halo is, in many ways, the memory of the Milky Way. Its wandering stars and ancient clusters carry records of cosmic collisions that built the galaxy from fragments. Its vast store of dark matter provides the hidden weight that keeps the spiral arms spinning in their graceful dance. Its scorching circumgalactic medium surrounds the Milky Way in a fiery shroud, while its Fermi bubbles testify to the eruptions of a restless central black hole. And all the while, it cradles our solar system within its boundaries, binding us into the galaxy's family with a grip that is invisible yet undeniable. Far from being an empty nothingness, the halo is a living archive of cosmic history, a guardian of the galaxy's shape, and a reminder that even the emptiest-looking corners of the universe are filled with secrets. It is everywhere around us, silent but powerful, patiently waiting for us to uncover more of its mysteries. When people usually think about what lies above the universe, the imagination tends to stay fairly close to home. We often picture the restless streams of solar wind endlessly blowing outward from the sun, or the occasional lonely planet wandering through space without a star to call home. Others may think of the faint and delicate mist of cosmic dust, the powder of stars past, gently floating in the darkness. These are all familiar and local things, still part of the space that feels like our neighbourhood. But if we step back, far, far back, and try to look at the universe not from the scale of planets or stars, but from the scale of the grandest structures ever discovered, then the meaning of the word above changes completely. Above does not simply mean the sky over our heads. It begins to mean something unimaginably vast. Entire oceans of galaxies, enormous rivers of matter, and invisible currents of gravity that shape the universe itself. Our solar system is only a tiny speck inside the Milky Way galaxy, a vast spiral of stars. But the Milky Way itself is not the end of the story. Our galaxy, along with countless others, belongs to something so enormous, so overwhelming in size, that it dwarfs everything we can see with the naked eye. Astronomers call this giant realm the Laniakea supercluster. Its name comes from the Hawaiian language and means immense heaven, and the name could not be more fitting. Laniakea is not just a random scattering of galaxies floating in all directions. It is a true structure of the cosmos, a kind of cosmic basin where the invisible pull of gravity has gathered matter together. To imagine it, picture rivers on Earth flowing across landscapes. Water never flows randomly. It follows the curves of valleys and mountains, always finding its way toward the sea. In the same way, galaxies in Laniakea flow along invisible paths shaped by gravity, slowly but steadily drifting toward deeper regions of attraction. This supercluster is staggering in size. It stretches across more than 500 million light-years. To grasp what that means, remember that light travels faster than anything else in the universe, racing through space at nearly 300,000 kilometers every second. And yet, even at this breathtaking speed, light would need 500 million years just to cross Laniakea from one side to the other. Within this span lie thousands upon thousands of galaxies, including our own Milky Way, all caught in a shared journey, like leaves drifting on the same vast current. At the very heart of Laniakea lies something even more mysterious, a hidden gravitational giant called the Great Attractor. We cannot see it directly. It does not shine with stars, yet its influence is undeniable. It acts like a cosmic whirlpool, pulling galaxies inward, bending their paths toward itself. The Milky Way, our neighbouring Andromeda galaxy, and hundreds of other galaxies in the Virgo cluster are all being slowly drawn toward this unseen source of gravity. They are like small streams feeding into the greater river of Laniakea. The recognition of Laniakea in the year 2014 marked a turning point in astronomy. Before this discovery, astronomers described superclusters mostly by their appearance, outlining them as shapes of light on star maps. But Laniakea was not revealed by its glow. It was uncovered through something far deeper. The study of peculiar velocities, the small motions of galaxies beyond the general expansion of the universe. By measuring how galaxies drifted relative to each other, scientists noticed a pattern. They found that many galaxies which once seemed separate were actually connected, threads of motion weaving together into one vast gravitational flow. In this way, the outline of Laniakea emerged not drawn by light, but traced by the invisible hand of gravity itself. From our position inside the Milky Way, much of Laniakea's mass appears to lie above the plane of our galaxy, stretching northward into the sky. It reaches toward constellations such as Virgo, Centaurus, and Hydra. When we look upward into those directions, we're not just gazing at scattered stars. We're peering into the densest regions of our greater cosmic home. Astronomers have long noticed that the northern half of the sky reveals a more complex and richer cosmic web than the southern half. Many of the largest rivers of galaxies flow northward, carrying with them the evidence of this grand gravitational order. This alignment is not only poetic, it is practical. Because so much of Laniakea's density lies above, many of the world's greatest observatories point their instruments toward those skies. Projects like the Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and the Cosmic Flows Project focus heavily on the northern hemisphere. In contrast, the southern skies are often harder to study, clouded by the thick band of our own galaxy's stars and dust. Fortunately, astronomers have found windows such as the Northern Galactic Cap, where the view opens more clearly. Through these cosmic windows, telescopes peer past the Milky Way into the emptier stretches beyond, where the grand architecture of galaxies and voids can be traced. Within Laniakea, astronomers have mapped vast cosmic filaments, long, thread-like structures where galaxies gather like beads on a string. These filaments act as highways of matter, guiding galaxies toward major hubs of gravity. Some of these hubs include the Great Attractor itself, as well as the enormous Shapley supercluster, which also lies inside Laniakea's domain. Our own Milky Way is moving along one of these filaments, steadily climbing upward into the northern reaches of the supercluster. It is as if our galaxy is scaling the backbone of this immense structure. Evidence of this motion even comes from the oldest light in the universe, the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light has a subtle temperature difference across the sky, a feature called the dipole anisotropy. That difference reveals that the solar system itself is moving upward, drawn toward the enormous mass at the center of Laniakea. This shows that our journey is not a mere drawing on a star chart. It is a real and measurable voyage. Yet, as vast as our understanding has grown, we are still only beginning to grasp the full nature of Laniakea. Ordinary telescopes cannot capture its boundaries because its structure is not defined by light, but by the invisible influence of gravity. Mapping it requires not only powerful instruments, but also sophisticated models and computer simulations. In the coming years, ambitious new projects such as the Euclid mission, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope will carry this work forward. They will reveal how groups of galaxies interact with mysterious dark matter, and how these immense gravitational rivers have changed and evolved across billions of years. But perhaps the deepest lesson of all is this: Laniakea reminds us that we are part of something unimaginably greater. The Milky Way is not drifting aimlessly through space, nor is our solar system wandering without direction. We are being pulled, guided along invisible highways carved by gravity itself. We are travelling upward and inward toward a destination we cannot yet fully see or understand. Above the universe lies more than just scattered stars and drifting dust. Above us stretches the grand current of the immense heaven, a journey of galaxies upon galaxies, all flowing together into the unknown. It is a reminder that our home is not only Earth, not only the solar system, not only even the Milky Way. Our true home is this vast and mighty structure of the cosmos, and we are all passengers on its endless voyage. When we look at the universe, we imagine the familiar family of planets circling the Sun, Mercury glowing closest, Venus wrapped in thick clouds, Earth with its blue oceans, Mars rust-red and dry, and then the mighty gas giants with their swirling storms and icy moons. Beyond them lies the dwarf planet Pluto, drifting in the darkness of the Kuiper Belt. For many, Pluto once marked the very edge of our Sun's kingdom, but in truth, that was never the end. Far beyond the Kuiper Belt, past the scattered disk where icy fragments wander like cosmic exiles, lies one of the most mysterious and distant structures ever imagined, the Oort cloud. Imagine a giant, ghostly sphere, made not of light or gas, but of frozen bodies, comets, icy rocks, and debris left behind from the dawn of the solar system. This shell, sometimes compared to a bubble or a cage of ice, is thought to surround the Sun on all sides, marking the very edge of its gravitational influence. The Oort cloud is ancient, older than human history, older even than the Earth itself, for it was formed when the solar system was still in its infancy, billions of years ago. Inside it are believed to rest trillions upon trillions of frozen wanderers, each a relic of creation, waiting silently in the cold dark until some disturbance hurls them inward toward the Sun. But there is a question rarely asked: what lies beneath it? The Oort cloud is usually imagined as a vast, symmetrical sphere. But what about its underside, its southern half that dips below the solar system's main plane of planets, stretching into the far reaches of southern space? Could it be different from the top half we usually picture in our minds? Could the bottom hold secrets untouched for billions of years, or perhaps even relics from other stars entirely? To grasp the sheer size of the Oort cloud, we must use a special unit of distance known as the astronomical unit, or AU. 1 AU is the average distance between the Earth and the Sun, about 150 million kilometres. For everyday scales, that is already an unimaginably vast gap. Yet the Oort cloud begins not at 1 AU, or even at 100 AU, but at around 2000 AU from the Sun, and may extend as far as 100,000 AU. Let us put that into perspective. Pluto orbits the Sun at about 40 AU. Humanity's most distant spacecraft, Voyager 1, has been travelling outward since the year 1977 and has already passed beyond the edge of the heliosphere, the Sun's protective bubble. Even so, Voyager 1 is only around 160 AU from home. That means it has not even scratched the surface of the Oort cloud. To Voyager, the cloud still lies like an unreachable horizon. The scale is so immense that if the Sun and its planets were shrunk down to the size of a coin sitting in your palm, the Oort cloud would stretch outward across an entire city. It is a frontier not only of distance but also of imagination. No telescope has ever seen the Oort cloud directly. It is too faint, too spread out, and too far away. Its icy fragments are small and reflect little sunlight. For us, the Oort cloud is an invisible structure, yet we know it exists. Its presence is betrayed by comets, icy messengers that come screaming into the inner solar system on highly stretched orbits. Unlike short-period comets that return every few years, these long-period comets come from random directions, some tilted at sharp angles, others even moving backward compared to the orderly paths of the planets. Such wild trajectories can only be explained if they originated in a faraway spherical reservoir, the Oort cloud. Some comets even appear to come from the underside, the southern half of this icy sphere. Famous examples include Comet Hale-Bopp in the year 1995 and Comet C 2017 K2 Pan-STARRS. Both entered the solar system on sharply slanted paths, almost as if they were tumbling down from below. These comets, like postcards from the deep, offer indirect proof that the Oort cloud is not a flat disk, but a true three-dimensional sphere wrapping all around the Sun. This symmetry brings us to a new puzzle. Is the Oort cloud truly the same everywhere, or is its bottom half, the underside, different? Some scientists believe the southern regions may indeed have unique features. One reason lies in the position of our solar system within the Milky Way. The Sun does not sit perfectly centred in the galaxy's flat disk. Instead, it hovers slightly above it. Because of this, the lower part of the Oort cloud may feel the pull of the galaxy's gravity differently. Over billions of years, such an uneven tug could stretch or compress the southern hemisphere in ways not mirrored in the north. If so, more comets might drift inward from the underside than from the top, making the southern Oort cloud a livelier, more restless region. The Oort cloud does not float undisturbed. As the Sun journeys around the centre of the Milky Way, taking more than 200 million years for a single orbit, it encounters other stars. Some pass close enough to disturb the Oort cloud with their gravity, stirring up its icy residents and sending them cascading toward the inner solar system. About 70,000 years ago, a faint red dwarf called Schultz's star drifted within less than a single light-year of the Sun. Though faint and barely noticeable in our skies, its proximity was enough to tug at the Oort cloud, likely shaking loose comets, perhaps especially from its southern half. In the future, around 1,300,000 years from now, another star, Gliese 710, will come alarmingly close, within only about 0.06 light-years. Such a flyby will almost certainly scatter countless comets inward. Many of these may emerge from the underside of the Oort cloud, raining down like icy arrows from the southern skies. But stars are not the only cosmic players. Some scientists speculate that the Oort cloud may also be shaped by something far more mysterious: dark matter. Dark matter is an unseen substance that makes up most of the mass of the universe. It does not shine, it does not absorb light, and it cannot be touched. Yet its gravity is real, sculpting galaxies and holding them together. Some models suggest that dense clumps of dark matter may occasionally pass through the outskirts of the solar system, especially from less observed directions such as the underside. These encounters could jostle the Oort cloud and send comets tumbling inward in waves. If such showers were large enough, they might even cause extinction events on Earth, just as asteroids and comets have done in the past. Though speculative, this idea adds an eerie layer of danger to the Oort cloud's underside, an unseen realm possibly linked to the great cycles of life and death on our planet. Another fascinating theory suggests that the underside of the Oort cloud may contain not just native solar system objects, but also outsiders, icy travellers from other stars. Billions of years ago, when the solar system was young and chaotic, countless small planetesimals were thrown outward by the giant planets. Some escaped entirely, while others became trapped in the Oort cloud. During this same era, the Sun was part of a dense star cluster, crowded with other newborn stars. It is thought that some of their icy debris may have drifted close enough to be captured by the Sun's gravity. If so, the Oort cloud, especially its southern regions, might be sprinkled with alien comets, frozen fossils from stars long gone. These alien comets would be chemically different, carrying isotopes, minerals, and volatile elements unlike those found in comets formed near our Sun. Each one would be a messenger not just from the solar system's edge, but from entirely different stellar nurseries. If we could one day study them, we would be holding pieces of other stars in our hands. The greatest challenge is distance. No spacecraft has ever gone anywhere near the Oort cloud. No telescope has glimpsed it. How then can we know its underside at all? The answer lies in comets themselves. Every comet that plunges into the solar system is like a note from the edge of creation. By charting their paths, astronomers can trace back where they came from. Comets that fall from steep southern angles are clues about the underside. By analysing their chemical fingerprints, scientists can compare whether southern comets are different from northern ones. New instruments will greatly enhance this detective work. The Vera C. Rubin Observatory, expected to begin its survey soon, will discover thousands of new long-period comets in the coming decades. Many of these will emerge from the southern skies carrying whispers from the underside of the Oort cloud. Each discovery will bring us closer to answering whether the bottom truly differs from the top. Someday, we may go there ourselves. NASA has discussed concepts for an interstellar probe, a spacecraft that could travel thousands of astronomical units outward, far beyond the planets. If launched, it could eventually skim the inner edges of the Oort cloud. Such a mission would be able to measure dust grains, magnetic fields, and the composition of particles drifting through space, offering the first direct evidence about the cloud's nature. By comparing data from above and below, we could finally discover whether the underside of the Oort cloud hides differences invisible from afar. This would be a journey into the oldest frontier of the solar system, a place untouched for billions of years, a place where the sun's power fades and the galaxy's forces begin. The underside of the Oort cloud is more than just a region of space. It is a frontier where our understanding falters, where speculation and science dance together. It may hold comets that carry the fingerprints of alien stars. It may be stirred by passing suns and sculpted by invisible dark matter. It may be lopsided, restless, and alive with comets waiting to fall. For now, it is silent, hidden in darkness. But with every new comet, with every future mission, we inch closer to hearing its story. The Oort cloud's underside is not just the bottom of a sphere. It is a doorway to the unknown, the edge of the sun's dominion, and perhaps the key to understanding the deepest cycles of our solar system and our galaxy. Deep beneath the smooth circular path that our solar system follows around the Milky Way lies something immense, ancient, and impossible to ignore: the galactic core. This is the very heart of our galaxy, the gravitational anchor that holds everything together. It is not an empty place, nor is it quiet. Instead, it is a restless, crowded, glowing, and often violent region where countless stars burn, where magnetic fields twist and tangle like invisible ropes, and where, at the very centre, there lurks a giant black hole known as Sagittarius A star. Our solar system is not sitting still inside the Milky Way. Like a tiny speck caught in a whirlpool, it moves along with the rest of the galactic disk, circling the centre in a broad, nearly flat orbit. One complete trip around the galaxy takes an unimaginably long time. about 225 million years. That means the last time we were in the same place in our orbit, the dinosaurs were walking the Earth, but our solar system's journey is not perfectly smooth or level. Gravity never allows such perfection. Instead, the solar system bobs gently up and down as it travels, the way a ship rises and falls with the swell of an ocean. Astronomers have learned that this vertical oscillation happens on a cycle of roughly 30 to 35 million years. Every so often, we cross the thin midplane of the Milky Way, rise high above it, and then sink back down again, pushed and pulled by the combined tug of stars, gas clouds, and even the mysterious invisible substance we call dark matter. At this very moment, our solar system sits about 25 to 30 light years above the galactic midplane. We are slowly drifting downward, ever so gently, in a movement so subtle that no human being could ever feel it in a single lifetime. And yet this vertical motion is not meaningless. It plays a crucial role in how material circulates through the galaxy. Gas, dust, even entire star systems can migrate above and below the disk, slowly funneling toward the centre in ways that astronomers are only beginning to understand. Imagine, for a moment, that you could release an object from our solar system's current position and simply let it fall downward toward the centre of the galaxy. At first, it would cut through the galactic disk itself, the broad, flat region where most of the stars, glowing nebulae and rivers of dust reside. This is the Milky Way as we see it stretched across the night sky, a dazzling band filled with so many suns that their light blends into a misty glow. As the falling object continues deeper, the pull of gravity grows ever stronger. The closer it moves towards Sagittarius A star, the more the invisible hand of gravity tightens its grip. Our Sun itself lies about 26,000 light-years away from the galactic centre, so the object would have an astonishingly long way to fall. Each passing light-year would increase its speed. Space-time itself, the very fabric of reality, bends inward, steepening the descent as though the object were sliding down a vast invisible funnel. This imagined plunge would never be a simple straight drop. The Milky Way is not a still pond, it spins, and like a whirlpool, its inner regions rotate faster than the outer edges. Anything falling inward from above or below would be swept into that spin. Instead of racing directly toward the centre, the object would spiral, caught in the swirling motion of the galaxy's arms. Its path would carry it through regions far denser than anything near Earth, areas where stars are packed so closely together that the night sky would blaze like a jewel box. The spiral descent would carry it through the galactic bulge, a thick rounded cloud of ancient stars that shines reddish with age. Here, star density can be hundreds of times greater than in our quiet neighbourhood near the Sun. Along the way, the object would pass vast molecular clouds, cold and dark, where new stars are quietly gestating. It would weave through magnetic filaments, invisible but powerful, and encounter the violent chaos of the central molecular zone, where star birth and star death occur side by side in an ongoing cycle of creation and destruction. One particularly fascinating aspect of imagining a fall from beneath the galactic disk is that the southern half of our galaxy, the sky below the disk, has long been less studied than the northern half. For centuries, most of the world's great observatories were built in the northern hemisphere, which meant astronomers had a clearer view of the stars above the disk than those below it. That imbalance is changing. New instruments in the southern hemisphere, such as the Vista telescope in Chile, have begun mapping the hidden southern skies. Soon, the powerful Vera C. Rubin Observatory will join them, giving us breathtakingly detailed views of regions we have only glimpsed until now. For the first time in human history, we will be able to study the southern route of this imagined fall toward the galactic centre with the same precision as the north. As the object descends further, it would pass through increasingly exotic environments. Matter and radiation become denser. Magnetic fields twist tighter and knot into chaotic patterns. Neutron stars, the collapsed remnants of massive suns, lurk like embers of cosmic violence. Stellar collisions occur, and smaller black holes roam unseen, each a trap hidden in the dark. And finally, at the centre of it all sits Sagittarius A star, a supermassive black hole with a mass equal to about 4,300,000 suns. Nearly motionless, it anchors the galaxy with its immense gravity, shaping the paths of stars even tens of thousands of light years away. To approach it is to enter a realm where light itself bends, where time slows, and where space takes on unfamiliar shapes. Although Sagittarius A star is relatively quiet now, scars in the sky suggest it was not always so calm. Astronomers have discovered evidence that a few million years ago, it erupted in vast outbursts, blasting jets of energy far into space. The remnants of those outbursts still remain today as two enormous bubble-shaped structures, the Fermi bubbles, that stretch high above and below the galactic plane. They are silent witnesses to the black hole's once fiery past. Close to the black hole lies the innermost stable circular orbit, a kind of invisible edge. Any object spiraling inward that crosses this line can no longer resist. It cannot hold a safe orbit. It falls. Yet in truth, most objects never survive that long. Long before reaching this boundary, they are shredded by tidal forces, roasted by radiation, or torn apart by magnetic storms. This grand thought experiment is not just poetic fancy. Astronomers take the idea of falling toward the galactic centre very seriously. The vertical motions of stars and gas, their rising and sinking above and below the galactic disk, are key to understanding how the Milky Way evolves over billions of years. These motions explain how stars drift to new neighbourhoods, how gas clouds spread out or collapse, and how, over time, matter is funneled toward the black hole at the centre. When enough material builds up near Sagittarius A star, it can trigger new outbursts of energy, colossal events powerful enough to reshape the galaxy itself. In this way, the Milky Way is not a calm, flat pinwheel of stars circling forever in neat paths. It is a living, restless system where matter constantly collides, migrates, and sometimes plunges headlong into the heart of darkness. This same story of rising, falling, and spiralling inward can be seen on a much smaller scale right here in our solar system. Surrounding the planets is a thick cloud of dust that lies mostly along the flat orbital path known as the ecliptic. For a long time, astronomers thought this dust was confined to a single thin layer. But thanks to powerful infrared space telescopes such as IRIS and COBE, we now know that the dust forms multiple layers, some stretching far above and below the main plane. The dust is slowly being pulled inward by the Sun's gravity, but the planets also sculpt its distribution with their own gravitational nudges. On top of that, a subtle effect known as Poynting-Robertson drag makes the dust spiral inward, closer and closer to the Sun, like grains of sand sliding down a whirlpool. Along the way, many of these dust particles cross Earth's path, sometimes from above the orbital plane, sometimes from below. Even more astonishing is that not all of these dust grains were born here. Some are interstellar micrometeoroids, tiny fragments of matter that come from outside our solar system altogether. These wanderers rush in on hyperbolic trajectories, entering the heliosphere from all directions. Measurements from spacecraft such as Ulysses, Galileo, and Cassini show that a significant fraction of this incoming dust comes from the direction of the galactic south, slicing through our system from below the planetary plane. These interstellar grains are unbelievably small and fast, so small that they are almost invisible, yet so quick that they strike with tremendous force. Most are too tiny to punch holes in spacecraft, but over long stretches of time they can cause serious damage. They scratch thermal blankets, blur lenses, and sometimes pierce fragile solar panels. The International Space Station treats this threat with the utmost seriousness. Its modules are wrapped in protective shielding, and its orientation is carefully adjusted to minimize exposure during meteor showers. The smallest fragments of dust may not look like much, but when you are moving at orbital speeds, even a speck can strike like a bullet. To study and predict these impacts, scientists use advanced instruments such as DRAGONs, short for Debris Resistive Acoustic Grid Orbital Navy Sensor. This device can detect dust impacts in real time, helping researchers map the angles and speeds of incoming micrometeoroids. Many of these measurements confirm that a large portion of them do indeed come from the southern sky, striking from beneath Earth's orbital plane. Future missions will face even more extreme challenges. Spacecraft like Solar Orbiter, which already travels outside the main planetary plane, are beginning to sample dust in unusual orbits. More ambitious missions that venture toward the distant Oort cloud, the icy shell at the edge of our solar system, will encounter micrometeoroids unlike any seen near the inner planets. Studying these grains, especially those that fall in from unusual angles, is teaching us that our solar system is not a neat flat pancake of planets circling the Sun. Instead, it is a three-dimensional, constantly shifting stage where dust and debris float, collide, fall inward, and reshape the cosmic environment around us. When most of us think about the universe, our minds usually go straight to the familiar: the round paths of planets circling the Sun, the long looping journeys of comets, and the steady pull of our star that seems to hold everything together. It is a picture of harmony, where orbits follow clear rules, and gravity is the quiet conductor keeping time. But beneath this familiar surface, there may be something far stranger, far more hidden, and far more fascinating. Astronomers and mathematicians are beginning to uncover what could be described as a secret architecture beneath the universe's stage, a delicate network of invisible gravitational corridors. These corridors are not physical tunnels or tubes that one could enter. They cannot be seen with even the most powerful telescope. Instead, they are subtle highways made of gravity itself, sculpted by the combined pull of the Sun, the planets, and even the greater Milky Way galaxy in which we live. They form natural routes through space, lanes where an object can move with very little effort, almost as if it is sliding along an unseen stream. To imagine them, think of a great river winding its way through valleys. The water does not carve the path with brute force in a single moment. It follows the gentle slope of the land, flowing where gravity allows. These cosmic highways are the space equivalent of such riverbeds, shaped not by water, but by the delicate balancing act of gravity. For a long time, scientists have studied similar paths on the flat plane where the planets circle the Sun, a region known as the ecliptic. In this thin slice of space lies something called the Interplanetary Transport Network. This is a system of invisible paths, shaped in part by what are known as Lagrange points. These are special spots where the tug of the Sun and a planet cancel each other out, producing little pockets of balance. In such places, a spacecraft, a comet, or even a drifting rock can hover, orbit gently, or slip into controlled chaotic movement. These points act as gateways, and together they create webs of motion, routes that link planets, moons, and other bodies together. But for centuries, our gaze has mostly been locked on this thin, flat sheet of orbits. What happens if we tilt our perspective? What happens if we stop looking only at the flat plane and instead explore the vertical dimension, the space above and beneath the solar system's disk? In recent years, mathematicians and astronomers have done just that. They have turned to a famous idea in celestial mechanics known as the restricted three-body problem. This problem explores how three objects, a star like the Sun, a planet such as Jupiter, and a much smaller traveller like an asteroid or a spacecraft, interact with each other's gravity. From this, it becomes clear that gravity is not a simple flat surface. Instead, it folds, curves, and dips in 3 dimensions. Imagine a great invisible landscape made not of soil and stone, but of gravitational energy, filled with valleys, ridges, and mountain passes. These curves open up secret routes not only across the flat planetary plane, but also far above it and deep below it. In these underexplored regions, gravity creates valleys that function like downhill slopes. Just as rivers guide water downward, these valleys may act as energy-saving lanes that guide objects with minimal force. A spacecraft that slips into one of these lanes could travel extraordinary distances while consuming only a small amount of fuel. Nature itself provides the push. This is not mere theory. In fact, space missions in our own time have already begun to take advantage of these hidden lanes. NASA's Lucy mission, designed to visit Jupiter's Trojan asteroids, and the European Space Agency's ambitious mission called JUICE, which is aimed at Jupiter's icy moons, both use gravitational highways to travel more efficiently. Instead of relying solely on engines and fuel, they surf along the natural contours of space. Yet the most intriguing idea of all is that these invisible corridors may also run deep beneath the Sun, in regions less disturbed by the pull of large planets. Such hidden routes could act like funnels, channeling asteroids, comets, and perhaps even fragments of interstellar material toward the centre of our solar system. Imagine an icy body nudged from the faraway Oort cloud at the edge of the Sun's influence. Instead of tumbling randomly, it might quietly slide inward along one of these invisible lanes, guided not by forceful tugging but by gentle encouragement, much like a leaf gliding along a calm stream. At the very centre of this grand system is of course the Sun. Its immense weight bends space itself, curving the very fabric of reality. And when the Sun's influence joins with the pull of the galactic mid-plane, the dense flat sheet of stars, gas and dust that makes up the middle of our Milky Way, an even grander design comes into view. The two together shape gradients and slopes that open low-energy routes in all directions, upward and downward, inward and outward. Picture, for instance, a spaceship placed beneath the Sun, aligned with one of these gravitational lanes. In theory, it could be nudged outward, riding along a natural escape path. With very little fuel, it could let gravity itself fling it from the solar system, sending it sailing into the southern sky and out toward the countless galaxies beyond. These hidden corridors may not only be tools for the future, they may also be the reason we're here at all. Billions of years ago, when the solar system was young and still forming, icy bodies and planetesimals scattered from the outer disk may have rained downward through these gravitational lanes. Over immense stretches of time, this slow but steady delivery of material may have shaped the inner planets, bringing water, ice, and essential minerals. The fact that some worlds have unusual tilts, or slightly uneven mixtures of elements, might even be the fingerprints of this ancient vertical infall, where southern streams of debris shape the very face of our planetary family. But these corridors are not always smooth highways. Sometimes they act as traps. Small pieces of rock, drifting dust, or even artificial fragments from human spacecraft can find themselves caught in these pathways, circling the Sun in unusual, temporary orbits. This may be the reason why astronomers occasionally find strange groups of rocks moving together or clouds of dust hovering in tilted, hard-to-detect tracks. Some of these trapped wanderers may be incredibly ancient, left suspended for billions of years, quietly held in place by the patient and invisible hand of gravity. Understanding this hidden architecture of motion is not just a matter of curiosity. It may be vital for humanity's future in space. Missions to the Kuiper Belt, journeys toward interstellar space, or even strategies to deflect dangerous asteroids away from Earth may all depend on our ability to map and use these gravitational lanes. Instead of burning vast amounts of fuel, we might one day learn to glide across the solar system as naturally as a bird riding a current of air. And if we can imagine this, perhaps others have too. If intelligent civilizations exist elsewhere among the stars, they might have long ago discovered and mastered these gravitational highways. Instead of building enormous engines, they may travel quietly along the hidden seams of gravity, slipping between star systems like sailors following invisible trade winds. Perhaps the universe is already threaded with such ancient routes, unseen by most, yet waiting patiently for us to recognize them. These hidden pathways, sculpted by the slow and silent work of gravity, remind us of something profound. Space is not empty. It is structured, patterned, and alive with subtle possibilities. And as we learn to see these invisible rivers for what they are, we may also learn how to follow them, whether to understand our origins, to protect our world, or to set sail toward the stars. Far beneath the familiar plane of our solar system's path through the Milky Way, there is a hidden world of space that is stranger and quieter than most people imagine. At first glance, one might think that the great void between the stars is simply empty. But in truth it is not. Even in the loneliest regions of interstellar space, there lingers a faint fog of gas and dust. This thin veil is what our solar system is currently travelling through, and astronomers call it the local interstellar cloud, often shortened to LIC. The local interstellar cloud is not a thick or heavy cloud like those we see in the sky on Earth. Instead, it is a delicate blend of partly charged hydrogen and helium atoms, so thin that it would be invisible to our eyes even if we floated right in the middle of it. This cloud stretches for about 30 light-years across space, impossibly vast to us, yet small when compared to the enormous scale of our galaxy. The LIC itself is only a fragment of a much larger structure known as the local bubble, a gigantic cavity in the interstellar medium. The local bubble is a region carved out long ago by violent stellar explosions, and within its emptiness drifts just a few fragile wisps of material. Among them, our modest LIC. But the story becomes even more fascinating when we look downward, toward the southern direction of our galaxy. beneath the thin plane of the local interstellar cloud. There, astronomers have discovered an even stranger environment, a region that is thinner, emptier, and less crowded with matter than the LIC itself. This underbelly of space is what scientists sometimes call the intercloud medium. Imagine the galaxy as a patchwork quilt. Some parts of the quilt are thick with fabric. These represent the dense clouds of gas and dust, where new stars and planets may eventually form. Between those thicker patches, however, are the seams, the spaces in between. These seams are not completely empty, but they are astonishingly sparse compared to the clouds around them. That is what lies beneath our current path, a vast stretch of extremely low-density interstellar material. To understand how different these places are, consider their densities. The local interstellar cloud has a density of about 0.3 atoms per cubic centimetre. That already sounds almost like nothing, but in cosmic terms it is still noticeable. By comparison, the spaces below the LIC can drop to around 0.05 atoms per cubic centimetre, or even less, so empty that it is closer to a vacuum than almost anywhere else nearby. These differences may sound trivial, but they are not. They shape the very edge of our solar system's protective bubble, the heliosphere. The heliosphere is created by the solar wind, the constant stream of charged particles that flows outward from our Sun. Where this solar wind finally meets the interstellar medium, its push is balanced by the pressure of the surrounding gas, forming a great invisible boundary called the heliopause. Now here is the remarkable part. If our solar system drifts into a region of lower density, the heliosphere can swell outward and expand because there is less outside pressure holding it back. If, instead, we wander into a denser region, the heliosphere is squeezed inward. That means the size and shape of the bubble protecting Earth and the other planets is not fixed. It breathes with the galaxy, expanding and contracting as we cross into different environments. Many models suggest that right now, we're nearing the very edge of the local interstellar cloud. If that is true, then in the not-so-distant future we may slip into one of those thinner, emptier regions beneath it. If this happens, the heliosphere will expand, and more cosmic rays, those high-energy particles launched from distant stars and galaxies, will be able to reach deeper into our solar system. The effect might be subtle, but it is real. More cosmic rays could mean stronger interference with satellites and spacecraft electronics, as well as increased health risks for astronauts on long missions beyond Earth. But how do we even know what lies below, when the matter is so thin that it is almost undetectable? The answer comes from light, specifically ultraviolet light from nearby stars. When this light travels through interstellar space, some of it is absorbed by the gas it encounters along the way. By carefully studying these faint absorption lines, astronomers can piece together a map of where the gas is thicker, where it is thinner, and where the clouds end. Instruments like the Hubble Space Telescope and the Far Ultraviolet Spectroscopic Explorer, FUSE, have been essential in this detective work. By studying stars south of the galactic plane, such as Alpha Centauri and Altair, astronomers can trace where the local interstellar cloud fades away into emptier territory. These stars act like beacons, their light carrying hidden clues about what lies between us and them. The origin of these empty stretches is dramatic. Millions of years ago, massive stars ended their lives in fiery explosions called supernovae. Each blast ripped through the interstellar medium, carving out cavities of thin, hot gas. Over time, several such explosions, likely occurring within the last 10 to 20 million years, merged to form the local bubble, a vast hollow about 300 light-years wide. Within this giant bubble floats only one small cloud, the local interstellar cloud itself, and beneath it lies a patch of space even emptier, a cosmic ghost town. This region is not filled with familiar molecules or heavy clusters of dust. Instead, it is occupied mostly by thin, hot plasma, atoms stripped of their electrons, glowing faintly as they drift in silence between the stars. If future missions, such as the proposed interstellar probe or any successor to the legendary Voyager spacecraft, venture south of the heliosphere, this empty region is what they will encounter first. Those missions would give humanity its very first direct measurements of the intercloud medium, the hidden underbelly of our galactic neighbourhood. Though it seems barren, this low-density environment is rich in scientific value. Its emptiness allows certain things to happen that would be impossible in denser regions. For instance, radio waves and other long-range signals can travel much farther and more clearly through such thin plasma, since there are fewer particles to scatter or absorb them. Some scientists have even suggested that if advanced civilizations exist elsewhere in the galaxy, they might take advantage of these cosmic corridors to send messages across light years. A listening station placed in such a clear zone would be able to hear faint signals from extraordinary distances, like a radio tower on a high mountain peak catching voices carried by the wind. So what lies beneath the local interstellar cloud is not chaos or crowding, but silence. It is the quiet pause between bursts of galactic activity, the thin calmness carved by ancient supernovae and preserved by time. In this southerly direction, our solar system is gliding toward the emptiest neighbourhood it has ever known. Paradoxically, this emptiness may tell us more about our galaxy than the clouds themselves. It is the blank page on which the story of stars is written, the space between the lines of the Milky Way's great poem, and as our journey continues, this silent stretch may reveal secrets we never expected, not by being full, but by being nearly empty. High above the glowing plain of our Milky Way, and far below its crowded heart, rise two of the strangest and most breathtaking structures ever found in the galaxy. They are called the Fermi bubbles, two gigantic towers of invisible light that span across tens of thousands of light years. They shine with a force so intense that it slices across the galaxy like deep scars in the heavens. Astronomers first discovered these bubbles in the year 2010, when NASA's Fermi Gamma Ray Space Telescope spotted their ghostly glow. From that moment on, they became one of the greatest mysteries in modern astronomy. Two colossal beacons hanging over the galaxy, daring scientists to figure out how they were made. Each bubble rises about 25,000 light-years above and below the thin, starry disk of the Milky Way. To give a sense of scale, that is about the same distance between our Earth and the very core of the galaxy itself. Perfectly balanced on either side of the galactic plane, they look as though some immense cosmic sculptor had carved them with a blade of energy. And what fills them is even more astonishing: gamma rays, the brightest and most energetic kind of light in the universe. Gamma rays are not gentle or harmless like the warm glow of infrared or the penetrating but familiar rays used in X-ray machines. They are born only in the most violent and extreme events in the cosmos: black holes swallowing matter, stars exploding in titanic supernova, and particles slamming into one another at nearly the speed of light. That is the raw energy that floods the Fermi bubbles. But the wonder of these bubbles does not stop at their size or brightness. What truly makes them remarkable is how sharply defined they are. They do not fade softly into the background haze of the galaxy. Instead, they look like glowing towers that pierce straight into the galactic halo, the vast, ghostly sphere of stars, dark matter, and thin gas that wraps around the Milky Way. Inside the bubbles, astronomers have found blazing plasma heated to extreme temperatures, streams of high-energy particles moving at staggering speeds, and magnetic fields twisted into strange patterns. Even more astonishing, the bubbles may be expanding outward at nearly 1,000 kilometers every second. To compare, that is many times faster than anything we can create on Earth, and it means that in the span of a single heartbeat, the bubbles push outward by hundreds of kilometers. And yet, when scientists looked for the cause, they found no nearby supernova explosion and no region of star formation strong enough to have created them. This puzzle forced astronomers to think bigger, to consider an even more dramatic origin. The most convincing explanation points to the supermassive black hole at the very center of our galaxy, known as Sagittarius A star. Today, this black hole is quiet, lurking silently at the core of the Milky Way. But millions of years ago, it may have lived through a violent outburst, devouring great clouds of gas and spitting out enormous jets of particles. These jets, blasting upward and downward from the galactic center, could have carved their way into the thin halo above and below the galaxy, heating the gas and filling the sky with gamma rays. What we see today may be the fading echo of that ancient eruption. There is, however, another intriguing possibility. Perhaps it was not the black hole at all, but rather a starburst event, a time when stars were born in a furious rush near the galactic center. Such star-forming frenzies can drive out titanic winds of gas and radiation, shoving matter outward with enough force to carve bubbles into the galaxy. In this view, The Fermi bubbles are monuments not to a black hole's rage, but to a storm of countless newborn stars. Whichever story is true, the result is the same. Two enormous lobes of energy, still glowing after millions of years, standing as silent reminders of a long-forgotten catastrophe in the heart of the Milky Way. The bubbles are also not simple in their structure. Within them, astronomers have detected layers of energy that shine in X-rays, first spotted by space observatories like Rosat and eRosita. Along their sharp edges are boundaries that look like pressure fronts, cosmic shock waves, showing how the bubbles press against the thin halo gas, squeeze it, and change its temperature. In some places, the Fermi bubbles overlap with other vast features, such as the North Galactic Spur, revealing that the true sky is far more tangled and complex than it first appears. Even more fascinating, the bubbles may not be stable. Some studies suggest that they are shifting and changing, swelling outward, or fading depending on how the pressure inside them fights against the gas outside. Their perfectly symmetrical shape, however, points like an arrow back to the galaxy's core, leaving little doubt that the energy that birthed them came from deep within. Astronomers now wonder if our Milky Way is unique in this respect. If we have Fermi bubbles, might other galaxies have them too? Observations of galaxies such as Centaurus A reveal giant lobes of radio energy that look remarkably similar to the Fermi bubbles, hinting that such enormous outbursts may be a natural stage in the lives of spiral galaxies everywhere in the cosmos. From Earth, we cannot see the Fermi bubbles with our eyes. They remain invisible to ordinary vision, hidden from the gaze of stargazers, but through the eyes of gamma-ray telescopes they appear clearly, covering an immense stretch of the night sky. If human eyes could somehow see gamma rays, the familiar constellations would vanish, drowned out by the overwhelming sight. Instead, when we looked up at night, we would see two towering pillars of energy glowing above and below the Milky Way's shining band. They would stand like ancient monuments in the heavens, reminders of a titanic event that shook the very heart of our galaxy long ago. Far beneath the familiar flat plane on which our solar system rests, beyond the quiet drifting of comets and the faint haze of cosmic dust, lies something far stranger. It is not a wandering object or a random cloud of particles. Instead, it is something woven into the very fabric of the universe itself, a kind of scar, an icy wound imprinted on the oldest light we have ever seen. This strange scar appears in what astronomers call the cosmic microwave background radiation, or CMB for short. The CMB is a dim and ancient glow that fills the entire sky, the afterglow of the Big Bang, the great explosion that gave birth to space and time nearly 14 billion years ago. If you look at the universe in ordinary visible light, you will see stars, galaxies, and nebulae scattered about. But if you could tune your eyes to microwaves, you would see this faint, nearly uniform glow everywhere, as if the whole sky were painted with the same dull colour. But uniform does not mean perfect. Hidden within this ancient glow are tiny variations, slight warm patches and cool patches, differences of only millionths of a degree. These tiny ripples are actually very important. They are the seeds from which all galaxies, stars, and planets eventually grew. Yet among all these subtle shifts in temperature, one region stands out as particularly bizarre. A vast cold patch that lies well below the galactic midplane, pointing toward the southern sky. Astronomers have named it the CMB cold spot. It rests in the constellation called Eridanus, a winding river of stars in the southern heavens, located far below the Sun's ecliptic path and even deeper beneath the flat disk of the Milky Way's galactic plane. This cold spot is not small. It spans nearly 5 degrees across the sky. To put that in perspective, that is about 10 times the width of the full moon as seen from Earth, a huge slice when compared to the entire CMB map. What makes it so striking is its temperature. This patch is about 70 microkelvin colder than the surrounding average. Now, by earthly standards, this difference does not sound like much. It would not even freeze a glass of water. But in the precise science of cosmology, where researchers measure tiny differences in ancient light, such a drop is like a chill wind cutting through the universe itself. It is a signal so unusual that it sends scientists into excitement and confusion in equal measure. The first hints of this cold patch came in the year 2004. when NASA's Wilkinson Microwave Anisotropy Probe, WMAP, revealed a detailed map of the CMB. Later, in the year 2013, the European Space Agency's Planck satellite confirmed the anomaly with even sharper precision. Both missions were designed to measure the faint glow of the early universe with extraordinary accuracy, and both showed the same thing. This patch of sky was too cold, too large, and too unlikely to be dismissed as mere random noise. Normally, small fluctuations in the CMB are expected. In fact, without them, galaxies and stars could never have formed. But the cold spot is a giant among these ripples, a deep hollow in the otherwise gentle pattern. Its size and depth are so unusual that the chance of it being a mere accident is extremely low. To make matters more convincing, it lies in the southern galactic hemisphere, an area of sky relatively free from interference like cosmic dust, radiation from our galaxy, or signals from nearby sources. That makes its existence even harder to explain away. So what could be causing this strange chill beneath our cosmic feet? One possibility is the simplest: pure coincidence. Perhaps in the chaotic froth of the early universe, a rare quantum fluctuation happened to grow larger than usual, leaving behind this unusually cold patch. Mathematically, this explanation makes sense, but emotionally and scientifically, many researchers are unsatisfied. The odds of such a large fluctuation occurring are so slim that it feels unsatisfying, like winning the universe's unlikeliest lottery. Another explanation is known as the supervoid hypothesis. According to this idea, the cold spot might be caused by a gigantic underdense region of the universe, a cosmic desert, hundreds of millions of light years across, containing far fewer galaxies than usual. If photons, the tiny particles of light from the CMB, had to cross such a supervoid on their way to us, they would lose just a little energy as they travelled. This loss, caused by something called the integrated Sachs-Wolf effect, would make them arrive slightly cooler than expected. Indeed, galaxy surveys have shown that there does seem to be an unusually empty region in the direction of the cold spot. But here lies the problem: it is not empty enough. The void is there, but its size and emptiness are not nearly sufficient to account for the full drop in temperature. The explanation almost works, but not quite. That has led some scientists to dream up more exotic possibilities. Perhaps they suggest the cold spot is not merely an internal quirk of our own universe, but the scar of something far grander. One particularly fascinating idea is that it may be the bruise of a collision, an ancient scar left behind when our universe bumped into another, during the brief period of cosmic inflation, when the universe expanded faster than the speed of light just after the Big Bang. If true, the cold spot might not only tell us about the early universe, but also hint that our universe is just one bubble in a far greater cosmic foam. Of course, no solid evidence yet supports this breathtaking theory. Still, it remains one of the most enticing possibilities because of the cold spot's precise alignment and the way it stubbornly appears in every set of observational data, no matter how carefully scientists check their instruments. There is also another twist. The cold spot is not alone. Astronomers have noticed that many other strange features of the CMB, not just this one, tend to show a preference for the southern sky. Odd alignments of large-scale temperature patterns, statistical imbalances between the northern and southern hemispheres, and unusual axes of evil, as some jokingly call them, all seem to point below the galactic plane. Some argue these are just artifacts of observation, perhaps slight errors in calibration or measurements. But repeated cross-checks with different satellites, different instruments, and different data filtering techniques continue to confirm that the anomalies are real. Even more intriguing, the area around the cold spot is one of the cleanest windows to the CMB in the entire sky. There is very little cosmic dust, very few interfering signals, and hardly any background noise. That means this patch of space is like a pristine laboratory, where cosmologists can test their theories about the beginning of the universe. It also means that any unusual finding in this region carries more weight, because there is nothing obvious to blame it on. Today, the cold spot remains one of the most puzzling discoveries in all of cosmology. It is not something you can see with your naked eye. It does not glow, shine, or sparkle. Instead, it is a subtle chill, a whisper in the ancient light, detectable only with the most sensitive instruments. Yet, despite its quiet nature, it echoes through every attempt to explain our cosmic origins. It lies not far beneath the plane of our solar system, haunting the great southern sky like a bruise on the fabric of reality. Some scientists see it as a statistical oddity, others as a cosmic desert, and still others as the possible fingerprint of another universe brushing against our own. Whatever it may be, the cold spot stands as a reminder that even in the vast and seemingly well-mapped sky, mysteries still lurk. Mysteries that may hold the key to understanding not just where we came from, but whether our universe is truly alone. Far beyond the stars that shine in our night sky, beyond the glowing galaxies we can see with telescopes, scientists have discovered something astonishing through powerful computer simulations. These simulations, which recreate the growth and evolution of the universe, suggest that hidden beneath everything visible is an enormous unseen skeleton. This skeleton is not made of bones, nor of any material we know. It is made of something mysterious called dark matter. Dark matter is unlike the normal matter that makes up our bodies, planets, and stars. We cannot see it, touch it, or hold it. Yet scientists believe it makes up most of the universe's mass. It is the invisible scaffolding that holds everything together. Without it, galaxies might never have formed, and the universe might look completely different. But dark matter is not spread out smoothly across space. Instead, it stretches and coils through the cosmos in a gigantic and tangled pattern called the cosmic web. This web is not delicate like the silk threads spun by a spider. Instead, it is built from colossal filaments of invisible mass that stretch for hundreds of millions of light years across space. These filaments weave through the universe like ghostly highways, connecting glowing knots of light where galaxies are born and gathered in enormous clusters. But the web is far from simple. It is rough and uneven. The filaments grow thick and rope-like around massive galaxy clusters where gravity is strongest. In contrast, they become wispy and faint in the vast, empty regions of space, known as cosmic voids. Some of these filaments even split apart into smaller branches, reaching deep into individual galaxies like veins carrying unseen currents. Our own Milky Way galaxy is no exception to this invisible framework. To us, the Milky Way appears as a beautiful spiral of stars, gas, and dust. Yet it is wrapped inside a much larger ghostly cocoon of dark matter known as a halo. Within this hidden halo may run smaller strands of dark matter, tiny sub-filaments, that could even pass through the region of space where our solar system drifts. These invisible threads may cross silently above and below the galactic disk without us ever noticing. But this raises a big question. If dark matter cannot be seen or touched, how do scientists know it exists? The answer lies in a strange and marvellous trick of nature called gravitational lensing. Normally, light travels in straight lines, but when light passes near a massive object, gravity bends its path, almost as if the object were a giant magnifying glass. Astronomers carefully measure how light from faraway galaxies is stretched, curved, or warped as it travels toward us. These tiny distortions allow them to create maps of the hidden mass in the universe. Time after time, these maps reveal the same pattern. Web-like threads of dark matter stretched across the sky, linking galaxy clusters together in a cosmic net. Some computer models go even further, suggesting that our solar system itself may occasionally pass near one of these dark matter strands. Inside the Milky Way's larger halo of dark matter float smaller, denser clumps called subhalos. If one of these invisible knots drifted close enough, it could slightly tug on the orbits of planets, stir the icy comets in the outer solar system, or even create faint lensing effects that might be detectable with highly precise instruments. So far, no scientist has directly observed one of these local filaments near us, but they are getting closer. The European Space Agency's Gaia mission, which is mapping the motions of more than 1 billion stars, is beginning to spot small wobbles and ripples in star streams. These tiny disturbances may be the fingerprints of dark matter, clumps gliding quietly through the galaxy. If a dark matter filament ever drifted near our solar system, we would not see it shine. Instead, we might notice its invisible presence only through its gentle tug on nearby stars and clouds of gas. Researchers are also beginning to wonder if these filaments of dark matter influence something else: the paths of cosmic rays. Cosmic rays are extremely fast, high-energy particles that race through space at nearly the speed of light. Denser strands of dark matter with their gravity and perhaps their magnetic effects, might bend the trajectories of these particles or alter their energies ever so slightly. If this turns out to be true, studying cosmic rays could provide yet another way to map the hidden shapes of dark matter's threads. Should we be afraid of these invisible structures drifting through space? The answer is almost certainly no. Dark matter is unimaginably thin and diffuse. Even in the thickest parts of a filament, there may be only a few dark matter particles in a space as large as a household refrigerator. To us, that would feel like complete emptiness. Yet, on the grand scale of galaxies, the pull of dark matter is powerful enough to guide the dance of star clusters, bend the paths of stellar streams, and even steer giant clouds of gas so that new stars can be born. Over the course of millions of years, dark matter filaments may decide where galaxies grow, how comet clouds like the Oort cloud are stirred, and how spiral arms shift slowly through space. Looking toward the future, scientists are designing even more sensitive tools to search for the faint traces of dark matter. One of these projects is the Laser Interferometer Space Antenna, LISA, which will try to detect weak gravitational waves, tiny ripples in space itself, that might emerge if filaments of dark matter interact. Another ambitious mission, called CMB-S4, will study the faint afterglow of the Big Bang, known as the cosmic microwave background. By searching for tiny distortions in this ancient light, it may reveal the fingerprints of dark matter structures formed when the universe was still young. If all of these predictions prove true, then the night sky above us is hiding far more than stars. Flowing invisibly across the galaxy may be entire rivers of dark matter, moving silently, shaping the future of the Milky Way without ever shining a single ray of light. They are the hidden threads of a story still unfolding, the story of how the universe holds itself together. Rogue planets are perhaps the loneliest wanderers in the entire universe. Unlike the familiar planets that circle around stars, basking in their warmth and glowing skies, these strange worlds drift endlessly in the cold, dark spaces between the stars. They carry no sun to light their skies, no steady warmth to comfort them, and no day or night to mark the passing of time. They are like ships adrift in a sea without a lighthouse, sailing forever through a silent ocean of shadows. Some of these lonely travellers were not always so alone. Long ago they were faithful companions of stars, moving gracefully around them in steady orbits, just as Earth moves around the Sun. But the universe can be violent and unpredictable. Enormous gravitational struggles, cosmic tug-of-war battles between giant planets, or sudden encounters with passing stars sometimes fling a planet away from its home. Thrown out with incredible force, the planet is cast into exile, forever banished to wander the dark gulf between stars. Other rogue planets never knew the comfort of a star at all. Some were born in solitude, forming from clumps of gas and dust that collapsed in the darkness, never gathering enough heat or light to ignite a star of their own. These planets entered the universe as orphans from the very beginning, doomed to live without a sun to call their own. Most of these free-floating worlds travel within the wide, flat disk of our Milky Way galaxy, moving quietly among the billions of stars. But not all follow this ordinary path. Some come from unusual directions, falling in from above or below, arriving at sharp, unexpected angles. When a rogue planet approaches from galactic north, the region of space above the flat plane of the Milky Way, it comes from a direction that astronomers rarely study in detail. This makes it even harder to detect, as though it were sneaking into the galaxy from a hidden doorway. Finding these planets is no easy task. They're cold, dark, and nearly invisible against the black backdrop of space. But astronomers have found clever ways to track them. One of the most powerful tools is something called gravitational microlensing. This effect is a gift from nature itself. When a rogue planet drifts in front of a distant star, its gravity bends the light of that star. For a brief moment, the star appears to brighten and flicker, almost as if it were winking at us. That tiny temporary flash is enough to reveal the presence of an otherwise invisible world. Using this method, astronomers have discovered rogue planets both small and large. Some no bigger than Earth, others many times heavier than Jupiter, the giant of our solar system. The numbers are astonishing. Studies suggest that there may be billions upon billions of rogue planets drifting through the Milky Way. In fact, There may even be more of these lonely wanderers than there are stars. Imagine that for a moment. A galaxy not only filled with glowing suns, but also teeming with invisible, silent worlds hiding in the darkness between them. But how do some of these planets end up far above or far below the galactic disk? The Milky Way is not a flat, motionless sheet. It ripples and vibrates like the surface of a pond stirred by a breeze. It is constantly disturbed by enormous galactic events. When two galaxies collide or even pass near each other, their overwhelming gravity can hurl stars and planets out of their regular orbits. Some are flung so far that they end up in the galactic halo, a vast region of space high above or deep below the disk. Other rogue planets may have been ripped away from small dwarf galaxies or tight star clusters that once plunged through the Milky Way at odd angles, leaving trails of torn stars, drifting gas, and abandoned planets. In crowded star systems with two or more suns, chaotic gravitational pushes can also fling planets far out on long arcs, sending them soaring above the disk before they eventually fall back toward it. If a rogue planet were ever to approach our solar system from galactic north, it would be very difficult to notice. Most of our telescopes are designed to watch the galactic plane, or track the familiar paths of planets within our solar system. A dark, frozen world falling straight down from above would be like a shadow slipping into a room from the ceiling, while everyone is staring at the walls. Such planets give off almost no visible light. Without a parent star to heat them, they shine only faintly with the leftover warmth from their birth, a weak glow that can only be detected in infrared light. Powerful instruments such as the James Webb Space Telescope or the soon-to-be-launched Nancy Grace Roman Space Telescope are sensitive enough to catch that faint whisper of heat. But even for them, the search is like looking for a dying ember in an endless desert of night. Could one of these wandering planets ever come dangerously close to us? The chances are very small. Space is unimaginably vast, and our solar system is but a tiny speck in the galaxy. Yet, small does not mean impossible. Scientific models suggest that perhaps once every few million years, a rogue planet or similar object might pass within just a few light years of our Sun. Even without colliding with Earth or any other planet, such a visitor could cause disruption. Its gravity might disturb the Oort cloud, that enormous icy shell of comets surrounding the solar system, and send countless comets plunging inward. Like ripples spreading across a pond after a stone strikes its surface, waves of icy bodies could sweep into the inner solar system, some even heading toward Earth. Some scientists believe this might not be only a future possibility, but also something that happened in the past. A daring idea suggests that the mysterious Planet 9, the hypothetical giant world believed to exist far beyond Pluto, might not be a native planet at all. It could be a rogue planet that the Sun captured millions of years ago, pulling it into a long, stretched-out orbit that keeps it hidden in the distant dark. While this theory is still uncertain, it reminds us that our solar system's history may include encounters with visitors from the galaxy's untamed wilderness. The story of rogue planets also reveals something greater. They are like silent markers that help us trace the hidden structure of the Milky Way itself. By studying how these planets move, astronomers can refine their understanding of the galactic halo, the wobbling of the disk, and even the invisible influence of dark matter, the mysterious substance that acts as the skeleton of the universe. Though they are cold, dark, and silent, rogue planets may hold the keys to unlocking secrets about the very architecture of our galaxy. In the years ahead, new wide-field sky surveys will search for them more carefully than ever before. Missions such as the European Space Agency's Euclid Telescope and the Vera Rubin Observatory will sweep across the heavens, looking for the faintest flickers of these hidden wanderers, even those arriving from the overlooked regions of galactic north. The night sky may look full of shining stars, but the truth is that it could be just as full of invisible worlds. They drift unseen, like ghost ships in the ocean of the cosmos. And perhaps, even now, one of these silent travelers is slowly making its way toward us from the darkness above. There may be answers to some of the greatest mysteries of the universe hidden in a strange kind of matter that we cannot see. This invisible substance, known as dark matter, might carry secrets about the universe's very foundation. Some scientists believe that part of this mystery could be hidden beneath the flat plane of the Milky Way galaxy. in quiet and shadowy regions where even light itself seems hesitant to wander. To search for dark matter, researchers have gone to extraordinary lengths. They have built underground laboratories buried deep beneath mountains to shield their instruments from cosmic interference. They have placed telescopes high up in the thin air of mountaintops, closer to the heavens. They have even created powerful machines called particle accelerators, which smash atoms together at incredible speeds in the hope of revealing the hidden particles that may form dark matter. But there may be a different and less explored realm just below the organised plane of the Milky Way. In this mysterious layer, scientists suspect that unusual, invisible particles might be moving in great numbers. Among the leading suspects are WIMPs, short for weakly interacting massive particles, and axions, an entirely different kind of hypothetical particle. WIMPs are thought to be heavy, ghost-like particles that almost never interact with ordinary matter. They slip through planets, stars, and even our own bodies without leaving a trace, except for the faint tug of their gravity. Because of this, they are strong candidates for the main ingredient of dark matter. Axions, by contrast, are imagined to be feather-light particles. They were first proposed as a way to solve a puzzle in a branch of physics called quantum chromodynamics, which deals with the forces that hold atomic nuclei together. But axions might also explain the hidden mass of the universe. Unlike WIMPs, axions could behave in unusual ways. They might gather into vast wave-like fields or condensates, and they might interact faintly with magnetic fields, giving them very different properties inside galaxies. To understand where such particles might gather, imagine the Milky Way not only as a shining spiral of stars but also as a thick disk filled with swirling gas, dust and radiation. Most of the galaxy is restless. Exploding stars send shockwaves through space, newborn stars pour out fierce radiation, and the central bulge of the galaxy releases storms of energy. Yet just below the central flat layer, the galactic midplane, there exists a calmer region. It is not as disturbed by exploding stars or strong radiation. This quiet zone, at the uniform heart of the disk, may act like a gravitational basin where slow-moving cold particles naturally settle. Over time, it could gather thin but extended layers of dark matter, perhaps forming subtle structures just below the plane of the galaxy. Computer models of galaxies support this idea. They suggest that dark matter does not always form smooth halos around galaxies. Instead, it may clump together in smaller shapes and patterns. Some of these clumps, called streams or caustic rings, might drift through the galaxy in specific directions. If one of these invisible streams passes near our solar system, it could mean that a steady flow of dark matter particles is reaching Earth, sometimes from below, along upward paths that few instruments are currently designed to track. Detecting these elusive particles is an enormous challenge. That is why scientists have built experiments such as Xenon, Lux Zeppelin and ADMX. These machines are designed to catch the briefest and rarest events. A WIMP striking the nucleus of an atom deep underground, or an axion transforming into a faint photon of light inside a powerful magnetic field. But Earth itself complicates matters. As our planet spins and orbits the Sun, the angle at which dark matter particles arrive changes slightly. This means that detection rates rise and fall with direction and season. Researchers are now considering whether these changes might also be influenced by Earth's position relative to the galactic midplane, especially if some particles are streaming from below. Our solar system does not sit exactly in the middle of the Milky Way's disk. The Sun is currently about 20 light-years above the galactic midplane. Over time, it moves in a slow up and down rhythm through the disk, like a ship bobbing on cosmic waves. This oscillation takes about 60 million years to complete. Right now, we are slowly drifting downward, falling toward the galactic underlayer. This descent could be leading us into regions with higher or different concentrations of dark matter than we have ever encountered before. Some scientists think this vertical motion could explain puzzling results from certain experiments. For example, the Gamma Libra detector has reported unusual seasonal patterns in its data, signals that might fit with the idea that Earth is passing through denser streams or sheets of dark matter beneath the galactic plane. In some models, axions may not just float randomly, but instead line up into great filaments or thin sheets. If these structures extend below the plane of the Milky Way, they could cross Earth's path at sharper angles than expected, creating bursts of detectable particles at specific times. Beyond the traditional detectors, a new generation of tools is on the horizon. Scientists are experimenting with quantum technologies, such as atom interferometers, devices that use the delicate motion of atoms to measure tiny disturbances, and superconducting microwave cavities, which may be able to sense axion-like particles with far greater precision. One bold idea is to point such instruments not only along the familiar path of the solar system's orbit, but downward, below the galactic disk, toward the quiet southern skies of the celestial hemisphere. By looking in that direction, we may be able to sense particles that have gone unnoticed until now. If these instruments succeed, they will not only reveal more about the nature of dark matter, they could also uncover the hidden architecture of our galaxy itself. Instead of imagining dark matter as a simple, smooth fog that fills space evenly, we may find that it is arranged like an invisible web of filaments and streams, threading its way beneath the stars. This unseen structure may shape the very way galaxies form, grow, and move through the cosmos. And humanity, perched on a small planet in the suburbs of the Milky Way, is only just beginning to peel back the curtain on this great cosmic mystery. When most people try to picture the universe, they often imagine something neat and orderly, a great flat disk where planets, moons, and comets quietly circle around the sun in smooth and steady paths. In this picture, everything sits nicely on a single plane, as if the cosmos itself were a tidy dinner table. The Earth's own path around the sun, which astronomers call the ecliptic, feels like the clearest example of this order. It is like a line of balance in space, a rule of symmetry that seems to keep everything in its proper place. But this is only the surface of the story. Beneath this thin skin of order lies something stranger, older, and far less studied. A hidden realm of chaos and mystery. It is a place where fragments of the past drift like forgotten relics, where comets plunge in unexpected directions, and where invisible rivers of gravity twist and pull in ways that defy our neat diagrams. In many ways, it is like an underworld of the solar system, dark, restless, and filled with secrets. The best-known citizens of this hidden domain are asteroids and comets. Most of them remain close to the ecliptic, circling along like faithful travellers on a highway. Yet not all follow this rule. Some, especially those that come from the faraway Oort cloud, dive steeply down from above or below. One of the most famous examples is Halley's Comet. Unlike the planets, which all move in the same general direction, Halley's Comet races along a tilted path, travelling backward compared to the planet's motion. Its orbit dips beneath the ecliptic, only to swing back upward again in a grand, dramatic arc. Other icy wanderers, such as the dark centaurs or the mysterious Damocloids, behave in much the same way. They slip in at odd angles, crossing beneath the ecliptic like shadows on hidden currents. Many long-period comets, which take thousands or even millions of years to complete their journeys, arrive on paths so steep and unpredictable that they seem almost random. When seen from the side, their travels look like sharp plunges from the southern depths of the solar system. They sweep past the sun in a flash of brilliance, then soar upward again, vanishing into the dark. Though their visits are brief, these comets hint at the enormous gravitational forces that shape the farthest outskirts of our system. Beyond the icy band known as the Kuiper Belt lies an even wilder territory, the scattered disk. This is a sprawling halo of frozen worlds and shattered fragments, many of which rest far below the ecliptic. Some scientists believe their strange alignments may not be accidental. They suggest that a hidden world, a giant planet sometimes called Planet 9, could be lurking out there. This world, still only a theory, might be tugging at these distant bodies, pulling them into steep orbits that dive beneath the ecliptic. If true, then what lies below our familiar solar plane may be influenced by the gravity of an unseen giant. But gravity alone does not tell the whole story. The sun and planets are not standing still in space. The entire solar system is moving like a great ship, sailing through the galaxy itself. As we drift along, we create a kind of gravitational wake, sometimes described as a bull wave, in the thin gas and dust of the interstellar medium. And our motion through the galaxy is not flat. It tilts slightly upward compared to the ecliptic. Because of this tilt, much of the material that drifts below the ecliptic may be more easily disturbed, swept inward, or tugged by galactic currents as we move through the wider Milky Way. There is also the hidden role of the Sun's magnetism. The Sun's magnetic field stretches outward in a great spiral, shaped by the rotation of the star. This structure is called the heliospheric current sheet. It is like a giant wavy blanket of charged particles twisting above and below the ecliptic. This current sheet reaches billions of kilometers into space, curling and folding beneath the ecliptic like a flowing curtain. Streams of solar particles and magnetic fields are dragged with it, creating a deep and shifting magnetic underworld. These invisible forces bend cosmic rays, scatter grains of dust, and trap drifting particles from interstellar space. Spacecraft have given us rare glimpses into this hidden region. The Ulysses probe, launched in the early 1990s, was built mainly to study the Sun's polar regions. But as it moved out of the ecliptic, it also revealed how plasma flows and magnetic fields behave far from the solar plane. Voyager 2, which crossed just below the ecliptic as it left the heliosphere, recorded strange particle streams, sudden shock waves, and the southern edge of the Sun's influence. Its findings hinted that space below the solar system may not be a simple reflection of the space above. It may be shaped in a different way altogether. Closer to home, even some near-Earth asteroids carry hints of this hidden order. One striking example is the asteroid known as 3200 Phaethon. Its orbit is shaped like a long ellipse that cuts beneath the solar plane. Because most telescopes are aimed along the ecliptic, where the majority of objects are expected, many tilted bodies like Phaethon may still be hiding, slipping past our searches unnoticed. And then there is the faint zodiacal cloud, the hazy band of dust made from crumbling asteroids and the trails of comets. To the naked eye, it looks like a soft glow stretching along the ecliptic. But infrared telescopes such as ERAS and WISE have revealed that this cloud is not thin and flat. Instead, it has surprising depth, spreading above and below the solar plane. The dust beneath the ecliptic scatters sunlight and re-emits it as a faint warmth in infrared light, creating a ghostly glow that most people never see. These telescopes have mapped the hidden dust, showing how it drifts and dances under the combined pull of gravity, the push of solar wind, and the twists of magnetism. So what then lies beneath the ecliptic? Not emptiness, but an entire hidden landscape. It is a realm of tilted orbits and crooked paths, of wandering comets and strange fragments, of invisible magnetic waves and subtle galactic currents. It is not simply a mirror of what lies above, it is its own strange, restless world. Here, comets rise like ghosts from the darkness. Here, unseen planets may tug at the edges of reality. Here, the forces of the sun and the galaxy fold and stretch space into shapes we are only beginning to glimpse. Far below the flat middle layer of our galaxy, in regions where sunlight fades away and great clouds of gas vanish into emptiness, there may be some of the rarest and most mysterious things in the universe. These are called primordial black holes. Unlike ordinary black holes, which are born when giant stars explode and collapse, these ancient ones were never tied to stars at all. They are thought to have come directly from the chaos of the newborn universe. Primordial black holes, or PBHs for short, could be incredibly tiny compared to the monstrous black holes we usually imagine. Some may have been no larger than an asteroid, while others could have been as massive as a mountain. And yet, despite their small size, they are among the most intriguing candidates for dark matter, the invisible substance that makes up most of the universe. The mystery lies in the fact that they are only a theory. They do not glow, they do not reflect light, and they are almost impossible to detect. If they exist, they may be gliding quietly beneath the galactic disk, hidden in the cold and silent dark. Scientists believe that these black holes might have been created during the very first instant after the Big Bang, within the very first fraction of a second. At that time, the universe was a storm of violent fluctuations in density, and some of those fluctuations could have collapsed straight into black holes. Unlike the black holes we know from exploding stars, primordial ones could cover a huge range of sizes, from tinier than an atom to heavier than thousands of suns, depending on how big those early density spikes were. In a way, they are like fossils of the cosmos, relics from a time before stars, before planets, even before galaxies had formed. But why would scientists expect to find them beneath the galactic midplane? The answer lies in the quiet mechanics of the Milky Way. Dark matter, wandering stars, and even black holes do not just circle in neat, flat paths. They also bob up and down, rising above and dipping below the disk, tugged by the galaxy's gravity. The Sun itself follows such a path, gently moving up and down through the midplane about once every 60 million years. Tiny primordial black holes, if they exist, could be caught in similar vertical orbits. That means some of them could drift naturally into the hidden southern side of the galaxy, where clouds are thinner and fewer stars get in the way. These low-density regions are perfect hiding places. With fewer stars and fewer exploding remnants of supernovae, there is far less background noise. That makes it easier to notice the faint gravitational fingerprints of something as elusive as a primordial black hole. Even though they do not shine, they still bend light around them. Scientists use a technique called gravitational microlensing, watching for the moment when a black hole drifts in front of a distant star and briefly magnifies its light like a cosmic magnifying glass. Ongoing surveys such as OGLE and the future Vera C. Rubin Observatory are watching the sky for these small but telling blips. And the quiet southern fields beneath the galactic plane may be the very best laboratory for this hunt. But gravitational lensing is not the only clue. If a primordial black hole were ever to pass near our solar system, it would not just bend the light of distant stars. Its pull might leave tiny fingerprints on the orbits of asteroids, nudge a spacecraft off course, or even disturb the thin web of dark matter itself. Detecting such subtle effects would require the most precise models of the Sun's motion and of the orbits in our solar system, but these signs could reveal what our eyes cannot see. Another possible clue comes from gamma-ray signals. According to Stephen Hawking's theory, black holes can slowly evaporate by giving off faint radiation, a strange quantum effect now known as Hawking radiation. If primordial black holes are evaporating, they might be leaking out weak gamma-ray signals. The southern galactic hemisphere, which is quieter and less crowded than the northern side, offers an excellent window to look for such whispers of energy. Some scientists have even suggested that certain puzzling gravitational waves, ripples in space-time first detected by LIGO and Virgo, might have been caused by two primordial black holes colliding. If they tend to gather in low-density areas, then the dark underside of the galaxy may be a place where such collisions are more likely to happen. If so, the echoes of their mergers would travel across the universe as ghostly vibrations, the only evidence of events we cannot otherwise see. If primordial black holes make up even a small part of dark matter, then Earth itself may sometimes drift through streams of them as it journeys around the Milky Way. Right now, our planet is moving downward toward the southern side of the galaxy. That means we may be heading into a region where hidden gravitational shocks and strange disturbances wait for us in the dark. We may never capture a picture of a primordial black hole. They may always remain unseen, drifting in silence beneath the galactic floor. But even if invisible, their presence might still be felt, in the bending of starlight, in the slight wobble of an orbit, in the faint hum of space-time ripples echoing through the cosmos. Somewhere deep below, in the vast ocean of darkness under our galaxy, these ancient objects may still be floating as they have for billions upon billions of years, silent witnesses to the birth of the universe itself. High-energy cosmic rays often reach us from above, falling toward Earth like invisible arrows shot from the farthest edges of the universe. To the human eye, the night sky may seem peaceful, a place of steady stars and quiet planets gliding in their orbits. But in truth, outer space is not calm at all. It is more like an endless battlefield where unseen bullets are always flying in every direction. These bullets are what scientists call cosmic rays. Despite their name, cosmic rays are not beams of light in the usual sense. They are tiny particles, mostly protons, some heavier atomic fragments, and a smaller number of electrons, that carry staggering amounts of energy. They rush through space at almost the very speed of the light, faster than anything we could ever build. Some cosmic rays are forged in the violent explosions of dying stars, in the roaring furnaces of supernovae. Others may come from even stranger places that we still do not fully understand, perhaps from the hearts of galaxies or from cosmic events more powerful than anything we can imagine. Many of them seem to rain down from above the solar system. Strangely, there is a heavier concentration coming from above the thin, flat plane where the planets circle the Sun, a region known as the ecliptic plane. Why this happens is still unsolved, but scientists think it has to do with the way our galaxy's magnetic fields twist and bend, with the sun's own magnetic forces, and with the vast protective bubble that surrounds us called the heliosphere. The heliosphere is like an invisible shield stretching far beyond all the planets. It is formed by the solar wind, the constant stream of charged particles blowing outward from the sun, and the sun's powerful magnetic fields. This shield does not keep all cosmic rays out, but it changes the way they reach us. When these fast-moving particles approach from interstellar space, they collide with this solar wind and magnetic barrier. Sometimes the shield is strong and fewer rays get through. At other times, such as during the solar minimum, when the sun is quiet and its activity is at its lowest, the shield grows weaker and more cosmic rays flood into the inner solar system, especially from the sun's northern direction. We have even sent scouts to test this invisible frontier. Voyager 1 and Voyager 2, the famous spacecraft launched in the year 1977, have journeyed to the edge of the heliosphere. Voyager 1, which crossed the northern boundary of this bubble, recorded a sharp rise in the number of cosmic rays, a clear sign that it had stepped outside the sun's protective influence and into the raw stream of galactic radiation. The fact that so many rays seem to pour in from above may mean that our solar system is moving through a cosmic headwind, or that the galaxy's magnetic fields are shaped in such a way that they funnel radiation toward us. Here on Earth, scientists use all kinds of clever tools to track these mysterious messengers. Balloons released over the icy skies of Antarctica, as well as sensitive ground-based detectors, measure the cosmic rays that strike our atmosphere. They have found that the poles of Earth are hit harder than other places. This happens because both the Earth's and the Sun's magnetic fields guide the charged particles toward the poles. When they plunge into our atmosphere, they collide with atoms in the air and unleash dazzling light displays. The auroras, those glowing curtains of green, red, and violet that ripple across the skies near the Arctic and Antarctic. But among all cosmic rays, there is a special group that puzzles scientists the most: the ultra-high energy cosmic rays. These are the champions of the universe's particle world. They carry more energy than anything humans have ever created, even in Earth's most powerful machines like particle accelerators. In fact, some of these particles hold millions of times more energy than what we can generate. And yet, they simply fall toward Earth from the sky. Many seem to come from above the plane of the Milky Way, but their exact sources remain hidden. Some scientists suggest they might be born near supermassive black holes, in the violent centers of galaxies, or during titanic explosions called gamma-ray bursts. Others admit that we may be seeing something entirely new. To solve this cosmic mystery, massive projects have been built. The Pierre Auger Observatory in Argentina spreads across the land like a giant net to catch these rare particles. Meanwhile, above our heads, the Alpha Magnetic Spectrometer attached to the International Space Station maps cosmic rays with extraordinary precision. This instrument has even detected something especially strange: an excess of positrons, which are the antimatter twins of electrons streaming in from above the ecliptic plane. This finding has sparked bold ideas. Perhaps dark matter is annihilating itself nearby, releasing these particles, or perhaps hidden cosmic engines are at work just beyond what our telescopes can see. Cosmic rays are both wondrous and dangerous. They can slip straight through spacecraft walls, through the fragile electronics inside, and even through the bodies of astronauts. On Earth, our atmosphere and magnetic field keep us mostly safe, but in deep space, beyond this protective shield, the danger grows. For future voyages to the Moon, to Mars, or even farther, this invisible radiation poses one of the greatest challenges. Engineers are already working to design smarter spacecraft and stronger shields, using the patterns of incoming cosmic rays as guides. In the end, cosmic rays are like whispers of the universe, tiny, energetic messengers that carry stories of explosions, black holes, and perhaps even of hidden forces beyond our understanding. They remind us that space is not empty silence, but a living, restless storm of energy, always reaching for us across the great cosmic ocean. Physicists have spent decades chasing a ghost of an idea, a mysterious particle called the magnetic monopole. If such a thing were ever found, it would completely change how we understand electricity and magnetism. Normally, a magnet always has two ends, a north pole and a south pole no matter how many times you cut it in half. A monopole, however, would be different. It would carry just one pole alone, either north or south, but not both. Scientists have never seen one directly, yet the possibility of monopoles is taken very seriously in the most advanced theories of physics. They appear naturally in grand unified theories, often shortened to guts, and also in some versions of string theory. These theories suggest that monopoles are not fantasy, but real things that may simply be very hard to find. So, where could we possibly look for them? One promising place is in the quieter regions of space below the path of our Sun, far away from dense matter and messy magnetic storms. Monopoles are thought to be extremely rare, perhaps created in the very first split seconds after the Big Bang, much like primordial black holes. If they do exist, they would not be tiny and light like electrons. Instead, they would be immense, possibly thousands of times heavier than a proton. Their great weight means they would not fly quickly through space like cosmic rays do. Rather, they would move slowly, drifting along the magnetic field lines of the galaxy, like beads sliding gently down invisible strings. Below the central plane of our Milky Way, space becomes calmer. The number of stars and the amount of glowing plasma drop sharply. There is less magnetic noise from exploding stars, radio bursts, and turbulent solar winds. In these quiet zones, the long, orderly magnetic fields of the galaxy are easier to pick out. If monopoles exist, they are most likely to follow those fields, and that is exactly where astronomers should be looking. Imagine the galaxy as a tangled bowl of magnetic spaghetti. The southern side of the galaxy may be one of the cleanest strands, and scientists are already watching. Powerful instruments like IceCube, buried deep in the Antarctic ice, and Antares, resting in the deep waters of the Mediterranean Sea, have both searched for signs of monopoles by looking for rare glowing tracks of energy left in water or ice. So far, nothing has turned up, but some physicists argue that the best chance lies not on Earth at all but out in space, especially beyond the reach of the Sun's magnetic field, where its constant turbulence no longer drowns out faint signals. A spacecraft stationed below the ecliptic, looking toward the galactic South Pole, could be perfectly placed to catch a slow-drifting monopole. Another clever method involves superconducting loops, rings of special material where electricity flows forever without resistance. If a monopole passed through such a loop, it would cause a permanent change in the current, almost like a toll gate counting a passing traveller. One day, fleets of robotic probes might carry these loops into the quieter southern reaches of the galaxy, scanning for strange disturbances in the magnetic silence. Some researchers even imagine that monopoles might sometimes be caught temporarily by the magnetic fields of planets, or trapped in Earth's long magnetic tail, only to be released during violent geomagnetic storms. But in the wide, dark stretches of interplanetary space, especially beneath our Sun's orbit, they would have the freedom to drift undisturbed, leaving subtle clues for us to find. For this reason, future deep space missions may carry finely tuned magnetometers designed to catch even the faintest trace of such a particle. Why does this matter so much? Because if magnetic monopoles exist, their discovery would confirm bold predictions that physicists have been making for half a century. Even more importantly, they could explain one of the deepest mysteries of the universe, why electric charge always comes in fixed, identical amounts. Every single electron in the universe carries exactly the same negative charge, as though nature stamped them all with the same mould. That odd consistency, as strange as it seems, could be the direct fingerprint of magnetic monopoles lurking somewhere in the cosmos. These particles are not just missing puzzle pieces, they may be the key to uniting all the forces of nature, gravity, electromagnetism, and the nuclear forces, into one grand picture. So far, no one has caught one. But in the cold, quiet, magnetically clean basement of the galaxy, far to the south of our familiar skies, the hunt continues. Somewhere in that hidden darkness, the secret may be waiting, the particle that could finally tie together the story of the universe. Neutral hydrogen is one of the universe's most widespread but least noticed ingredients. Imagine it as a vast, invisible ocean lying beneath the main disk of our galaxy, the Milky Way. Unlike the shining brilliance of stars or the roaring energy of quasars, neutral hydrogen does not glow or dazzle. Instead, it hums faintly at a special frequency of 1,420 MHz, a cosmic whisper rather than a shout. This neutral hydrogen, often called Hi, is just the simplest kind of atom, one lonely proton paired with one equally lonely electron. By itself, a single atom is impossible to detect, far too faint to notice. But when billions upon billions of them gather into great clouds, they give off radio waves at a very particular wavelength, known as the 21 centimetre line. This signal has become one of astronomy's most powerful tools, allowing scientists to trace out hidden shapes and movements of gas across the galaxy, even in regions where ordinary telescopes cannot see. The most fascinating discoveries are made below the galactic midplane, a quieter and darker zone where conditions are colder, calmer, and more pristine than the crowded regions above. Radio surveys, such as those from the Hi4PI and Galpha High projects, reveal that hydrogen here is not spread evenly. Instead, enormous layered clouds stretch for thousands of light years, often curling and twisting into wave-like patterns. These clouds are not still, they drift and ripple, pulled and sculpted by the galaxy's rotation and the tug of its gravity. Some of these gas structures form part of what astronomers call the galactic warp. Think of the Milky Way's disk as a giant spinning record that is not perfectly flat but bent, dipping downward on one side and arching upward on the other. Our own solar system is currently sliding downward into this bend, heading directly toward one of the densest regions of hydrogen in the southern sky. Why does this matter? Because neutral hydrogen is the raw fuel from which stars are born. Long before a star shines, it begins as a cold, dense cloud of hydrogen slowly collapsing under gravity. By studying these hidden layers of gas beneath the galactic disk, astronomers are essentially watching a time-lapse of stellar history, especially in quiet, low metallicity regions where ancient processes still echo. These gas clouds are like a memory of the galaxy itself, recording past events the way scars record old wounds. Indeed, some of the hydrogen streams found below the disk are relics of galactic collisions. Wisps of gas, perhaps once part of small galaxies such as the Sagittarius Dwarf or the Magellanic System, were pulled apart by the Milky Way's gravity and dragged down over billions of years. These streams continue to move on their own, colliding with the halo of gas around the galaxy and creating shock waves, compression zones, and changes in temperature that can either spark the birth of new stars or smother it entirely. Among the most puzzling mysteries are the so-called high-velocity clouds. These are enormous blobs of neutral hydrogen racing through space at speeds that do not fit the normal rotation of the Milky Way. Many of them lie below the galactic plane, and their origin is still uncertain. Are they leftovers from ancient collisions? Are they material blown out by long-gone stellar explosions now falling back into the disk? Or could they even be fresh gas arriving from the cosmic web itself, drifting slowly into the galaxy like cosmic rainfall? One of the most striking examples is the Smith Cloud, a colossal object of neutral hydrogen on a direct course toward the Milky Way, approaching from below the disk. This cloud carries enough raw material to form 1 million new stars and is rushing forward at nearly 240 kilometers per second. In perhaps 40 million years, when it slams into the Milky Way's disk, it could ignite a spectacular burst of star formation in the southern galactic hemisphere. Even before this dramatic collision, however, the shock waves it sends through the hydrogen layers beneath us may give astronomers priceless clues about how gas behaves in the deep, cold stretches of space. And this is only the beginning. With new technology, especially the square-kilometre array, an immense radio telescope soon to rise, astronomers will be able to chart these hydrogen layers in exquisite three-dimensional detail. They will track their movements, measure their density, and study how they interact with cosmic rays and magnetic fields. It will be a little like scanning the floor of a cosmic ocean, finding its sediment layers, its buried rivers, its fossil records of past events. So, while we often lift our eyes to the brilliant stars and glowing nebulae above, there is also a hidden world below, a quiet realm filled with ghostly hydrogen fog. It whispers across the radio spectrum, carrying stories of creation, collision, and rebirth. Neutral hydrogen is not just a background presence. It is the very foundation of galaxies, the seedbed of stars, and the silent witness to everything that has ever drifted into the Milky Way. Even though space often feels empty and calm, it is far from still. High-energy particles, Cosmic rays, neutrinos, and ions move through the galaxy in all directions, but not always evenly. This unevenness in particle flow is called directional anisotropy. Scientists have detected a mysterious cosmic whisper. Particles sometimes arrive from preferred directions rather than uniformly. Surprisingly, some of this flow seems to come from beneath the circular plane of the Sun, the vast invisible disk in which our solar system orbits. The term anisotropy simply means unevenness, and in this case, it describes how particles do not arrive the same from every direction. Sensitive instruments like the IceCube Neutrino Observatory in Antarctica, as well as cosmic ray detectors aboard satellites such as Pamela and MS-02, have consistently recorded small excesses and deficits in incoming particles depending on the region of the sky being observed. When the data is mapped across the whole sky, a remarkable pattern emerges. Some of the highest energy particles appear to be arriving from southern galactic latitudes, beneath the plane. This bias is not random noise. Statistically, it is significant, and in some cases it has remained consistent over many years of observations. This strongly suggests that the effect is a real feature of our nearby galaxy, rather than a measurement error or a quirk caused by Earth's magnetic field. But why would the particle flow favour one direction? One possibility involves galactic magnetic fields. Cosmic rays, especially lower energy ones, are influenced by these fields. If the southern galactic hemisphere contains denser magnetic lines, remnants of ancient supernova shockwaves, or coherent plasma structures, these could funnel or deflect particles upward toward the solar system. Picture this as an invisible cosmic subway system, moving near the speed of light, carrying particles along preferred routes. Another explanation might lie in the Milky Way's history of collisions. Over billions of years, our galaxy has absorbed smaller galaxies, leaving behind streams of stars, gas, and dark matter below the galactic plane. If these remnants include active black holes, collapsed cores, or dense clumps of dark matter, they could act as powerful particle accelerators, flinging high-energy particles toward us and producing the observed anisotropy. Our own motion through the galaxy also plays a role. The solar system is currently moving downward through the galactic plane, toward the southern sky. This motion creates a kind of kinetic frame shift, making incoming particles from below appear slightly more energetic, much like driving into a rainstorm makes the raindrops seem harder from the front. This effect, known as Compton-Getting anisotropy, magnifies directional differences and helps scientists separate real particle flows from observational biases. By combining measurements from instruments in both hemispheres over long periods, researchers have begun constructing three-dimensional maps of particle flows around the solar system. These maps reveal that the space beneath our feet is far more active than once believed. Even more intriguing, these particle anisotropies seem to align with other signals, such as gamma-ray gradients detected by the Fermi Gamma Ray Space Telescope and neutrino bursts recorded by IceCube. Many high-energy phenomena appear more frequent or intense in the southern sky beneath the plane. Are these coincidences, or clues to hidden sources, active remnants, magnetic funnels, or unknown astrophysical structures lurking below? Understanding these directional flows is not just academic. It improves models of space weather, which is crucial for future deep space missions. It may also reveal the distribution of matter and energy in hard-to-observe regions of the galaxy, and perhaps even hint at exotic physics, from dark matter decay to unknown cosmic accelerators. While most telescopes focus on the sky above, the space below is sending particles with stories to tell. Stories of movement, structure, and unseen forces. For most people, tides are the rise and fall of Earth's oceans caused by the moon, or the stretching of stars near black holes. But gravity stretches space over enormous distances, affecting stars, clouds, and even entire galactic disks. In the southern parts of the Milky Way, below the solar system, tidal forces from massive structures are subtly reshaping how stars move, how the solar system drifts, and possibly even the galaxy's overall shape. The Milky Way is not a static, flat disk. It ripples and responds to gravitational nudges from within and beyond. One major influence comes from the Sagittarius dwarf spheroidal galaxy, a small satellite currently being devoured by our galaxy. Its tilted elliptical orbit plunges through the Milky Way's disk, sending ripples like stones dropped into a pond. These disturbances are strongest beneath the galactic plane, where Sagittarius leaves behind streams of stars, gas, and dark matter. its gravity stretches the lower half of the Milky Way, tugging on stars, including our Sun, and even affecting dark matter distribution. Other satellites, like the Large and Small Magellanic Clouds, orbit below the southern disk. Their combined gravity drags dark matter and bends the Milky Way's outer ring, creating a gravitational wake. This uneven pull causes vertical waves through the stars and gas, a motion sometimes called galactic seismology. Recent data from the Gaia satellite, which maps the positions and motions of over 1 billion stars, confirms that these vertical waves rise and fall over thousands of light years, proving the disk is vibrating in response to ancient tidal impacts from below. These tidal forces may even influence life on Earth. Some researchers suggest that as the solar system moves up and down through the galactic plane, a cycle taking roughly 60 to 70 million years, it passes through denser regions of cosmic dust or experiences increased comet activity. This could coincide with mass extinction events, hinting at a subtle but real link between galactic tides and terrestrial history. The southern part of the Milky Way, pulled and warped by tidal forces, bends differently than the northern half. These forces do more than distort the disk. They reshape the galaxy, cluster dark matter, ripple gas clouds, and shift stars. Even the solar system is caught in this dance. Far from being empty, the vertical frontier below the galactic plane is full of invisible forces, unseen structures, and possibly the next great discoveries in astrophysics. Black holes have always been the monsters of the universe's tales. They are dark, bottomless pits that crush stars, twist time itself, and swallow anything that drifts too close. But what if black holes are not the ultimate story of extreme gravity? What if something even stranger is hiding in the shadows? Something that challenges everything we know about space, time, and even the idea of death. That something is the Gravastar. Unlike a black hole, it does not have a singularity at its centre. Instead, its heart is filled with dark energy, surrounded by a shell made of bizarre, exotic matter. There is no event horizon, no point of no return, only a strange throbbing core that might keep the information black holes seem to erase. Could Gravastars be what black holes eventually turn into, or perhaps what they have been all along? Gravastars are one of the strangest and most fascinating ideas ever to come out of modern physics. The word itself is short for gravitational vacuum star, and just hearing the name makes you think of something mysterious and cosmic. They are often brought up in conversations about black holes, because on the surface they seem to be a possible alternative to them. To really understand what a gravastar is, we have to go back to the long history of black holes themselves, because black holes have always been the giants in the world of cosmic mysteries. They are the monsters of space, regions so dense and so powerful that not even light itself can get away from them once it falls in. For centuries, scientists and philosophers alike have wondered what happens to matter when gravity crushes it beyond recognition, and gravastars are one possible answer to that question. The idea of gravastars came into being in the early 2000s, when physicists began questioning whether black holes were the only possible outcome of a star collapsing under its own gravity. For a long time, the black hole seemed like the unavoidable final chapter of a massive star's life. When a star many times heavier than our Sun runs out of nuclear fuel, it can no longer push back against the crushing force of its own gravity. The outer layers fall inward, the core implodes, and if the star is heavy enough, not even the formation of a neutron star can stop the collapse. The result, according to traditional physics, is a black hole. This is a place where gravity is so extreme that space and time themselves break down. At the centre lies the so-called singularity, a point of infinite density where the known laws of physics simply stop working. For many scientists, that conclusion always felt unsatisfying. How could the laws of nature that work everywhere else in the universe suddenly fail here? Shouldn't there be a different explanation? One that avoids the uncomfortable infinity at the heart of a singularity? That is where gravastars enter the picture. A gravastar is proposed as an object that looks very much like a black hole from the outside, but is very different on the inside. Instead of having a singularity hidden behind an event horizon, a gravastar would have something more exotic, something that might even solve some of the biggest puzzles in physics. The key idea is that when a star collapses, it may not always form a singularity. Instead, under some conditions, the collapse could stop just short of creating a black hole. The matter of the star could be transformed into something entirely new, forming a shell around a strange kind of space filled not with matter, but with vacuum energy. This is a strange form of energy that physicists believe fills the universe itself, tied to the idea of dark energy that pushes the cosmos to expand faster and faster. Inside a Gravastar, this vacuum energy would balance the crushing force of gravity, holding the object stable and preventing a singularity from ever forming. From the outside to telescopes and detectors, a Gravastar would look so similar to a black hole that it would be almost impossible to tell them apart. But if you could peel it open and look inside, you would see something radically different. To grasp how radical this difference is, we have to step back and look at what makes a black hole so special. A black hole is defined by its event horizon, the invisible boundary that marks the point of no return. Cross it, and you are trapped forever. No signal, no particle, not even light, can escape once it passes this horizon. At the centre of this trap lies the singularity, a point where gravity has crushed matter to zero size and infinite density. The laws of physics as we know them no longer make sense here. That has always been the troubling part of black hole theory. Scientists generally dislike infinities because they signal that our theories are incomplete. A Gravastar avoids this problem by removing the singularity altogether. Instead of an infinite point, there is a bubble of vacuum energy. Instead of an event horizon that traps light forever, there may be a kind of thin shell of matter, incredibly dense and strange, that holds the structure together. In other words, a Gravastar would mimic a black hole's appearance without actually being one. This difference is not just a small technical point. It has enormous consequences for how we think about the universe. If Gravastars are real, they would solve what is called the information paradox of black holes. According to quantum physics, information about matter cannot be destroyed, but black holes seem to erase information when they swallow it. If Gravastars exist, the information might not be destroyed at all, but instead stored in their shell or somehow preserved in the vacuum energy interior. This could reconcile two of the biggest frameworks in science: general relativity, which describes gravity and the large-scale universe, and quantum mechanics, which rules the tiny world of atoms and particles. The two have long clashed when it comes to black holes, but Gravastars might offer a bridge. The concept of Gravastars first gained attention around the year 2001, when physicists Powell Mazur and Emil Motola suggested them as an alternative to black holes. They argued that instead of collapsing into a singularity, matter might undergo a phase transition, much like water freezing into ice, but on a cosmic scale. In this transition, the interior of the collapsing star would become a kind of vacuum state, while the outer layers would form an ultra-dense shell. This structure would be stable and could mimic the external gravitational pull of a black hole so closely that astronomers might not be able to tell the difference. To an outside observer, light bending around the object, matter swirling into it, and even the way it influences nearby stars would look almost identical to a black hole. But beneath the surface, the physics would be entirely different. Explaining this in simple terms, you could think of a Gravastar as a cosmic trickster. From a distance, it wears the mask of a black hole, pulling in matter and light with nearly the same strength. But inside, it hides something else, something less violent, something that does not involve ripping the fabric of the universe into a singular point. The vacuum energy at its core acts like a spring pushing outward, balancing the inward pull of gravity. The result is an object that sits right at the edge of becoming a black hole but never quite crosses that final step. It is a balancing act, a stalemate between forces that would otherwise lead to total collapse. One of the reasons Gravastars are so intriguing is that they might explain some puzzling observations in astronomy. Black holes are thought to power quasars, the extremely bright centres of distant galaxies, as well as many of the X-ray sources we see in the sky. But in some cases, the data does not perfectly match what black hole models predict. Gravastars could offer an explanation, because they might behave slightly differently, especially when it comes to how they radiate energy and how they interact with matter falling toward them. For example, when matter falls onto a Gravastar's shell, it might create bursts of energy that differ from those produced by a black hole's accretion disk. Detecting such differences would be one of the ways to test if Gravastars exist. Still, it is important to be clear that Gravastars are, as of now, a theoretical idea. No one has yet found definitive evidence of one. Every candidate object we know that looks like a black hole could either truly be a black hole or in theory a Gravastar. Our instruments are not yet precise enough to distinguish between the two in most cases. The real challenge is that from the outside they behave so similarly. Both have extreme gravitational pulls, both can bend light dramatically, and both can anchor powerful cosmic jets. The only way to tell them apart would be to study tiny details in the way they emit radiation, or perhaps in the gravitational waves they produce when they merge. Some scientists have even suggested that future detectors might catch a subtle echo in gravitational wave signals that would reveal a Gravastar instead of a true black hole. These echoes would come from waves bouncing off the Gravastar's surface, instead of being swallowed by an event horizon. The idea of Gravastars also sparks the imagination when we think about the broader universe. If Gravastars exist, they could be scattered throughout galaxies, quietly masquerading as black holes. They could lurk at the centers of galaxies driving cosmic evolution, or they could be hiding in binary systems, feeding off companion stars just like black holes do. Even the giant object at the center of our Milky Way, known as Sagittarius A star, could, in principle, be a Gravastar instead of a black hole. We simply do not know for sure yet. The differences between Gravastars and black holes also highlight the way science constantly evolves. For most of the 20th century, black holes were themselves only theoretical. When Albert Einstein's equations first hinted at them in the early 1900s, even Einstein himself doubted they could be real. They sounded too extreme, too strange, like a mathematical curiosity rather than a real object. It was only decades later, when evidence piled up, that black holes became accepted as genuine parts of the cosmos. Today, we not only believe in them, we have even imaged one directly with the Event Horizon Telescope in the year 2019. The glowing ring of matter around the supermassive black hole in the galaxy M87 was one of the most dramatic confirmations of Einstein's theory ever seen. But just as black holes went from speculation to observation, Gravastars might follow a similar path. What seems strange and exotic today could turn out to be part of the real universe tomorrow. Another way to look at Gravastars is to consider how they challenge our sense of extremes. Black holes are often described as the ultimate endpoints of matter. Nothing can escape them, nothing survives inside them, and time itself is distorted beyond recognition. Gravastars, however, suggest that maybe nature has another trick up its sleeve, a way of avoiding the harshness of singularities while still creating objects of immense power. They remind us that the universe is not always as simple as the first explanations we come up with. There could be layers of complexity we have not yet discovered, and Gravastars might be one of those hidden layers. The possibility of Gravastars also touches on the fate of information, one of the deepest puzzles in physics. If black holes truly destroy information, that would break one of the fundamental rules of quantum mechanics. Scientists like Stephen Hawking wrestled with this paradox for decades, and it led to some of the most heated debates in theoretical physics. Gravastars neatly sidestep the issue by providing a place for information to be stored or preserved, making them very attractive to physicists looking for consistency. In this sense, Gravastars are not just about stars and collapse, they are about the very foundations of how reality works. On a more imaginative level, thinking about Gravastars raises philosophical questions as well. What does it mean if the most terrifying objects in the universe, the black holes that have haunted science fiction and science fact alike, are not the final word? What if they are shadows of something deeper, a hint at new physics waiting to be uncovered? Gravastars suggest that the universe might be playing a cosmic trick on us, showing us one face while hiding another. They invite us to look closer, to question what we think we know, and to keep pushing the boundaries of discovery. So, to define the concept as simply as possible, a Gravastar is a hypothetical object that forms when a collapsing star stops just short of becoming a black hole. Instead of forming a singularity in an event horizon, it forms a shell of exotic matter surrounding a core filled with vacuum energy. From the outside, it acts almost exactly like a black hole, but on the inside, it is something else entirely. The difference between the two is like the difference between a locked room with no exit and a sealed bubble filled with strange light. Both are mysterious, but one hides a dead end, while the other hides something new. Gravastars remain a theory, a possibility rather than a proven reality. The story of the Gravastar is one of those rare moments in science where imagination, boldness, and a willingness to question the most accepted ideas all came together. To understand how this idea was born, we need to step back into the late 20th century, a time when the study of black holes was already booming with discoveries and debates. Black holes had moved from being strange mathematical solutions written on paper in the early years of Albert Einstein's theory of general relativity to being treated as real, physical objects scattered across the universe. By the end of the 20th century, astronomers had already gathered strong evidence that black holes were not just abstract theories, but true celestial monsters. They found stars moving around invisible companions. They detected enormous bursts of X-rays coming from regions where matter was falling into invisible pits, and they saw signs of huge gravitational forces bending space itself. To most of the scientific world, it seemed beyond doubt that black holes were real. But science is never as simple as everyone agreeing on one neat answer. In fact, it thrives most when people dare to question the obvious truths. And this is where the story of the Gravastar begins. In the year 2001, two physicists, Paul O. Mazur from the University of South Carolina and Emil Mottola from the Los Alamos National Laboratory, put forward a new and daring idea. They proposed that what astronomers had been calling black holes might not be black holes at all. Instead, these terrifying objects might be something stranger, something that had never been imagined before, a Gravastar. The name Gravastar itself is short for gravitational vacuum star. It sounds almost poetic, yet also mysterious. What Mazur and Mottola were really suggesting was that nature might be playing a trick on us. The universe might be showing us something that looks like a black hole, behaves like a black hole, and even fools us into thinking it is one. But at its core, it is actually a very different kind of object. To appreciate how daring this idea was, it helps to know just how deeply rooted the belief in black holes had become. From the 1960s onward, physicists like John Wheeler, Roger Penrose, and Stephen Hawking had made the concept of black holes central to modern astrophysics. By the 1990s, black holes had almost become household names, appearing in science books, movies, and even children's stories. They were symbols of the most extreme and unshakable laws of the cosmos. Yet Mazur and Mottola were not satisfied with the black hole picture. They looked closely at the mathematics of Einstein's general relativity and began to see problems that made them uneasy. A black hole, as normally described, has at its centre what is called a singularity, a point where density and gravity become infinite. But infinity in physics is usually a sign that something is wrong, a signal that our equations have gone beyond their proper limits. The singularity at the heart of a black hole is not really a physical object, but rather a breakdown of our theories. And Mazur and Mottola asked themselves, should we really believe that nature allows such a breakdown? Should we accept that physics ends at the core of a black hole, or should we search for another explanation? Their answer was bold. They suggested that instead of collapsing into a singularity, a star that dies in extreme gravity might take on another form. In their model, the collapsing matter does not crush itself into an infinitely small point, but instead undergoes a kind of phase transition, almost like water freezing into ice, or steam condensing into liquid. In this process, the inside of the star becomes a strange state of matter, dominated not by normal particles, but by what physicists call vacuum energy. This energy is linked to the idea of dark energy, the mysterious force that drives the expansion of the universe. What Mazur and Mottola proposed was that the core of a collapsed star could be filled with this exotic energy, forming a bubble of repulsive pressure that prevents the singularity from ever forming. Around this bubble there would be a very thin shell of extremely dense matter, almost like a cosmic skin holding the structure together. To an outside observer, this Gravastar would look very much like a black hole. Light and matter falling toward it would disappear from view, time would seem to slow near its edge, and its gravity would be almost impossible to resist. But unlike a black hole, a Gravastar would not have a singularity, and would not contain an event horizon in the same way. Instead, it would have a surface, an actual boundary, although this surface would be so extreme that it would be almost impossible to detect directly. This was the birth of the Gravastar theory, a bold proposal in the year 2001 by two physicists who dared to challenge the most feared object in the universe. It was more than just a new model. It was a statement that our understanding of gravity, of energy, and of the deep structure of space and time might still be incomplete. The timing of their idea is also worth noting. The early 2000s were years when cosmology was going through a revolution. In the year 1998, astronomers had discovered that the expansion of the universe was not slowing down as everyone had expected, but speeding up. This shocking finding led to the idea of dark energy, a mysterious force that seemed to make up most of the cosmos. Suddenly, the concept of exotic forms of energy was no longer just abstract speculation. It was real science, supported by observation. Mazur and Mottola were therefore proposing Gravastars at exactly the moment when physicists were beginning to take seriously the idea that vacuum energy and dark energy might play huge roles in the universe. It is important to understand the personalities behind this theory as well. Pavel Mazur was known for his bold thinking and his willingness to explore unorthodox ideas. Emil Mottola had a background in theoretical physics and had worked on problems in quantum field theory and gravity. Both of them were respected scientists, yet they were not afraid to walk a path that many of their colleagues might have considered too risky. In fact, when they first published their papers on Gravastars, the reaction was mixed. Some physicists admired the creativity and daring of the idea, while others dismissed it as too speculative, too strange, or even unnecessary. Why replace black holes with something so complicated, many asked, when black holes already seem to explain the observation so well? But science is not about always finding the quickest or simplest answer. It is about exploring possibilities, even if they seem strange at first. The Gravastar idea stood as a reminder that black holes, for all their fame, were still not completely understood. After all, nobody had ever truly seen a black hole itself. What astronomers had observed were the effects around black holes, the motion of stars, the glow of hot gas, the bending of light, but never the object directly. And if appearances could be deceiving, then maybe Gravastars were hiding in plain sight. In the years that followed their proposal, the Gravastar idea continued to stir debate. Other physicists began to explore its consequences, asking whether Gravastars could really form in nature, how they would evolve, and whether they could be distinguished from black holes by observations. Some tried to connect Gravastars with other exotic objects, such as boson stars or dark energy stars, exploring whether these might all be different sides of the same coin. In this way, the Gravastar theory became part of a larger conversation about what really happens when gravity reaches its most extreme limits. The birth of the Gravastar idea, then, was not just about two scientists writing a paper. It was about a turning point in how we think about the universe. It was about daring to ask whether the most terrifying monsters in the cosmos might actually be illusions, disguises hiding something even stranger. It was about questioning whether the universe is still holding secrets that we have not yet unwrapped. Looking back, it is fascinating to think that this all began in the early years of the 21st century, when humanity was just beginning to map the universe with new telescopes, satellites, and instruments capable of peering deeper into space than ever before. The Gravastar was born in that atmosphere of discovery, uncertainty, and wonder. And while the debate about Gravastars versus black holes is still far from settled, the very fact that the idea exists reminds us of the essence of science, that every answer opens the door to new questions, and that even the darkest corners of the cosmos might not be what they seem. The physics behind Gravastars is one of the most fascinating areas of modern thought in astrophysics and theoretical physics. It combines the deep ideas of Albert Einstein's general relativity with the strange and almost ghostly concept of vacuum energy, which is linked to quantum mechanics and the structure of space itself. To understand Gravastars, one must first stretch the mind to accept realities that at first sound impossible, because they live at the edge of our knowledge of the universe, where the familiar laws of nature seem to bend and even break. Gravastars were proposed as alternatives to black holes, and the reasoning behind them is built on both the known rules of gravity and the less understood but equally important rules of quantum fields and energy. By exploring how general relativity and vacuum energy meet, the strange physics of Gravastars begins to unfold. General relativity is the key to understanding the gravity that governs stars, galaxies, planets, and the universe itself. Before Einstein, gravity was explained by Isaac Newton as a force between objects that had mass, and for centuries this explanation worked well. But Einstein showed in the early years of the 20th century that gravity was not a force in the usual sense, but rather the result of the bending of space and time. When something heavy like a star or planet exists, it curves the very fabric of space-time around it, and other objects move along those curves. This is why Earth circles the Sun, not because it is being pulled by an invisible string, but because the Sun bends space-time so that Earth follows a curved path that looks like an orbit. This idea becomes even stranger when we talk about extreme objects like neutron stars and black holes. These are the corpses of stars that used up their nuclear fuel and collapsed under their own gravity. A neutron star is already unimaginably dense, with the mass of more than one sun squeezed into a ball only about 20 kilometers across. But when the collapse cannot be stopped, the theory of general relativity predicts that the star shrinks into a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. The edge of this region is called the event horizon. Once anything crosses it, it is lost forever. The math of relativity says that at the very centre of a black hole lies a singularity, a point of infinite density where the known laws of physics break down. The idea of a singularity is both powerful and troubling. Physicists often take it as a sign that our understanding is incomplete. Infinite density is not something nature should allow so easily. This is where the idea of Gravastars enters. Gravastars, short for gravitational vacuum stars, were suggested as objects that look from the outside almost exactly like black holes, but without the troubling singularity at their centre. Instead of collapsing all the way into a point, the matter of the star would trigger a strange transition in space-time itself, producing a core filled with vacuum energy. This idea offers a way to use the mathematics of general relativity while avoiding the puzzle of infinities. Vacuum energy is one of the strangest concepts in physics, and to understand Gravastars it must be explained clearly. Normally, people think of a vacuum as empty space, a void with nothing in it. But quantum mechanics tells us that even the emptiest space is not truly empty. It seethes with invisible activity, with particles and antiparticles popping in and out of existence for the tiniest fractions of a second. This restless background is called quantum fluctuations, and the energy tied to it is called vacuum energy. It is a kind of latent power hidden within space itself, and although it cannot be directly seen, its effects are very real. One famous example of vacuum energy is the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force, not because of any electrical charge, but because the vacuum between them is altered by the plate's presence. This shows that empty space has measurable physical effects. On the larger scale, vacuum energy is also thought to be linked to dark energy, the mysterious force that is pushing the universe to expand faster and faster. Now, when we take general relativity and add in the possibility of vacuum energy, a new picture forms. Instead of a collapsing star shrinking into a singularity, what if the collapse reached a point where space-time itself changed state, like water freezing into ice? The inside of the star could transform into a bubble of vacuum energy, a region of space where negative pressure counteracts the pull of gravity. This bubble would be surrounded by an incredibly thin but extremely dense shell of matter. The shell would act like a boundary, holding the vacuum core inside and balancing the gravitational pull from outside. The result would be a Gravastar. From far away, a Gravastar would be nearly indistinguishable from a black hole. It would have an enormous gravitational field, and light passing near it would be bent in almost the same way. To an outside observer, it would appear dark and menacing, because the shell would absorb or trap nearly all light. But at its heart, instead of a singularity, there would be a region filled with vacuum energy, perfectly smooth and free of infinities. This resolves one of the biggest problems with black holes, the issue of the singularity. Another reason Gravastars are interesting is because of the way they connect with the problem of information. Black holes famously raise the question of whether information can be lost. According to quantum mechanics, information about the state of particles can never be destroyed. But when things fall into a black hole and cross the event horizon, they seem to vanish forever. Stephen Hawking showed that black holes can slowly evaporate by releasing what is now called Hawking radiation, but even then the fate of the information remains unclear. Gravastars might offer a way around this paradox. Since they do not have a singularity, and since their surface is a real physical shell rather than a point of no return, it is possible that information falling into a gravastar could be stored in or interact with this shell, avoiding the deep paradox of information loss. To make this clearer, one can think of the difference between a soap bubble and a solid ball. A black hole is like a ball with a dark and inaccessible core. A gravastar, on the other hand, is more like a bubble, with a thin but strong skin surrounding a strange interior. The skin, or shell, does all the work of holding things together, while the inside is an exotic vacuum state. Of course, the mathematics behind this is complex. General relativity provides the equations to describe how mass and energy curve spacetime. The vacuum energy provides a term in these equations that represents a constant negative pressure. By balancing these effects, physicists can construct theoretical solutions that describe gravastars. One of the key ideas is that the negative pressure inside the gravastar acts in opposition to the normal pressure of matter trying to collapse. In this way, the inward pull of gravity is resisted, and equilibrium is reached. The negative pressure of vacuum energy is crucial here. Unlike ordinary matter or radiation, which exert positive pressure and add to gravitational collapse, vacuum energy pushes outward. It is the same kind of effect that causes the expansion of the universe to accelerate. Inside a gravastar, this pressure balances the star's gravity perfectly at the shell. Without it, the collapse would continue without end. Another fascinating aspect of gravastars is the possibility that they could form naturally in the universe. If a massive star collapses, and under certain conditions the collapse causes a transition of spacetime into this exotic vacuum state, then a gravastar could form instead of a black hole. This means that some of the objects we think are black holes might in fact be gravastars. Since from the outside they look so similar, it is extremely difficult to tell the difference. But careful studies of gravitational waves, or perhaps the detailed radiation coming from the region around such objects, might one day reveal a clue. In 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, first detected gravitational waves from merging black holes, some physicists wondered if they could also detect the subtle signature of merging gravastars. The ripples in spacetime from such collisions might differ in very small but important ways. For example, if a gravastar lacks a true event horizon, the waves might echo differently after the collision. Some scientists even search for these echoes in the data, though the results are not yet clear. If one day these signals are found, it could point to the existence of gravastars and change our whole understanding of cosmic collapse. The role of vacuum energy in gravastars also links them to cosmology. The same strange energy that fills their interior is also thought to drive the expansion of the entire universe. It is remarkable to think that the same force shaping the fate of stars could also be shaping the fate of the cosmos itself. In fact, the equations describing a gravastar's interior are very similar to those describing the universe during its early moments of inflation, when vacuum energy made space expand at an almost unbelievable rate. This connection hints that gravastars are not just exotic star remnants, but perhaps windows into the deepest laws of physics. There are still many open questions. Some physicists argue that gravastars are elegant in theory, but may never exist in reality, because the conditions needed to form them may be too specific. Others think that nature often surprises us, and that the universe may prefer gravastars over singularities because they avoid infinities and paradoxes. It is possible that with more data from gravitational waves, or with sharper images from telescopes like the Event Horizon Telescope, we will one day be able to tell whether the supermassive dark objects at the centers of galaxies are black holes or gravastars. When one reflects on the physics behind gravastars, it is clear that they are more than just alternatives to black holes. They are a meeting place of two of the greatest theories in science, general relativity and quantum physics. General relativity provides the rules for how spacetime bends and collapses under gravity, while quantum theory provides the idea of vacuum energy, the restless sea of energy that never goes away. Gravastars exist in the imagination of scientists at the point where these two worlds collide. To explore gravastars is to explore both the grand scale of the cosmos and the smallest fluctuations of the quantum vacuum. It requires thinking of stars not as simple balls of matter, but as stages where the very laws of physics perform a complex play. If gravastars exist, they are not just dead stars. They are monuments to the hidden power of space itself, objects that hide a bubble of the universe's deepest energy behind a thin, dense shell. Black holes have for many decades been seen as the ultimate monsters of the universe, the endpoint of gravity taken to its most terrifying extreme. They are the places where space and time collapse into something so warped that nothing, not even light, can escape their grasp. Gravastars, on the other hand, are a far stranger and more subtle idea. Proposed not as a fantasy, but as a serious alternative to black holes. To understand the ongoing debate between black holes and gravastars, one must not only explore their similarities and differences, but also the reasons why scientists still do not fully agree on which of these cosmic objects may actually exist. In order to do this, it is important to begin by carefully unfolding what makes a black hole what it is, what a gravastar is supposed to be, and why the two are sometimes so difficult to tell apart yet so profoundly different in their nature. A black hole is born when a very massive star runs out of fuel. The nuclear reactions that once fought against gravity's inward pull cease, and the star collapses under its own weight. If the star is massive enough, several times the mass of our Sun, then nothing can stop the collapse. The star is crushed to an infinitely dense point called a singularity, wrapped inside an event horizon. The event horizon is the ultimate boundary, the surface around the black hole beyond which nothing can return. To an outside observer, the black hole looks like a region of space where light disappears, as though space itself has been torn into a dark well. Time slows down near its surface, and physics itself reaches the edges of what we understand. This picture of the black hole comes directly from Albert Einstein's general theory of relativity, published in the year 1915, and ever since then astronomers and physicists have been trying to understand the exact details of these fascinating but frightening objects. A gravastar, whose name comes from the phrase gravitational vacuum star, is not as well known but is in many ways just as mind-bending. The concept was proposed in the early years of the 21st century by physicists Pavel Mazur and Emil Mottola. They asked a bold question: what if what we call black holes are not black holes at all, but something else entirely, something that only looks like a black hole from the outside? In their theory, when a star collapses under its own weight, it does not form a singularity and an event horizon. Instead, the collapse stops just short of those extreme conditions. A gravastar, in their description, has a very thin outer shell made of extremely dense material, but inside that shell, rather than a singularity, is a core filled with exotic energy that has negative pressure, something like the energy that scientists believe is causing the expansion of the universe. This inner vacuum energy balances the outward push against the inward pull of gravity, creating a stable object that looks, to a distant observer, almost exactly like a black hole. But it is not one. There is no singularity at the center, and there is no event horizon. That means that information and energy are not lost forever inside it, and this has enormous consequences for physics. When comparing black holes and gravastars, one can begin with their similarities. Both are born from the collapse of very massive stars, and both are incredibly compact. Their gravitational pull is so intense that they curve the paths of light and distort the geometry of space around them. For an astronomer observing them from far away, both black holes and gravastars would look like dark, compact objects surrounded by swirling matter, with gas and dust heating up as it falls toward them and shining in X-rays and radio waves. Both can power quasars and active galactic nuclei, some of the brightest beacons in the universe. Both can also produce gravitational waves when they collide with one another, sending ripples through space-time that can be detected here on Earth. In other words, black holes and gravastars are observationally very hard to tell apart. For all practical purposes, if one were to look at the center of our own Milky Way galaxy, where a dark mass 4 million times the mass of our Sun sits, one could not be sure whether it is a black hole or a gravastar. The observations would look nearly the same, but once one looks deeper, the differences between the two become immense. A black hole has an event horizon, a point of no return. A gravastar does not. A black hole hides a singularity, where density and curvature go to infinity, while a gravastar replaces that nightmare with a strange but manageable core of vacuum energy. A black hole eats everything that comes too close, trapping light and information forever. A gravastar may appear to swallow matter, but in theory, because there is no horizon, that matter might be able to interact with the shell or even leave in some form. A black hole violates many of the usual principles of physics, such as the preservation of information, leading to what is known as the information paradox. A Gravastar, in contrast, might offer a way out of this paradox by avoiding the singularity altogether. In essence, a Gravastar is an attempt to heal the contradictions that arise when black holes are pushed to their logical extreme. Scientists debate fiercely between these two ideas because each has strengths and weaknesses. Black holes are supported by a mountain of evidence. Astronomers have observed stars orbiting around invisible massive companions, moving so fast that the only possible explanation is the presence of a black hole. They have watched X-rays being emitted as gas falls into compact objects. They have detected gravitational waves from what appear to be the mergers of black holes. Most striking of all, in the year 2019, the Event Horizon Telescope collaboration unveiled the very first image of a black hole's shadow, captured at the heart of the galaxy M87. The dark circular silhouette with a glowing ring of hot gas around it matched exactly what general relativity predicts for a black hole. All of this evidence strongly supports the idea that black holes exist. On the other hand, Gravastars are attractive because they solve some of the biggest puzzles that black holes create. The biggest of these puzzles is the information paradox. According to quantum physics, information can never be destroyed. But if black holes swallow everything that falls into them and hide it behind an event horizon, then information seems to be lost forever. Stephen Hawking famously showed in the 1970s that black holes emit radiation, now called Hawking radiation, and can eventually evaporate. But this process appears to erase information in a way that quantum theory forbids. Gravastars, by avoiding event horizons and singularities, might provide a way for information to remain accessible in some form. The exotic matter in the shell and the vacuum energy inside could make the laws of physics consistent once again. For this reason, Gravastars are an elegant theoretical solution to problems that black holes cannot solve. The debate grows even more intense when one considers how hard it is to distinguish between black holes and Gravastars by observation. Both would look like dark spheres surrounded by hot gas. Both would bend light around them, producing the so-called shadow captured by the Event Horizon Telescope. Both would merge with partners to send out gravitational waves, yet subtle differences might exist. For example, the surface of a Gravastar, being a real shell rather than an event horizon, might reflect some of the energy that falls on it. This could produce faint echoes in the gravitational waves, or tiny signals in electromagnetic radiation that black holes would not produce. Some researchers have looked for these echoes in the data from gravitational wave detectors like LIGO and Virgo. So far, the evidence is not conclusive, but the possibility remains open. If even one of these signals were detected, it could mean that what we thought were black holes are actually Gravastars. It is also worth noting that Gravastars, though elegant, face their own challenges. The idea requires exotic matter and vacuum energy arranged in very particular ways. Whether such structures can form naturally in the collapse of a star is not clear. The equations that describe Gravastars work well on paper, but translating them into realistic astrophysical conditions is much harder. Nature may not provide the precise ingredients needed for their creation. Black holes, by contrast, are a natural outcome of stellar collapse according to Einstein's relativity, requiring no exotic substances. They are the straightforward, if frightening, prediction of gravity taken to its extreme. For many physicists, this makes them the more believable option. The story of black holes versus Gravastars is not just about astronomy, but about the very foundations of physics. If black holes truly exist with singularities and horizons, then our understanding of space, time, and quantum mechanics is incomplete. If Gravastars or some other alternative exists, then the universe may be more subtle than we think, hiding solutions to problems that currently baffle us. Either way, the debate pushes science forward. New observations, whether of shadows of supermassive objects or of the delicate ripples of space-time, may one day reveal which of these strange ideas is correct. Until then, the question remains open, and the cosmic contest between black holes and Gravastars continues. The similarities between the two remain a constant source of confusion for observers. A black hole and a Gravastar would both create accretion disks, rings of superheated matter spinning around them at incredible speeds. These disks would shine in X-rays and radio waves, flickering as clumps of gas spiral inward. Jets of particles could also shoot out from near their poles, powered by magnetic fields twisting around the swirling material. To a telescope on Earth, such jets would look the same whether they come from a black hole or a Gravastar. Similarly, when two of these objects spiral toward each other, the gravitational waves they emit would have nearly identical patterns at first. Only in the final moments of merger might subtle differences emerge, like faint echoes or delayed signals. Detecting those differences requires instruments of extraordinary sensitivity, instruments that are only now reaching the needed precision. Another similarity lies in how both ideas challenge human imagination. Black holes already stretch the limits of understanding with their infinite densities and warping of time. Gravastars add a different kind of strangeness, replacing infinities with vacuum energy and shells of exotic matter. Both are reminders that the universe is far stranger than our everyday experience suggests. Both force physicists to ask deep questions about what space and time really are, what happens at the edges of knowledge, and whether reality might hold answers that seem absurd until proven true. In this way, even if Gravastars do not turn out to exist, their very proposal has enriched the discussion and deepened the search for truth. One of the reasons scientists debate so strongly between black holes and Gravastars is that the answer matters far beyond astronomy. If black holes exist as described in relativity, then at their heart lies a singularity, a place where the known laws of physics collapse. That would mean that our theories are incomplete and that new physics is waiting to be discovered. If Gravastars exist instead, then they may point the way to uniting relativity with quantum mechanics, since they avoid singularities while still allowing strong gravity. This is why debates about these objects often spill into discussions of string theory, quantum gravity, and the nature of dark energy. They are not just questions about stars collapsing in space. They are questions about the deepest structure of reality. The cultural impact of this debate should also not be ignored. Black holes have captured the imagination of the public for decades. They appear in novels, films, and countless works of art. They are symbols of mystery and terror, of the unknown swallowing everything. Gravastars are newer and less well known, but as the idea spreads, they may capture imaginations in a different way. They are not monsters, but strange survivors, stars transformed into objects filled with the same mysterious energy that drives the universe's expansion. To think that such things might exist makes the cosmos even richer and more mysterious. When scientists gather at conferences or write papers debating black holes versus Gravastars, the arguments are often technical, involving equations, simulations, and models of collapse. But beneath all of that lies something simple and human, the desire to know what is really out there. The universe has already surprised humanity countless times, from galaxies beyond the Milky Way to the expansion of space itself. It would not be shocking if the truth about black holes turned out to be stranger still, perhaps in the form of Gravastars or some other exotic alternative. This sense of wonder drives the debate just as much as the data do. To draw the picture fully, one can imagine the life cycle of a massive star leading to these possibilities. A star many times heavier than our Sun burns brightly for millions of years. When its fuel runs out, it collapses. If relativity rules without modification, the result is a black hole, dark and final. If instead new physics intervenes, the collapse halts and a Gravastar forms, strange and stable. In both cases, what remains is far beyond ordinary matter, far beyond human experience. The debate between black holes and Gravastars is, in many ways, the story of modern physics itself. Bold ideas, fierce arguments, astonishing observations, and above all, the humility to admit that we still do not know all the answers. Black holes remain the leading candidate, supported by decades of evidence. Gravastars remain a daring alternative, offering solutions to deep puzzles. The similarities between them make the task of distinguishing them challenging. The differences between them make the stakes of the debate enormous. As telescopes sharpen their gaze and detectors grow more sensitive, the universe itself will have the final word on which of these strange possibilities is real. Until then, the conversation continues, a cosmic argument that is as much about the nature of reality as it is about stars and space. The hollow star concept is one of the strangest and most thought-provoking ideas in modern astrophysics. At its heart lies a vision of a cosmic object that looks on the outside like a star that has collapsed under its own weight, yet on the inside hides something utterly unexpected. Instead of being a solid, crushing ball of matter or a bottomless pit like a black hole, this object is hollow, its core replaced by a vast, empty-seeming void. Scientists call this type of hypothetical object a Gravastar, short for gravitational vacuum star, and the thought of such a star challenges the way we usually think about the life and death of massive suns. To appreciate the hollow star idea, it helps to think first of what happens when a huge star runs out of fuel. In the normal story of astrophysics, when a star much larger than our Sun burns through its nuclear fuel, gravity takes over and squeezes it. If the star is heavy enough, nothing can stop this collapse, and the star shrinks into what we know as a black hole. Black holes have no surface in the usual sense. They have an event horizon, a one-way boundary beyond which nothing, not even light, can escape. Inside this horizon, matter is thought to be crushed into a point of infinite density, a singularity. This is the classic image that people know, a cosmic abyss that swallows everything. But the hollow star concept tells a different story. It suggests that, instead of falling into a singularity, matter might stop collapsing just before reaching that fate. At that point, something extraordinary happens. Space itself changes form, and the inside of the star is transformed into a region filled not with matter, but with a special kind of energy that behaves like the opposite of normal matter. This strange energy pushes outward instead of pulling inward. The result is that the middle of the star becomes hollow, like a bubble, and the outer layers form a thin, dense shell that traps the void inside. From the outside, such an object could look almost exactly like a black hole, but the inside would be nothing like it. The idea of a hollow star brings up images of a cosmic Russian doll. On the outside, a dark sphere that seems to hide a mystery, and on the inside, a bubble of emptiness that is not really empty but filled with something very exotic. The void-like interior of a Gravastar is not a vacuum like the space between the stars. It is thought to be a vacuum of a different kind, one that is bubbling with what scientists call dark energy or vacuum energy. Dark energy is the same mysterious force that astronomers believe is making the universe expand faster and faster. In the hollow star, this energy holds open the bubble at the core, preventing the crushing collapse that would otherwise form a black hole. To picture this more simply, think of blowing up a balloon. The air inside pushes outward, while the skin of the balloon holds it in. A Gravastar is like that balloon, but on a mind-bending scale. The thin outer shell of matter acts as the balloon's skin, while the interior is filled with a repulsive energy that pushes outward, keeping the shell from collapsing in. This balance creates stability where we would expect only doom. What makes this idea so fascinating is that it changes the story of stellar death into something far stranger. The hollow star would be an object where matter and energy meet in a delicate balance, creating a structure that is part star, part vacuum, and part mystery. If black holes are the monsters of the cosmos, pulling everything into a crushing singularity, then Gravastars are like tricksters, pretending to be black holes but secretly hiding a bubble of nothingness in their hearts. The shell of a Gravastar is another strange feature. Scientists describe it as being incredibly thin compared to the size of the whole object, but unimaginably dense. To give a sense of scale, the shell could be only a fraction of a millimeter thick, yet it would weigh as much as an entire star. This shell is where all the mass of the Gravastar resides. The inside void does not add weight in the usual sense, since it is not made of ordinary matter. Instead, the shell is the anchor that holds the entire structure together, like a cosmic eggshell around a bubble of vacuum energy. Now, what would it be like inside such a hollow star? If you could somehow enter the Gravastar without being destroyed, you would pass through the dense shell and find yourself in a region that seems empty, yet is far from ordinary. There would be no solid ground, no swirling gases, no blazing plasma like in a normal star. Instead, you would be surrounded by a strange, smooth nothingness that pushes outward with invisible pressure. Space itself would feel stretched and unnatural. Time would also behave differently, because the exotic energy in the void changes the way gravity and space-time interact. To an observer floating inside, the world might appear frozen, or distances might feel distorted. It would not be emptiness in the everyday sense. It would be more like stepping into a region of reality where the rules have been rewritten. The thought of a hollow star naturally leads to many questions. Could such objects really exist in the universe, or are they only mathematical possibilities? If they exist, how would we tell them apart from black holes, since from the outside both look almost identical? Scientists have tried to answer these questions by studying how light and matter behave near these objects. A black hole swallows everything beyond its horizon, but a gravastar might interact with its surroundings in subtler ways. For instance, when gas falls toward a black hole, it heats up and gives off radiation before crossing the horizon. In a gravastar, the presence of the shell and the strange void might change the pattern of this radiation. Detecting such differences could one day prove whether hollow stars are real. The concept of a hollow star also touches deep philosophical questions about the universe. If black holes are not the final fate of collapsed stars, and instead gravastars take their place, then the universe may be more diverse and surprising than we thought. The singularity of a black hole has always been a troubling idea, because it represents a breakdown of the laws of physics. By replacing the singularity with a bubble of vacuum energy, the hollow star concept offers a way to avoid that troubling infinity. In this sense, gravastars are not just strange stars, they are also attempts to heal the cracks in our theories of the cosmos. It is worth noting that the hollow interior of a gravastar is not a void in the sense of nothing at all, but more like a stage filled with invisible players. Quantum physics suggests that even the emptiest space is filled with fluctuations, tiny bursts of energy that pop in and out of existence. Inside a gravastar, these quantum effects could be magnified to cosmic proportions, turning the core into a seething sea of vacuum energy. This is why the gravastar's heart is sometimes described as a false vacuum, a state of space that is unstable compared to the normal vacuum we experience. The shell keeps this false vacuum contained, preventing it from spilling out into the rest of the universe. The scale of these objects is staggering. A gravastar formed from a star many times the size of the Sun could be only a few kilometers across, just like a black hole of similar mass. That means an object with the weight of several suns would be squeezed into a sphere no larger than a city. Within that tiny sphere lies the thin shell, holding in the hollow void. To imagine it in human terms, it would be like compressing the entire Earth into a ball the size of a marble and then hollowing out the inside. The density of the shell would be beyond anything we can imagine, far greater than even the core of a neutron star, which itself packs matter so tightly that a teaspoon would weigh billions of tons. The hollow star idea also sparks the imagination when we think about what might happen near its surface. If you are falling toward a black hole, once you cross the horizon, you are doomed. Nothing can escape. But with a gravastar, some theories suggest you might encounter the shell instead of vanishing into a singularity. Would you bounce off? Would you be absorbed and spread across the shell? Or would you pass through into the void and be lost in the strange vacuum inside? These questions show just how mysterious such objects remain. Some scientists have even suggested that the universe itself might resemble a kind of hollow star on the larger scale. Just as the interior of a gravastar is filled with vacuum energy that pushes outward, the cosmos we live in is expanding faster because of dark energy. This parallel makes the hollow star concept feel like a miniature model of the entire universe. In a sense, every gravastar could be seen as a tiny universe trapped inside a shell, mirroring the larger cosmos outside. The hollow star also connects to the human fascination with hidden spaces. Throughout history, people have imagined caves, chambers, and secret worlds hidden beneath the surface of the Earth. The Gravastar is like the cosmic version of these myths, a star that looks solid and impenetrable, but that hides a hollow interior filled with a different reality. Instead of rock or fire, its hidden chamber contains the very fabric of space in a different state. One of the reasons scientists take the hollow star idea seriously is that it offers a possible answer to long-standing puzzles about black holes. For example, the so-called information paradox arises from the question of what happens to information that falls into a black hole. According to quantum physics, information should never be destroyed, but a black hole seems to erase it forever. A gravastar, with its shell and hollow core, might provide a way to store or release this information without breaking the rules of physics. The void inside could act as a kind of cosmic vault, where information is preserved in a form we do not yet understand. Exotic matter shells are one of the strangest and most puzzling ideas in modern astrophysics. and they are at the very heart of the theory of Gravastars. A Gravastar, short for gravitational vacuum star, is thought to be an alternative to black holes, where a black hole is described as a region of space where gravity has crushed matter down so tightly that nothing, not even light, can escape. A Gravastar is built on a very different idea. Instead of being a bottomless pit of collapse, it is thought of as a bubble of space. Inside this bubble is not normal matter at all, but a strange form of vacuum energy, and surrounding it is a thin but incredibly powerful shell made of something that does not exist anywhere we can easily find or touch. This is what scientists call exotic matter. The shell of exotic matter is the key feature that holds the entire Gravastar together, separating the eerie interior from the outside universe and giving this hypothetical object its unique identity. Exotic matter is not the same as ordinary matter that makes up stars, planets, and people. Ordinary matter obeys familiar rules. It has positive mass, it pulls things toward it with gravity, and it resists being squeezed. Exotic matter, by contrast, is defined by its ability to break those rules. One of its most important qualities is that it can have negative pressure, or in some cases even negative energy density. That sounds impossible at first, but in physics it simply means that instead of pulling things in as gravity usually does, exotic matter can push outward. It is this pushing effect that makes exotic matter so valuable in theoretical models. For example, wormholes, which are shortcuts through space-time often described in science fiction, could only stay open if exotic matter lined their throats. In the same way, the Gravastar would only be stable if its outer layer consisted of exotic matter that pushes outward, perfectly balancing the inward pull of gravity from the material outside. The idea of the exotic matter shell is that it acts like a cosmic barrier. On one side of the shell lies the bizarre vacuum energy interior, a region where space itself is filled with a strange kind of energy that behaves differently from normal material. On the other side lies the rest of the universe, with stars, gas, dust, and radiation behaving as usual. Without the shell, the vacuum energy would not be able to remain in place. It would either expand uncontrollably, like the rapid inflation thought to have occurred in the earliest moments of the universe, or it would collapse inward. The exotic matter shell is therefore the balancing point, the firm but flexible skin of the Gravastar that keeps the whole structure intact. To understand why this shell is so mysterious, it helps to think about how unusual it is for physics to allow matter with negative pressure. In our daily experience, pressure is always positive. When you pump air into a tyre, the air pushes outward against the rubber. When you press on a sponge, the sponge resists the squeezing. Negative pressure is the reverse. It is not something we can create with air or water or solids. But in cosmology, negative pressure has been suggested to exist in the form of dark energy, the invisible force that is believed to be pushing the universe to expand faster and faster. Exotic matter in the shell of a Gravastar would work in a similar way, but in a much more concentrated and extreme form. One way to describe the exotic shell is to think of it as a membrane with impossible strength. It is unimaginably thin compared to the size of the whole Gravastar, so thin that it could be smaller than the thickness of a human hair when scaled to cosmic dimensions. Yet within that tiny space it carries all the tension needed to resist collapse. If a Gravastar were the size of a star like our Sun, the shell would be only a few billionths of its radius in thickness. That means it is more like a sharp boundary line than a solid layer we can imagine. But this line of exotic matter is what separates reality inside from reality outside. The energy stored in this shell would also be vast beyond measure. Because the exotic matter has negative pressure, the shell acts almost like a spring under extreme compression, holding in an enormous amount of stress. The pressure inside could be so great that it is balanced only because of the counteracting negative properties of the exotic matter. If the shell ever failed, the Gravastar would instantly collapse, perhaps even turning into a black hole or exploding outward with unimaginable force. This makes the shell not only a stabilizer, but also the most dangerous and fragile part of the entire concept. Another fascinating feature of the exotic matter shell is the way it interacts with space-time. Ordinary matter bends space-time by curving it inward, like a ball resting on a stretched sheet. Exotic matter does the opposite. It bends space-time outward. In the case of the Gravastar, the exotic shell warps space in such a way that the strange vacuum interior does not spill out, while also preventing the Gravastar from developing the event horizon that defines a black hole. That means to an outside observer, a Gravastar might look almost identical to a black hole. It would be dark, compact, and exert intense gravitational pull, but it would lack the horizon beyond which no light escapes. Instead, the exotic shell would sit just outside the radius, where the black hole's event horizon would have formed, creating an object that mimics a black hole in appearance but is completely different in structure. This brings about one of the great mysteries of Gravastar shells. If they really exist, how would we tell them apart from black holes? Astronomers today look for black holes by observing the way light bends near them, the way stars orbit around them, or the bursts of radiation created when matter falls toward them. A Gravastar would produce almost the same signals. The exotic shell would not shine by itself. It would be as dark as the void inside. But it might reflect or scatter light in unusual ways, or it might create tiny echoes in gravitational waves that ripple out when two such objects collide. Detecting those tiny differences is one of the ways scientists hope to test whether Gravastars and their exotic shells might be real. The physics behind exotic shells is tied to general relativity, the great theory of gravity put forward by Albert Einstein in the early 20th century. In Einstein's equations, matter and energy determine how spacetime curves. Normally, the energy density is positive, and so space curves in one direction. But the equations also allow for negative values, at least in principle. Exotic matter shells are therefore not forbidden by mathematics, though they are extremely difficult to reconcile with known physics. In fact, quantum theory does predict tiny amounts of exotic behavior in certain situations, such as the Casimir effect, where two metal plates placed very close together in a vacuum experience a strange force due to quantum fluctuations. The Casimir effect creates negative energy density in a laboratory setting, though at scales far too small and weak to build anything like a Gravastar. Still, it shows that the concept is not pure fantasy. When scientists describe exotic matter shells, they often use the language of balance and tension. The Gravastar is thought to be a star that began collapsing under its own gravity, much like how a black hole forms. But instead of collapsing into a singularity, the process halted at the shell. The exotic matter formed a boundary at exactly the right radius, locking the vacuum interior in place and preventing further collapse. This is why the shell is sometimes compared to the crust of a neutron star, but far stranger. Neutron star crusts are made of dense atomic nuclei packed together like a metal lattice. Exotic shells, by contrast, are not made of protons, neutrons, or electrons at all, but of something beyond ordinary particle physics. It is worth noting that exotic matter shells raise many unanswered questions. For example, where would the exotic matter come from in the first place? Is it produced during the collapse of a massive star? Does it arise from quantum effects at the boundary of extreme gravity? Or is it a leftover ingredient from the early universe, present only in rare places where conditions are just right? None of these possibilities have been proven. The exotic shell remains a hypothesis, something that might or might not exist, but without it the Gravastar theory could not work. If exotic matter shells are real, their implications would be extraordinary. It would mean that the universe is capable of creating structures that are not only stranger than black holes, but perhaps more stable. A Gravastar with its exotic shell would not contain a singularity, so it would not suffer from the paradoxes that plague black hole physics, such as the information loss problem. Instead, information about matter that falls into the Gravastar might be preserved in the exotic shell, encoded somehow in its structure. This would make Gravastars a possible solution to one of the deepest puzzles in theoretical physics. The shells also spark the imagination when it comes to cosmic engineering. Science fiction writers have sometimes speculated about advanced civilizations using exotic matter to build stable structures, perhaps even Gravastars as sources of power. Because the exotic shell holds back vacuum energy, the object might serve as an energy reservoir, one that could be tapped in ways we cannot yet imagine. Though this is speculation, it shows how exotic matter shells, though only theoretical, push the boundaries of our thinking. Even in pure scientific terms, the exotic shell stands as an example of how extreme conditions force us to consider possibilities far beyond daily experience. Gravity near a collapsing star pushes matter to densities greater than anything we can create on Earth. In such environments, new faces of matter might appear, and exotic matter could be one of them. The fact that our equations allow it, and that its presence could explain phenomena otherwise attributed to black holes, keeps the idea alive. As research continues, astronomers search for subtle differences that might reveal the presence of exotic shells. For instance, gravitational waves from black hole mergers have been detected by instruments like LIGO and Virgo. If any of those signals show tiny echoes or deviations from what general relativity predicts for black holes, it could hint at the presence of a Gravastar shell instead. So far, the data has not conclusively shown such differences, but the possibility remains open, and scientists are refining their tools to look closer. The exotic matter shell is more than just a barrier. It is the very essence of what makes a Gravastar distinct from a black hole. Without it, the vacuum interior could not be held in, and the object would either collapse or disperse. With it, a new kind of astrophysical body could exist, one that mimics a black hole but avoids its deepest paradoxes. The shell is thin but mighty, strange but mathematically consistent, hypothetical yet tantalizing. It is the line between the ordinary and the extraordinary in the universe, the place where physics bends toward the impossible. When stars are born, they begin their lives as giant clouds of gas and dust. Gravity slowly pulls these clouds inward, squeezing hydrogen atoms until they start to fuse together. This nuclear fusion is what gives a star its light and heat. For billions of years, stars exist in a delicate balance. Gravity is always trying to pull everything inward, while the pressure from nuclear fusion pushes outward. As long as this balance is maintained, the star shines steadily. But when the fuel begins to run out, everything changes. The core starts to collapse, outer layers may be thrown away, and depending on the star's size, the end result can be a white dwarf, a neutron star, or a black hole. At least that is what standard astrophysics has taught us for many decades. Yet Gravastars enter the story as a new alternative, another possibility for what might happen when gravity takes over and squeezes a star to its absolute limits. The formation of a Gravastar is often described as a possible escape route from black holes. Normally, when a star many times heavier than the Sun runs out of fuel, the inward pull of gravity becomes unstoppable. The core collapses, and eventually a singularity is thought to form, a point of infinite density where space and time break down. Around it, an event horizon appears, a boundary from which nothing, not even light, can escape. This is the black hole. But some physicists began to wonder, is this really the only possible outcome? Must stars always create singularities? Perhaps there is another way the collapse could settle, creating an object that looks very much like a black hole from the outside but is very different on the inside. That is where the Gravastar enters. To understand this strange alternative, one has to picture the collapse of a star in its final stages. Imagine a massive star that has burned through all of its fuel. Its core begins to shrink at an incredible pace. Pressures become unimaginable, trillions upon trillions of times greater than what we experience on Earth. Temperatures soar, particles are squeezed together, and matter is crushed almost beyond recognition. But instead of reaching the singularity stage, some scientists have proposed that a strange phase change might take place. Much like how water can suddenly turn into ice or steam depending on conditions, the collapsing core could undergo a transformation of its own. Instead of becoming infinitely dense, the matter inside the star might transform into something entirely new, a region of vacuum energy, sometimes called dark energy, which has a repulsive effect on space. In this scenario, the collapse does not go all the way to a singularity. Instead, it stops at the threshold and produces a new structure. At the very centre of the Gravastar would not matter at all, but this strange vacuum energy, pushing outward with incredible strength. Surrounding this vacuum bubble would be a thin but extremely strong shell of exotic matter, the likes of which we do not fully understand but which would serve as a kind of membrane holding everything together. This shell would balance the push from the vacuum energy inside with the pull of gravity outside. The result would be a stable, compact object that looks like a black hole to anyone observing it from afar, but does not contain an event horizon or a singularity. The pathways to forming such an object are still hypothetical, but the most likely route begins with the collapse of very massive stars. When a star many times heavier than our Sun dies, the collapse can be so extreme that the laws of physics as we know them might not be enough to describe what happens. Traditional black hole theory assumes that gravity wins completely, crushing matter into nothing but a point. But Gravastar theory suggests that at a certain density the rules change. Instead of continuing the collapse, the star's core transitions into this exotic state, forming a bubble of vacuum energy. This would require conditions that are so extreme that no laboratory could ever reproduce them. Yet the universe naturally provides such laboratories in the form of collapsing stars. One can imagine the process unfolding in stages. First, the star lives its long, bright life, burning fuel steadily. Then, as billions of years pass, the fuel begins to run low. Fusion slows, the outward pressure weakens, and gravity begins to take control. The core shrinks rapidly, crushing atoms closer and closer together. At this point, if the star is small, it will end as a white dwarf, and if it is medium-sized, it may end as a neutron star. But if the star is very massive, the pressure will be too great, and the collapse will continue beyond these states. Instead of forming a black hole, though, something unusual might happen. A sudden change in the fabric of space and energy could occur, and the core could reorganize itself into this strange configuration we call a Gravastar. Scientists have speculated about what might trigger this transition. One idea is that quantum effects, tiny processes happening at the smaller scales, might step in to prevent the formation of a singularity. In normal black hole theory, nothing can stop the collapse once it starts, but quantum mechanics suggests there may be limits to how dense matter can become. The Gravastar model takes advantage of this possibility. Rather than letting the collapse go all the way to infinity, it suggests that quantum processes create a sort of quantum pressure, or vacuum bubble that resists further collapse. This would be like the universe finding a loophole in its own rules, stopping the collapse just before a singularity forms and settling into a new stable state. Another possible pathway involves the behavior of dark energy. In the wider universe, dark energy is thought to be driving the expansion of space itself. If a collapsing star could somehow trap a pocket of dark energy inside its core, that energy might resist collapse and create a repulsive force. The outer layers of the star would then be held back by the vacuum energy inside, while the exotic matter shell stabilizes the structure. This balance of forces is very delicate, but if it works, the Gravastar could exist indefinitely, neither collapsing further nor exploding outward. From the outside, a Gravastar would be nearly impossible to distinguish from a black hole. Both would have extremely strong gravitational pulls, bending light around them, warping time, and swallowing anything that ventured too close. Both would appear as dark voids surrounded by glowing material if gas or dust fell in. But deep inside, they would be utterly different. Instead of a singularity hidden behind an event horizon, the Gravastar would have a strange vacuum bubble and a thin shell of exotic matter. The idea that Gravastars might form through stellar collapse also raises questions about how common they could be in the universe. If every massive star ended as a black hole, then Gravastars would be rare. But if there are conditions where the collapse naturally favours the Gravastar pathway, then there could be many of them hidden among the population of black holes we think we see. Astronomers are still trying to determine whether any of the black hole candidates detected so far might actually be Gravastars in disguise. To make the idea more vivid, one can picture a massive star nearing the end of its life. For millions of years it has burned brightly, fusing hydrogen into helium, then helium into heavier elements. Its core grows hotter and denser with each passing stage. When it finally runs out of fuel, the collapse begins. In seconds, the core shrinks, crushing protons and electrons into neutrons. If the star is large enough, this is still not enough to stop gravity, and the collapse continues. The density rises to levels where normal matter cannot survive. But instead of collapsing into a singularity, the core undergoes a strange transformation. Space itself changes. A bubble of vacuum energy appears, pushing outward with enormous force. A shell of exotic matter forms around it, locking the structure in place. The star has not created a black hole, but something just as mysterious, a Gravastar. The possible formation of Gravastars is not only fascinating but also deeply unsettling, because it forces us to rethink the very endgame of gravity. Black holes have long been the champions of extreme gravity, the objects that mark the ultimate victory of collapse. But Gravastars suggest there might be another outcome, one where the universe avoids the paradoxes of singularities and event horizons, by replacing them with a different, equally exotic structure. If gravastars do form in this way, then every black hole we have ever observed could secretly be something else. We might be staring at gravastars without realizing it, mistaking them for black holes because from a distance they look the same. Only the subtle details of how they interact with their surroundings might reveal their true nature. For example, the way they swallow matter, or the way they emit radiation, might carry clues. Some scientists have even suggested that the ripples in space-time caused by collisions, gravitational waves, could hold the key to telling them apart. The observational challenges are so overwhelming that the scientific community still debates whether we will ever be able to know if these strange objects are really out there or if black holes remain the only explanation. The difficulty begins with the fact that black holes themselves are already very hard to observe directly. A black hole does not emit light, does not shine, and does not reflect radiation in the way that stars or planets do. Everything we know about them comes from indirect evidence: how they affect nearby stars, how they bend light through gravitational lensing, how matter heats up when it falls toward them, and how gravitational waves ripple through the cosmos when they merge. Gravastars, if they exist, would produce almost identical signs in all of these situations. If one looked at the sky through a telescope, even the most advanced one, a gravastar sitting quietly in space would appear no different from a black hole of the same mass. The light around it would curve the same way, the gravitational pull would be nearly identical, and unless some small difference is detected, the two objects would be indistinguishable. Another problem lies in the fact that the difference between black holes and gravastars only shows up very close to their surfaces. For a black hole, that surface is the event horizon, an invisible boundary beyond which nothing escapes. For a gravastar, there is no event horizon, but instead there is a thin shell of exotic matter. To notice the difference, one would need to see extremely fine details of how light, radiation or particles behave right at the edge. But that edge is unimaginably far away, often tens of thousands to millions of light years from Earth, and any signals we receive are blurred by distance, dust, and interference. Even the Event Horizon Telescope, which in the year 2019 gave us the first image of a black hole in the galaxy, Messier 87, did not truly photograph the event horizon itself, but rather the bright glowing gas swirling around it. Such data cannot yet separate the subtle features that would reveal whether the central dark spot is a black hole or a gravastar. One might think gravitational waves could provide the answer. When two compact objects like black holes spiral into each other and merge, they create ripples in space-time that detectors like LIGO and Virgo can pick up. The pattern of those waves encodes information about the nature of the objects involved. In theory, if two gravastars collided, the signal might have a slightly different afterring compared to black holes. Black hole mergers produce a so-called ring-down, a fading vibration as the newly formed hole settles into a stable shape. Gravastars might produce echoes instead, as the waves bounce inside the exotic shell before escaping. These echoes would be very faint, arriving after the main signal, and could in principle serve as a fingerprint. But the difficulty is that gravitational wave detectors are noisy, filled with random fluctuations from the Earth and from the instruments themselves. Extracting a faint echo from that sea of noise is like trying to hear the faint sound of a single raindrop in the middle of a thunderstorm. Some researchers claim to have seen hints of such echoes, but others argue that these are statistical illusions. Until detectors improve to a much higher sensitivity, we cannot say for sure. Another observational challenge comes from the way matter behaves when it falls toward these objects. Around black holes, infalling matter forms an accretion disk, heating up to millions of degrees and emitting X-rays. Gravastars would also pull matter in, and the disk would shine in a nearly identical way. One possible difference might arise if matter strikes the solid shell of a gravastar rather than disappearing beyond an event horizon. If this happened, one could expect a sudden burst of radiation, a flash revealing that the object has a surface. But the shell of a gravastar, if it exists, might absorb or scatter this energy in ways that mimic the disappearance into a horizon. Even if flashes occur, they may be too weak or too rare to be noticed from Earth. We would need to monitor countless objects over long periods of time with extremely sensitive instruments, and even then the signals could be confused with other cosmic phenomena such as pulsars, magnetars, or supernova remnants. There is also the difficulty of scale. The objects we are studying are unimaginably large and far away. A stellar mass black hole, formed from a collapsing star, may be only a few tens of kilometers across, yet it could lie thousands of light years from us. A supermassive black hole, like the one in the center of our Milky Way galaxy, stretches across millions of kilometers, but it is over 25,000 light years away. At such distances, even the most powerful telescopes reduce these cosmic giants to tiny specks of data. The subtle differences between a Gravastar and a black hole could be smaller than the margin of error in our instruments. It is like trying to tell whether a coin on the surface of the moon is heads or tails using a pair of binoculars. The technology simply is not sharp enough. Another issue is that the mathematics describing Gravastars is itself uncertain. Different versions of the theory predict different observable effects. Some models suggest strong echoes in gravitational waves, while others predict almost none. Some suggest bright flares when matter hits the shell, while others say the shell would reflect energy inward, making the object appear just as dark as a black hole. Without a consistent prediction, astronomers do not even know exactly what to look for. If one team searches for echoes but another version of the theory says echoes should not exist, then even a null result proves nothing. This uncertainty in the theory makes observational testing extremely challenging. Cosmic background noise adds another layer of difficulty. The universe is full of radiation, particles, and random events that complicate measurements. Gamma-ray bursts, X-ray flashes, quasars, and countless other energetic phenomena fill the sky with signals that can mask the faint signs we need to distinguish a Gravastar from a black hole. Gravitational lensing, for example, bends light around massive objects, but galaxies and dark matter also bend light, mixing their effects with those of the compact object itself. This makes it extremely hard to isolate the unique fingerprint of a Gravastar. Even if we manage to approach closer in our measurements, quantum effects create more confusion. Black holes are thought to emit Hawking radiation, an incredibly faint glow that slowly causes them to evaporate over trillions of years. Gravastars, on the other hand, may not produce this radiation, or may release it in different ways. But Hawking radiation is so weak that no telescope on Earth or in space has ever detected it, and we are unlikely to do so anytime soon. The difference, therefore, remains invisible. Another subtlety lies in time dilation. Near a black hole, time slows down for an outside observer watching matter fall in. To us, the infalling material appears to freeze near the event horizon, never quite crossing it. For a Gravastar, the shell may produce a similar effect, with time dilation causing matter to appear stuck near the surface. In either case, from our viewpoint on Earth, the two scenarios would look almost identical. The only way to tell the difference would be to detect radiation emitted from the final impact, but as explained earlier, this is far from easy. We also face limitations in building simulations. To predict how a Gravastar should look, scientists use supercomputers to solve Einstein's equations for these exotic objects, but the equations are so complex that they can only be approximated, and small differences in assumptions produce very different outcomes. When comparing those results with telescope data, the uncertainties are so large that one cannot claim a firm distinction. It is like comparing two blurry sketches with a blurry photograph and trying to decide which one matches. Future instruments may help. Projects like the Laser Interferometer Space Antenna, planned for the next decade, could detect gravitational waves from sources across the entire universe with far greater precision. Extremely large telescopes, being built in Chile and other locations, may capture finer details of accretion disks and shadows of compact objects. Space-based X-ray observatories might detect subtle variations in bursts and flares. With these tools, the hope is that scientists might catch the one key signature that betrays a Gravastar. But until then, the challenge remains almost insurmountable. It is also worth remembering that nature may not cooperate. Even if Gravastars exist, they may behave so much like black holes that no observational difference is ever detectable. In such a case, the distinction would remain purely theoretical, a matter of equations and philosophy, rather than measurable science. Some physicists even argue that if Gravastars and black holes cannot be told apart by any experiment, then they are effectively the same object, at least from the standpoint of observation. This raises deep questions about the nature of science. Is something real only if it can be measured, Or does it exist if mathematics allows it? Still, the search continues, driven by curiosity. Each new observation of a black hole candidate becomes an opportunity to test whether the universe is hiding Gravastars in plain sight. The black hole at the centre of our galaxy, Sagittarius A, is under intense scrutiny. Astronomers are examining its flares, its orbits of nearby stars, and its radio emissions for any irregularities. Some claim tiny deviations might hint at a surface instead of a horizon, but none of these claims are confirmed. Similarly, the study of mergers by gravitational wave detectors continues, with researchers reanalyzing every data set for faint echoes. So far, the evidence leans toward black holes, but the door for Gravastars is not yet closed. The mystery of distinguishing Gravastars from black holes is not only about technology, but also about human perception. Our senses evolved to handle the middle-sized world of Earth, trees, rivers, mountains, and skies. To deal with the extremes of the cosmos, we rely on machines, equations, and indirect reasoning. Gravastars challenge us to stretch those tools to their absolute limits. They sit on the razor's edge between the known and the speculative, between what we can measure and what we can only imagine. The observational challenges, therefore, are immense. Gravastars and black holes cast the same shadows, bend light in the same way, pull on stars with the same force, and swallow matter with the same hunger. Their differences lie hidden in tiny details that our instruments barely graze. To distinguish them requires not only better telescopes and detectors, but also sharper theories and more patient analysis. Perhaps in the future, with space-based interferometers and next-generation observatories, we will finally catch a glimpse of the difference. Gravitational waves are one of the most extraordinary discoveries in the history of science. They are ripples in the very fabric of space and time, created when some of the most violent and energetic events in the universe take place. When black holes crash into each other, when neutron stars spiral together, or when colossal explosions shake dying stars, these waves travel across the cosmos, stretching and squeezing space itself. For a long time, their existence was only a prediction of Albert Einstein's general theory of relativity, proposed in the year 1915. But in the year 2015, humanity finally detected them directly for the first time, a century after they were predicted. That historic moment proved that space and time can indeed ripple like the surface of water, and that we have the ability to listen to the universe in a completely new way. Ever since that breakthrough, scientists have been developing increasingly sensitive detectors to capture more of these whispers from space. Current detectors like LIGO in the United States, Virgo in Italy, and Kagra in Japan have already given us dozens of gravitational wave detections, most of them from merging black holes and neutron stars. But even though these instruments are incredible achievements, they are still just the beginning. They can only detect waves in certain frequency ranges, and they are sensitive enough to catch events that happened within a certain distance of Earth, but not beyond that. There is an entire hidden universe of gravitational wave signals that remains invisible to us, simply because our current technology cannot reach them. That is why the future of gravitational wave astronomy is so exciting. New detectors, more advanced than anything we have now, may reveal signs of things we cannot yet imagine. One of the most intriguing possibilities is that these future detectors might reveal signals not just from black holes or neutron stars, but from completely new kinds of objects such as Gravastars. A Gravastar, short for gravitational vacuum star, is a theoretical alternative to a black hole. Instead of collapsing into a singularity surrounded by an event horizon, as black holes are thought to do, a Gravastar would be a strange, hollow object. At its core, instead of matter, it would contain a bubble of dark energy or vacuum energy, pushing outward, while the outside would be held together by a shell of exotic matter with unusual properties. To an observer from far away, a Gravastar might look almost exactly like a black hole, but its interior would be radically different. This raises an important question. Could gravitational waves carry the fingerprints of such exotic objects? Could the ripples in space-time tell us whether we are looking at a black hole or at something even stranger? The answer may lie in the fine details of the signals we collect. When two black holes collide and merge, the gravitational waves they send out follow a very precise pattern. The first stage is the inspiral, when the two objects orbit closer and closer, losing energy through radiation. Then comes the merger, when they crash together. Finally, there is the ring down, when the newly formed object settles into a stable state, like a struck bell slowly quieting down. If the final object is a black hole, its ring down has a very specific mathematical shape, described by the equations of general relativity. But if the final object were a Gravastar or something else, the ring down might look slightly different. Future detectors, with more sensitivity, could potentially pick up on these subtle differences. They might notice extra echoes in the signal, little reverberations of space-time bouncing back and forth inside the exotic matter shell of a Gravastar, or signs that the waves die away in a different way than expected. This idea of echoes in gravitational waves has already been explored in theory. A black hole has an event horizon, a point of no return where nothing, not even light, can escape. Because of that, waves simply fall inside and are lost forever. But a Gravastar has no event horizon. Its outer shell might reflect or trap some of the waves, sending them back out again in faint secondary signals. Detecting these echoes would be one of the strongest pieces of evidence that something other than a black hole exists in the universe. However, the echoes would be extremely faint, buried deep in the noise of the data. Current detectors are not quite sensitive enough to confirm them, though some researchers claim to have seen hints. This is where the future comes in. The next generation of detectors, such as the Einstein telescope in Europe or the Cosmic Explorer in the United States, both planned for the coming decades, will be much more powerful. They will be able to measure gravitational waves with 10 times the sensitivity of current instruments, opening a window to these delicate features. Even more revolutionary will be space-based detectors like LISA, the Laser Interferometer Space Antenna, planned by the European Space Agency for launch in the year 2035. Unlike ground-based detectors, which are limited by Earth's size and by seismic noise from the planet itself, LISA will place 3 spacecraft millions of kilometers apart in space, linked by laser beams. This enormous scale will allow it to detect gravitational waves at much lower frequencies than ground-based observatories. Those low-frequency waves come from different kinds of cosmic events, such as supermassive black holes merging at the centers of galaxies, or possibly from exotic objects like Gravastars if they exist on such large scales. With LISA, scientists hope to listen to the deep, slow rumblings of the universe that are completely hidden from us today. The question then becomes, what kinds of signs should we look for in these future detectors to know whether we are seeing a black hole or something stranger? One possibility is the exact frequency spectrum of the waves. Black holes obey very strict rules called quasi-normal modes in their ring-down stage, with frequencies and decay times determined only by their mass and spin. If the observed signal does not match these rules perfectly, it could mean we're not dealing with a black hole. A Gravastar with its shell and vacuum interior would likely produce additional modes, slightly shifting the frequencies or adding new peaks. In practice, detecting these differences requires detectors with not only high sensitivity, but also long observation times, since the more data we have, the better we can extract faint features from the noise. Another possible sign is in the inspiral stage, before the merger. As two objects orbit each other, their gravitational pull depends on their structure. Black holes are bald in the sense that they have no extra features beyond mass and spin, but Gravastars might deform differently, changing the way they radiate energy. This could alter the phase of the inspiral signal in subtle ways. If future detectors can track the inspiral for long enough with great precision, they may be able to notice these deviations. In other words, by listening carefully to the rhythm of the spiraling dance, we might tell whether the dancers are black holes or Gravastars in disguise. Beyond Gravastars, gravitational waves may reveal other exotic possibilities. Some scientists have suggested objects like boson stars, made entirely of hypothetical particles called bosons, or wormholes, which are tunnels through space-time. Each of these strange objects would leave its own mark in the gravitational wave signal, often in the form of echoes, unusual ring-downs, or distorted inspirals. The future detectors will not only confirm more black holes and neutron stars, but may also act as hunters for these exotic objects. If even one convincing detection of such a signature were made, it would revolutionize our understanding of physics, showing us that the universe contains entities beyond the black holes and neutron stars we know. Of course, detecting these signs will not be easy. The universe is noisy, and gravitational wave signals are often incredibly weak by the time they reach Earth. To detect them, scientists use advanced techniques of data analysis, filtering out background noise and enhancing the signals. The search for echoes or other exotic features requires even more sophistication, since the signals are expected to be faint and ambiguous. That is why improvements in detector technology must be matched with improvements in computing power and analysis methods. Machine learning, artificial intelligence, and better models of how exotic objects behave will all play a role in making sense of the data. The excitement lies in the fact that gravitational waves offer a new kind of evidence different from light. Traditional astronomy relies on photons, whether visible light, radio waves, or X-rays, but these can be absorbed, scattered, or hidden by matter. Gravitational waves, on the other hand, pass through matter almost undisturbed, carrying clean information about the most extreme events in the universe. They give us a direct line to phenomena that would otherwise remain invisible. If Gravastars or other exotic objects exist, they may not be visible through telescopes, but their fingerprints in gravitational waves might give them away. Looking forward, the timeline of progress is already set. The current generation of detectors will continue to improve over the next decade, with upgrades increasing their sensitivity. By the early 2030s, the Einstein telescope and cosmic explorer may be built, ushering in a new era of ground-based observations. In the mid-2030s, LISA will take to space, expanding the range of frequencies we can hear. With these instruments combined, scientists will have a network of ears listening to the cosmos across a vast spectrum, from the rapid high-pitched chirps of stellar black holes to the deep bass of supermassive ones. Somewhere in that orchestra of cosmic sounds, the subtle notes of Gravastars may finally be heard. If such a discovery were made, the implications would be enormous. It would challenge our understanding of gravity, quantum physics, and the ultimate fate of collapsing stars. It would show that nature has more tricks than we imagined, and that the story of extreme gravity is not limited to black holes. Perhaps Gravastars are rare, or perhaps they are common but have always been mistaken for black holes. Only the gravitational waves can tell us. The future detectors, with their heightened sensitivity, longer baselines, and broader frequency coverage, will act like magnifying glasses for these cosmic mysteries. They will allow us to go beyond the shadowy outlines of black holes and peer into the deeper truths of space-time. The universe is vast, and we have only just begun to hear its gravitational symphony. Each new detector is like adding another instrument to the orchestra, sharpening the sound and expanding the range. With every detection, we learn more about how stars die, how galaxies grow, and how exotic matter might exist. In the decades to come, the dream is that gravitational waves will not only confirm Einstein's theories again and again, but will also reveal where those theories break down, pointing the way toward new physics. Signs of Gravastars, echoes of exotic structures, or whispers of unknown particles may all lie hidden in the cosmic ripples, waiting for the day when our ears are sharp enough to hear them. The danger of extreme gravity deals with what happens when matter and light themselves are exposed to conditions that go beyond anything we normally experience in the universe. To understand the danger of such a thing, we must picture what it would be like to come close to a Gravastar, a strange object that some scientists believe might exist as an alternative to black holes. A Gravastar is short for gravitational vacuum star. It is not like an ordinary star that shines by burning nuclear fuel in its core. Instead, it is thought to be made of a hollow interior filled with an exotic type of energy, surrounded by a very thin but extremely dense shell of matter. This strange shell could be made of material that behaves in ways we cannot normally imagine, able to resist collapse and trap the strange energy inside. Outside, the Gravastar's pull would be almost identical to that of a black hole, because its mass would be squeezed into such a small space that it bends space and time around it to an extreme degree. Now imagine approaching such a thing. The danger begins long before you even reach the surface or the edge. Gravity that's strong does not act gently. It pulls differently on the parts of you that are closer compared to the parts that are farther away. This effect is often called tidal forces, but in extreme gravity it would not feel like the mild pull of tides on Earth. Instead, if you were a person drifting toward a Gravastar, the side of your body closer to it would be yanked more strongly than the side farther away. Your legs might be pulled downward while your chest and head lagged behind. The difference in force would stretch you out like a long thread. Scientists sometimes call this process spaghettification, because your body would be pulled into a long, thin shape like a piece of pasta. Even atoms themselves would not be safe from this stretching, because the difference in gravitational pull would grow so strong that it could rip apart the bonds that hold matter together. The particles that make up atoms might themselves be torn from one another if you came close enough. But the story does not end with just being stretched. The deeper danger is that light itself, the fastest thing in the universe, cannot easily escape such a pull. Around a Gravastar there would exist a region where light is trapped in circles, unable to escape outward but also not falling inward. This is sometimes called the photon sphere, a place where beams of light could orbit the object endlessly. If you were looking at a Gravastar, you might see distorted and repeated images of the same stars behind it, bent around in strange rings and arcs, as if the sky itself had been twisted into knots. Light from your own flashlight, if you tried to shine it toward the object, might curve around and come back toward you, making it seem as though the darkness itself was playing tricks with your eyes. The danger here is that you could not trust your senses, because light no longer travels in straight lines the way it does in ordinary space. The pull on time itself would also become terrifying. Near a Gravastar, time for you would slow down compared to someone far away. Imagine that you had a friend waiting at a safe distance while you moved closer. From your own point of view, perhaps only a few minutes might pass as you drifted near the shell of the Gravastar. But to your friend far away, hours, days, or even years could slip by while they watched you move slower and slower, never seeming to actually reach the edge. To them, you would appear to freeze, trapped at the boundary, fading into darkness. Yet for you, the passage of time would feel normal until you reached a point where the forces destroyed you. This stretching of time, called time dilation, is not just a trick of the mind. It is real, caused by how gravity bends space and time itself. Matter near a Gravastar also faces strange dangers. If gas, dust, or even entire stars wandered too close, they would be shredded into thin streams by tidal forces. These streams would swirl around the Gravastar, forming what scientists call an accretion disk. Such a disk glows with unbelievable brightness, because as the matter falls inward, it is squeezed and heated until it gives off enormous amounts of light and energy. The glow of such a disk could outshine entire galaxies, making the Gravastar look like a blazing beacon in the darkness of space. Yet no matter how bright the disk, the inside remains invisible, because the extreme gravity bends and swallows the light before it can escape. If a spaceship ever tried to fly close, it would be roasted by radiation from the disk long before it could even touch the shell itself. Radiation is another danger, because near such strong gravity, particles move at nearly the speed of light, colliding and releasing high-energy rays. These rays, like X-rays and gamma rays, can destroy the molecules of life, tearing apart DNA and breaking chemical bonds. For a living creature, such radiation would be deadly in seconds. Even machines would not last long, because the electronics would be fried by the constant bombardment. The environment around a Gravastar would therefore be not only gravitationally dangerous, but also poisoned with lethal energy. The strangest part of a Gravastar is its shell. Unlike a black hole, which hides everything behind an event horizon, a Gravastar might have a physical surface where matter hits and interacts. If you could somehow survive the tidal stretching and the radiation long enough to strike the shell, you would not land gently. The speed at which you would be pulled in means you would slam into the surface at nearly the speed of light. The impact would release more energy than an atomic bomb, but concentrated into the size of your body. You would be instantly vaporized, and the shell itself might quake from the force of the collision, sending out ripples of energy across space. This makes the Gravastar not just a passive object, but an active one, able to react violently when struck by matter. Light that tries to leave the Gravastar's surface faces another cruel fate. Because of the extreme warping of space and time, light emitted outward loses energy as it climbs away from the strong gravitational field. To someone watching from a safe distance, the light would appear redder and dimmer, stretched into longer and weaker wavelengths. This process is called gravitational redshift. If you stood at the shell and tried to shine a bright lamp upward, by the time the light reached someone far away, it might appear as only a faint glow, almost invisible. In fact, if the shell is strong enough, nearly all light trying to escape could be redshifted into nothingness, making the object look as dark as a black hole, even though it has a surface. The extreme gravity of a Gravastar would also play havoc with orbits of nearby objects. A planet wandering too close might have its path twisted so violently that it spirals inward to destruction. A star in orbit might be slowly robbed of its gas, feeding the glowing disk. Even entire clusters of stars could be disturbed, flung out of their galaxies or drawn inward to fuel the beast. Over millions of years, a Gravastar could carve up its surroundings, leaving behind only chaos and darkness. Galaxies with such objects at their centres might show violent jets of energy shooting out for thousands of light years, powered by the feeding frenzy of matter being torn apart and devoured. If you think about what this means for light, it is even more chilling. Light, which normally sets the cosmic speed limit, is bent, slowed, and in many cases completely trapped. Imagine standing near a Gravastar and trying to send a message with a laser beam. The beam would bend back, curve into orbits, or vanish into the shell. Communication itself would become impossible near such a monster, because signals could not travel in straight paths. You could shout into the void with the brightest light, and no one would ever see it. It is as if the Gravastar erases not only matter, but also the very possibility of sharing information. And yet, for all this danger, Gravastars also hold a strange beauty. The way light bends around them can create patterns called Einstein rings, where the image of a star or galaxy behind the Gravastar is warped into a glowing circle. A single object can appear many times, duplicated and stretched by the curved space around it. To an observer, this would look like a hall of mirrors written across the sky. Such beauty is deadly, however, because to witness it closely means to be too near to escape. The danger is not limited to individuals or small objects. If a Gravastar sat in the centre of a galaxy, as scientists believe black holes do, it could shape the fate of billions of stars. The galaxy's spiral arms might be influenced by its pull, and the rhythm of star birth and death could be tied to the energy released as matter falls in. In this way, the Gravastar becomes not only a destroyer, but also a cosmic architect, shaping the grand design of galaxies through its hunger and its gravity. The thought of being near such an object is almost unbearable. For us on Earth, gravity feels gentle. It holds our feet to the ground and keeps the moon in orbit. But the gravity of a Gravastar is not gentle at all. It is a force that can stretch space itself, slow time, crush matter, bend light, and poison everything with deadly radiation. It is a reminder that the universe is not built only for comfort. It has places where the laws of physics push to their most terrifying limits, and where survival is not possible. Yet scientists still wonder whether Gravastars might exist, because they could explain some mysteries that black holes cannot. If they do, then somewhere out there are objects with shells of exotic matter, filled with a vacuum energy that pushes outward while gravity pulls inward, balanced in a fragile dance. They would be objects that look to us like black holes from far away, but are in fact stranger still. To come close to one would be to step into a place where the normal rules of space and time collapse, where matter and light face dangers they cannot overcome, and where the universe reveals just how extreme its creations can be. The danger of extreme gravity, especially near a Gravastar, is not simply a matter of being pulled in. It is the loss of identity of matter itself, the destruction of information carried by light, the collapse of time into strange rhythms, and the transformation of order into chaos. It is both fascinating and horrifying to imagine. A Gravastar may be a hollow shell filled with vacuum energy, but the dangers it presents are as solid and deadly as any nightmare the cosmos can conjure. Cosmic traps for spacecraft are among the greatest nightmares that humankind could face in its daring journey into the vastness of the universe. When people dream of exploring other planets, crossing the dark oceans of interstellar space, or sending missions to the very edges of the galaxy, they often imagine the dangers of hostile environments, radiation storms, or mechanical failure. Yet, the true danger, the one that lies hidden in silence, is not simply what can break a machine, but what can completely erase it from existence. These traps are made not by enemies or by chance, but by the laws of nature themselves, waiting in the dark like invisible snares. The universe is beautiful, but it is also merciless, and the traps it has set for spacecraft are proof that nature can both inspire and terrify. A spacecraft travelling through space may face many regions where the rules of gravity and energy combine into something so powerful and strange that escape becomes nearly impossible. These are the cosmic traps, places where matter, light, and even time itself can become tangled. A ship that strays too near can find itself stretched, twisted, and swallowed, without leaving the smallest trace behind. To human imagination, these regions are like black whirlpools in a cosmic ocean, pulling everything down into their silent depths. Unlike whirlpools of water, which can be seen, measured, and avoided, cosmic traps are often invisible. They announce their presence not by their own shape, but by what they do to the world around them. A star that circles too closely, a cloud of gas that glows brighter as it falls, a strange bending of light from a distant galaxy. All these signs whisper of a trap lurking unseen. The most famous of these cosmic traps are black holes, but they are not alone. The universe may hide other strange structures, like Gravastars or wormholes that have collapsed into deadly pits. Whatever their nature, the principle is the same. They are regions where gravity grows so overwhelming that even light, which is the fastest traveller in the universe, cannot escape. A spacecraft that drifts too close will discover that ordinary engines are useless no matter how powerful. The closer it gets, the more the very fabric of space and time seems to betray it. Distances stretch, time slows, and directions lose meaning. For the crew inside, it would feel like being caught in quicksand made not of earth or mud, but of reality itself. Imagine a future spacecraft, long and sleek, its silver body gleaming as it sails between the stars. Its engines burn quietly, pushing it forward at a steady pace. The crew inside is busy with routine tasks, charting their course, checking the instruments, recording the faint signals of distant worlds. Around them stretches an endless ocean of stars, glittering like jewels. Then, slowly, the readings begin to shift. Gravity detectors start to register a pull that should not be there. At first, it is too small to notice, no more than a whisper in the data. But over hours and then days, the numbers climb. Something massive is nearby, something invisible. The ship's cameras sweep the region, yet there is nothing. No star, no planet, no glowing nebula, just empty space. And still, the pull grows stronger. The crew does not yet realize that they are approaching a cosmic trap. Their instruments will give hints, but the trap itself hides its body behind a cloak of darkness. The only evidence may be strange distortions of starlight ahead. Points of light curve and bend as though seen through rippling water. This bending is gravity's handwriting, the sign that an object of immense weight lurks there. If the crew does not change course soon enough, the ship will cross a point of no return. Past this invisible line, escape is impossible. Engines could roar with all their strength, yet the ship would still fall inward, drawn deeper and deeper into the dark heart of the trap. The nightmare of such a moment is not only in the knowledge that escape is gone, but also in the way the fall takes place. To those far away, watching from safety, the ship would appear to slow down as it approached the edge, stretching into a faint shadow that freezes in place, never quite crossing the boundary. To them, time would seem to stop for the doomed explorers. But for the crew inside, time continues. They would feel the acceleration, the stretching, the endless dive inward. The light outside their windows would grow stranger. Stars would smear into arcs, colours would shift, and darkness would creep in from all sides. The closer they fell, the more reality itself would twist. Seconds would feel like years compared to the world outside. In one direction, the universe would rush forward into a distant future, while in another, it would drag backward into the past. The spacecraft would be caught not only in space but in the trap of time. And then comes the tearing. Gravity does not pull evenly when one part of an object is closer to the trap than another. This difference is called tidal force, and in a cosmic trap, tidal forces become unbearable. The nose of the ship, being closer, feels a stronger pull than the tail. Slowly, then violently, the spacecraft begins to stretch, like dough being pulled apart. The crew feels the same effect. Feet tugged harder than heads, arms pulled wider than shoulders. The force increases until bones, muscles, and metal alike cannot withstand it. Scientists call this spaghettification, a name that may sound almost humorous, but hides one of the most horrifying fates possible. A human body, a spacecraft, a mountain, Even a planet would be drawn into long, thin streams of matter, ripped down to the smallest particles before being swallowed entirely. The universe offers no mercy in these traps. No last-minute rescue, no clever maneuver, no secret exit. Once inside, all paths lead only inward, deeper into darkness. Even information itself cannot escape. This makes cosmic traps not only physical dangers, but also mysteries that hide their cause forever. What lies beyond the final veil of a black hole? Is there a center, a point where all matter collapses into something infinitely small? Or does the trap open into another space, another universe, a place forever cut off from ours? These questions make cosmic traps not only deadly, but also profoundly fascinating. They are the prisons of reality, but also its deepest secrets. Now imagine what such traps mean for the dream of exploration. Humanity hopes one day to travel across the galaxy, to send ships into regions no one has seen. But hidden among the stars are these invisible snares. They do not announce themselves with roaring fires or flashing lights. They simply wait. A starship could wander too close without knowing. A navigation error, a broken detector, or even a moment of overconfidence could send it drifting toward one of these silent killers. The nightmare is not only for the crew but also for those left behind. From Earth, mission control would watch the signals grow weaker, delayed, stretched, and then vanish. The ship would fade from reality, leaving behind only questions and silence. No wreckage, no return, no explanation, just absence. The human imagination has always filled the unknown with monsters, from sea serpents to dragons. But in space, the monsters are not creatures of flesh and blood. They are traps built from gravity and time. Their hunger is endless, not because they choose to feed, but because the laws of the cosmos make it so. For a crew facing one, the terror is not in fighting, but in realizing there is nothing to fight. The ship is caught in an embrace stronger than any weapon, held by forces that no strength can resist. It is a nightmare not of struggle, but of helplessness. These cosmic traps are not rare. Astronomers believe that our own galaxy, the Milky Way, may hold millions of black holes scattered like mines across its spiral arms. Some are the remains of massive stars that collapsed long ago, others are giants lurking at the centers of clusters. At the very core of our galaxy lies a monster black hole with the mass of millions of suns. It sits there silently, bending the paths of nearby stars like toys on strings. A spacecraft crossing near the galactic center would have to navigate with extreme care, for the region is full of such traps, each capable of swallowing entire worlds. Even closer to Earth, smaller black holes may drift unseen, their presence betrayed only by the way they tug at nearby stars. To explore space fully, humanity must accept that these hidden snares are part of the landscape, as natural as mountains or oceans, but infinitely more deadly. The nightmare of these traps goes beyond destruction. They also challenge understanding. Every spacecraft that vanishes into one takes its knowledge with it. Instruments, data, recordings, none of it can be sent back once the boundary is crossed. To explore too close is not only to risk loss of life, but also loss of answers. The deepest secrets of gravity and the universe may lie inside, but no probe, no matter how clever, can bring them out. This makes the traps both barriers and invitations. They say, come closer, but not too close. Learn what you can from the edges, but never expect to see the heart. Yet, humanity has always been drawn to danger. Sailors once set out across seas where maps warned of monsters. Explorers crossed deserts and climbed mountains that had killed many before. In the same way, spacecraft will one day be sent near these cosmic traps, trying to skim the edges without falling in. Powerful detectors, careful planning and courage will all be needed, but always the nightmare will remain. The thought that one miscalculation, one slip, could send the ship spiraling past the point of no return. And when that happens, the universe itself becomes the executioner, pulling the explorers into a silence that no signal can pierce. The most chilling truth of all is that these traps are not rare exceptions, not flaws in the universe. They are part of its very structure. Gravity, the same gentle force that keeps our feet on the ground and holds planets in orbit, also builds these prisons when pushed to extremes. The same laws that let galaxies form also let them hide devourers at their cores. In a sense, cosmic traps are not accidents, but necessities, as natural as stars themselves. To explore the universe is therefore to accept that danger is woven into its fabric, and so the nightmare remains. Cosmic traps for spacecraft are the silent killers of the universe, waiting without malice, without intent, but with absolute certainty. To come too close is to vanish, body and machine, light and memory, swallowed by gravity's endless hunger. They remind us that space is not only a place of wonder and possibility, but also of danger beyond imagination. They are the dark truth behind the dream of exploration, that the universe, for all its beauty, has places where even the bravest ship must never tread. Could Gravastars power the universe is a question that drifts like a whisper across the minds of scientists who dare to step into the grey and shadowed regions between hard physics and imaginative speculation. Gravastars, those hypothetical siblings of black holes, are born from the same equations of general relativity that describe how matter bends space-time, but they take a very different turn. Instead of collapsing into a singularity that traps everything inside, a gravastar is thought to stop just short of that crushing end. At its heart, there may be a strange bubble of dark energy, an inner void that stretches space-time outward instead of drawing it in, wrapped in a shell of exotic matter that resists collapse. This makes gravastars one of the strangest and most mysterious ideas in astrophysics, objects that might hide unimaginable stores of energy waiting to be discovered. The question, then, is whether these hidden reservoirs could serve as engines capable of shaping the destiny of the universe itself. To grasp the possibility of gravastars powering the universe, one must first sit with the idea of how much energy might be contained inside such an object. When a massive star dies and collapses, gravity takes over, pulling everything inward. In the case of a black hole, this collapse continues until a singularity forms, a point where density is infinite, and all our equations break down. For a gravastar, however, the collapse halts when the intense pressure and density of space-time itself triggers a phase change, much like water freezing into ice or boiling into steam, but on a cosmic scale. The matter of the star's core does not form a singularity, but instead transforms into a vacuum-like energy field, often described as a bubble of dark energy. This inner region, sometimes thought of as pure vacuum energy, has properties that push outward instead of pulling inward. Surrounding it is a razor-thin shell of ultra-dense exotic matter that balances this outward push with an inward pull, holding the object together in a stable configuration. This balance between expansion and collapse suggests that gravastars may trap within themselves an ocean of vacuum energy, far greater than the energy stored in normal matter. Vacuum energy is not just emptiness. It is a restless sea of quantum fluctuations, a constant churning of energy at the smallest scales of reality. If gravastars are truly filled with such energy, then their interiors may contain more power than entire galaxies of stars combined. Here lies the temptation for cosmic speculation. Perhaps gravastars are not simply dead ends of stellar collapse, but hidden batteries of the universe, silent powerhouses whose reserves could, in theory, illuminate civilizations, drive cosmic processes, or even fuel the very expansion of the cosmos itself. One must reflect on the scale of energy hidden in vacuum energy to appreciate the enormity of this speculation. A single teaspoon of vacuum energy, if harnessed, could outshine the energy output of a planet's entire civilization for countless ages. If gravastars indeed harbour vacuum bubbles the size of collapsed stars, then we are speaking of an energy stockpile so vast that it stretches the imagination beyond ordinary limits. If there are millions or billions of gravastars scattered across galaxies, the total energy bound inside them may rival the energy of all luminous matter in existence. In such a picture, gravastars could be silent custodians of energy on a scale so massive that it overshadows the burning of stars, the collapse of supernovae, and even the rotation of galaxies. The idea that gravastars could power the universe naturally leads to comparisons with black holes. Black holes are often thought of as destructive, swallowing matter and light into a singularity from which no return is possible. Yet they too are paradoxically sources of energy, as seen in the form of Hawking radiation, accretion disks blazing with light, and powerful jets shooting across intergalactic distances. Gravastars, if real, may outmatch them in subtle ways. Instead of energy leaking from the edges like a candle burning down, Gravastars could be self-contained furnaces of vacuum energy. The challenge is that their hidden energy is sealed behind layers of exotic matter, making them inaccessible unless some unimaginable process could tap into that store. Speculation invites one to imagine what might happen if such energy could indeed be tapped. Civilizations far older and wiser than our own might have learned how to extract the energy locked inside Gravastars. To them, stars might seem like weak embers compared to the blazing potential of these dark, compact objects. They might build machines orbiting Gravastars, harvesting power the way we gather sunlight from the sky. Whole galaxies might be engineered to revolve around these energy sources, their civilizations lit for eons by what to us seems like unreachable fuel. In this vision, Gravastars become not just natural phenomena but pillars of cosmic engineering, secret engines turning the wheels of the universe's grand design. This speculation pushes deeper still when one considers the link between vacuum energy and dark energy, the mysterious force driving the accelerated expansion of the universe. Observations of distant supernovae, the cosmic microwave background, and the large-scale structure of galaxies reveal that the universe is not just expanding but accelerating in its expansion. The force behind this, called dark energy, makes up about 70% of the cosmos, yet it remains one of the greatest puzzles in science. Gravastars, filled with vacuum energy, might not be isolated curiosities but actual contributors to this cosmic acceleration. Each Gravastar could act like a tiny bubble of dark energy, and collectively, billions of them scattered across space might help drive the universe outward, fueling expansion on a grand scale. If this is true, then Gravastars are not just strange remnants of collapsed stars but participants in the largest scale drama of all, the shaping of cosmic destiny. They might form a hidden network of energy reservoirs that stitch the universe together, influencing its growth and its fate. Instead of being rare or marginal, Gravastars could be central players, their hidden interiors pulsing with the very energy that rules the evolution of space and time. The thought of this bends the mind, that the universe's future might be written in the interiors of objects we cannot even prove exist yet. One must also reflect on the possibility that Gravastars could represent not merely natural energy stores, but perhaps natural regulators of energy in the cosmos. The universe is a place of balances and cycles. Stars burn fuel, shine and die. Black holes swallow matter and energy. Galaxies spin in halos of dark matter, and expansion is driven by dark energy. Gravastars could fit into this pattern as regulators, preventing collapse into singularities while storing energy in vacuum form. They could act as cosmic safes, locking away vast sums of energy that might otherwise tear the fabric of space-time apart. Perhaps they are nature's way of balancing the books, storing what would otherwise be destructive force and turning it into silent, stable reservoirs that maintain cosmic order. The danger, of course, is that hidden energy is also a hidden potential catastrophe. If Gravastars are real, and if their interiors are filled with unimaginable energy, then what would happen if their balance were disturbed? If the thin shell of exotic matter were to rupture, the release of vacuum energy could trigger an explosion unlike anything seen in the universe. It would dwarf supernovae and gamma-ray bursts, releasing power capable of sterilizing galaxies. Such a thought is terrifying, for it would mean that Gravastars are not only possible power sources, but also cosmic bombs, ticking silently in the dark, awaiting only the wrong touch to unleash devastation. The universe, then, could be dotted with potential engines and potential doomsday devices, depending on how stable these strange structures truly are. The mystery deepens when one considers how Gravastars might be detected. Black holes can be inferred by the way they bend light, swallow stars, and produce X-ray emissions from matter falling into their gravity wells. Gravastars, on the other hand, would mimic many of these same effects. To an observer, they might appear identical to black holes, since their shells bend light in almost the same way. The only clues might lie in subtle differences, the absence of a true event horizon, unusual echoes in gravitational waves, or tiny shifts in how matter interacts near their surfaces. If future instruments, gravitational wave detectors more sensitive than those we have today, or telescopes capable of peering at cosmic edges with higher resolution, could pick out these differences, then perhaps we could confirm their existence. Only then could the speculation about their energy reservoirs move from wild imagination to scientific reality. Until that day, the question of whether Gravastars could power the universe remains suspended between dream and theory. Yet, one cannot help but linger on the images it creates. Whole civilizations gather power from Gravastars like bees around hives. The universe's expansion is pushed outward by countless bubbles of vacuum energy sealed inside them, cataclysms awaiting if one should rupture. And perhaps, most daring of all, the idea that the very engine of existence, the force that keeps galaxies racing apart, might not be some mysterious uniform field, but the collective breath of countless Gravastars whispering outward through space-time. To think of Gravastars in this way is to stand at the threshold of imagination and science. Gravastars are among the strangest ideas ever imagined in modern astrophysics. They were proposed as possible alternatives to black holes, those dark monsters of gravity that trap everything, even light itself. When black holes were first taken seriously as real objects in the universe, scientists quickly realized that they posed a deep puzzle. According to classical general relativity, a black hole once formed would remain forever, unless something collided with it or fed it more matter. But then the famous physicist Stephen Hawking showed in the 1970s that this picture was incomplete. By combining ideas from quantum theory with general relativity, Hawking discovered that black holes are not perfectly black. Instead, they emit tiny amounts of radiation, now called Hawking radiation. Over incredibly long spans of time, this radiation causes black holes to shrink, lose mass, and eventually evaporate completely. This discovery was shocking because it meant black holes are not eternal. They have a finite lifetime. The bigger the black hole, the longer it survives, but even the most massive ones will eventually disappear, though only after times far longer than the current age of the universe. This raised a haunting question. If black holes are not forever, then what about Gravastars, these strange proposed cousins of black holes? Do they also leak away energy in the form of Hawking radiation, or do they evade this fate and endure forever in some stable form? To answer this, we must carefully look at what makes a Gravastar different from a black hole. A black hole is defined by its event horizon, the ultimate boundary beyond which nothing can escape. It is this event horizon that is responsible for Hawking radiation, since the quantum fields in the universe behave strangely near it, creating particle-antiparticle pairs where one falls in and the other escapes as radiation. A Gravastar, however, does not actually have an event horizon. Instead, it is theorized to have a very thin shell of exotic matter on its surface, and inside that shell is not a singularity or empty space, but rather a strange region dominated by vacuum energy, which behaves like a form of dark energy. The absence of a true horizon is critical. If there is no event horizon, then the standard mechanism of Hawking radiation may not apply at all. That would mean Gravastars do not radiate away their mass in the same way black holes do. Instead of gradually evaporating, they might remain almost perfectly stable. If this is correct, Gravastars could be effectively immortal, surviving indefinitely without fading away. But here we encounter a deep uncertainty. The theory of Gravastars is not complete. It is a speculative model, one of many attempts to solve puzzles about the ultimate fate of collapsing stars. Whether Gravastars radiate like black holes depends entirely on the exact quantum properties of their shell and interior, which no one fully understands yet. Some scientists suggest that Gravastars might give off a faint glow of radiation, not because of an event horizon, but because of quantum effects in their exotic shell. Others think they might release occasional bursts of energy when matter falls onto them, mimicking some behaviors of black holes. Still, the central question remains: could a Gravastar live forever? Imagine a massive star that collapses. Instead of becoming a black hole with an event horizon, it forms a Gravastar. Its outer shell of exotic matter holds the star up against total collapse, while its inner vacuum energy keeps it inflated like a strange cosmic balloon. Time passes. The universe grows older, stars are born and die, galaxies collide, and black holes slowly radiate away through Hawking's process. But the Gravastar sits there, unchanged, untouched by this slow bleeding of energy. Billions upon billions of years pass, and still it survives. If Gravastars truly evade Hawking radiation, then in the unimaginably distant future, when black holes have evaporated and ordinary stars have long since burned out, Gravastars might be among the last remaining structures in the universe. To appreciate the scale of this idea, consider that the evaporation time for a black hole as heavy as our Sun is around 10 to the power of 67 years, which is far, far beyond the current age of the universe, which is just under 14 billion years. For a supermassive black hole with a mass of millions or billions of suns, the evaporation time is even more staggering, up to 10 to the power of 100 years or more. If gravastars avoid this process, then their lifetimes are not just long, they are infinite compared to any black hole. They would represent eternal monuments in a universe where even the most massive black holes eventually vanish. But could it really be that simple? Some physicists argue that even without a horizon, gravastars might not be completely immune to quantum effects. Spacetime itself is a quantum field, and the exotic shell of a gravastar could in principle interact with those fields in subtle ways. This could create a tiny trickle of radiation, different from Hawking radiation, but still enough to slowly erode the gravastar over inconceivably long times. In this view, gravastars might not be eternal, but their lifespans could still dwarf those of black holes, making them last for unimaginable durations. Others suggest a different outcome. If gravastars truly contain a core of vacuum energy, then they may not be eternally stable at all. Vacuum energy itself might be unstable, capable of decaying into other forms of energy under the right conditions. If that decay happens, the gravastar could suddenly release an enormous burst of energy, essentially exploding and disappearing in a dramatic flash. Instead of quietly evaporating like a black hole, a gravastar might end in one colossal event. This leads us to an even more speculative thought. What if gravastars, by avoiding Hawking radiation, actually hold on to their energy forever, until some quantum instability triggers them to collapse or explode? In that case, they might be cosmic time bombs lurking in the universe for billions of years before suddenly unleashing devastating outbursts. Some astronomers even wonder whether unexplained cosmic events, such as mysterious gamma-ray bursts, might in rare cases come from collapsing gravastars rather than the usual explanations involving massive stars or neutron star mergers. When we compare gravastars and black holes side by side, the contrast is fascinating. Black holes are defined, predictable in their long-term decay, and doomed to eventually vanish. Gravastars, if they exist, are undefined, mysterious, and possibly eternal. This makes them attractive theoretical objects, since they provide an alternative way for nature to avoid singularities and the paradoxes of information loss. Hawking's discovery of radiation created the so-called information paradox, where information about matter falling into a black hole seems to vanish forever. With gravastars, that problem may not exist, since there is no true horizon to hide information behind. Matter falling onto a gravastar might be preserved in some form in its shell or interior, never truly lost. If this is true, then gravastars would not only evade Hawking radiation, but also solve one of the greatest paradoxes in physics. They would represent a kind of loophole in the laws of the universe, sidestepping both the destruction of information and the slow death through evaporation. Now imagine the far future once again. Picture a universe so old that black holes, those giants of gravity, have finally evaporated into nothing. The galaxies have spread apart into vast emptiness, stars have all burned out, and only faint traces of radiation remain. In this silent darkness, gravastars might still persist, unchanged since the day they formed. They would be ancient relics, older than the oldest black holes, lasting longer than any star, perhaps even outliving the very fabric of the universe itself. This possibility is both beautiful and unsettling. If gravastars do not evaporate, then they represent a form of cosmic permanence, things that endure while everything else fades. They might become the last monuments in a dying universe, silent and dark, their exotic shells holding in their strange energy forever. If they can never release their energy, then they are like locked vaults, hoarding cosmic secrets eternally. But if they do one day collapse or explode, then they are ticking bombs, waiting for the right moment to unleash their hidden power. The truth is that we simply do not know. Gravastars are still a theoretical idea, not confirmed by observation. We cannot yet tell whether the strange radiation of quantum fields interacts with them the same way it does with black holes. We cannot measure their lifespans or watch them evolve over time. All we can do is imagine, calculate, and debate. But the question itself, do gravastars evade Hawking radiation, is one of the most profound in modern astrophysics because it touches on the nature of eternity, the fate of information, and the ultimate future of the cosmos. If they do evade it, then Gravastars might be immortal guardians of the universe, persisting through ages when all else is gone. If they do not, then they will eventually die, like black holes, but perhaps in stranger and more violent ways. In either case, they remind us that the universe still hides mysteries deeper than our current understanding, mysteries that stretch across time, span so vast that human imagination struggles to hold them. The vision of a cosmos where gravastars endure while black holes vanish is a haunting one. It suggests a future where the most powerful and frightening objects we know, black holes, are only temporary, while their stranger cousins, the gravastars, might be the true eternal rulers of the night. Whether they shine, collapse, or remain forever silent, gravastars hold within them the possibility of immortality, a possibility that pushes us to rethink what it means for anything to live forever in a universe that itself may not. When we look at the universe through the rules of general relativity, black holes appear to be the ultimate prisons. They are regions of space where gravity is so strong that not even light can escape. Anything that falls inside is thought to be lost forever, hidden behind the event horizon, which is the invisible boundary that separates the inside of a black hole from the outside universe. But when we look at the same problem using quantum mechanics, which is the set of rules that governs the smallest parts of reality, a very different picture appears. Quantum physics tells us that information, in the form of the arrangement of particles and their states, should never be destroyed. This is not just a philosophical idea, it is a deep principle that lies at the heart of quantum theory. Yet black holes seem to destroy information, because once something falls inside, the outside world can never recover what went in. This conflict between relativity and quantum mechanics gave rise to the information paradox, and it has kept scientists puzzled for decades. The paradox became even stronger when Stephen Hawking, in the 1970s, showed that black holes are not completely black. According to Hawking's calculations, black holes emit radiation due to quantum effects near the event horizon. This radiation, now called Hawking radiation, slowly drains energy from the black hole, causing it to shrink over unimaginably long periods of time. Eventually, the black hole could evaporate completely. But here lies the problem. If the black hole disappears, then all the information about the things that fell into it is gone too, erased from the universe. That would break the fundamental laws of quantum mechanics, which say that information is never truly lost. It is like writing a book, throwing it into a fire and watching the book burn. The paper is gone, the ink is gone, but if you are careful enough, you can still, in principle, reconstruct what was written from the smoke, the ash, and the heat. In quantum mechanics, the universe keeps the records no matter how scrambled they become. But if a black hole vanishes without leaving behind a trace of the information it swallowed, it is as though the universe has torn out pages of its own history. That is why the paradox is so disturbing. Now comes the idea of gravastars. Gravastars, or gravitational vacuum stars, are a bold alternative to black holes. They were proposed as a way to avoid the information paradox and to show that perhaps the universe has a trick up its sleeve. A gravastar looks very much like a black hole from the outside. It is extremely compact, incredibly heavy, and surrounded by gravity so strong that anything coming too close would find it impossible to escape. But unlike black holes, gravastars do not have a singularity at the center or an event horizon. Instead, they are thought to have a very thin shell made of exotic matter, surrounding a core filled with something even stranger, a bubble of dark energy or vacuum energy. In this picture, the collapsing star never truly forms a black hole. Instead, the collapse stops just before an event horizon can form, and the shell of exotic matter stabilizes the structure. The result is an object that fools the outside observer into thinking it is a black hole, but at its heart it is something entirely different. If gravastars exist, they could provide an elegant way out of the information paradox. Since gravastars have no true event horizon, information that falls toward them is not lost forever. The shell of exotic matter and the vacuum core could interact with infalling matter in ways that allow the information to be stored, scrambled, or even radiated back out over time. The object may still appear black from far away, but in principle, the information is not destroyed. It could remain encoded in the complex structure of the gravastar, or it might eventually leak out in some subtle form. This means that Gravastars would obey the rules of quantum mechanics while also respecting the predictions of relativity. They would solve the paradox by showing that what we thought were black holes might instead be these mysterious hollow stars. To appreciate how radical this idea is, one must remember the long struggle between quantum mechanics and relativity. Albert Einstein's general relativity describes the universe on large scales, the movement of planets, the bending of light by gravity, and the dynamics of galaxies. Quantum mechanics describes the small scales, the behavior of atoms, particles, and fields. Both theories work spectacularly well in their own domains, yet when we try to put them together in extreme places like black holes, contradictions arise. The information paradox is one of those contradictions, and for decades physicists have wondered whether the solution lies in changing relativity, changing quantum mechanics, or inventing something entirely new. Gravastars offer a middle path. They keep relativity intact by explaining why ultra-compact objects look like black holes, but they also keep quantum mechanics intact by avoiding information loss. Imagine a spaceship approaching what appears to be a black hole. To distant observers, the spaceship seems to slow down and freeze at the edge of the event horizon, never quite falling inside. From the perspective of the crew, however, they cross the horizon and plunge inward. If the object is truly a black hole, the crew and their ship are lost to the outside universe. But if it is a Gravastar, things might be very different. There is no true horizon, just a strange shell of exotic matter. As the ship comes close, it would interact with this shell, perhaps being shredded or transformed, but the information about its structure would not vanish into a singularity. Instead, it would be imprinted on the shell or absorbed into the vacuum bubble. The details are deeply theoretical and far beyond current experiments, but the key point is that nothing is lost forever. The universe keeps the record, even if it is hidden in a strange and alien form. The Gravastar model has other advantages too. Black holes suffer from the problem of singularities. At the very centre of a black hole, relativity predicts that density and curvature become infinite, meaning that the equations break down and stop making sense. Many physicists believe that true infinities do not exist in nature. They are a sign that our theory is incomplete. By removing the singularity, Gravastars give us a more consistent picture. Instead of infinite density, the centre is filled with vacuum energy, which is strange but not mathematically impossible. This makes Gravastars not just a potential solution to the information paradox, but also a possible answer to the problem of singularities. Of course, the big question is whether Gravastars really exist in the universe, or whether they are just a clever mathematical trick. To answer that, scientists are searching for signs that could distinguish Gravastars from black holes. The differences might be very subtle. For instance, the way gravitational waves echo after two of these objects collide might reveal whether they have horizons or shells. Black holes would give off a clean signal as they merge and then fade away, while Gravastars might produce faint echoes caused by waves bouncing off their shell. Similarly, the way light bends around them, or the way matter swirls in the disk of gas surrounding them, might carry hidden clues. These are not easy measurements to make, but new observatories, such as gravitational wave detectors and advanced telescopes, are beginning to test these ideas. The information paradox has driven physicists to wild proposals. Some argue that information escapes from black holes in a subtle way through Hawking radiation, which somehow encodes the history of what fell inside. Others argue for new structures like firewalls, blazing barriers of energy that sit just outside the horizon and destroy anything that falls in, though this idea creates new contradictions of its own. Some physicists suggest that the entire concept of space-time may need to be rethought at a fundamental level. Gravastars, in this landscape of bold speculation, stand out because they are relatively conservative. They do not demand that we throw away relativity or quantum mechanics. Instead, they say that perhaps we misinterpreted what happens when stars collapse, and the universe gives us Gravastars instead of true black holes. The beauty of this proposal is that it gives us hope that information is never truly lost. For centuries, humans have sought to understand whether the universe is lawful, whether it plays fair, or whether it allows things to simply disappear without explanation. The information paradox threatened that faith by suggesting that black holes could act like cosmic shredders of history. Gravastars reassure us that even the darkest corners of the cosmos may still respect the deep rules of physics. The price is that we must accept objects stranger than anything we have ever seen, with shells of exotic matter and hollow hearts filled with vacuum energy. But then again, the universe has never been shy about surprising us. To put the timescales into perspective, consider how long it would take for a black hole to evaporate through Hawking radiation. A black hole the mass of our Sun would take about 10 to the power of 67 years to vanish. That is a 1 followed by 67 zeros, a timescale so vast that it dwarfs the current age of the universe, which is about 1.4 times 10 to the power of 10 years. Larger black holes would take even longer, up to unimaginable stretches of time. If information really does vanish with the black hole, then the universe would be breaking its own laws for all those countless years. Gravastars, by avoiding evaporation in the first place, would avoid the problem entirely. They could persist indefinitely, storing information for eternity. One can also think of gravastars as cosmic vaults. When matter falls into them, it is not destroyed but locked away in the strange physics of the shell and vacuum interior. Perhaps one day, if our understanding deepens, we might even imagine ways of retrieving or decoding that information. Of course, that is pure speculation today, but it shows the kind of possibilities that emerge when we try to solve the paradox. Gravastars turn a hopeless problem into an open door for new ideas. There is also a poetic side to this idea. The universe is often described as a grand book written in the language of physics. Every particle, every atom, every star is a letter in that book, and the laws of quantum mechanics ensure that no letter is ever truly erased. The information paradox threatened to tear pages out of the book, leaving gaps in the story. Gravastars restore those pages, telling us that the universe's story remains whole, even if the writing is hidden behind dark and mysterious covers. They transform black holes from destroyers of history into keepers of secrets. In the end, the information paradox problem is not just a technical debate among physicists. It strikes at the heart of what it means to understand the universe. If information can vanish without a trace, then science itself faces a limit, because we could never be certain that the universe's rules are consistent. But if gravastars or some other solution preserves information, then the universe remains lawful and knowable, no matter how strange it appears. Gravastars may or may not turn out to be real, but by exploring them, we are forced to ask the deepest questions about the nature of space, time, and reality itself. The search for answers continues. Perhaps one day, gravitational wave observatories will detect echoes that reveal the presence of gravastar shells. Perhaps future telescopes will catch subtle patterns of light that betray their hollow nature. Or perhaps black holes will triumph after all, and we will find that information does escape them in some mysterious way. Whatever the outcome, the struggle with the information paradox has already reshaped our thinking. It has led us to consider that the universe might be stranger and more subtle than anyone dared to imagine. And so gravastars, these ghostly alternatives to black holes, stand as one of the most daring ideas in modern science. They promise to solve one of physics' greatest puzzles by showing that the universe does not erase its own history. They remind us that even in the darkest depths of space, the laws of physics still whisper their secrets, waiting for us to listen closely enough to hear them. At the heart of nearly every galaxy, including our own Milky Way, there lies a powerful and invisible object that shapes the stars, gas, and dust swirling around it. For a long time, scientists have believed that these central objects are supermassive black holes, colossal monsters with masses millions or even billions of times greater than our Sun. These black holes are thought to act as engines that drive the motion of stars in their galaxies, and sometimes produce dazzling jets of energy that can outshine everything else in their cosmic neighborhood. But in recent years, a bold new idea has surfaced, one that challenges this long-standing belief. What if, instead of black holes, the true rulers of galactic cores are gravastars? A gravastar, short for gravitational vacuum star, is a strange and exotic object predicted by certain theoretical models. Unlike a black hole, which is said to trap everything, including light behind its event horizon, a gravastar does not collapse into a singularity. Instead, it is believed to have a shell of exotic matter that holds back its collapse, enclosing a core filled with a special kind of vacuum energy. This makes it hollow at the center, unlike the crushing singularity of a black hole. Gravastars have been proposed as a possible alternative to black holes, solving some of the paradoxes that black holes create in physics. The big question is whether these hypothetical objects could actually exist at the centres of galaxies, taking the place of black holes, and if so, what kind of universe would we be living in? To understand this, it helps to look at how galaxies behave. Astronomers have found that stars near the centre of galaxies orbit at incredible speeds. In the Milky Way, for example, stars close to the core are moving so fast that only an object millions of times the mass of the Sun could possibly hold them in place with gravity. The central object has been named Sagittarius A, and it has been considered a supermassive black hole for decades. But when scientists study the behaviour of Sagittarius A in detail, certain mysteries appear. For example, the energy bursts it sometimes produces are difficult to fully explain. Some researchers have wondered if what we are actually seeing is not a black hole, but something more subtle and exotic. A gravastar might be able to mimic a black hole so closely that even powerful telescopes would struggle to tell the difference. The first big difference between a black hole and a gravastar lies in the event horizon. A black hole has an event horizon, a point beyond which nothing can escape. Once matter or light crosses that invisible boundary, it is lost forever, pulled into the singularity at the centre. But a gravastar does not have such an event horizon. Instead, it has a thin outer shell of exotic matter that resists collapse. If matter falls toward a gravastar, it might crash against this shell rather than disappearing into a singularity. From the outside, however, this difference would be very hard to detect, because the shell would still trap most of the light and radiation, making it look nearly as dark as a black hole. This means that when astronomers point their instruments at galactic cores, they could be staring not at black holes but at gravastars, and they might never know unless they find a subtle clue that distinguishes one from the other. One of the strongest arguments in favour of gravastars is that they avoid the so-called information paradox. In black hole theory, when matter falls past the event horizon, all information about that matter is lost, at least from the point of view of the outside universe. This creates a clash with the laws of quantum mechanics, which say that information cannot be destroyed. For decades, physicists have wrestled with this paradox, searching for ways to reconcile black hole behaviour with quantum theory. Gravastars sidestep the problem by never allowing matter to truly vanish into a singularity. Instead, the exotic shell and vacuum energy inside the gravastar might store or recycle the information, keeping the laws of physics intact. If galactic cores were gravastars, then the universe might be more consistent with quantum rules than if they were true black holes. Of course, if gravastars sit at the hearts of galaxies, their influence would not stop at the philosophical level of paradoxes. They would also change the way galaxies grow and evolve. Supermassive black holes are often thought to play a crucial role in shaping galaxies, controlling star formation by spewing out enormous jets of radiation and streams of particles. These outflows can heat up surrounding gas, preventing it from collapsing into new stars, or sometimes trigger star formation in certain regions. If gravastars replace black holes in this role, then the mechanics of how these outflows are generated could be very different. Perhaps the exotic shells of gravastars reflect and focus in falling energy in unusual ways, creating bursts that appear similar to black hole jets, but actually come from very different processes. This means that when astronomers look at distant galaxies with blazing cores, they might be witnessing the work of gravastars rather than black holes. To test this idea, scientists have tried to imagine what kinds of signatures gravastars might leave behind. One possibility is in gravitational waves, the ripples in space-time first predicted by Albert Einstein and finally detected in the year 2015. When two black holes collide, they send out gravitational waves that can be detected by instruments like LIGO and Virgo. If two gravastars collided instead, the signal might be slightly different. For instance, instead of a clean merger into a larger black hole, the collision of two gravastars might produce echoes in the gravitational wave pattern, caused by the exotic shells bouncing energy back and forth. Detecting such echoes could reveal the true nature of these cosmic objects. If galactic cores are gravastars, then one day we might capture the smoking gun evidence in the form of these unusual gravitational wave signals. Another possible signature comes from the Event Horizon Telescope, the worldwide network of radio telescopes that produced the famous first image of a black hole in the year 2019. That blurry orange ring showing the shadow of the black hole in the galaxy Messier 87 was hailed as proof of black hole's existence. But some researchers argue that a Gravastar could produce almost the same image. The key difference might lie in the details of the brightness of the ring, or the way light bends around the object. Future, sharper images might be able to tell the difference. If one day we look at Sagittarius SC or Messier 87 again with even clearer vision, and find that the image does not quite match black hole predictions, it could point toward Gravastars as the real explanation. The concept of Gravastars also sparks fascinating speculation about the deepest workings of the universe. If the centres of galaxies are Gravastars, then the vacuum energy inside them might connect to the same mysterious energy that drives the expansion of the universe, known as dark energy. In this sense, galactic cores might not just be gravitational anchors holding galaxies together, but also reservoirs of the very force that shapes the cosmos on the larger scales. Perhaps every Gravastar is like a pocket of dark energy, and together they form a hidden network influencing the fate of the universe. This would make Gravastars not only black hole mimics, but also keys to solving the riddle of why the universe is expanding faster and faster. Skeptics, of course, point out that black holes already explain much of what we see without needing to invent new exotic objects. The behavior of stars orbiting galactic centers, the radiation from accretion disks, and the outflows of energy all fit well with black hole models. To replace black holes with Gravastars, scientists would need very strong evidence, something that cannot be explained by black holes alone. Right now, such evidence is lacking, and Gravastars remain speculative. Still, science has always advanced by questioning old assumptions and considering radical alternatives. The very idea of black holes was once dismissed as too strange to be real, and yet today they are widely accepted. Gravastars may follow a similar path, moving from speculation to serious consideration as new observations come in. If galactic cores are Gravastars, then the story of cosmic history might need to be rewritten. Galaxies formed in the early universe when clouds of gas collapsed under gravity, and supermassive objects grew rapidly at their centres. If those objects were Gravastars instead of black holes, then the early universe may have been filled with shells of exotic matter and bubbles of vacuum energy rather than singularities. This would mean that the universe's first great engines of growth were not as destructive as once thought, but instead strange structures that recycled matter and energy in unusual ways. The galaxies we see today, from spirals like the Milky Way to giant ellipticals, may carry the fingerprints of Gravastars hidden in their cores. Even the question of life in the universe could be touched by this possibility. Black holes are often seen as ultimate dead ends, swallowing everything without a trace. But Gravastars, by preserving information and perhaps interacting differently with matter and energy, might allow for a more balanced cosmic ecosystem. The jets and radiation from galactic cores could still be dangerous, but they might also be more controlled or varied if Gravastars are behind them. Civilizations looking at the stars might one day realize that the very structures they thought were monstrous devourers are instead complex engines of balance, sustaining the cosmic order in ways we never imagined. The debate between black holes and Gravastars at galactic cores is not just about astronomy. It is also about our imagination and willingness to question what we think we know. Black holes have become a symbol of the universe's mystery, an ultimate boundary where known laws break down. Gravastars offer a different vision, one in which those boundaries are illusions, hiding deeper truths that are stranger but also more consistent with the rules of physics. Perhaps in the coming decades, with better telescopes, sharper gravitational wave detectors, and deeper theoretical insights, we will finally know whether the hearts of galaxies are true black holes or the hollow shells of Gravastars. Until then, every observation we make keeps this cosmic mystery alive, reminding us that the universe is always more surprising than we expect. The idea that Gravastars could somehow be linked to the expansion of the universe through dark energy is both mysterious and exciting. Gravastars, or gravitational vacuum stars as they are fully called, are theoretical cosmic objects that some scientists have suggested as possible alternatives to black holes. Unlike black holes, which trap everything that falls beyond their event horizons, Gravastars are imagined as strange hollow spheres where an outer shell of exotic matter keeps a vacuum-like interior from collapsing. Inside that vacuum-like space, it is believed that a special form of energy, something very similar to what we call dark energy, might be at work. If this is true, then Gravastars may not only challenge the long-standing belief that black holes dominate the centers of galaxies, but they could also connect directly to the greatest mystery in modern cosmology. The fact that the universe is not just expanding, but expanding faster and faster as time goes on. Dark energy itself is a term we use to describe whatever it is that is making the universe's expansion accelerate. For many decades, scientists thought that after the Big Bang, the expansion of the universe would slowly decelerate because gravity should be pulling everything back together. But in the late years of the 20th century, astronomers using distant exploding stars known as supernovae discovered that the opposite is happening. Instead of slowing down, the galaxies are rushing away from one another at an increasing rate. The unknown cause of this acceleration was named dark energy. It is called dark, not because it is literally black or shadowy, but because it is invisible, mysterious, and unlike any ordinary form of energy we know. Today, scientists estimate that nearly 70% of the entire energy content of the universe is made up of dark energy, while matter, both normal and dark matter, makes up the remaining 30%. This means that the vast majority of the cosmos is dominated by something we cannot see or directly detect, and yet it shapes the fate of the universe itself. Now, the intriguing possibility arises when we compare the properties of Gravastars with what we know about dark energy. The inside of a Gravastar is thought to be filled with what physicists call a false vacuum, or de Sitter vacuum, a state of space that resists collapse with a kind of repulsive pressure. This repulsive pressure is mathematically very similar to the way cosmologists describe dark energy on the scale of the universe. In other words, what prevents the Gravastar from collapsing into a singularity is the same type of force that pushes galaxies away from one another. If Gravastars really exist, then each one could be like a small laboratory of dark energy locked inside a cosmic shell. Instead of black holes swallowing matter and leading to a point of infinite density, Gravastars would be cosmic objects whose very existence relies on dark energy's ability to counteract gravity. This raises breathtaking questions. Could the countless black hole candidates we have identified in galaxies actually be Gravastars hiding in plain sight? If so, then the universe could contain trillions upon trillions of small pockets of dark energy-like interiors, scattered across space wherever massive stars collapsed. If every Gravastar contains a region of repulsive vacuum energy inside it, then their combined effect might contribute to, or even explain why the universe as a whole is accelerating. Rather than dark energy being some mysterious fluid spread evenly everywhere, perhaps it is partly contained and stored within these strange cosmic shells. One can imagine the history of the universe under this possibility. In the first billions of years after the Big Bang, stars formed, burned their fuel, and many of the most massive ones collapsed at the end of their lives. Traditionally, we say they formed black holes, but if instead, at least some of them formed Gravastars, then each one would have created a new bubble of repulsive vacuum energy sealed inside a crust of exotic matter. With every passing epoch, more Gravastars would form as more stars died, and this would mean that the universe would gain more and more bubbles of vacuum energy. The total effect would be an increasing outward push on the fabric of space itself, reinforcing the cosmic acceleration. This would tie the birth and death of stars directly to the destiny of the universe as a whole, a link that makes the story of cosmic evolution even more interconnected. Another interesting aspect is that Gravastars may avoid the information paradox that troubles black holes. Black holes, according to the traditional picture, trap information forever behind their event horizons, which conflicts with quantum theory that says information cannot be destroyed. Gravastars, with their dark energy-like interiors, may not have such horizons. Instead, the exotic matter shell and repulsive vacuum prevent full collapse. If this is the case, then the connection to dark energy is not just about cosmic acceleration, but also about the consistency of physics itself. Perhaps the laws of nature prefer Gravastars because they avoid contradictions, and in doing so, they reveal why the universe is dominated by this mysterious repulsive energy. The mathematics behind this idea also has elegance. When cosmologists describe dark energy, they often use what is called the cosmological constant, a term Albert Einstein originally introduced into his equations of general relativity. This constant represents a uniform energy density filling all of space. Inside a Gravastar, the vacuum interior behaves exactly like a miniature cosmological constant. It creates negative pressure that pushes outward, keeping the shell from collapsing. The fact that the same mathematical concept works on both the small scale of a Gravastar and the large scale of the cosmos suggests a deep unity. It is almost as though the universe is built on repeating patterns, where the same type of energy governs both the structure of individual objects and the evolution of the cosmos itself. Skeptics may argue that even if Gravastars exist, their combined influence would be tiny compared to the vast amount of dark energy needed to explain cosmic acceleration. After all, the universe is unimaginably large, and most of it is empty space not filled with Gravastars. But this may not be a decisive objection. If the interiors of Gravastars are truly regions of dark energy like vacuum, then their contributions could interact with the larger cosmic background. In fact, the creation of Gravastars could act as seeds, enhancing the presence of dark energy across the cosmos. In such a picture, the universe does not have dark energy as a separate, independent field, but as something naturally produced whenever matter collapses under its own gravity, but refuses to form a singularity. The death of stars would literally be feeding the expansion of the universe. Another way to think about this is to imagine the universe as a giant tapestry of space and time. Normally we imagine gravity as creating dents or curves in this tapestry, pulling matter together. But dark energy is like a stretching force that pulls the threads apart. Now imagine that scattered across this tapestry are Gravastars, each one like a bead of tension that keeps pushing outward from within. They do not collapse, and instead their insides keep the surrounding fabric stretched. Over time, as more Gravastars appear, the whole tapestry experiences more stretching. This mental picture captures how local processes like star collapse could add up to global effects like cosmic acceleration. The connection between Gravastars and dark energy also opens fascinating questions about the fate of the universe. If the acceleration continues forever, galaxies will drift farther and farther apart, and eventually, billions of years from now, even the closest galaxies will vanish beyond our horizon. Stars will die, and the universe will become a dark and cold place. But if Gravastars keep forming, then the dark energy-like interiors will multiply. Could this mean that the universe will accelerate even faster than we predict today? Could the presence of Gravastars change the ultimate outcome, leading perhaps to a scenario known as the Big Rip, where space itself is torn apart? Or could they balance the acceleration in some subtle way, preventing such a catastrophe? The truth is, we do not know, but the possibilities highlight how linking these strange objects to dark energy makes the cosmic story far richer and more dramatic. There are also observational challenges. So far, astronomers cannot easily tell the difference between black holes and Gravastars. Both would appear as invisible regions surrounded by glowing disks of hot matter, and both would produce powerful jets and radiation. However, the internal structures are very different. If we can one day detect tiny differences in how gravitational waves behave when two of these objects collide, or if we can see unusual patterns in the shadows of supposed black holes, then we might be able to confirm the existence of Gravastars. If that happens, and if their interiors really are regions of dark energy like vacuum, then we would have a direct experimental link between astrophysics and cosmology. The mystery of dark energy would no longer be just a property of empty space, but a tangible feature of actual objects scattered across the cosmos. Even at a philosophical level, the connection is thought-provoking. Dark energy in many ways represents the unknown frontier of physics. It challenges our understanding of reality itself because it acts like a property of space rather than of particles or fields in the usual sense. Gravastars, on the other hand, challenge our understanding of collapse, death, and rebirth of stars. To think that these two mysteries may not be separate but two sides of the same coin is almost poetic. It suggests that nature does not waste its tricks. The same repulsive force that saves stars from becoming singularities may also drive the universe to grow without end. This idea also reshapes our view of cosmic balance. In ordinary thinking, gravity pulls things together, while dark energy pushes them apart. These are opposite and competing influences. But in Gravastars, the two are not simply opposed. They cooperate. Gravity tries to crush the star, but instead of winning completely, it gives rise to a new state of matter and vacuum that resists collapse. Out of destruction comes stability, and that stability itself is powered by the same type of energy that rules the cosmos. It is as though every Gravastar is a miniature version of the cosmic struggle between attraction and repulsion, a reminder that the forces shaping the universe are also at play inside individual stars. When we look at the universe in this light, even familiar astronomical events take on new meaning. The collapse of a star is no longer just the end of its life, it is the beginning of a new cosmic laboratory, a place where the mysteries of dark energy are encoded and preserved. Every Gravastar could be thought of as a monument to the hidden connection between death and creation, between the local and the universal. It makes us see the night sky differently, as not just filled with stars and galaxies, but perhaps filled with countless hidden chambers of dark energy, quietly contributing to the expansion of all that exists. The connection also challenges us to rethink the role of humans in the cosmos. We are creatures who evolved on a small planet orbiting a medium-sized star, yet we're daring to imagine links between the collapse of giant stars and the acceleration of the entire universe. This is a bold act of imagination, but it is also a testament to the human spirit of inquiry. Gravastars and dark energy may seem like abstract concepts far beyond our everyday experience, yet they may hold the key to the ultimate fate of everything. By studying them, we are in a sense trying to read the universe's diary, to glimpse the hidden logic that governs its story from beginning to end. To grasp how vast this idea is, consider numbers. The universe is about 13.5 billion years old, and galaxies contain billions of stars. If even a small fraction of those stars ended their lives as Gravastars, then we are already talking about trillions of these objects scattered throughout space. Each one would be a sealed chamber of dark energy, contributing its repulsive influence. Imagine a cosmic ocean dotted with countless floating lanterns, each one glowing not with light, but with invisible pressure. Together, they would shape the currents of the whole ocean, guiding the flow of cosmic expansion. This is the scale on which the Gravastar dark energy connection operates. Of course, many mysteries remain. We do not yet know if exotic matter, required to stabilize Gravastars, really exists. We do not yet know if the false vacuum inside a Gravastar truly mirrors the properties of dark energy on the larger scales, and we do not yet know whether Gravastars are abundant or rare. But the beauty of science lies in asking these questions and following where the evidence leads. If the universe has given us this hidden connection, then it's up to us to uncover it, piece by piece, observation by observation, idea by idea. A Gravastar is a hypothetical object that is suggested as an alternative to black holes, while a wormhole is a tunnel-like structure that might connect two distant regions of space, or even two separate universes. Both of them belong to the world of theoretical physics, a world where imagination and mathematics meet, where the laws of space and time are stretched into shapes that go far beyond ordinary experience. When people speculate about their possible role in exotic space travel, they are really imagining ways in which the deepest mysteries of the universe could one day be harnessed to allow journeys that today seem impossible. To think about this is to stand at the edge of human knowledge and peer into possibilities that might reshape the future of exploration forever. A Gravastar, short for gravitational vacuum star, is an idea that tries to solve the puzzles that come with black holes. Black holes are regions where gravity has become so strong that nothing, not even light, can escape. Yet black holes create serious problems for physics, such as the information paradox, the singularity at their center, and the way they distort space-time in seemingly infinite ways. Some scientists have wondered if nature avoids these problems by never truly making a black hole, but instead creating a Gravastar. In this picture, when a massive star collapses, instead of squeezing into a singularity, it creates a shell of extremely exotic matter around a hollow core filled with what resembles dark energy, or a vacuum-like state. From the outside, a Gravastar would look almost identical to a black hole, but deep inside it would be very different. This is not just a small change. It could mean that instead of swallowing information forever, a Gravastar could preserve it, and instead of being a cosmic dead end, it could be a strange container of energy and structure. Now, if Gravastars exist, they might play a role in more than just astrophysics. They could serve as anchors or even as engines for exotic space travel. Why? Because the very materials and energies they are made of could hold the keys to manipulating space-time itself. Exotic matter, which is required to stabilize wormholes and make faster-than-light travel possible, is also the kind of substance thought to hold up the shell of a Gravastar. This connection between Gravastars and wormholes is not just a coincidence. it suggests that these two exotic ideas might actually be two sides of the same coin. Where one appears, the other might not be far behind. If the universe does allow Gravastars, it might also allow wormholes, and together they could form a natural toolkit for bending the geometry of reality. A wormhole is often imagined as a tunnel through space-time. It was first described in the early 20th century by Albert Einstein and Nathan Rosen, which is why it is sometimes called an Einstein-Rosen bridge. Imagine folding a sheet of paper so that two far-apart points touch, and then poking a hole through the fold to connect them. That is how a wormhole is often explained, though in reality the mathematics is much more complicated. If wormholes exist, they could allow instant travel between points separated by vast distances. A journey to a star tens of light years away could become as short as stepping through a door. But wormholes are unstable. They collapse almost instantly unless held open by negative energy or exotic matter. This is where Gravastars might come in. If the shell of a Gravastar truly is made of exotic matter, it could, at least in theory, provide the stabilizing ingredient needed to keep a wormhole open long enough for passage. Speculating about using Gravastars and wormholes for space travel means imagining technologies that can manipulate them. For example, if a civilization were able to harness a Gravastar, it might be able to peel away or use part of its exotic shell to feed and stabilize a wormhole. Or, perhaps even more astonishing, Gravastars themselves might naturally act as gateways to wormholes. Some theorists suggest that what looks like a Gravastar from the outside could actually be a wormhole throat in disguise. Instead of being a hollow star-like body, it could be the mouth of a tunnel leading elsewhere in the universe. If this is the case, then the universe could be scattered with hidden doors, waiting for someone advanced enough to open them. Now, picture what this means for space travel. Our current rockets are painfully slow. Even travelling to the nearest star system, Alpha Centauri, would take tens of thousands of years with conventional technology. But if wormholes stabilized by Gravastar-like structures exist, then it might be possible to leap across the galaxy in seconds. Imagine a spacecraft approaching what appears to be a black hole, but instead of being destroyed, it enters into a carefully stabilized Gravastar wormhole system and emerges light years away. Entire civilizations could spread across the stars, not in millennia, but in mere moments. This would change not only how we travel, but how we think about distance and time itself. There are, of course, enormous challenges. For one, we do not yet know if Gravastars exist at all. They are still only theoretical, proposed as an alternative to black holes. Detecting them would be difficult because they mimic black holes so closely. Observing a Gravastar wormhole connection would be even harder. Then there is the matter of energy. The exotic matter required to keep a wormhole open is not something we can create in large amounts. Even tiny amounts of negative energy are incredibly difficult to produce in laboratories. To stabilize a wormhole large enough for a spacecraft, the energy requirements might be beyond anything we can currently imagine. Yet history has shown that what seems impossible in one century can become practical in another. The idea of heavier-than-air machines flying across oceans once seemed absurd, and yet airplanes now circle the globe every day. Another possibility is that Gravastars and wormholes are not built by us, but are natural features of the universe. If so, then advanced space travel might mean learning to locate and navigate them, rather than trying to build them from scratch. The galaxy could contain hidden networks of natural wormholes, stabilized by Gravastars or exotic matter fields, waiting like ancient highways. Civilizations far older than ours might already know how to use them. Perhaps this is one reason why the cosmos appears so quiet. If other beings are travelling through hidden wormhole corridors, they might not leave many traces in normal space. The silence of the stars could be hiding a bustling network of travel routes beyond our current perception. The speculative link between Gravastars and wormholes also raises deeper questions about the structure of the universe. For instance, if wormholes can connect not only 2 points in space, but also 2 points in time, then Gravastars could be gateways not just to distant stars, but to the past or the future. Exotic space travel could then also become exotic time travel. The implications of this are staggering. Civilizations might step through a Gravastar-stabilized wormhole and emerge in an entirely different era. They could witness the birth of galaxies or travel to the heat death of the universe. This adds another layer of wonder, but also danger, since tampering with time raises paradoxes that physics does not yet know how to resolve. If Gravastars truly exist as alternatives to black holes, then their interiors might hold the secret to wormhole creation. The vacuum-like energy at their cores could be similar to the kind of energy that drives cosmic expansion, the same mysterious dark energy that makes up most of the universe. If so, then tapping into this energy might allow us to shape space-time itself. In that sense, Gravastars might not just be gateways to wormholes, they might be cosmic laboratories where the very tools of faster-than-light travel are stored, waiting for a mind clever enough to unlock them. There is also a poetic quality to this speculation. For thousands of years, humans have looked up at the stars and wondered how to reach them. Our myths told of gods and heroes crossing the heavens with ease. Wormholes and Gravastars are the scientific versions of those ancient dreams, giving a possible physical mechanism for travelling across the cosmos as swiftly as stepping through a doorway. They embody the same longing but translated into the language of physics and mathematics. Yet speculation must also be balanced with humility. Gravastars may turn out not to exist. Wormholes may remain forever unstable. The universe may deny us the shortcuts we dream of, leaving us with the slow crawl of rockets and generations-long journeys. But even if this is the case, the act of imagining Gravastars and wormholes as tools for space travel pushes human thought forward. It challenges us to think bigger, to consider possibilities beyond our current reach, and to keep striving toward new horizons. Sometimes the path to discovery begins with daring to imagine what seems impossible. Still, there are hints in the mathematics that keep the speculation alive. Solutions to Einstein's equations of general relativity do allow wormhole-like structures. Quantum field theory does suggest the existence of negative energy, at least in principle. Exotic matter is strange, but not forbidden. Gravastars offer an elegant way to avoid the singularities that trouble black hole physics. None of these ideas have been ruled out, and so long as they remain possible, the door is open for speculation. If the laws of physics truly allow Gravastars and wormholes, then space travel might one day be transformed into something far beyond rockets and fuel. Imagine again a spacecraft drifting toward what seems like a black hole. Its crew braces for destruction, but instead of being crushed, the craft slips through a shimmering shell of exotic matter. Inside, there is no singularity, no crushing end, but a corridor of warped space. Lights flicker as space-time itself bends around them. Moments later, the ship emerges, not destroyed, but orbiting a star on the far side of the galaxy. What today seems like science fiction could one day become science fact, if Gravastars and wormholes truly can be used for travel. That vision, however distant, is why scientists and dreamers alike continue to speculate.